Z5U. These are all kind of class 2 dielectrics. If you take a look at this little chart over here, this is a chart showing the relative capacitance change versus temperature. And this very shallow little linear line here, that's your MP0 and C0G capacitors. The X7R capacitors might vary plus or minus 10 or 15% around their original value or their nominal value over that temperature range. So that's not too bad, but that's still a pretty good variation. The Y5V and Z5U, they're kind of horrible when it comes to temperature variation. They may go up as high as 10 or 15% over their nominal value, but drop down to 60 or 70 or even 80% of their below their nominal value at the temperature extremes. They also have got a higher dissipation factor, and both of the class 2s are somewhat voltage dependent as well, where the capacitance will change with applied voltage. But you get larger capacitance value. Reasonable compromise between the stability of the class 1 dielectrics, but the larger values of the Y5V and Z5U materials. So if you have a choice for a given value in your application between X7R caps and the Y or Z type caps, go with the X7Rs. They're going to be a bit more stable. All of the ceramic caps are generally pretty low cost. They've got low dissipation factor, low ESR, good RF performance. But the ceramic materials are also microphonic. So if they're in a high vibration environment or things like that, that can actually cause the capacitor to become a little bit microphonic, almost like a quartz type of device. So you have to kind of be aware of that. So again, typically good for RF applications. They're very low cost, bypassing interstage coupling, decoupling around gain stages and things like that. They're good applications for that. Generally not so good for use in voltage controlled oscillator designs or frequency generation designs because of the variation over temperature. The class 1 like MP0 and C0G are the exception here. They certainly can work very well in those applications. And they're not really good for low frequency filtering where you can't really withstand this kind of tolerance with temperature. So especially the Y5V and Z5U are really bad. An X7R wouldn't be so bad for that application, but very, very common types of capacitors that you'll find all over the place in many, many different package styles. Now, something I'll mention at this point is if you're reviewing a schematic or you see something online you're going to go build and the capacitors aren't labeled in terms of what types they are, whether they're ceramics or electrolytics or film or mica or whatever, the most likely case is that any of the polarized caps are electrolytic caps, and in many cases could be substituted with tantalums. Any of the others that are non-polarized, generally lower value caps, they're most likely ceramic capacitors. If the application really warranted something other than those two, hopefully the schematic would be labeled that way. But it's a pretty safe assumption that for the polarized caps, they'll be electrolytics, non-polarized or ceramic. But that being said, let's go take a look at some of the other common types of capacitors that are out there and some of their characteristics and see where they'd be applicable. Probably the next most common type of capacitors are the film capacitors. Now there again, just like the ceramics, there are many different types of film capacitors. One of the differences though here is that there aren't that many film capacitors that are available in surface mount, or certainly not nearly as many as there are for ceramic. But there's actually some really nice characteristics of film capacitors that make them worth taking a look at. So some of the things that film capacitors have in common is that they're generally available from the low tens of picofarads to in the neighborhood of even 1,000 microfarad, very large values, and working voltages from relatively low voltages to well over 1,000 volts. So a very wide capacitance and voltage range. Generally, the film caps have got really tight tolerances and very low leakage, very low absorption, very low ESR and dissipation factor. All really good characteristics for capacitors. They're very stable with temperature and voltage, but they're moderately to high priced with respect to ceramics. They're relatively large. They don't have as good of a volumetric efficiency, capacitance per unit volume, that the aluminum electrolytic or the tantalums do, but they're also not polarized, and they're they're going to have a, probably not even as good of volumetric efficiency as even the multi-layer ceramic caps. They are available in two kind of broad different types. There's a metallized film or metal foil and film. So we talk about film capacitors because what we're talking about is the dielectric material, the insulator between the two plates of the capacitor is some type of a film, plastic type of a film typically. And that film can either be metallized on one side and then rolled up, and that's the metallized film capacitors. They've got the highest density because you don't have a separate foil in there. Where the metal and foil film is, you've got alternating layers of plastic insulator, metal foil, plastic insulator, metal foil, and that's rolled up. They generally will have a lower ESR, they can operate with higher AC currents, but they're not going to have as high a value because they're not you don't get as much capacitance per unit density with those. But that's kind of the common characteristics of these film caps. Now, as I mentioned, there are many different film types that can be used in these film capacitors, and they have some slightly different characteristics that make them useful for certain applications. The polyester or mylar caps are very, very common, and they're moderately stable with temperature, 5 to 15% variation over temperature. They're pretty good with dissipation factor, a little bit higher than some of the other types, but they're generally lower cost. Probably the other most common type is the polypropylene or PP type caps. Polypropylenes are very common, like these orange drop caps or the brown drops over here. They're generally very low absorption, they're very stable with temperature. They're just a bit pricier than the polyester or mylar caps. One of the problems, though, with some of these types of caps, like a polypropylene and polyester, is that you can't often tell from the packaging what type it is. You can get a mylar cap or a polypropylene cap that looks like it's packaged the same way in these little plastic encapsulated packages here, rolled up in these type of axial type of devices or dipped in some of these others. I've seen the polypropylene and polyester in both of those package styles, so you can't always tell by looking at them what they are. You can be pretty sure that it's a film cap, but you can't necessarily tell what type of film they are. Now, some of the other types of film is a polystyrene capacitor. These are really stable with temperature with very low dissipation factor and absorption. A little bit harder to find. They're pricey. I don't have any here. Oftentimes, what these look like, they look almost like a clear tube, like a clear plastic tube, almost like a glass diode, if you will, but it's made of plastic with like a foil inside of it. They're not really good in operating in very high temperature environments, like next to a vacuum tube or next to some power resistors, because the polystyrene plastic itself will begin to deform and melt. But in applications where it's low power type applications, they actually are pretty superior to some of the other films. But they are harder to find, they're a little bit pricey. Polycarbonate caps, very high reliability, they're also pretty pricey. Performance is about the same as the polypropylene. There are lots of other different types of film caps that different types of films that are used, and you almost have to look up and see what the characteristics are. But the two most common that you'll come across will be the polypropylene or the polyester, with the polypropylene generally being the higher performance of the two. They're really good for high voltage applications. They're really good and stable with temperature and voltage. They got pretty low dissipation factor and dielectric absorption, and they're really good from everything from audio to RF applications. The downsides is that they're pricey, they're physically a bit large, and they're a bit limited in the package styles that you can get. These film caps are often the ones that, if you're doing some restoration of old antique radios and things like that, you're going to be replacing some of these early film caps. These are old paper and wax, so it wasn't really a film that was the dielectric, it was actually a paper that was used. So it was like paper and foil wrapped up and then stuck in the tube and sealed with wax. These capacitors by now are all kind of dried out and leaky and all need to be replaced. And replacing them with mylar or polypropylene caps is the most common thing that you would do in these type applications. Now, one other point I'll make about these film caps, especially those that are wound up like a coil here, is oftentimes you'll see they've got a band marking on them. That would make you think that they're polarized. Well, the reality is they're not polarized caps. They're not like the tantalums or the aluminum electrolytics. What that band indicates is which terminal on the capacitor is connected to the outer foil wrapping. So if you think about it, you've got basically an insulating layer and a conductive layer that are wrapped up. So one of the conductors is going to be on the inside of that last wrap. The other conductors will be on the outside of that last wrap, with the insulator being in the middle. So the band indicates the outer wrapping is connected to that wire. And oftentimes in the electronics, what you're going to want to do is connect that to the lowest potential, lowest voltage potential in the circuit, so that you don't have a high voltage on the outer perimeter of here. But there may be applications where you may choose one end or the other to be connected up in a certain part of the circuit to prevent coupling to the capacitor. Like you might want to connect the outer foil edge to the lowest impedance node in the circuit. But that's why these film capacitors are often marked with a band. You'll see them like on that, and even on this dipped variety, you've got the band marked here. That means that this lead here is connected to the outer foil wrapping of the capacitor inside this molded case. So the next type of capacitor we'll talk about are mica capacitors, where the dielectric material is actually a mica material. Some of the older ones were in these what we call domino packages that typically had these colored dots that would indicate what the value is, and others typically in these kind of molded packages. Again, typically relatively low value, a picofarad to maybe 10 nanofarads or so, but can operate at very high voltages. Mica caps are really stable with temperature, really stable with voltage. They're available in very tight tolerances, not these particular devices, but they are available in some very tight tolerances. And they've got really good RF performance. The dissipation factor is very low. They're very, very commonly used in RF applications, in filters, and voltage-controlled oscillators, or other oscillator or frequency generation circuits. Very commonplace to have mica caps because they're very, very stable. The bad thing is that they're smaller values, they're limited in package styles and things like that. Now, you might say these look an awful lot like those molded film caps. Now, the way you can generally tell the mica caps apart is that they're a bit lumpy, if you will. If you take a look at this package, it's kind of bulged at the ends, or it maybe almost a little bit dog bone shaped, if you can think about it that way in terms of the way the package is, compared to the film caps, which are generally a bit more smooth and I would say cylindrical, or just don't have the lumpiness, especially associated at the ends. And that's almost the only way you can kind of really tell whether that's a mica capacitor or a film cap, because the molded caps kind of look the same. But generally, if it's kind of a lumpy kind of a package, that would almost tell you that it's a mica capacitor. And also, you can often tell from the application. If it's in an RF circuit, a VCO, or something like that, if a mica cap was available, it likely would have been used in that application. Now, of course, there are lots of varieties of variable capacitors as well. Some of these larger air dielectric kind of bread slicer variable caps, and the smaller what we call polyvaricons, because they are like a polyfilm variable capacitor. Typically, they've got some trimmers as well as kind of main tuning on them. You find these in some of the older transistor radios. You might find some of these in some of the older larger transistor radios, or tabletop or even tube radios and things like that, to make the tuned local oscillators for tuning the radio around. Then you'll also have trimmer capacitors that might be small little ceramic type trimmer caps. I've got a bag full of different types here. Maybe some compression caps. These guys are basically two plates that, when you loosen the screw, the plates separate, and they'll often have a mica insulator between them. These types of caps obviously are all used in RF applications. Here's kind of a slug-tuned variable cap here as well. Lots of different types of variable capacitors that you'll run across. But in general, all of these are typically used for RF applications, where devices like these two are designed to be kind of tuned and operated all the time, whereas the trimmers are typically set and adjusted to tune or align a circuit, and then they're left alone and never adjusted again, so they don't have the durability of some of these continuously variable devices. Of course, really kind of impossible to cover all the different types of capacitors and all the specific application and characteristics in one short video, but I hope this brief introduction to the different types of capacitors, their characteristics, and their basic applications and where you'll find them has been helpful. And again, just remember that the vast majority of the polarized caps that you see will be aluminum electrolytic or possibly tantalum, and the vast majority of the non-polarized capacitors you see in a design are most likely ceramic, whereas you could use film capacitors or even mica capacitors in those applications, particularly if you're operating at over a wide temperature range or at higher frequency. So I hope it's been helpful. If you like what you see, give me a thumbs up. If you haven't subscribed already, please do so. And we'll see you again next time. Thanks for watching. In today's video, we're going to take a brief look at some of the practical aspects of power supply decoupling and filtering. What we'll learn is that the size and placement of the various capacitors on a circuit board is largely driven by these various roles that these capacitors perform. Large value capacitors like these big electrolytic capacitors essentially form kind of charge storage reservoirs and do the bulk of the filtering for large, relatively low frequency current demands of the rest of the board. While the smaller surface mount capacitors are placed very close to various active devices, form a different role. They also provide local charge storage, but not nearly as much charge as the bulk electrolytic capacitance. But more important, what they provide is a return path for high-speed signal currents. So the high-speed signal currents that might be flowing out of a pin are going to flow back through the ground plane and ultimately have to get back to the power supply. And they typically get back through these locally placed higher frequency decoupling caps. I'm going to attempt to illustrate this on a more simplified board. Now here's the simplified mock-up board that I'm going to use to illustrate the various roles that these capacitors play. I've got a 3.3 volt power supply coming in, running along a power supply rail, which could essentially be a trace on a circuit board running up to, in this case, an inverter chip that's running as an oscillator and then driving a 50 ohm transmission line into a termination here. And that transmission line is sitting over a ground plane. Now right now there is no power supply filtering on this at all, which is never a good idea, but this is where we're going to start. I'm probing the output of the pulse that we're generating here, and this is going to generate about a 3 volt pulse, so result in about a 60 milliamp current draw when the pulse is on, and a much lower current draw when the pulse is off. And we're going to also probe the power supply pin right at our active device, so we can see the effect of filtering right at the power supply pin. Okay, so the first thing we'll do is take a look at the effect of the bulk capacitance on the low frequency content of the noise in the power supply. In order to see that, I'm going to zoom in a little bit on that power supply. A better way to do that is to set up an offset that's equal to the power supply voltage, and that will allow me to set up a better vertical scale, say maybe 100 millivolts of division or 50 millivolts of division, to actually see that noise a little bit better. So we can actually see that when we're driving the transmission line, we're pulling an extra 60 milliamps through the supply, and that's causing a little bit of a dip in the supply voltage, and then it releases back up again. So if we place this bulk capacitor right near the power entry point to this board, we'd see we've collapsed that low frequency noise down to just about nothing, maybe a tenth of a division. If I move that bulk decoupling cap closer to my active device, it's basically about the same. It's marginally better, but it's basically about the same. And the reason for that is that this low frequency content really is very insensitive to this placement, because as far as the low frequencies are concerned, all of these points are virtually identical. They're essentially, it's a ground plane. There's no change in impedance between those various points. So typically you'll have these bulk decoupling caps right at the power supply or the power entry point to the board, because the placement isn't that critical. So let's actually solder this in place and then take a look at the effect of the high frequency component. Okay, with our bulk capacitor in place, let's change our vertical scale here so that I can now see the extent of the high frequency noise associated with the edges of our waveform. And we'll take a look at the placement of the high frequency decoupling cap and how the location of this on the board will affect how well it works in reducing that noise. Okay, let's start off by placing this 1.5 nanofarad capacitor right near the power entry point. And you can see a relatively small reduction in that high frequency noise. If I pull that cap off, you can see it grew about 0.2 of a division there and then reduced again. But now let's place that same capacitor very close to the chip. And we can see a very dramatic change in that high frequency noise. And this is essentially why we've got these capacitors located very, very close to the devices to get rid of that high frequency noise locally. Okay, so we've got both capacitors in place here now. Now let's talk about how the roles of these two capacitors differ. As we mentioned earlier, the large bulk capacitance is taking care of the large low frequency current demands and on the power supply and helping to stiffen the power supply rail in that case. But the high frequency cap here is kind of forming a little bit of a different role. It is still kind of a charge reservoir, but it also is a high frequency current path. Let me explain what I mean by that. The active circuitry in here is creating the square wave that's coming out here with some very fast edges. And those edges contain obviously high frequency components. Now we've all heard the adage that current will take the path of least resistance. When we talk about current or at high frequencies, we have to modify that statement a little bit and say that the current is going to take the path of least impedance, which in this case really means least inductance. And the amount of inductance in a current loop is proportional to the loop area. So let's see what that means here. If I've got power supply current coming in to power up this chip, that's creating the signal that's going out into this transmission line. So high frequency currents are going down this transmission line through the terminations into the ground plane. And they're going to go through the ground plane and ultimately return back to the power supply. But remember, we're talking about the high frequency currents here, and we want to minimize loop area, and that means that the high frequency currents are actually going to go into the ground plane and follow a path underneath the transmission line, because that will represent the least amount of loop area. It's not going to just go straight across this board, because that means that the current would have a big loop and a lot of inductance. So the high frequency currents are going to follow a path underneath the transmission line back towards the chip. So how does it get back essentially to the power supply? Well, it actually gets back through this cap. When we had this cap located up over here at the power entry point, that means the current kind of came back through here because that's where the high frequency currents were flowing, but then had to kind of work its way all the way back around and come through here, so adding a lot more loop area. By placing the high frequency decoupling caps close to the chip, we provide a path for those high frequency currents to get back to the power supply, minimizing the inductance and minimizing the amount of noise generated. So this is really a very big part of the reason why if you look at any of the active devices and ICs on any circuit board, you will see local decoupling caps right here, right here. There was one actually I removed off of the board right there. There's plenty on the underneath side of this board associated with this chip. And these are providing that local storage and high frequency return path for any of the high frequency currents that are demanded by these particular chips. And this is essentially what we modeled here on my little mock-up board. Okay, so I hope you learned a little something about the different roles that the different power supply decoupling and filtering capacitors play on a circuit board, and why some of them are placed close to our active devices and some of them are not. If you like what you see, please give me a thumbs up. If you haven't subscribed already, please do so, and thanks again for watching.
Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. One of the antennas that I typically recommend is a dipole. It's real simple, doesn't take much to construct one. There's lots of examples on YouTube and in the ARRL handbooks, antenna books, all kinds of places to show you how to put one together. One easy way for me to remember the length of a dipole is 1, 2, 3, 4. One side is 234 divided by the frequency in megahertz. So for example, I'm going to make a 20 meter dipole, so 234 divided by 14.2 is a little over 16 feet, and that's one side, so it's 1, 2, 3, 4. One side is 2, 3, 4. As far as the center insulator goes, it is really easy to do with some off-the-shelf PVC parts. Don't need to buy one, you can make one. When we first went on the air in '63, what most of us used was an insulator. We'd bring the coax up and split it so the shield would go to one side and the center conductor to the other. That was fine until it rained, and then water would come into the house through the coax and ruin the coax. But what I'm going to make is something that I believe will be watertight. To do it, I'm going to use some PVC pipe. This is 1¼ inch, happens to be schedule 40. I've got some glue, eye hooks with nuts. These are 3/16. I bought both plated and stainless steel just to see which I would prefer to use. I'm going to use a stainless steel. An SO239, and the one that I've decided to use is the bulkhead, and I'll show you why in just a minute. Going to need a couple of pipe caps for 1¼ inch. There are two kinds that I found in going to Home Depot and some local hardware stores. This one is domed, this one is flat. Decided to get both, and I got several of each, and I'm glad I did because I made a few mistakes along the way. The domed one I'm going to use on the top, and the flat one I'm going to use on the bottom to mount because it provides a good surface for mounting the coax connector. Short section of this PVC pipe. I'm going to notch it so when I put it together, this notch will go around the nuts for the eye hooks. So assembly is really easy, and getting it ready is not a big task. You're probably going to want slightly larger than an 1/8 inch drill bit. Locate the center of two caps, whether you use two flat ones or two domed ones or one each, doesn't matter. Drill a pilot hole. The eye hook is going to go in one of them, and what I ended up doing was putting the eye hook in the top of, let's see if I can get one here, in the top of the pipe cap. Actually, I changed the one that I'm making. I changed this slightly. I decided to put a nut on top, so it's going to be nut, washer, and then the bottom washer and nut, and another nut, so that it's got two nuts on it. So drill a hole, put in the eye hook. That part's finished. About 1.5 inches of PVC pipe, and then cut a notch in it 180 degrees apart. You can put this PVC pipe into the cap and just take a hacksaw and cut about a 1/2 inch swath out of both sides. Break it off with a pair of pliers. While it doesn't sound like the best way to construct something, it really is going to be fine. You're going to glue this thing together. It doesn't need to be perfect. No one's going to see this, and it'll work just fine. The bottom part of this assembly is that pilot hole, and I enlarged the pilot hole using a stepped drill bit to the point where the coax connector will sit flush with this flat surface. So I just kept running this in, test fitting the SO239 until it would be relatively, the flange would be relatively flush with the bottom cap, and that's mostly for appearance sake. Put that on the back side, and I soldered on the wires. The wires are braid, and the reason for braid is I wanted something flat because I wanted to be able to sneak past the pipe and the cap and come out the sides. Using number 14 wire or something else really wouldn't work very well. So basically I soldered in the two wires. Two more holes that I drilled were 180 degrees apart. Again, I used a 3/16 drill bit to accommodate these hooks. I happen to have a drill guide that would allow me to sight and get these 180 degrees, but Frankly, you can take a ruler and probably mark it off just as easily. The location of the hooks is about halfway between the top and the bottom, and that's so you can accommodate the nuts on the inside. So ran those in, and again I did a nut, a washer on the inside, and tightened it down with, in this case, some a couple of open end wrenches. Once those are secure and you've got the wire soldered on, you're just about done. Using some PVC glue, glue one end of this piece of pipe that you've cut off with the two notches. The notches are going to be facing down, and then put glue around this piece and put it together. And again, I used a braid because it's flat and allowed it to sneak out the sides. So even though I haven't done it on the video, it didn't take long to make this once I figured out what design I was going to use. So here's the completed center insulator. I've got a hook for a rope so I can hang it like an inverted V. Wires for the dipole connect to here. This is going to wrap around the wire, and I am going to solder these on. If you wanted to make this longer, it's fine, it doesn't matter. And the SO239 on the bottom, easily handle legal limit, and dipole is a very effective antenna. So here for probably less than $15, you can make a center insulator with off-the-shelf parts from your local Ace Hardware or Home Depot. If you want to make a dipole using some of that horse fencing material, and I haven't tried that yet, you can do it this way, and instead of using hooks I used 1/4 20 screws. The SO239 is connected to those screws using solder lugs, and then some flat washers, and I haven't tested this yet. My main concern is how much power can it take, and at what point does this stainless steel wire heat up. I don't know the answer to that. But as far as this dipole goes, once you've got this thing together, it should be able to handle legal limit. There's nothing here that's going to fail. As far as hooking up a ballon or a choke ballon, that's a good idea. I would, because I can't accommodate it on the inside, what I'd recommend is snap-on ferrite beads that are the right mix, and just clip on 4, 5, or 6 down the coax, and that'd probably be good enough. Anyway, time to construct this was probably less than half an hour, and again, it didn't cost all that much. So that's my dipole center insulator. I'm going to string up a 20-meter dipole when the weather improves. It snowed a couple of days ago, so there's no snow on the ground, but it's still kind of cold and wet out there. Anyway, if you have any questions, post them below. If you have a version of this that is better than this, I'd love to hear from you. There's lots of ways to do this. This is the one that works the best for me. So for now, I'm Jim, W6LG for Ham Radio Basics. Thanks for watching, and if you have enjoyed this or want to see some more, please subscribe. 7-3. See you next time. Thanks.
On the bench today is this Yaesu FT736R VHF and UHF all-mode transceiver. And the problem with this is that it doesn't power up. This rig has a built-in switching power supply that is actually known to fail as these rigs age. So to verify this, we'll just disconnect the line cord and then pull out the pigtail. This pigtail actually runs from the internal power supply and brings 13.8 volts into the rig. So I'll just supply power directly here from an external power supply and see if the rig powers up. And if it does, that'll tell us that the problem is rooted in this power supply, as we suspect. Okay, I've got an external power supply hooked into the DC jack, and we powered up, and it does indeed work. We can see that this rig is loaded up with the 50 meg, 146 meg, 440 meg, and 1296 meg modules, so it's a nice fully loaded rig. So it also looks like the dial light is out here. The dim light seems to work on the vacuum fluorescent display, but there's no dial light on the meter, so it looks like we have a second little problem, but that is secondary to fixing the power supply, I think. So let's deal with the power supply first and see where we go from there. And we'll start off by pulling the covers. With the bottom cover off the rig, we can see the optional 50 meg and 1.2 gig modules sitting here. And this is the switching power supply. Okay, to remove the power supply module, there are 3 screws that go through the back here that attach this metal heatsink plate to the back panel, so they come out of the back. And then there are 2 screws on this metal plate holding it down to the chassis inside. So you got to remove all of those and then wrestle out the little strain relief for the pigtail out of the back of the chassis. With that out, the power supply's out, we can remove the shield and the circuit board and go on to fix the problem. Okay, so there's 5 small screws to remove to take the shield off of this power supply. And with the shield off, we can see what the problem is. There are a couple of power resistors in here. These two 33 ohm resistors here, they dissipate enough power that if you look carefully you can see how the board is discolored, it's a little bit brown. And look what's sitting right next to them, at least 2 electrolytic capacitors. So these things are getting cooked and getting dried out. They get dried out, their capacitance goes down, their ESR goes up, and eventually the power supply fails. Now these 2 capacitors are most likely faulty right now. And it's also possible that these 2 guys, which are sitting right next to the transformer, they could have gotten dried out and their values have changed. There's also a couple of other electrolytics in here, over here, these 2 large filter cans. All of these are potentially suspect because they've been sitting inside this power supply with a lot of heat being generated. Now, I mentioned up front that this is a fairly well-known problem, and it's actually documented pretty well online. I'll put a couple of links in the video description down below of where I found this information. There's some really good documents that describe the problem, and I also have lists of all the components to go purchase to do the replacement. I found out that document was prepared several years ago, and a couple of the part numbers that are on that list, like for DigiKey, are not valid anymore. So I had to kind of find additional replacements for those. So what I'll do also linked down below is a PDF file of the list of components that I purchased to repair this power supply. Okay, with the board removed from the chassis, we can actually see the discoloration of the circuit board even here underneath those power resistors. So we'll take a really close look also under the magnifier at the quality of these various solder joints. They tend to become brittle with that thermal cycling. So in addition to replacing the capacitors, we'll just make sure that all of these solder joints are good and fresh and don't have any fractures or anything like that in them. So that'll just be part of the refurbishment. The 2 capacitors that are most likely worst damaged are these 2 guys here. This guy C12 right next to the resistors, and this guy here, which is C9. Let's pull both those first and make some measurements, and then we'll just do a bulk replacement of all the rest. I love it when the part just drops out of the board after doing the desoldering. This is a 220 microfarad capacitor. So let's go take a look and see what it measures on the multimeter here. Okay, a little bit unsteady there. There we go. 33 microfarads. That's a far cry from 220. So I would say it's pretty well dried out and used up. I'm not even going to bother trying to measure ESR on it. Yeah, so here's the replacement 220 microfarad capacitor, and it's reading correctly, so it's ready to get installed in the board. And of course, when you're doing this, make sure that you get the positive and negative squared around right when you install it in the board. The capacitors are usually marked on the body, usually on the negative side for electrolytics. If the capacitors are too small to be marked, then usually the leg that's cut the shortest is the negative side of the capacitor. Make sure we get the negative going into the negative side. Push that in place and pull the leads back here. Get ready to solder that. Okay, we've replaced all of the electrolytics, and I touched up a couple of the joints on the back side of the board that looked a little dull, like they might be stressed a little bit from thermal cycling, and cleaned up the board, and we're ready to put everything back together. Alright, all the screws in place. Let's put this back in the rig. And the 3 screws in the back that are tying in the power devices into the heatsink. Okay, next we snake in the wires through the slot in the back here, and then get the strain relief snapped back into the hole. There we go. Now before putting all the covers on, we'll do a quick check to make sure that the power supply is working. Yep, and we're powered up off of the line supply. So that repair to the power supply was successful, brings the rig up. Okay, we've got everything back together. This rig is rated for 25 watts on VHF and UHF. So we'll just verify that we're getting that out of it, and that'll tell us that the power supply can deliver the sufficient current to operate this rig. So just in the 2-meter band, the FM mode, got a 50 watt slug in the bird watt meter here, and if we key up, we can see the power is just a little over 25 watts. So we're getting full power on FM. We'll put the meter into peak reading mode, switch to upper sideband, and now if I key the rig and speak, we can see that the peak reading is also just exceeding 25 watts here on the voice peaks. So that tells us we're getting full power out of the power supply, and the rig can operate at its full rated output power. Now the only remaining problem with the rig is that I've got no backlight here on the S meter. I made some measurements while we were inside and found that the 2 incandescent bulbs that light up the S meter were both burned out. And it's kind of a known thing with this rig as well. The backlighting of the meter is not very good to begin with, and it also the bulbs tend to burn out early. So discussed with him the possibility of trying to convert them over to LED, but he said no, he'd rather have it put back the way it was new. So I did find that Yaesu has some of the bulbs available in their part stock. So I ordered a couple of bulbs, and when they come in, we'll replace those. So this will do a part 2 repair video to replace the lights for the meter. Anyway, that completes the power supply repair. Got this rig back up and running on line voltage, and once we do the second repair for the S meter backlight, we should be good to go. And if you like what you see in this repair video, give me a good thumbs up. If you hadn't subscribed already, please do so. And thanks again for watching. Okay, we've got the Yaesu FT736R brought back to life by recapping the internal switching power supply. The only thing that remains to be done is take care of the backlight for the S meter. When I had the rig opened, I verified that the 2 incandescent bulbs that are used to backlight the meter were indeed burned out. So the first thing to do, power off the rig and start taking off the covers. Okay, we'll unplug it and start removing some screws. I'll get this bottom cover off here. There we go. Now Yaesu did a really cool thing to help us service things behind the front panel. With the front screws of the top cover removed and the whole bottom cover removed, you can simply loosen up these 2 screws on both sides, and you can tilt the front panel out and up so you can actually get to things behind it. Okay, and this side, loosen that up a couple of turns, and we'll tilt the rig up on its side to get this thing all the way up and out. Okay, you can pull the panel forward and tilt it down, and there we go. Real easy to get to things on the back panel here now. Okay, here's the back of the S meter. And the 2 incandescent bulbs are sitting in these little silicone rubber sleeves, and we can basically pull them right out of their holders. One there, and then the one down here. We can see each of these is soldered to a set of posts right here on this board. I've repositioned the camera to kind of show how this bulb fits into that hole for a reason. Because you might wonder, well, if we're going through the trouble of replacing these bulbs, why don't we convert it to LED? And I thought about that, but let's take a look at how the light is coupled to the meter face. The light basically comes out of this bulb through the silicon, kind of all around the perimeter of it, and it couples into the sides, the interior of this hole, into the plastic. And you might notice that the exterior of this plastic is kind of painted silver. And the idea is that light couples into this plastic piece, which is clear, and gets reflected by the silver paint and goes down essentially a plastic light pipe, and then is routed essentially to the front panel. So if we wanted to replace these bulbs with LEDs, we'd have to make sure that the light from the LED gets coupled effectively into the interior perimeter of this cylinder. And most LEDs emit a lot of the light out of the surface of them, and maybe a surface mount LED positioned in there and kind of glued in place might work, or we might modify this, cut this off and polish this surface to couple light in, but I don't want to do that much modification to the rig right now. So we're going to start off just replacing the bulbs with a new set of incandescents, and then we'll consider conversion to LEDs down the road. Okay, simple matter of grabbing hold of these wires. We should be able to pretty easily unsolder them from the post here. There we go, one set and other set. There's always a good idea, make sure that our replacement set of bulbs work before we put them in place, and they do. We're good to go. Okay, we use a little compressed air to blow out the dirt or any contamination inside these silicone sleeves. Just mount those on the bulbs. We'll stick them inside the meter and then connect them up to the posts. Alright, let's get the top one in here. And there we go. And the lower one. Okay, these are incandescent bulbs, of course, so the polarity doesn't matter. Let's solder each of these onto the posts and we'll be good to go. Okay, let's see. Yep, and there we go. The meter is lighting up again. Okay, with the covers back on, that completes the replacement of the incandescent bulbs that are lighting up the S meter. Now, there's always been a lot of complaints about the S meter backlighting in here. It's not that great, but we'll see how long these bulbs last, and if we need to in the future, we'll look at replacing them with LEDs. But for now, the rig's all done, and we can get this one back to its owner. If you like what you see, please give me a thumbs up, and if you haven't subscribed already, please do so, and thanks again for watching.
Hi, I'm Jim W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. Today I'd like to talk a little bit about coax connectors again, and because it really is a subject that has a lot of depth to it, and the basic coax connector that we're all familiar with, the PL259, goes back to the 1920s when coax was becoming popular. And at that time, 30 megahertz and above was considered UHF, so this was called a UHF connector. This is a UHF male PL259. Frankly, it's not good at UHF, and we really shouldn't be using it there. So, but the name from almost 100 years ago has stuck, and if you order these from a company and you ask for a UHF male, they're going to know probably what you're talking about. This kind of connector comes in a couple of different varieties. This one has a plastic insulator, and I don't like that much because if you heat the pin up too much, the insulator melts, and it's not very good. You can buy them with a Teflon insulator, and it's good to several hundred degrees. Pretty hard to melt the Teflon. This connector happens to be the kind that you crimp onto the coax, and I've done a video doing that, and I'm going to do another one today. This connector solders, this one crimps. You may also be familiar with the common SO239 or socket 239, which is the mate for the PL259. This one is silver plated Teflon insulator. It's a really good connector. It's a 4-hole flange. There's also a 2-hole version of this. Another connector that's a female coax connector that is really easy to use is this one. You drill a hole, bolt it into place, got one connection on the other side, and you're good to go. This one happens to be silver plated Teflon, and the socket part of it, the receptacle part, is gold plated. It's a really good connector. Another connector that you may be familiar with is a double female. It's actually called a plug. It's a PL258. This one is nickel plated. Also comes in, this one's slightly tarnished, silver plated. This one I like a lot because, again, it's silver plated, Teflon insulated, and a gold conductor down the middle of it. There are several hundred adapters of various persuasions that you can get to go with a PL259. Here's one that you may not have seen. This one, and just to show an example of what's out there, and just about anything you could need is available, actually. This one is a double male, so it's a male on both sides. Used to be, it was a common connector when we had separate transmitters and receivers. You'd connect the relay, the changeover relay, the coax changeover relay, to the back of your transmitter with one of these. There are also adapters that adapt from one kind of connector to another. By that I mean from, for example, this one has a UHF male or a PL259 on one end and an N female on the other. So if you had an N connector and you needed to go into an SO239, this is the adapter that will do that. This adapter is available in a lot of different varieties. This one is nickel plated. You can also find it silver plated. And by the way, and a bulkhead connector for an N, that's also available. So another easy way to install a coax connector onto a chassis. A friend of mine dumped out a bunch of coax connectors. Here's something you may not be familiar with. It's a threaded cap. And you can, if you have connectors outside, like an SO239, and you want to, and this happens to be an N connector, but if you want to protect it from the weather, let's try one of these on here, and it's protected. There's a price point, $1 to $2. There are also plastic caps that are really inexpensive that you can slip over and weather protect the connector. There are also a number of, the one I'm going to open up here is a 2-inch bulkhead type. Comes with a couple of nuts. So if you wanted to penetrate something that was an inch thick or so, this is what you'd use. And these come in various lengths. This one, I believe, is 12 inches. And again, they generally come with nuts, so if you had to go through like a concrete block wall or something, this is a great way to do it. Recommend putting some kind of washer on underneath the nuts on this one, like a metal washer and then perhaps a rubber washer. Also, so I'm looking through these connectors. There are, this is a right angle connector. So if you needed to turn a corner, or if you have a transceiver that's up against a wall and you need to, and you want to change the space from the back of the transceiver to the wall, it's a tight space, you can use one of these and then run your coax in this way. So these are generally $3 to $4. You need to think about the source for some of these coax connectors. If you can, avoid the Chinese ones because generally they're not very good. The connectors I'm showing you were made for the most part in another country, Taiwan, and they were CNC machines, so they're generally pretty good. Also, there are, as I talked about adapters, there are a ton of adapters from one kind of connector. Here's one. This is an N connector on one end and a B and C on the other. So B and C bayonet Neil connector, I believe, and the N connector, I believe, is a Neil connector. I think that's the guy who invented it. This is a good time to talk about impedance. These connectors tend to be used on instrumentation because their impedance is predictable, and this connector, the end connector, comes in a couple of different varieties for 50 and 75 ohm coax. So if you're wondering what the impedance is of PL259, I don't know. It varies with the frequency. The range from somewhere around 30, 40 ohms to 60 ohms. So they're in the ballpark of 50 ohms. Does it matter? Well, it matters at UHF, but we're not going to use this connector at UHF, and it does incur some losses at UHF. It's such a short portion of a feed line in a portion of the wavelength that at HF, when we've done that test where I connected a whole bunch of PL259s and SO239s and double males and double females, there wasn't a measurable loss. So it doesn't really matter what the impedance is as long as it's kind of in the ballpark, and this is. There are also right angle BNC connectors like this one. Let's see, what else have I got here? Here's one that you may not have seen, but it's used in a lot of mobile applications. It's an SO239 on one side. You drill a hole, and it has the standard 3/8-24 coupling nut on the other, so that if you wanted to install a whip through a piece of metal, this is what you'd use. There's a nylon shoulder washer that fits through a 1/2-inch hole, and that gives you a way to screw in the standard whip thread. The ferrule on a typical whip is a 3/8-24 thread. So that's a pretty handy thing if you're going to do a mobile installation. Let's see, what else have I got here? Here's another variation on, oh well, here's what we should talk about. This is it's called a lightning arrestor, and it's male on one side and female on the other, and it has a small gap on the inside. The theory being that lightning would come in, it would arc to the gap instead of going onto the transceiver or transmitter or receiver. It doesn't work. It really doesn't. There's a small gap here, and yeah, what happens is the lightning strike is going to go both ways. So it's still going to destroy the transceiver. This is a coax connector that I helped design. It has a gas discharge tube on the inside that will short at a certain voltage. So if a lightning strike were to enter, it would be shorted to ground, and there's a grounding screw on the other end, as opposed to the arc, which splits the lightning strike. This one would shunt it to ground. Probably okay to have these, and they do work to a point, but if you've got a lightning strike that hits your antenna, nothing's going to save your transceiver except disconnecting it and setting it aside. My advice is, if there are lightning strikes in the area, disconnect everything from the transceiver, and other stuff, just disconnect it all. Put it on a chair, or put it aside. Getting back to adapters, if you wanted to go from pretty much any kind of BNC to UHF to N, it's there. If you want to go N to UHF male to BNC, they're available in all kinds of shapes and sizes. SMA, those are readily available in a variety of sizes, even ones that you think might not exist. There's actually somebody who makes it and sells it, and you can find it if you Google it. Some of those are sold by Mouser, for example, and that's a good source to find it. Getting back to putting on a coax connector, in the next half of this video, I'm going to just very quickly go again through making a jumper and installing a coax connector. So I'm going to end this video here. If you have any questions about coax connectors, post them below. A lot of guys are good at answering questions, and I do appreciate those who come in with an answer before I do. It's good. Okay, that's it for right now. Going to start another video real quick and do the installation of a coax connector. Thanks for watching. I'm Jim, W6LG for Ham Radio Basics. See you the next time, which will be doing one of these connectors. Thanks. Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room. I'm going to install a coax connector, and I'm going to do it really quick. I need a jumper for my station, so I had this one from another short piece of coax from another project. What I'm going to do is cut off the end. I'm going to do this with some of the proper tools. If you want to use a knife, go for it. You could even use a pair of scissors if you want. I'm going to use a coax prep tool, and to position the tool on the coax, I'm just going to sort of eyeball it. I know that the center conductor I want to extend past the end of the pin, so I'm going to cut it at a point where it will be a bit long and then trim it afterwards, and that'll make more sense after I get it together. Okay, I've pulled that off, and I'm going to take off the dielectric. So, and the next thing I have to do is remove a little bit of the jacket on the coax. So I've got the center conductor long on purpose, and I'm now going to pull off a little bit that didn't quite cut through, so I'm going to do it manually here. Okay. And that's off. So now I've got about 3/8 of an inch of braid. I've got about 1 1/4 inch and 1/8 of center conductor. I'm going to do a crimp connector as opposed to solder type because I like the crimp better. So I'm going to open up a bag. Got to remember to put the ferrule in. It's hard to do this one wrong. You can forget to put on the barrel of the PL259 and solder it, but you can't crimp it without this ring. So I'm going to push that on. So, and use these. Make sure there's nothing going across. Now I'm going to push this down until it's pretty much up against the jacket. And then I'm going to slip the ferrule over, grab the crimping tool, crimp that. Then I'm going to cut this off, and I dropped something on the floor. Alright, now all I need to do, and I'm going to do that off camera, is solder, get solder to flow in through the pin. That's installing a coax connector. How do you test it? There's a guy who did a video and he licks the coax connector. I don't recommend you do that. Puts an ohmmeter on one end and licks the other. I don't even want to go there. So, transmit through it. Test it with an ohmmeter, of course, real quick, and if it shows open, it's probably okay. You can check continuity from pin to pin, but put it into the transmitter, put a few watts through it, make sure it works okay, and then go to 100 watts. It's just that easy to install a coax connector, and it's much easier than fiddling around with a PL259 that you have to solder through these little holes and not melt the dielectric. All right, get these things off. That's it. That's how you put on a coax connector, and it's the same thing for RG58, RG8X, RG59, LMR400. It's the same process, and that connector will work fine. It's just got to do a little bit of soldering. Thanks for joining me. If you have any questions, post them below. If you have a comment or an idea about how to put on a PL259, let me know. I'd like to read about it. And for now, I'm Jim, W6LG for Ham Radio Basics. Thanks for joining me. See you the next time. Thanks. Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. Been asked several times about what is all of that stuff behind you. And today I'm actually in the station instead of a green screen. And I'm going to go through some of the boxes. At the time I was manufacturing and designing antennas, it was great to be able to put an antenna on a vehicle, connect it to a bulkhead connector, and make some tests in here with the computers and the transceivers. I'm no longer manufacturing antennas, so a lot of it now is just remnants from that time. I have the basic antennas are 3 towers. One has a 10-meter beam. The other 2 towers have 20-meter Yagis, 4-element monoband Yagis. And one Yagi is on the south side of the house. That's the most prominent part of the property. The other Yagi is down the hill just a bit, but it really works the best. And it's 100, maybe 120 feet down the hill. Both are fed with hardline, 7/8" hardline to cut feedline losses. Probably I'm delivering 95% of the power to the antennas. The antennas have 6 dB gain. There are 2 of them, so combined, probably in the ballpark, and including sloping ground, between, and this is a huge range, between 10 and 12 dB gain. What really counts is what can I hear? So it hears really well. The antenna down the hill is really quiet. There are no houses in front of that antenna. The antenna on the south side of the house shoots through the house to Europe, so a lot of times I'm picking up noise from inside the house. Anyway, I'm going to go through the station real quick. I'm going to take the camera off of a short tripod that's mounted on, put it on a floor tripod. I'm not going to hold the camera. I'm just going to shoot pictures of the stuff and then try to explain what it is. It has to do with basically feeding 2 antennas and how do I balance it out, achieve a good SWR and a good result. So give me just a minute. I'm going to move the camera. I'll start with the transceivers and kind of work my way around. If you have a question at the end, send it out and I'll be happy to answer it. Been busy with doctor's appointments and other things, but hopefully that's going to slow down just a bit. All right, be right back. Okay, so those are the 2 K3s. One on the right's for SSB. I've got an SDR receiver connected to the IF. That's what the boxes are, playing with that. The other one's for JT65 and Whisper. To the left of those 2 is the Elecraft P3, which is a pan adapter. On the opposite side is the KPA 500 amplifier, which is good for 500 watts. It's kind of a nifty amp. It's showing it's at 38 degrees C. Above that and running, just for demonstration purposes, is a very much modified Drake L4B. By that, the power supply is in a similar size box to the RF deck. It has 2 transformers in it. The amplifier has instead of 2 3500Zs, it has a GS35B. It's capable of easily running legal limit. To the right of that is another Drake L4B. That's also modified with a higher voltage plate transformer. To the right of that is the ASU FT450, and above that is a switch box for different antennas. It's homemade. Below that are the 3 rotators for my towers. That thing in the corner is a power supply for 12 volts. The Drake speakers are connected to the 2 transceivers through a switch, so I can select any one. There's a Drake MN2000 antenna tuner that works great. Further to the right is yet another speaker, so I can do left and right channels. So it could be VFO number 1 and VFO number 2 when doing dual receive. The little box above is used to switch between amplifiers, keying lines. I use 2 monitors. One's logging DX cluster. The other one is the SDR receiver connected to the IF and acting as a pan adapter. All the way to my left is a, do I get there? Is a homemade amplifier.
The bottom part of it is a Staples file cabinet turned around backwards with a Verac mounted in it and an on and off switch. The RF deck is pretty much all homebrew and frankly pretty junky. On top is a small antenna tuner. The little black box measures the temperature and if needed increases the fan speed inside the amp. So it's looking at the exhaust temperature. At 32 degrees it starts to come on. Now these boxes are going to be tough to explain. Start at the top. Each antenna has its own little tuner system. So I can, one knob is one antenna, the other knob is the other antenna. So I can do a little bit of matching, let's say from 25 to 75 ohms. That's a box made out of a Drake speaker, a 2-watt meter, so I can measure the power going to each antenna and decide if I want to change. I'll show you how that works. If I want to change the power to one antenna. Okay, so that box switches in different delay lines. These switches are different lengths of coax that come out the back. Antenna number 1, antenna number 2, and by adjusting the matching network above, I can change the amount of power going to each antenna if I want to. Most of the time I want them balanced where they're getting the same amount of power. You can see they're both mid-scale for about 100 watts. And actually are a little bit more than that. So that's what that box does. The bottom box is a standard antenna tuner, and its job is to match to a 50 ohm. So if I'm using both of those antennas and I can't quite get them as a combination to 50 ohms, I can invoke that antenna tuner. So my SWR will be less than 2 to 1. And I can select either transceiver with switches, coax switches that are bolted to the bottom of the desktop. So I reach underneath to put them in the line. I don't need to see them. I know that transceiver to the left is switching it to the left. Switch the knob to the right, and the transceiver on the right is connected. So that's my station. This is the microphone I use. It's an old static 10D. It's from the 1960s, but it has an Art Deco look. It's a really good mic, has great quality. The antenna tuner behind it, I frankly don't use much. It's there, I have it. It's some of the Drake equipment. There's another antenna tuner. For a guy who doesn't like antenna tuners, I've got a lot of them. That's the Elecraft antenna tuner that matches the KPA 500. Transistorized amplifiers don't like high SWR, so that's pretty much a necessity. All right, that's my station. I think I've shown pretty much everything. So hope you've enjoyed that. Thanks for joining me. This is Jim, W6LG73.
In today's video, we're going to be talking about diode mixers, like this ADE-1ASK mixer from Mini Circuits. When selecting a mixer for your application, there are a couple of obvious considerations. One, is it operate over the frequency range that you need, and two, is it packaged the way that you need it to use in your application. Beyond some of those obvious considerations, probably the next most important consideration is the drive level, or LO, local oscillator drive level for the mixer. And usually in mixer specifications, this is just called the level of the mixer. And you'll see that there are mixers that are level 7 mixers, or level 10 mixers, or level 17 mixers. And what they refer to is the drive level for the local oscillator input frequency. A level 7 mixer means that the mixer requires plus 7 dBm drive level into the local oscillator port. Level 10 means it's 10 dBm, level 17 means it's 17 dBm, etc. And this is important because this really sets the response of the mixer. Now, setting the local oscillator drive power correctly will ensure that the diodes in the mixer are getting fully commutated, and by doing that you ensure that you minimize the conversion loss from the RF input port to the IF or converted output frequency port. Now, a subtle thing that's interesting to note is that when we talk about, say, a level 7 mixer like this one, that refers to the amount of drive power plus 7 dBm as measured into a 50 ohm load. But a mixer's input is not going to be a perfect 50 ohm load. It may have an SWR of about 2.5 to 1. So if you actually measure the drive power at the mixer input, you're probably not going to see what you'd expect, especially if you set up the RF drive power into a 50 ohm load. Nevertheless, the specs refer to the drive power as going into a 50 ohm load, kind of regardless of what happens to it when you connect up to the mixer input. Let's take a quick look at that. Okay, I'm going to disconnect the LO drive from this mixer, and we'll move it over and set it up onto the spectrum analyzer input. Okay, so with the LO connected to the input here, you can see that my local oscillator is at 100 megahertz, and we can see it's at plus 6.96. That's pretty darn close to plus 7 dBm. Let me reconnect it up to the mixer, and we'll take a look at it in the time domain with the scope. Alright, let's turn on scope channel 1 here, and bring my probe over. Got a nice short ground lead on here, and let's measure that signal level. If we take a look at it, it doesn't really look sinusoidal, and now that's to be expected because the load presented by a diode mixer is nonlinear. So as you commutate the diodes, the impedance changes, and that's going to change the waveform, so that's to be expected. Now if we look at the RMS value on the measurement over here on the scope, it's showing about 305 millivolts. Now a plus 7 dBm signal would normally be about 500 millivolts RMS into 50 ohms. So we're not seeing what you'd expect. But this is really what happens. So when you're considering the LO drive power for a mixer, you would measure it with a 50 ohm load and expect that it'll be something a little bit different when you look at it with a scope maybe inside your circuit. So if you're really kind of unsure about how much LO drive power you need, you might want to play with adjusting that and taking a look at conversion loss as a metric to see whether or not you've got adequate drive power for the mixer. Okay, so let's take a look at the insertion loss with respect to the LO drive power. So there's my LO signal as coming out of the IF port. Remember, we're putting plus 7 dBm in, and I'm getting about minus 34 dBm out. So I've got a little bit more than 40 dB of loss from the LO port to the IF output port, and that's right in line with the specs for this mixer. I'm also putting in an RF signal at at 110 megahertz. That's this signal here, and that's going to be kind of attenuated greatly here too. I'm putting minus 30 dBm input to the RF port, and I'm seeing something more like minus 55 or so here coming out of the IF port, and that's again pretty typical. So the converted signal is going to be the difference of those. That's the one we're really interested in. That's this signal here at 10 megahertz. Now we can see what the insertion loss is because I know that I'm driving the RF port with minus 30 dBm, and I'm getting about minus 35.3. So that means that I've got about 5.3 dB of conversion loss in this mixer, and that's about what it's supposed to be. Now if I reach up to my LO signal generator here, and let me start reducing the power. So I reduce the power, I can see that coming down, and I can also see the power coming down on my IF output. So I'm increasing the amount of insertion loss or conversion loss that I have in the mixer. So let me bring my LO drive back up again. And I see as the LO drive is coming up, my conversion loss is getting less and less. And I'll reach a point where, as I keep popping this up, my conversion loss kind of levels out. If I go way up high in my RF power, my conversion loss is really, it's kind of stuck there. So I'm at minus 35.2. If I come back down, it's still staying pretty steady. And then I'll reach a point where it starts coming back down again. See how it's coming back down? It's because I don't have enough LO drive power. I'm sitting at about 0 dBm drive power now. And if I bring it up till, keep bringing this back up again until this goes steady, okay, that's right about there. That's plus 7 dBm. Anything higher than that, I'm fully commutating the diodes, and my conversion loss is now holding steady at at about 5.2, 5.3 dB. So this is how, if you don't have a spec on a mixer, or if you've homebrewed your own, diode ring mixer like this one, the way to kind of decide how much drive power you really need is to vary the amount of LO power coming in and look at the IF output. And when the IF output no longer raises up anymore as you bring the LO drive power up, then you know you've reached the required drive power for that diode ring mixer. So another rule of thumb to think about is how much RF power can I put into a diode ring mixer? And that's also related to the LO drive power. A good rule of thumb is that you want your RF power to be probably 10 dB lower than the LO drive power. If you make it any higher than that, then you start running the risk of getting some distortion, because the RF will start commutating or affecting the commutating of the diodes. Now, one measure of that is the 1 dB compression point. And the 1 dB compression point is where, as you go up in RF power, the IF output, or the converted output, will track that one for one. There'll be the loss there, in this case about 5.3 dB. But as you go up higher in power, now eventually the RF output, or the IF output, won't go up as much as the increase of the RF input power. Once that deviates by more than a dB, for example, the conversion loss goes from 5.3 to say 6.3 dB, that's the 1 dB compression point. And that's going to occur a couple of dB below the LO drive power typically. So you want to be well below that so you don't get into that area of distortion. Because 1 dB compression point is just one measure of distortion. Other measures are like the third order intercept and things like that. And all of those will be related to the input power with respect to the LO drive power. If you've got an application where you need a higher RF input into the mixer, then you're going to have to go with a mixer that's either an active mixer, or if it's a diode mixer, something with a higher level, like a plus 10 or plus 17 or plus 13 or whatever is necessary to get that LO drive power high enough to prevent distortion issues from your RF input to the IF output. And so I hope this video has given you a little bit of insight as to what's meant by the level of a diode mixer, like a level 7, level 10, etc., and what that affects when it comes to the mixer's performance. Any questions, of course, please post them below. If you like the video, give me a thumbs up. And if you haven't subscribed already, please do so, and tell your friends. And thanks again for watching, and we'll see you next time. Hey everyone, it's Alan, W2AEW, making a rare appearance in front of the camera this time instead of behind it. I just want to give you a little bit of a status update as to my medical condition. A lot of folks have asked. Also take this time to answer a lot of frequently asked questions that I get, and also provide you just a little bit of well-deserved thanks. So let's get started. Now, regular viewers know that I seriously broke my ankle earlier this year, and a lot of folks have asked how I'm doing and have wished me well in comments of videos that I've done since then, and just happy to report that progress is moving along slowly but surely. I'm still hobbling around a bit, but I am being able to get around and drive and that kind of a thing again, and obviously able to get down here into the shop. So I thank you all for your well wishes, and I'm certainly glad to report that things are moving along in a good direction there, even though I'll be carrying around a small hardware store in my ankle for the foreseeable future, unless the screws and a plate give me a problem in the future. They're all just going to wind up staying there. Well, one of the really common questions and comments that I get on my videos is, am I a teacher? And no, I'm not actually. I spent about 25 years as a design engineer, test engineer, and application engineer, and since 2006 I've been a field application engineer for Tektronix. So in that role I do a lot of teaching and tutorials and things like that, and helping customers out with using equipment and applying equipment to solve their problems. So I do have to do a lot of education, but I'm not a teacher or professor by profession. So just an engineer that likes to play with this stuff. Another very common question I get is, do I maintain an index of all the videos that I've done to make it easier for you to find them? And the answer is I do. A lot of you have found it, and I've told a lot of folks about it, but if you look at my main channel page, at the main channel graphic there, you'll find a link right about where I'm pointing over here that says Video Index. This index was started by one of my viewers Dino KL0S several years ago, and I've picked it up and maintained it since then. So a great resource. The indexes lists all the videos numerically and also lists them by topic. And every video is hyperlinked, so it makes it really easy to find the topic that you want, click on it, and watch that video. A lot of folks have asked if I'd set up a Patreon account, and I haven't. I really didn't have any interest in creating any content that was, paid for content. I want everybody to have equal access to everything that I create. So still a lot of folks have wondered how they could support me, and the great comments you give me is support enough, really, but some folks are insistent. So actually several months ago I put a little PayPal link up on my channel. Link is right in the corner of the graphic right there is a little P. So if you're so inclined, you could certainly follow that link to support the channel. But and I thank those that have actually found it without me saying anything about it at all. But that's there just in case you're so inclined, but I never expect anything financial from any of my viewers. I just want you to watch the videos and give me good comments, and that's pay enough for me, that's for sure. Another question is, do I take video requests? Well, really, most of the ideas that I have for videos come out of either requests that folks have made or comments that they've made to videos that I've done, or sometimes even interesting questions that I see posted on blogs like EEV blog and things like that. So certainly I'm open to requests. Some of them will get addressed very quickly because I find the topic very interesting and timely. Others might not really get addressed for quite some time because I don't have the facilities, the capabilities, that type of a thing to get a particular topic done. But I'm certainly open to requests through leaving comments directly on my channel. Another question I get pretty often is where can I get a copy of the notes that I use in the videos that I create? Now for most of them, especially recently, any of the notes that I create or use or show for a particular video, I'll scan and create a PDF file. And you'll find that if you look at the video, there's always a kind of a description down below to talk about what the video is. And there's usually a show more button. And if you click on that, that will usually open up to a place where there's more description about the video and any particular links that might go to a PDF file or other videos that I've referenced. So it's always a good idea to look in that video description because there'll be some good stuff in there, including links to PDF files for my notes. Now, one question I've gotten a lot just over the last week is, since I work for Tektronix, have I gotten a hold of one of the new 5 Series MSOs from Tektronix, and will I be doing videos on that? So the answer is, of course, I've got one here I've had for a couple of weeks. And I have done a few videos, but the videos that I created are actually on the Tektronix YouTube channel. So just a couple of them. If you want to see them, I will put links to them in the video description down below this video. So go take a look at those. And finally, I really just want to say thank you. I've got over 67,000 subscribers to the channel now, and surpassed 8 million video views right around the beginning of the year. So that's pretty amazing for a little channel that I create, and videos that I create down here in my little basement shack, so a basement lab. So I really appreciate it. All the comments, really kind of inspire me to keep going and continue doing this. And I wish I could keep up a cadence of doing a few videos a month, but I do as many as I can. But I really do appreciate all the support, both in comments and getting thousands of views on my videos when I post them. It really means an awful lot to me, and I thank you for that. Again, always keep the good comments coming. Tell me what I'm doing wrong, and tell me what you'd like to see more of, and I'll try to do the best to accommodate you. Thanks again, and we'll see you next time. Thank you.
To my radio room here on Wolf Mountain. When you get your ham radio license, one thing that becomes pretty apparent early on is you're going to be looking at meters, and could be SWR meters, power meters, S meters, voltmeters, watt meters, meters, and it's a neat device. There are a couple broad categories of meters that I'm aware of. There may be some others. Digital and analog. And what I'm talking about is single sideband, which if you look at the waveform is up and down, up and down, up and down, up and down. And so you've got this sometimes called in some cases called a Christmas tree pattern, but no matter what you call it, if you look at it on a scope, there are excursions that go way up, and some that don't go that far, and some that are very tiny. So as you talk, it's doing this. The mechanical meter that you're looking at could be a watt meter, could be a plate current meter. Can't keep up with that. So, and I'll graphically show that in just a second. So you may have a voice peak that goes to 100, but the meter only indicates 10. And if you turn up the drive or the mic gain because you want the meter to indicate 100, all kinds of things start to go wrong. There's distortion products that enter into the picture, perhaps RF feedback. There's a chance of splattering or causing distortion, causing splatter that interferes with other folks on either side of you. If you don't have a scope, and most of us don't, and most of us don't want one, you can take a measurement with a peak reading watt meter and compare it to what the mechanical meter is showing you. And so let's do that now. I'm going to I've got a bunch of watt meters here, and I've got a couple of amplifiers. Let's do this. Let's transmit a carrier at something that gives the panel meter full scale reading. Could be 200 watts, could be an amp of current, could be any number. And then we will run the same amount of power, getting whatever output that is, probably in the neighborhood of 200 watts, and see what the mechanical meter shows. And what it's going to show is a very small percentage of full scale, and in some cases 10%, some cases 20%. If I were to run the mic gain up until the meter indicated a full scale, and that would cause distortion because you'd be driving the crap out of the amplifier. You'd be exceeding the grid current rating of the tubes, one or more. You shorten the life of the tubes if you have a tubed amplifier, and you will destroy some stuff along the way. Along the same line, I've found that in testing the K3 and the other handy transceivers that I have, that oftentimes the voice peak from the transceiver exceeds its nominal rating. So, for example, the transceiver may say it's capable of 100 watts output. You hook it up to a watt meter, and yeah, it does 100 watts out. The K3s barely do 100 watts. But occasionally, especially at the beginning of a transmission, it may have excursions that go way beyond that. And what we're going to see is my 100 watt transceivers occasionally put out 140 watts. So does that hurt anything? Well, it doesn't if you're just into an antenna, because the antenna doesn't care. If you're into an amplifier, it hurts. And what it's going to do is the drive that you're putting into the grid is not going to be dissipated into the plate. It's going to damage the grid of the tube eventually. And I'll show that in a couple of tests. The watt meter is going to show way more than 100 watts out, but just for an instant. And if you look at it with if you have an SDR receiver, which makes kind of a neat scope, and you look at the transmitted signal on that SDR receiver, you're going to find spikes that go beyond, if you draw a line at 100 watts, you're going to have spikes that go beyond that point. Hopefully that's clear. It may not be. The part about the watt meters, the panel meter, is really important, because as you graduate to bigger and more powerful pieces of equipment, the chance of causing distortion and interference to others grows. So I don't want to belabor the point. I'm going to film these meters. I'm going to move the tripod around. I'll narrate over that what I'm doing, and basically I'm going to count and give my call sign. I'm going to do steady carrier. I'm going to put the transceiver in the FM mode, key it, and then I'm going to talk into the microphone in the SSB mode, and we'll look at the difference. And it's really pretty surprising. There are going to be times when you think you have no output, and if you're looking at an analog meter, when in fact you have a lot of output. All right, see you in a minute. I'm going to put the tripod over here and do some tests. 1, 2, 3, 4, 5. Hello, test, hello. 1, 2, 3, 4, 5. Hello, test, hello. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Hello. One, 2, 3, 4, 5. Whiskey 6 Lima Golf. 1, 2, 3, 4, 5. W6LG test. Ella test. Ella. 1, 2, 3, 4, 5. One, 2, 3, 4, 5. Hello test. Hello. One, 2, 3, 4, 5. W6LG. One, 2, 3, 4, 5. W6LG test. 1, 2, 3, 4, 5. One, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. At the end of that video, I was videoing the play current meter on a linear amplifier, and the play current meter, I didn't say it in the video, was indicating about 1/3 of the total peak play current. So again, an analog meter in the SSB mode doesn't have a lot of value because it can't keep up with the changes, the swings in voltage or current. So having a peak reading watt meter is a really good thing and will give you a better feel for what the output is. So analog meters and SSB, not a lot of value. In CW, key down, or in the FM mode, it's great because you got a steady state and you can read the meter. If you have a question, please post it below. If you have an answer to a question, please go ahead and do that. I've had some really great answers from some guys. If you haven't subscribed, I hope you will. I've got a couple of videos in the works right now and hope to have those out in the next few days. I'm Jim, W6LG for Ham Radio Basics. Thanks for joining me, and see you the next time.
Is the frequency in use Whiskey 6 Lima Golf? Anybody using this frequency, Whiskey 6 Lima Golf?
No, you're good. I just cleared out, so you're good to go.
All right, thanks. I'm sorry, double with you. What's the call?
KC9RF.
Okay, thank you, W6LG. Name is Jim. CQ calling CQDX, CQDX beaming Europe, Whiskey 6 Lima Golf. W6LG calling CQDX, CQDX calling CQDX. Beam towards Europe, short path, Whiskey 6 Lima Golf. W6LG calling CQDX, CQ calling CQDX, Whiskey 6 Lima Golf. W6LG listening.
Good morning from Germany. W6LG, DJ4 Ocean America. Good signal, Jim. A solid 5-9 and over. Go ahead.
Yeah, Mr. Gaia, how are you, sir?
Quite well this morning. It's a brisk morning here. It's just 12 degrees Celsius. And the humidity is high, too, but we're going to have a very nice warm day today. A typical summer day. Temperature will be up to about 25 or so degrees, which is just the upper end of my comfort zone, Jim. Good morning, good morning. I heard you yesterday also. and was looking at listening for Joe, of course, but not yet. Maybe he's listening too. See, if we're both just scanning the bands and looking for one another, nobody's transmitting. Nobody will hear each other. H.I., go ahead.
Well, that may be part of it. It may be that a lot of guys are listening, but it's been awfully quiet. DJ4OA, W6LG. By the way, we're about 50 cycles different in frequency, and I think my calibration may be off. So I've got to see if I can net the transmit and receive. I suspect I'm off a little bit. Anyway, 5x9, 59 plus a little. I didn't pay real close attention to the S meter, but you're plenty strong. And okay on Joe. Yeah, the conditions the last few days have been good. Who knows how long that's going to last? I'm thinking maybe a few more days, and it'll go back into the WC. DJ4OA, W6LG, over.
Roger, Jim. Yeah, as you say, as long as it may last, H.I. And the one observation I made is that this is a very brief window of opportunity for us. In the old days, olden years, as they say, we would have propagation on the West Coast in my morning hours to the evenings from, say, late April until at least August, if not even the beginning of September. But with a low solar cycle at the moment, it will be a brief window only. See, the last days of May and probably the last days of June will be just about it. But anyway, yeah, very good. As far as frequency, I was trying to adjust to your frequency, and I think I'm pretty close. At least this is when I'm hearing your voice the best, Jim. Very good. So, looking out the window, I see clear blue skies, but the one thing I don't see is our oldest cat. We have two cats, and the older one is giving us trouble because he's running away from us. He's not coming to the house anymore, and that gives great distress to Monica, and we'll be waiting for the test results there. Okay, Jim, very good. So, do work some more and get some all the DX here. It's a beautiful signal, of course, and as I said before, these opportunities will not last forever. So, Jim, good morning. I'll be looking for Joe, and I did have a good contact. Well, see, on Friday, I had two contacts with Joe. One in my morning, his evening on Thursday, of course, and the other one in my afternoon. So, the second one on 20 meters was not nearly as good as the first one, though. Anyway, Jim, good night. Thank you so much for the contact, and good luck on the DX. You have one of the top signals from the West Coast. I think you know that very well, Jim. W6LG, DJ4 Ocean America. Bye-bye.
Okay, thanks, Wolf. And let's see if Joe's on frequency. Joe, are you here?
I don't hear him.
Okay, just hoping he was. All right, 73 Wolf, thanks so much. DJ4OA, W6LG. Bye-bye.
Bye-bye, Jim. Thank you. I think the men will peak in about half an hour or so. 73.
See ya. Anybody else over before I get out of here? QRZ W6LG over the North Pole. Again? Okay, Fox Mike Golf. FMG, what's the prefix? Over. Okay, look, I asked for Fox Mike Golf. Station ending Italy. I didn't say your call sign. Fox Mike Golf, please go ahead, sir.
Ocean Henry, 6 Fox Mike Golf in Finland, over.
Oh, okay. Very good. Nice to hear you again. Ocean Henry 6, Fox Mike Golf, Whiskey 6, Lima Golf. Good morning, Timo. Nice to hear you. 5x9. My name is Jim, Japan, India, Mexico. Jim. I'm in Northern California in the Sierra Nevada mountains, north and east of Sacramento. Ocean Henry 6, Fox Mike Golf from Whiskey 6, Lima Golf, over.
Okay, QSL2, 59 and plus 10 dB over in the West Coast in Finland, over.
Well, I'll take that. What are you using for an antenna, Timo?
6 element dry-band Yagi.
Okay, sounds really good. I'm using two 4-element Yagis and Elecraft K3 and a homemade amplifier. OH6 Fox Mike Golf, W6LG, over.
Okay, QSL, only 200 whiskey, only 200 whiskey at the moment, and old boat anchor scenery issue Fox Tango 1000 Delta over.
Okay, well, you're 5x9 plus 5, so the 200 watts is doing great. 73 Timo, thanks for the call. 086 FMG for your final transmission, Whiskey 6 Lima Golf. Go ahead, Timo.
Okay, God bless.
Thank you, sir. 73. QRZ? You're pretty weak. Try that again. QRZ W6LG.
Fox Yankee.
Fox Yankee, what's the call sign? Fox Yankee, over.
Yeah, Roger, Jim. Nice to see you. This is Radio Alpha 3, Fox Yankee. Yes, Radio Alpha 3, Fox Yankee. Yeah, that is true.
Okay. Nice to hear you again, Mike. Radio Alpha 3, Fox Yankee. Whiskey 6 Lima Golf. Dober Utra, Mike. Manyazavu, Jim. My name is Jim. I'm in California. You're 5x858. Radio Alpha 3 Fox Yankee from Whiskey 6 Lima Golf. Brilliant.
Yeah, Roger, Jim. Nice to hear you again. Thanks a lot for answering. Wouldn't keep you. Enjoy my love. Definitely 60 years. Good luck and catch you later.
All right. Thank you, sir. 73. Appreciate the call. RA3FY Whiskey 6 Lima Golf. Dasodanya.
Bye-bye, Jim.
Again? Denmark, Japan 5 something kilowatt, DJ 5 something kilowatt, Whiskey 6 Lima Golf. Give me your call sign, please.
Whiskey kilowatt, Whiskey kilowatt, Delta 2 Whiskey kilowatt,
Del Japan 5 Whiskey kilowatt, Whiskey 6 Lima Golf. Okay, nice to hear you, Peter. I think you're 5x959. Peter, my name is Jim, Japan, India, Mexico. Jim, I'm in Northern California near Sacramento. Back to you, Peter. DJ5WK from W6LG, over.
Whiskey 6 Lima Golf, Denmark, Japan 5 Washington Kilo, and returning here. Thanks for 5 and 9, you 5 and 8 here, 5 and 8, a good signal from your side. Very clear, and the modulation is very good from your side. Microphone back to you.
Okay, thanks. I'm using 2 4-element Yagis and an Elecraft K3. What is your antenna, Peter? Over.
I have bought a 2-element quad from a Cubex 2-element quad, about 700 watt, and the antenna is at the moment only 10 meters over ground. The boom is 10 meters over ground.
Wow. And I looked at the S-meter again. You're 5x9 plus 10 on that transmission. So that Cubex quad is certainly working well. 73, nice to meet you again, Peter. DJ5WK from W6LG.
Okay. Thanks, Jim. Yeah, I brought it in the air, built it up last week, and it seems it works at low elevation. So thanks, have a nice weekend, 73, and till the next time. Bye-bye.
Okay, 73, Peter, thank you. Rafi, was that you?
Yes, Norway Radio.
Bye.
Well, to you. Good morning from Tel Aviv. Early morning, over.
Yeah, Radio Tel Aviv, nice to hear you. 4X4FR, W6LG. Good morning, sir, nice to hear you. 5x7, 5x8, Rafi. WX here, it looks like it'll be about 20 degrees tomorrow, so should be a very nice day. 4X4FR from W6LG. Go ahead, please.
Wonderful, yeah. W6LG, 4X4FR. Temperature here right now is 24. Going to be up to 28, 29, so just early spring, early summer. Going to be a long, hot, dry, humid summer. We already use our air conditioner here, you see, just because of the humidity. So the situation hot and humid is very uncomfortable. So better to sit in my shack, in my radio room, over.
Yes, I understand. All right, you're getting stronger. You're 5x9 that time, Rafi. Nice to hear you. If you hear Ed, Ehud, or Aaron, please say hello. I talked to David earlier. He was 5x9 plus. 4X4FR W6LG, over.
Roger, 73. And shalom. I'll send you some blessings from the Holy Land. That's the only support I can give you, over.
I will take that any day of the week, over.
Yes, you better use it. Shalom, thank you.
Yeah, you're right. You better use it. Exactly.
In today's video, we're going to take a look at the basics of the IQ modulator. We'll look at the block diagram and then describe and demonstrate its operation. We'll use the modulator to generate a couple of different types of modulation, and then we'll take a look at some of the impairments that might affect the operation of the modulator and look at those effects in the resulting modulated output. And then finally, we'll run a single sideband suppression test, which is a pretty common performance test that's used to characterize IQ modulators. Now, it's important for you to have a pretty basic understanding of IQ signals as well as how a diode ring mixer works in order to get the most out of this video. If you're not familiar with those topics, I recommend going and viewing these kind of prerequisite videos beforehand and then come back and take a look at this. If you want to do a little bit of extra study, there's a couple of additional videos that might be helpful, some more on IQ signals, the basics of mixers themselves, and I did a video on the diode mixer LO drive level. I'll put links to each of these videos in the description of the video down below. Now here's a block diagram of a typical quadrature modulator like this one from Mini Circuits. The local oscillator signal comes in and goes into something like maybe a quadrature hybrid, or maybe even a splitter and a delay line or 90-degree phase shifter to create the in-phase and quadrature LOs that are applied to the mixers. Now, the best way to understand the operation of the modulator is to consider these mixers as multipliers. So essentially here we've got the product of the in-phase LO and the I component, so I times cosine, and the output of this mixer is essentially Q times the quadrature LO, or the sine wave. So after the summation of those signals, we have the sum of I times cosine and Q times sine. Now, of course, as the I and Q signals are varied over time, that's essentially what creates the modulated RF signal at the output here. Now, in order to demonstrate the operating principles of the IQ modulator, rather than use this pre-built one, we'll use this one that I put together here with some basic components. I've got a pair of diode ring mixers. These are ADE-1ASKs from Mini Circuits. So they're right here and here. I'm driving the LO inputs of those mixers through a pair of connectors here that are going to a 2-channel function generator that allows me to generate sine waves that are in quadrature. So I'll use those instead of a quadrature hybrid. This will allow me to kind of take a look then at what happens if those signals are not in quadrature later on. The output of each of these mixers then goes into an RF splitter combiner right here, and then the output from that we're going to take to the oscilloscope and the spectrum analyzer to go take a look at things. Okay, we can see we've got 3 active traces on the oscilloscope, channel 1, 2, and 3. And where they're coming from is channel 1 is looking at the in-phase LO signal, channel 2 is looking at the quadrature LO signal, and channel 3 is looking at the output of the splitter combiner. All right, we can see that the channel 1, the in-phase local oscillator, is essentially our cosine wave, and then 90 degrees off from that is our quadrature LO signal, and they're both coming from the function generator. Channel 3 is the output of the combiner. Now right now we've got nothing applied to the I and the Q inputs, so they're effectively 0. And again, if we think about those mixers as multipliers, 0 times either one of these gives me 0, so that's why we have nothing at the output. Now, to demonstrate the basic principle of these mixers in the modulator, I've just hooked up a simple variable DC power supply to the I input. Well, let's take a look at the effect of that as we turn this voltage up. Now, with 0 volts applied to the I and the Q inputs, we essentially get nothing out because the mixers are multiplying by 0. If we apply a small DC bias to the I input, we can now see an output that comes out that's exactly mirroring the ILO, or the in-phase local oscillator. Now, that local oscillator signal has dropped in amplitude, and the reason for that is because by turning these diodes on, we're now allowing the function generator to look through the mixer and actually see the 50 ohm termination on the other end of it. So that's what's reducing the amplitude of the I signal here. So now let's look at what happens if I reduce that DC input amplitude and reverse its polarity and apply it in the opposite polarity. So now with about a negative 300 millivolts applied, I'm getting an output, but now it's 180 degrees out of phase from the ILO. So by varying the input to the mixer between a positive value and a negative value, we can get either an in phase or 180 degree out of phase signal from the I side of the IQ modulator. Of course, similarly, if we apply a positive DC bias to the Q input, we're going to get an output that is in phase with the Q local oscillator. And if we reverse that polarity, we'll get an output that is 180 degrees out of phase of the Q. So we can see that we're getting, can vary between in phase and 180 degrees out of phase of the I and the Q, and those two signals are going to be the ones that are applied to the summing circuit to create our modulated output. Now if I apply the same DC bias to both inputs, I essentially get another sinusoid out, but now its phase shift is midway between the I and the Q. And that's the whole idea. When we adjust the magnitude of the I and Q products in the modulator, by varying their magnitude, we'll get a sine wave output whose phase can be varied to anywhere between plus and minus 180 degrees, depending on the magnitude of each I and Q component. In order to demonstrate a couple of basic digital modulation types, I'm using the IQ signals that come out of my vector signal generator. I'm going to apply them to the I and Q inputs of my quadrature modulator. But in between, on the I input, I'm going to give myself the ability to inject a DC offset, so we'll take a look at the effect of that. And on the Q input, I've given myself the ability to adjust its magnitude independent of the I signal, and we'll take a look at the effect of that on the modulation as well. But the first thing we'll do is just apply them directly over and take a look at some basic digital modulations. So now in this case, I've got the Q signal sitting at essentially at 0 volts, but the I signal is varying between some negative value and some positive value with this kind of binary pattern. And this is going to create a binary phase shift keyed signal, where we're going to have the RF output be at one phase during a low and at 180 degrees out of phase during a high. Let's zoom in on this and actually see that. So I'm going to zoom in here a little bit and take a look at one of these transitions. I'm going to add in a reference signal here that might make it a little bit easier to see what's going on. This green square wave I've just added is not affected by the modulation, so we can compare the phase of the output with respect to that. And we can see that while the I input was high, the peak of my carrier is occurring, right about at the rising edge or just after the rising edge of the square wave. And as we transition down through 0, we can see that the carrier collapses down to nothing, and as we go down negative, now the peak of that carrier is occurring 180 degrees later during the right after the low of the square wave. So we're basically created binary phase shift keying, alternating the phase between 0 and 180 degrees between the high and the low. Now in this case, the I signal is filtered. If we unfilter it, make it transition a lot faster, it's a little bit more obvious that the abrupt phase transition that we're getting between the 0 and 180 degree phase states. But in most systems, the baseband signals, the I and Q signals, are filtered to slow down the phase transitions, and that helps to minimize how much bandwidth the signal occupies. Now if we add in a similar signal to the Q, now I've got I and Q signals that are both varying between a positive and negative value with, again, essentially a digital pattern. And what this is going to result in now is 4 different states of the phase. One when both the I and Q are sitting low, another when they're both sitting high, and then 2 more when the I is high and Q is low, and then another when the Q is high and I is low, like right here. Again, let's zoom in and take a look at those. Now, this is known as QPSK, or quadrature phase shift keying, and a very, very common digital modulation method. And we're zoomed in right up here where both I and Q are sitting at a negative value, and we can see the peak of my RF signal is occurring kind of towards the tail end of the low portion of my square wave reference here. If we scoot over one more bit here, both I and Q are positive, and now we can see the phase is shifted 180 degrees from where it was here, now that the peak is occurring towards the tail end of the high side of my reference waveform. We look at the 2 opposite states here. Here we have the Q signal is high, the I is low, And we can see my positive peak is kind of lined up with this falling edge of the square wave. And if we go and take a look at the opposite state here, I is high and Q is low. Now I can see that the peak is lined up with the rising edge of the my square wave reference. So we can see there are 4 separate phase states, each of them separated by 90 degrees. And again, this is a quadrature phase shift keyed modulation. Now, in order to take a look at some of the effects of some impairments that can happen, such as a DC offset between the I and the Q, or a gain offset between the I and the Q, or even a quadrature offset within the modulator, it's best to look at this in the modulation domain. So we're going to introduce the vector signal analyzer here and take a look at our signal with that. I'm using my Tektronix RSA607A real-time spectrum analyzer to take a look at the effect of some impairments on the IQ modulator. Okay, so we're looking at a couple of different views of this modulated signal. There's the kind of average spectrum, the live real-time spectrum, the demodulated I and Q waveforms, and the constellation diagram, which essentially shows the 4 phases of this RF signal. Now, the first impairment we'll look at is a DC offset between the I and Q waveforms. If I inject that DC offset, there isn't a whole lot that's visible. The constellation diagram doesn't change very much, but if you look carefully, you see a little bit of a peak popping up here on the spectrum, and it's visible here as well. And that's known as carrier leakage. Now, carrier leakage is not that big of a deal for a simple modulation like BPSK or QPSK in this case, but it can be a very big deal for things like OFDM and that type of a thing. The next impairment we'll take a look at is IQ gain imbalance, and that's where the I and Q magnitudes aren't the same. So if I introduce a little bit of attenuation into one of the I and Q waveforms, you can actually see different amplitude here now, and we can see what it does to the constellation. It actually squishes it in one direction or the other. So instead of being lined up perfectly at our 4 equidistant constellation points, we've got less gain in one direction compared to the other. And again, that's IQ gain imbalance. Now, the last impairment we'll take a quick look at is quadrature error. And this is referring to the I and Q sine waves that are going to the 2 mixers. They're supposed to be exactly 90 degrees apart, and we get a nice perfect constellation when that happens. If there is a phase shift that is not 90 degrees between them, this is what can happen. You can get a skew in almost like a parallelogram effect in the constellation diagram, and that's an indication of quadrature error. Let me reverse it and go in the other direction here, introducing a phase shift in the wrong direction here. So this is what can happen when you've got a phase shift that is not 90 degrees between your quadrature LOs. Now, oftentimes if you're testing a quadrature modulator chip or a module like this, you won't have access to all the various points and adjustments we did in this video. So a common thing to do is to do a single sideband suppression test. And in that case, we apply our carrier signal to the local oscillator input. We apply a pair of sinusoids in quadrature to the I and Q inputs. And then we take a look at the RF output. And ideally, the RF output is going to give us a tone that is offset from the carrier frequency by an amount equal to the frequency of the I and Q. But of course, nothing's ideal, so we're going to get a little bit of carrier feed-through, or carrier leakage, I should say, as well as some magnitude of signal on the opposite sideband. In this case, it's the upper sideband. If we wanted to reverse this, all we'd have to do is change which signal is leading the I and the Q of the inputs to the quadrature modulator here. So the figure of merit is how far down this opposite sideband is suppressed compared to the desired sideband. Now, I didn't do anything in my setup here to optimize the phase shift between my I and Q input signals, so this could potentially be a bit better than the 37 dB down that I'm measuring here. But that's essentially what the single sideband suppression test is. And various impairments, the IQ offset, the IQ imbalance, and DC offset will affect the levels of the carrier feed through and the single sideband suppression. So it's more of a composite measurement of all of these errors or all these impairments kind of rolled up into one. Well, I hope this video gave you a little bit of insight into what an IQ modulator is, how it works, and how some of the impairments of an IQ modulator will manifest themselves in their performance that they produce. Thanks again for watching. If you like what you see, as always, please give me a thumbs up, tell your friends, please subscribe if you haven't done so already, and we'll see you next time. Thank you. About a year ago, I picked up this Bird Thermaline watt meter. It's rated to 150 watts from 25 megahertz to 1 gigahertz. But I suspect that that frequency range is more limited by the response of the power meter, not so much by the impedance of the dummy load itself. So I'll take a look and sweep the dummy load with the VNA to see over what frequency range I actually can use this dummy load. I've inverted the screen color on the VNA display to hopefully make the menus show up better here on video. Well, the first thing I want to do is set the sweep over what frequency range I want to measure this dummy load. Now, even though it's rated only down to 25 megahertz to a gig, I'm interested to see if it's going to work well for my HF needs. So I'm going to start the sweep at just at 1 megahertz. And then it's rated to go to 1 gig, but I'm really interested to see if the unit will go up to the 23 centimeter amateur radio band, which is 1296 megahertz. So I'm going to sweep it out to 2 gigahertz. And that'll give me a good idea of how well this will work from HF all the way up to 1296. Well, once the sweep is set up, the next thing to do is run a user calibration. And this does a number of things. It will take care of the directivity errors of the analyzer, as well as the source mismatch and tracking errors. But then more importantly, it also establishes a new reference measurement plane right here at the end of my connector and adapter that we're going to use to connect up to the dummy load. So in this case, we're just using one port, so we can do a single one-port calibration, which will just involve using 3 standards, an O, S, and L, or open, short, and load. Okay. Start off by hitting the calibrate button until we want to do a calibrate. And we're going to do a 1-port SOL, or short open load, on port 1. So we'll start by connecting our open to the end of the test cable, and then we'll hit the open button, and it runs a measurement on the open. And we do the same for the short standard. We'll connect that up and click the short button. And then the same for the calibrated load. Connect that up and hit the load button. Okay, with those 3 calibration measurements made, we just hit apply, and it'll apply those corrections now to the measurements, and we're ready to go sweep our dummy load. So now we can connect up our calibrated cable and test system up to the dummy load here and make the measurement. Now, one thing you didn't see me do is actually select the measurement that we want to make, because the default measurement, which was an S11 or return loss, is the measurement I want. And this is showing me now the return loss of this dummy load. And we can see down at low frequencies it's down close to 40 dB, even better than 40 dB down return loss, which is excellent. And we get out to a gigahertz, and we're still at about 23 or so here. In fact, we can throw a marker on here so we can actually go see that. Let me go grab that marker and move it over. So that's sitting at 23.3 dB. That's about a 1.15 SWR or so. So that's still quite good at 1 gigahertz. And if we take this marker out to say 1296, which is right about there or so, we can see we're like 34 dB of return loss. So this dummy load would work great on the 23 centimeter band. Now, most hams would be interested in looking at the SWR, or more familiar with that parameter. So I'm going to set my display format to SWR, and then let me auto scale this display. And so now here's our SWR sweep from, again, 1 megahertz out to 2 gigahertz. And we can see here's 1-to-1 right here. So down at this low frequency down here, down in HF, we're sitting at about 1.02 to 1. It peaks out just over a gigahertz at about 1.14, 1.15 to 1, which is about what we suspected from the return loss, and dips down again, luckily enough, right around 1296 to be about 1.03, 1.04. And even out at 2 gigahertz is only at about 1.5 to 1. So it's a pretty good dummy load even out to 2 gigahertz here. That was an interesting point of reference. Let's take this very inexpensive dummy load that was designed just primarily for HF, I would imagine, and see how well that compares on this same frequency range. I'm going to start off by saving this SWR sweep that we have. So I've got a trace that we can compare into memory here. And now we'll disconnect my bird dummy load, and we'll connect up the cheap HF dummy load and see what it looks like on the same scale. Interesting, the SWR is just rocketing right off the screen. I mean, the top of the screen here is only 1.65 to 1. So let's just take my scale and let me pop that up here a little bit. Alright, with the scale change, we can kind of see that this cheap dummy load here at 200 megahertz is at about 1.3 to 1. That's not too bad, so it's usable to VHF. We get up around 300-400 megahertz. Now we're over 2 to 1, so certainly would not work well at all for UHF and above. And you may be able to see here that the reference trace that we saved is actually this green trace. This is actually the SWR sweep for the good bird dummy load. So we can see it's basically flat across this whole range, well under 1.5 to 1, all the way up to 2 gigahertz, where the inexpensive dummy load would really fall apart. A little bit more above HF. So anyway, I hope you enjoyed this video. Quick look at sweeping some dummy loads with a vector network analyzer. If you like what you see, give me a thumbs up. If you haven't subscribed already, please do so. Comments are always welcome, and thanks again for watching. Just a short video for fun from the shack here this evening to show how you can visualize the operation of an antenna tuner like this one here by using a vector network analyzer and setting it up with a couple of displays, each of which will show you the operation in a slightly different way. Well, normally when you use an antenna tuner like this, you're tuning up at a particular frequency. So we're going to do the same thing with the VNA. We'll set it up in 0 span, in this case at 7.2 megahertz. Now the analyzer is set up with 3 displays, but each display is really just measuring S11, the reflection coefficient, but it's displaying it in 3 different formats. Down here in the lower right corner is the traditional logarithmic magnitude of the S11, but again we're in 0 span, so we're going to have a flat line. The reflection coefficient is also expressed as the standing wave ratio, or SWR, which is the most common thing that hams will look at. So I displayed that here as well. And then thirdly, we're also displaying the reflection coefficient as the complex impedance looking into the coax. So this is what the transmitter would see on the Smith chart here. Now, the Smith chart is just quickly a way of displaying a complex number, in this case complex impedance, where we have essentially circles that represent constant resistance, and we've got arcs that represent constant reactance, both inductive and capacitive reactance. And the location of where you are on the chart tells you essentially the complex impedance. So right now, before we start adjusting the tuner, we've got our marker sitting right at our single point at 7.2 megahertz, and that's giving us a input impedance looking into the coax of 20 ohms plus J 38 ohms, so an inductive 38 ohms and a real part of 20 ohms, and that's what that point represents. Now if I reach up and grab the capacitor control on the tuner, I can see a couple of things. I can move the impedance that's seen on the Smith chart kind of on an arc as we adjust that capacitor. I can also see the return loss and SWR curves moving as well. If I grab the roller inductor of the tuner and start adjusting that, I can actually see myself moving along on the Smith chart as well as the other displays. Now our goal is to get a 1-to-1 SWR, which will be achieved when the input impedance is right here in the center of the chart, right at 50 ohms resistive. So all we need to do is essentially adjust our controls to kind of get us there. And you can see if I adjust my inductor down, my capacitor back here, and get ourselves really close, if we're really careful here, and zero in to something very, very close to just a 50 ohm resistive termination. And if we look here now, I'm at 49.7 ohms and about 0.4 ohms of inductive reactance. And if we tweak that a little bit more, I might be able to get even closer. Okay, and with ourselves very closely centered here, we take a look at our SWR plot, and we're sitting at 1.008 to 1. and our return loss is 47 dB. So we've achieved a really good match by simply tuning the capacitor and inductor on the tuner and visualize that a couple of different ways. Well, now that I've tuned up at my desired frequency of 7.2, I've changed the VNA to give me a span of 400 kilohertz. So now we'll sweep from 7 meg to 7.4 megahertz, which more than covers the 40 meter amateur radio band. Now, of course, on the Smith chart, I can see the input impedance to my antenna system. Now, what I mean by that is the antenna, the tuner, and the coax leading to the transmitter. And this is what that impedance looks like over frequency. And if I can drag that marker around and actually see what that impedance looks like at any frequency within that sweep, going back and forth. Okay. Of interest to most hams would probably be this plot right here, which is showing me my standing wave ratio, or SWR, versus frequency. And I've actually put a pair of markers here at the 2-to-1 SWR points, and this indicates that I've got something in the neighborhood of about 140 kilohertz of 2-to-1 SWR bandwidth. So covering, not quite half of the 40 meter amateur radio band. And of course, of interest to most RF engineers would probably be just the log magnitude of the reflection coefficient, which is shown down here. But all of these are essentially the same measurement, just displayed a couple of different ways. And today's video was basically just for fun, but I do plan on doing some more tutorials on the use of a VNA for various applications in the future, as well as maybe even some tutorials on the Smith chart itself. An old tool that RF engineers have used for many years, but maybe a bit of a lost art these days in terms of how you can actually use it manually. So maybe we'll cover that in some future videos as well. Anyway, if you like what you see, give me a thumbs up. If you haven't subscribed already, please do so. Comments are always welcome, and thanks again for watching. See you next time. When working on radios, oftentimes the service manual or the alignment instructions will specify the use of an RF millivoltmeter for making some of the measurements. Now, I never had one here on the bench, and I always got by using like an oscilloscope measurement or something on a spectrum analyzer. But when you're doing alignment measurements, oftentimes there's really no substitute for watching the peak reading of a meter when you're trying to peak up a circuit. So I was lucky enough to find this RF millivoltmeter at a Hamfest last weekend for 60 bucks. So I really almost couldn't pass it up. So in today's short video, just going to take a quick little look at this meter and do an initial checkout to be sure that it works. Right, so this meter is a Booten Electronics model 92C, made right here in Booten, New Jersey, only about a half an hour from where I live. Now, if you're going to look for one of these meters, you really want to look for one that comes with the original probes. And the reason for that is that the probe and the meter were calibrated together. If we look at this probe, we might be able to see that it says this probe was calibrated for serial number unit 423. If we look at the top label of the meter itself, serial number 423. So this is the original probe that came with this meter, and that's a really nice find. In addition to that, the probe came with two additional accessories. There's a 50 ohm adapter here, and this 50 ohm adapter, again, if we look, serial number 423. So this is the original 50 ohm adapter that came along with this meter when it was made and calibrated along with it. And then the meter also comes along with, or the probe comes along with this, just a flying probe adapter. And with this ground lead on there, this is usable up to about 100 megahertz or so, while with the 50 ohm adapter we're good to a little over 1.2 gigahertz. Okay, we've got the meter turned on. I've got it, the 50 ohm adapter put on the end of the probe, and have that connected up to my signal generator up here, which is set to output a signal at 10 megahertz at 0 dBm. So I hit the 0 dBm scale, which is also the 300 millivolt full scale on the meter. Let's turn the signal generator on. And lo and behold, that reads right dead on top of 0 dBm. Now, the way the dBm scale works on here is depending on what scale you've got, you add or subtract the dBm reading from the setting. So in this case, when it's set to 0 and it reads 0, we have 0 dBm. You'll notice if I set this to plus 10 dBm, and the meter now is going to read down here at minus 10. So I'm going to have plus 10, minus 10, so that's still 0 dBm. So that's how the dBm scales work. That's kind of a bonus for me that the meter is actually quite accurate. Oftentimes, if I'm going to use a meter like this for doing an alignment of a radio, we're just looking to peak the response like in an IF stage, so absolute measurements generally aren't as important, but nice bonus that we've got a nice accurate meter here. So let's check it out on a couple more scales. Let's start working our way up. So there's a +1, +2, +3 dBm. Let's pop up one scale here. So now on the +10 dBm scale, -7, so that's still +3 dBm. Work our way up. Okay, let's see, we get to right there is +10 dBm out of my signal generator, and I guess the generator here starts to run out a little bit out of steam, but it's still pretty good at +12 dBm. So I know on the high end of the range here we're pretty good. If I go to the +20 dBm scale here, so I've got +20 in this case, -8, which is still +12 dBm, so even that higher level scale is good. Let's check it out on the lower scales too. Okay, I've set the signal generator to -10 dBm. On the -10 dBm scale, we're sitting right at 0, so that all looks good. Let's start working our way down. And let's see, we work down to -20 dBm, so there's 10 dB down from 0, so that's -20. This should bring me to the 0 mark, and it does. And we'll go down another 10 dB, so there's -21, 22, 23, and I work my way down to -30 dBm. Now before I switch to -30, the lower two scales on this meter actually have a 0 adjustment. Okay, so I pulled the probe off, sat it up here. Let's go to the -30 dBm scale and adjust our 0. And I should get it pretty close. And now we can connect back up to the signal generator, which is putting out -30 dBm. And there we go, reading pretty darn close to 0 on the dBm scale, so that means that we're right at -30. Let's work again my way down. Let's go down to -40 dBm, right there. And there we are at -10, so that all works out good. Now again, before I change to the -40 dBm scale, we're going to 0 that out as well. So let me disconnect from the signal generator here again, switch to -40, and we'll adjust the 0 to kind of get ourselves on the line there. And that looks, let's see, there we go, that's pretty close. I guess this pot might be a little bit dirty. Might have to go in there and clean that. And let's go put this on there, and there we are at 0. So that's -40. Let's work my way down to -50. And there we go. -10 on the -40 scale is -50 dBm. And that corresponds also to, if we look at the scale here, on the 3 millivolt scale, there's 1 millivolt, so this is 700 microvolts. And of course, -50 dBm is 704 microvolts or so, so that's pretty darn good. Well, I hope you enjoyed this quick little look at this Booten 92C RF millivoltmeter that I picked up at a Hamfest. Lucky enough to find it with the original probes, the original 50 ohm adapter, and the original browser tip. With this browser tip, you get a reasonably high input impedance, high enough to even pick up RF if I touch the input, so as we can see that. But you know, over 100K at low frequencies, and even above about 5K ohms of input impedance, up close to 100 megahertz. So this will work great for probing IF stages. Anyway, if you like what you see, please give me a thumbs up. If you haven't subscribed already, please do so. And comments are always welcome. Thanks for watching, and we'll see you next time.
Hi, I'm Jim W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain Lookout. Was trying to figure out a different way to connect two antennas to one transceiver. I usually have two Yagis. There are times when I point one direction and the other Yagi another direction. I combine them through a vacuum relay that has a control box, a 28 volt power supply, and a series of fairly expensive vacuum relays. And I was looking for a less expensive way to do that. What you might think about is, let's say you had a dipole that ran north and south and a dipole that ran east and west. and you want to talk to two friends, and one is north and one is east, he's going to be okay on one antenna, but maybe you can't hear him on the other. And so how do you combine those two antennas? Or maybe you have a vertical and a dipole, and one guy's stronger on the vertical, the other guy's stronger on the dipole. How do you put those together and make it work? Or you may be net control and you need to hit different portions of the country. So again, you want to be able to switch antennas as you call certain regions. As it turns out, it's easier than I thought it was in my fairly complicated system of vacuum relays. While it works okay, it is probably a waste of money. So here's what I've come up with, and to facilitate the mechanical part of it, I'm using two coax switches. These are Chinese. They really are pretty good. Retail price is around 25 bucks. Dealer cost is about $10 to $12. I'll see if I can get a close-up of the inside of this, but basically there's a bar inside, and as you rotate the switch, the bar moves one side or the other, moving a copper beryllium strip, and it makes contact with one or the other SO239 on the top. In the process of doing that, it shorts out the unused portion, or the unused coax connector. These will handle legal limit. I've run RTTY through them. I've really abused them, and they work great. How do you put these together? What do you do to make it work? Well, what I've done is I've added two double males to the output or input end of the coax switch. Done that on both of them. Now I need to figure out a way to combine these two, so the easiest answer is a T, and here's a T. A little bit expensive, maybe $5. The double males are $3 to $4. And as we learned in an early episode, having extra coax connectors doesn't introduce any great loss. And the insertion loss of the switch on 20 meters, for example, or even 10 meters is not much. On 2 meters or 440 or something else, yeah, then it wouldn't be advisable. But at 20 meters, it's just such a small portion of that wavelength that's 65 feet long, 64 feet. Okay, so I've got this. And what I did was to screw in a double female. So here are my connections, and here's my simple switch. This goes to it happens to go to my amplifier, but it could go to your antenna tuner. Actually, it goes to my antenna tuner first. Antenna number 1 connects here. There's no connection to this side. The other antenna connects here, and there's no connection to this side. So how does this work? Well, when the switches are in that position, both antennas are connected to this T. When you flip this switch, this side is no longer connected. This side is no longer connected to the antenna. So you're connected just to this antenna. So let's say this is antenna number 2. Now you're connected to, I am connected to number 1 with both switches in that position. Both are connected. And so that would be like position number 3. So at this point, you're probably wondering about SWR, and that's a good question. But there is an easy answer, and you probably already have it. And that is, if, for example, you have an antenna that's 50 ohms and 50 ohms, when you combine them, it's going to be about 25 ohms. Ratio of 25 to 50 is 2 to 1. So in theory, the SWR is 2 to 1. Likely it's going to be greater because the impedances are going to be different. And what happens when you switch to just one antenna? You're back to 50 ohms. So the combined thing might be 20 ohms, 30 ohms, something. And now you do one and you're back to maybe 50 ohms. What I did was to put a manual antenna tuner, and I also tried an automatic one in the manual mode. So this would go to the antenna tuner. And what I did was to find a compromise position where this was a reasonable SWR, this was a reasonable SWR, and combining the two of them was also a reasonable SWR. It takes a bit of balancing, but I was able to get them with my two Yegis to about 1.6 to 1.8 to 1 SWR, and that's fine. So how well does this work? It works great. And for me, sometimes combining the two antennas pointing over the North Pole, I have now 8 elements pointed that way. And on some signals, it does make a 3 dB improvement in the DX station signal strength. It's a reasonably simple solution, probably, let's say less than $75. You can do all this. And if you have a need to be able to connect two antennas, it's a great way to go. The way I did this is so that it isn't on the top of my desk, is I bolted it to the underside, or I screwed it to the underside. These switches happen to come with wood screws. I have to pay attention to what I'm doing, but I can reach underneath, flip one, flip the other, and either be antenna number 1, antenna number 2, or 1 and 2. And it's worked out really well. I was talking to a guy in Australia and a buddy of mine east. So I put one antenna at roughly 240 degrees, the other one at 90 degrees, switched to both. I could hear both guys. And if you have a need, you can do delay lines and other things. I haven't talked about what happens if one length of coax is longer than the other. You can measure that, but for right now, I'd say give it a try. If you need to do this, you might find out that what you already have installed works great. Anyway, this is my simple solution to dueling dipoles, if you will, or if you've got a vertical and a dipole, and it works slick, and it was reasonably inexpensive. I hate to tell you how much I spent on those vacuum relays and 28-volt DC supply. Anyway, that's my solution to having two antennas combined. It's not perfect. If you're an engineer, you probably have noted some flaws in the design, but you know what? It works okay. If you have any questions, post them below. I'll do my best to answer. I've gotten behind in answering. In fact, I think I'm going to do a video where I'm just answering questions that have come up, and some have been really good. Anyway, for now, I'm Jim, W6LG for Ham Radio Basics. See you the next time. If you're inclined to do so, please subscribe. Thanks a lot. 7-3. Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. Have you ever thought about making a microphone? Have you ever thought about saving maybe a couple $100 by making your own microphone that's going to sound even better than the one you might buy? And in this case, that's really likely to happen. You can take an electric cartridge, one like this, that you can literally you can buy this at a dollar store for a couple of bucks, or you can go to Mauser and order electric cartridges, probably 25 cents a piece. This one happens to be about 3/8 of an inch in diameter. That one's about 1/4 of an inch. The ones in my cell phone must be even smaller. I have some electric cartridges in some headphones that they do noise canceling, and they're maybe 1/8 of an inch in diameter. I'm kind of partial to the larger diameter one because it's a little easier for me to work with. And I'll try to bring up a picture of this in the video here so you can see what it looks like. There are two connections on the back side of the electric cartridge. Ground is pretty obvious because it's grounded to the body of the electret, so that's ground. The other side serves two purposes. It's voltage in and audio out. So how do you do that? Well, you do it with a blocking capacitor. So you need our coupling capacitor value. The one I used in this microphone was 0.1 microfarads. If you had a 2 microfarad or a 1 microfarad, that would be fine. Basically, you're looking for something fairly small. In this case, it could be quite large because I could stick it in the housing. Same thing with these. There's plenty of room for a larger capacitor. Sounds really good. The electrets have a fairly flat response over the voice range. Our voices, for SSB need to be less than 3 kilohertz. For example, Collins used 2.1. The Elecraft is, my filters I think are 2.8. Just a real quick step aside for a second. Frequency range from about 300 hertz to about 3000 hertz is great. Anything below 300 hertz is a waste of energy. Your power level is in the lower frequencies, so you need a little bit of boost there, very little, and a lot in the range of, a lot of boosting or increase in the range of 1000 to 3000 hertz. So the curve will look like it's got a bit of a bump in the lower frequencies, it dips down in the middle range, and in the highs it rises again. The relationship between those two, about 1/4 of your energy in the lower frequencies and about 3/4 in the high. And you can sort of judge that if you look at it on a scope, or if your transceiver has a built-in equalizer where you can adjust the curves. Back to the microphone. So you need to find the body of a microphone. Maybe you can find one at a Hamfest, a broken microphone that the cartridge isn't any good anymore, or it never sounded any good. These are great. These work okay. You just have to talk into it, into the end of it. I mounted the electret, attached the wires, put a piece of plastic tubing over it, shoved in some caulking in the end of it just to kind of hold it all in place. I didn't want something to pull loose. Kind of a strain relief. I used cotton balls, so I packed this with cotton balls, shoved in the mic cartridge, and then put a piece of black foam, much like this, over the windscreen just for appearance sake. So I'm going to play a recording made by Bruce, VK4YS, on 20 meters a couple of nights ago, and I just had gotten the microphone going. I hadn't completely adjusted the equalizer, so it was relatively flat, but it sounds really, really good. So I'll play that recording, and you can hear how good this sounds. Cost to do this, the cartridge is $1, the parts are less than $1. The thing to find is this, whether it's a dollar store microphone or something from a swap meet that meets your needs in terms of its physical characteristics. You probably can do the whole thing for $25 to $50. So let's go listen to me making some tests, and that'll be the end of the video. If you've enjoyed this or found it interesting, please subscribe. If you have a question, post that at the end, and give a listen. I think you'll find it really pretty neat. So from here, I'll say 73 and just go to the other video. I'm Jim, W6LG. Thanks for watching.
The point of the video is you can buy this cheap electret resistor and a capacitor and some wires. Find the cheap housing somewhere, either in a thrift store or at a swap meet or something, like an old D104, and put this electret in it, and it can sound pretty good. So I'm happy about the way it turned out. Go ahead.
Hi, I'm Jim, W6LG for Ham Radio Basics. I thought it would be interesting to test two transceivers. I have a Yaesu FT450. It's the original model. Value about $500. I think I paid around $700 for it when I bought it. This is an Elecraft K3, been modified to K3S. Has upgraded filters, 100-watt PA, antenna tuner, I/O ports across the back, upgraded filters, audio recorder, pretty much everything you put in a K3. This has a retail value of, at new anyway, of over $5,000. So this is roughly 10 times the price of this. And the question then would be, what's the difference? Can you hear the difference? And I'm going to play the recording. I'll do it with Audacity, and I'll show the waveforms of the audio. I'll mark who's transmitting which guy, and I'll switch between the two receivers. Also, you'll hear K2RD Ira, who's my friend on the other side of the Sierra Nevada. I'm in Grass Valley. He's in Reno. We're about 70 miles apart. Because we're so close on 20 meters, we don't hear each other all that well. But you'll hear Ira, and that's a pretty good test because he's really weak in how does he sound as I switch back and forth. Now, I'm not going to tell you which receiver is which. I'm going to ask you to vote. So pick the one that sounds best to you. Let me know which one does sound the best. Just a couple of word description as to why. I would recommend you listen for, can you detect a difference between the noise level on the two receivers and the peak signal? So we're kind of guessing at what is a signal to noise? And yeah, we don't have equipment to measure that, but we're just sort of looking at it or listening to it. So as you listen to it, think about the difference in price too, about $500, about $5,000. Now, there are lots of transceivers that we could test, and I do plan to do some more. I've got an ICOM IC7000, which I think is going to sound really good. If I can convince one of my neighbors to lend an ICOM 7300, I'd like to do an A/B test on those two. I think that would be really interesting. So again, listen to the two and think about which one sounds the best, and vote for either receiver receiver number 1 or receiver number 2. And just say why. Clearer, better signal to noise, whatever your description is. And keep in mind, some of that can be cleaned up with some audio stage processing that we'll talk about in a subsequent video. This morning I got an email from KL3DO Eric, and he happened to record me on 20 meters. And so I've stuck that at the end of the audio recording. And you might find it interesting. It's Eric apparently he's in Alaska, does the KL3DO, does a lot of antenna work, experimenting, going into the field, really does a lot of stuff. In any case, the main thing is vote for a receiver. Not to tell you which one's which. Vote for number 1 or number 2 at the end, and just a brief couple of words about why. If you enjoy this video, please subscribe. I've got a lot more things in the works. I get behind once in a while, as I have recently. Trying to get to 10,000 subscribers by the end of the year, that's asking for a lot, but we're at 6,000 in a little more than a year, so that's pretty good. Anyway, for now, 73, watch the rest of this video, enjoy.
Bravo Whiskey calling CQDX, CQDX, CQDX. There is Delta Lima 5 radio Bravo Whiskey. Delta Lima 5 radio Bravo Whiskey calling CQDX, CQDX, CQDX. CQDX 20 meters. K2 Radio Delta, Ira, good morning, how are you doing? Ira? Yeah, I was checking the band and I was listening to the beacons, and there's not much going on. I heard Kilo 6 Mike Golf remote via Hungary, so I wasn't too optimistic, but then I was checking the beacons and I heard W6 coming through pretty well, so I thought K2 RD, DL5 on BW. Okay, very good. DL5 RD. Interesting propagation. You're running anywhere between 7 and 9, and fairly rapid QSB in that range, but at least there is some propagation there, and with the low noise makes it also probably out of Europe you won't expect much activity at this. Okay, very good. And final being, we will stick around here for a couple more minutes, and then also do some breakfast here. Lobiax this morning, it cooled off a little bit. We had again over 30 degrees every day around the last week, and extreme high humidity, so made it very, very uncomfortable in the office. So I went to the office with a motorcycle. Did it very early in the morning when the temperature was still okay, and left when it was a little bit later in the evening, around 5:30 or almost 6 o'clock, when it was cooling down again a little bit. So from EA5IKJ, thanks for the call. Good evening. You're about 15 over with me tonight. Beautiful signal. 15 over S9. And nice to catch up with you again. Yeah, it's been a wee while. Back in June sometime, Jeff. Just about 25 past midnight here, and already into Sunday morning. And very hot, sticky evening here, Jeff. WN3DX. Yeah, well, it's always nice to get a good bit of sunshine over the summer period, Jeff. Unfortunately, you're from Scotland. You're not guaranteed any summer up there. That's the unfortunate thing, living in a lovely part of the world, but the weather's garbage to be honest. And I had a wee smile on my face when you mentioned about going out and you just come in to play a wee bit of radio. That's exactly what I'm like. Thanks for the call. Whiskey Alpha 4 India Papa United from EA5 IKJ. Thanks for the call. Good evening. My name is Paul, Papa Alpha Uniform. I'm located here near the city of Valencia. EA5 Italy Kilo Japan. Good evening, Bob. Nice to hear you. Signal tonight here. You're 20 over 9. Bob, and appreciate the nice support. Nice to hear your voice again, Bob. Thanks for the call. Have a nice good morning from Spain. Local time is 12:30. Hot night here around 28. I think it is at this moment in time, Bob.
Weeds that they are growing are the kind that they smoke. Go ahead. Yeah, we don't have the document for that. That's what it is. Show up here. Go ahead. Yeah, I know you don't. I'm 2 years older than you are, and so I'm really beginning to feel it. Unfortunately, I was hoping it wouldn't get to be that bad. So, yes, I've got a neighbor with about the same size property. His is about 5 acres, and he has large greenhouses, and he doesn't have to drive to the office.
Hi, I'm Jim W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain Lookout. Which is the best antenna tuner? By that I mean not what can it match, but what are the losses in the tuner? A big tuner probably has fewer losses than a small tuner because the Q of the coils is going to be higher. But I don't know. I was talking to Ivan Shapiro, WK1W, and the question came up about antenna tuners and how efficient they are. And I don't know the answer to that. So, which is the most efficient antenna tuner? If you put 100 watts into it, what comes out? If you put 500 watts into it, what comes out? Little guys like this, or big ones like my Nye Viking, which is good for 1500 watts all day long, every day, RTTY. Has big coils in it. I also have a Drake MN2000. It has slightly smaller coils, but it's also good for, in the rules that existed in the 1960s, 2000 watts input, about 1200 watts output. Which is the most efficient one? Could it be a little one like this, or that's automatic, or a big one? And I took the cover off of this LDG AT200. This is what it looks like on the inside. It's got little, let's turn it this way, little toroidal coils, relays to switch between the coils, relays to switch between the capacitors. These coils are maybe, try it this way, maybe an inch, well, maybe an inch and a quarter in diameter. This one, they're even smaller. So my guess is because the coils on this are relatively small and the Q is probably lower, they're not going to be as efficient. What efficiency do you use when you're designing a tuner because you have a customer who's going to want to tune it and not have it retuned every time the customer moves a few kilohertz? Back to the question, and how do we figure it out? Well, I think the easiest way is to transmit into some of the tuners that I have. So I'll take the Nye Viking, the MN2000, and this one, because this one's automatic, and I'll transmit into it. And I'm very fortunate to have one of Larry Phipp's N8LP, one of his watt meters and 2 couplers. So I can put 1 coupler at the input and 1 coupler at the output of the tuner. So 1 coupler will be attached here, and this is antenna number 1. The other coupler will be here, and I can switch back and forth so I can read the watts going in and the watts coming out. And I think what I'll do is a screen grab of the software that Larry provides, and it'll show the watts coming out and the watts going in if I switch correctly between the two. So that means I've got to coordinate switching readings keying the transceiver, making sure I've got the right one connected. So there'll be a bunch of jump cuts in the video. It'll be interesting to figure out which one is better. Again, my guess is this is not as efficient as a big one. The losses, I don't know. So we'll have to go see. Anyway, here comes the video. It's going to be kind of jumpy, maybe a bit blurry. I'm not sure how the screen grab's going to work out, but we'll get an idea for what's what. So watch the rest of this video, and at the end I'll come back with a comment after I figure out what the heck happened. All right, see you on the other side. Okay, so here we go. I'm going to start and stop the video recorder as needed. Okay, so let's first see if both couplers to the watt meter read the same, and I'm going to transmit 100 watts and see what the couplers read, see how close they are. So I'll start up the video recorder so you can see what's going on. What we're looking at is the screen from the LP100, and there's 103, 104 watts. So that's the in coupler. This is the out coupler. So I'll switch over, and it is 103.4. So about 0.6 of a watt different between the two couplers, which is, we'll keep that in mind. It doesn't amount to anything, but we now know that the two couplers read slightly different values. One is about 0.6 of a watt different from the other. Next part of this will be to look at the Nye Viking watt meter, which is a really heavy-duty big one, and I'm going to put power into it, and I'll read the first I'm going to put it in a bypass. So I'll transmit into it now with and have it in the bypass mode. So I'll read the power going in and the power coming out the other end. So let's see if I can get there with this. Okay, keying it now. Okay, 99.58 watts. No, 100 watts. Now what's coming out the other end is 98. So about 6/7 of a watt different. Okay, so the difference was maybe 7/10, and we had 4/10 before. So the net difference is about 0.3 of a watt. So there's really no loss in the Nye Viking. So I'm going to next I'm going to transmit in, and I'm not going to do much in the way of adjusting. I'm just going to let it stay at the position it's in right now, and I'll put power into it, and we'll see what the difference is. Again, one coupler's on the in, this one, and that's reading 99, roughly 99.8, and coming out the other end is 99.0. Okay, so the difference is 0.8. The in and out on that Nye Viking is virtually the same. There really is no loss. So next I'm going to go to the Drake MN2000, and I'll take a break here and connect the cables, move things around so I can do it. This is the MN2000. Got a coupler at the beginning of it, or the in, and a coupler at the out. Going to key into it and see what happens. Okay, there's 68 watts and 67 coming out, about 0.8 of a watt difference, I think that was. Let's see, 6.724, 6.724. Virtually no difference between the in and the out. They're within 0.4 of a watt, which was the difference between the couplers when we made the first test. So now I'm going to move on to the automatic tuner. Okay, here's the Elecraft KAT500, and I can put power from the KPA500 through it. 504.62. 509.66, 506.51. All right, there's 514 watts coming out, rather going into the tuner, and 513 coming out. So maybe 1 watt difference, and we know the couplers are different by 0.4 of a watt. There's 514 versus 510. May have throttled back a hair. Okay, 508.4, 507, well, same number, 508.4. Well, I'm surprised. Basically, the answer is, what's the difference between the antenna tuners? Nothing. These guys, and I tested every one I had pretty much, were just as efficient as the big ones. And by that I mean the losses were almost nothing. Out of 500 watts, maybe 1 watt, something that you could never measure. Well, I mean, with any kind of accuracy with the stuff that I have, if we were in a lab and we had some sophisticated equipment, probably we could figure out a better number. But in terms of what I could do at 100 watts, not even 1 watt loss difference between this one, or the other ones. Even kind of a junky homebrew one that I have, I tried it. It worked great too. So to answer the question, which antenna tuner is the more efficient, the little guys or the big guys? The answer is they're the same, and never would have guessed that. That flies in the face of what we know about the queue of circuits and coils and other stuff. But that's how I measured it, and I didn't fudge the results. Anyway, I hope you enjoyed this. The prior video I did on testing 2 transceivers in the first 3 days had about 5,000 views, which was a huge number. I haven't done a follow-up video to that, but I'm going to. So, but I want to get a few more votes. It's been really interesting. Some really great comments from folks. Hopefully, I'll get the same kind of comments on this about antenna tuners that I generally haven't liked and haven't used, and now I've got a whole different perspective on them. If you've enjoyed this video, please do subscribe. I'm trying to get to 10,000 subscribers by the end of the year. That would be wonderful. In any case, 73, I'm Jim, W6LG. See you the next time. Thanks.
In today's video is just a quick little tip about reading part numbers on integrated circuits and transistors and such. And I was reminded of this trick that I've used in the past by an article that just recently appeared by Jay Davis in EDN. It used to be that the part numbers on ICs were screen printed in a nice white ink, and it made it really easy to read these part numbers. Increasingly these days, though, parts are laser marked, and it's kind of a laser etching in the top of the chip. And unless you get the angle of the lighting just right, sometimes it can be very difficult to see that part number. But there's a really easy way to get around that. Now the tip is simply to use an ordinary piece of cellophane tape. You place that tape on the top of the part that you wish to read and push it down. It kind of magically makes that laser etching much easier to read. You also want to take a little care sometimes when you're doing this that cellophane tape can be a source of ESD. So you want the part generally to be mounted in a circuit board. It's usually okay. Maybe stick them on a piece of dissipative foam or something like that if you're concerned about it. Or just take general good ESD precautions, especially when removing the tape. But it's a quick little tip. I thought you might enjoy that. If you liked the video, give me a thumbs up. If you like what you see on my channel, please subscribe and tell your friends. And thanks again, and we'll see you again real soon.
Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. One of the things that my neighbor asked me about the other day was FT8. And I thought he meant an island off of Africa that's on the DXCC list, but actually he was asking me about a mode of transmission called FT8, a digital mode. Never heard of it at that point, and then it seemed like everybody I talked to locally at coffee or something was discussing FT8 and how much fun they were having with it. So sure enough, another guy asked me about it, and that was Marty Lane OH2BH. And he asked if I could get on FT8. Marty said he's going to go on a DXpedition to Market Reef. And if I could get on FT8, maybe I could work him from here to there, which is, I don't know, 5, 6, 7,000 miles. So I'm going to try to get on FT8. Not sure what's involved in hooking it up. Once I get it going, and I'll film some of that, video it. Once I get it going, I want to do a test to see just how efficient this thing is, because it seems to have taken on these almost, I don't know, an impossible. Guys are telling me they're working the world with just a few watts and with really compromised antennas, and I don't know how that's possible. There are some digital modes that are really good, but just how good is FT8? So to do that, my first thought was, well, I could run low power. The antennas I have for 20 meters, for example, are Yagis, and I can put up a vertical in the backyard or maybe a dipole. But I know a dipole is pretty efficient antenna, and a vertical properly installed can do fairly well too. So I want to make this challenging. So one of the things I thought about was using a mobile antenna, like a stick antenna for 20 meters, and putting it on a mount, putting it in the backyard. And then I thought, well, how about if I use a 2-meter antenna? Can I match a 2-meter antenna on 20 meters? I sort of don't think that's possible, but I can give it a try. Then it occurred to me that when I was a novice in 1963, most of us went to the hardware store and bought what was called a keyless porcelain light socket, and you'd screw a light bulb into it, and that would be your dummy load. So you could tune your transmitter into the dummy load and then switch to the antenna. Now the light bulb, I don't know what the impedance is of the light bulb. It could be huge. I suspect it's actually low. But how about if I use a light bulb? I go on FT8 and I use a light bulb. And so to that end, I've made a light bulb dipole. And if I can reach it, that's my light bulb dipole. It's not really dipole, but we'll call it that for now. So this is my light bulb dipole, and I'm going to go on FT8 with it. So how much could this radiate? Well, I don't know. It's maybe, there's not much in there that radiates. There's some parallel lines, and they probably don't radiate the filament. I doubt that it would radiate at all, because it's taking the energy and turning it into white heat. So I talked with a couple of engineers and some other guys, and we've come to the conclusion that if I put 100 watts into it, it might radiate a milliwatt. And not all that well. And the feedline losses will be huge, because let's say the impedance of the antenna is, I don't know, really low. The SWR to the feedline is going to be really high, and I'll match it with one of these tuners and see how that goes. Anyway, how far can I talk on a light bulb dipole? Well, we're going to find out. So I'm going to hook this up, be back in, I hope not too long, and start the machine again, and we'll go from there. Anyway, stick around back in a few, what'll be just a jump cut, and I'll be right back. Okay, well, that wasn't so easy. The hookup of the transceiver to the computer was really pretty easy. You need a line out and a line in, and the K3 fortunately has those connections on it. I looked at my FT450, it also does, and I have a line in and a line out, and the data port in the back. So I made up a cable for that. So I may end up with the Yaesu, it's over there, the Yaesu FT450 as the FT8 transceiver. I looked at the ICOM 7000. It doesn't have a serial connection in the back, and it needs that level control thing, which I don't think I have. Anyway, it looks like with most transceivers to connect FT8 won't be that hard. The subject of this video is not how to hook up FT8, but how far can it transmit, or how far can it receive? I don't know. The answer to each of those is, or both of those, is going to be probably not very far. I had a hell of a time loading up the light bulbs on 20 meters. With the LDG tuner, it wouldn't match. It just sat there looking at me. With the this big Nye Viking antenna tuner, it wouldn't match. Not even close. The Elecraft KAT500 antenna tuner wouldn't do it either in automatic or manual mode. So what I ended up using was the tuner behind me, which is an old Drake MN2000. The reason why I like that tuner and I haven't given it up is really ridiculously high mismatches it can match. And what makes it work better than most things is it has a de-arsenal meter in it. So as you tune that thing, you just see a little bit of a dip, and then you know you're on your way. So back and forth, and I got it down to about 1.5 to 1, 1.4 to 1 match. So it is going to be the antenna. What I'm going to do is there's a window, north window behind me. And there's an air conditioner in that window. It's about 90 degrees in this room right now, and it's 11 o'clock at night. I'm going to put the antenna in the room, not outside, and I'm going to set it on the top part of that air conditioner and put it right in the window. That window faces due north. So how far can I be heard? And to help figure this out, I've set up a schedule with Phil W6PD for tomorrow, and we're going to meet and see if he can hear me. I don't know if they can. Phil is maybe 4 miles away at a 1 milliwatt or 2 milliwatts. That would be pretty tough. Well, I made contact with a guy on the other side of the highway about 4 miles away. Found a neighbor that I forgot was down in Hidden Valley. He probably could see the light in the window if he'd He's only 4/10 of a mile. But I worked a guy in Canada, 750 miles away, and it's like 1,200 kilometers. And some other guys heard me. I got some emails in the last few minutes of guys who heard me in other parts of the country. So how far away did it go? I think it's over 800 miles for one of them, maybe 900 miles. For that kind of power and no antenna but a light bulb, that's really amazing. Again, I was using a light bulb for an antenna stuck in the window. Well, actually 2 light bulbs in a V configuration. Stuck in that window, really inside the room. The window is a really narrow window. It's like 18 inches wide. Somehow they heard me. Now the signal strength varied a lot, I could tell. And I heard all kinds of stuff. I heard all over the US guys working DX. I didn't hear the DX. 20 meters is probably 500 to 1,000 miles, depending. So that sort of fits with the guy that's 750 miles away, and the other guy that heard me that's 800 and some odd miles leaves here, lands in their backyard, and so they can hear me. From there, it would bounce up and hit the ionosphere again, and I think at that point there's just too much in the way of circuit losses. Speaking of losses, think about it for a minute. I'm loading into a resistor, basically, and the feedline losses are huge. I'm using RG58, RG58, and so what does that mean? I don't know what the hell it means. It means that this is going to be a really popular mode, for one thing. And two, if you're, and I could be in the same situation in a year or two, if you're in an area where you're not allowed to put up antennas, or you're not supposed to put up antennas, and you want to put up something, here's a way you can communicate. And looks like you can work the world. It's not a thrilling contact in the sense that it's a long conversation. It's just, back and forth. And actually, I think that could be shortened up to a whole lot, to about half what it currently is. But still, you're making contact with these guys, and if the software gets any better, you might be able to even go further with better software. Better, I don't know if it can be better, but sometimes there are improvements that can be made in things to make it work better. I'm shocked. I'm flabbergasted, gobsmacked, absolutely blown away as to what it could hear. I left it on and walked away, and you just left it on receive, and it heard station after station after station after station. Now, they were weak, for sure, and maybe they wouldn't hear me calling CQ, but it heard them using a light bulb. Anyway, I talked to Mark Cherry, WT6P, and we were talking on the phone about this FT8, and he may give it a try too. And he said that you could hook up your Christmas lights on the outside of the house as an antenna, and this would probably work. And it would. What might be interesting also is it might be a good way to look at how the voltage and current are distributed on an antenna. In other words, in the middle, where it's high current and low voltage, the bulbs wouldn't be lit up, but as you go towards the outside, you've got this increase and then decrease, this quarter wavelength thing going on. Well, if you take the whole dipole, it's a half wave. So you'd have the brightest bulbs at the end and the dullest in the middle. And what a great way to show how voltage and current are distributed on a dipole antenna using FT8, a good antenna tuner, and some kind of feed line. So if I can do that, I'm going to do it. I don't have any Christmas tree lights or outside lights that have incandescent bulbs, but I'll be out looking for something like that. Anyway, I think Mark's idea was neat. Next video will be how do you hook this stuff up and make it work, because it turned out it really wasn't all that hard, and I'll go through a couple of steps. The software has a couple of things in it that you might miss because they're kind of vague in their descriptions, but I have no criticism of the software or the system because it's just amazing. I mean, one guy that I listened to, the band died. There was, I'll finish here. There was just noise, and the receiver and FT8 was still decoding signals. Now, with the speaker on or headphones on, I couldn't hear him. I could hear nothing, but the computer was picking call signs out of the noise, putting them up on the screen, and giving it a signal report. Absolutely amazing. Anyway, I hope you've enjoyed this. Give FT8 a try, especially if you're in an area where you're not supposed to put up an antenna. There was even, I got to stop talking. Run out of time. There was even a guy on from Pakistan on FT8 and Alpha Papa 2. It looks like this is going to be all over the world and really hot. And I hope that we can work out band plans maybe and a bigger split in frequency so one's not clobbering another. But it's truly amazing. I mean, CW is really neat for weak signal stuff. This goes beyond that. All right, I'm running out of time. The average video that people watch on YouTube is about 6 minutes. I've gone way past that. So for now, I'm Jim W6LG on FT8. Believe it or not. I can't believe it. All right. See you next time. Thanks for watching. If you have tried FT8, post a comment. If you know anything about it, post that too, and we'll see how it goes. I think I'm going to do several videos on FT8 because I think it needs that. Anyway, 73. Thanks for watching. W6.
So we're down here on vacation at Surf City, Long Beach Island. And I thought I'd make a short video to show how to use this little Z-Match tuner. This is the ZM2 from M0ODZ. I built about 10 years ago, and really works great for operating QRP into non-resonant antennas. So let's take a look at how you operate it. I'll usually start by presetting the two capacitors to their mid-scale positions. The ground link control, I usually switch it over to ground when I'm using a coax fed antenna, and I'll leave it open usually when driving a balance feed antenna, so we'll leave that over there. Now the additional capacitance to add 500 picofarads or 250 puff will depend on the antenna, and we'll play with that as we need to. There's a tune and operate control, we'll talk about that in a moment, so we'll leave that in operate as we start. And so to get started here, I'll switch the rig to AM. This AM I've found is a good way to listen to the noise floor to kind of get the tuner basically started or set up in the right position. Now what I'll do is just adjust the capacitors to try to maximize the received noise level. And it's probably right about in that neighborhood we've maximized the receiver noise level. Now if, when you were adjusting them, you really had to go to the maximum extremes of one of the capacitors, you might find that adding an additional 250 or 500 puff might be necessary. But in our case here on the lower portion of the 40-meter phone band, we're okay with this antenna the way we are. Okay, let me turn the volume down so I don't have to listen to the noise here. Next thing we'll do is switch from the operate mode into tune. Now what this does is it inserts a resistive tuning bridge in between the tuner and the radio. So that does two things. One is it allows the transmitter to see a good 50 ohm load, so it'll put out the rated power and won't fold back on SWR. But at the same time, it also gives us a visual indicator on this LED of the reflected power. And the idea is we're going to just adjust the tuner to make the LED go out. Okay, so ready, I'll key up the radio, and we adjust the knobs here. We can actually see that LED come on when I've got a higher SWR and then dim out and come back on again. So the idea is to find that point with the two capacitors where the LED stays out. And it looks like I was actually pretty close with my pre-tuning just to minimize noise. And once we've done that, then we can switch back to operate and switch to the mode we want to operate on, and we're good to go. And now just to verify that we've actually found the minimum SWR point, I'll switch back over to AM. I actually have the meter set up to show SWR. So if I key, let's switch that back off. If I key, I don't see any meter indication, but if I adjust my knobs, I am seeing the SWR pop up. So we were successful in finding the minimum SWR using that tuning method. Yeah, so this little ZM2 Z-Match tuner by M0ODZ. Great little lightweight, easy to build tuner that is a great addition to your Go kit to operate portable out in the field with non-resonant antennas. Anyway, I hope you enjoyed this video from the beautiful Barnegat Bay, Long Beach Island, just outside of Surf City. And if you like what you see, give me a thumbs up. If you'd like to subscribe, please do so. And we'll look for you again next time. Thanks for watching. While I'm not a repair shop, I do occasional repairs for my local ham radio friends. So on the bench today is the battleship of a transceiver here, the legendary Yaesu FT1000. Now this one, my friend said that the receiver died on it. So let me walk you through kind of a review of my debug process here, and we'll see if we can get this rig repaired. Alright, so we've got the rig on the bench, got the top and the bottom covers removed, and we verified that the rig is not stuck in transmit or anything like that, so we powered it on into a dummy load just to be sure it comes up in essentially receive mode so we don't accidentally transmit something into my signal generator. Alright, so we've got the rig turned on here, listening in 40 meters. We turn the volume up. Sounds like we've got static, so the receiver's not like stone cold dead quiet, so that's a good thing. Maybe the audio circuits are all working okay. See, we've got it tuned to 7.2 megahertz, listening lower sideband. So let's inject a signal at 7.199 megahertz. So it'll be 1 kilohertz below, so we'll have a 1 kilohertz tone in the receiver, and set the amplitude to minus 73 dBm. If everything's working correctly, then this should result in an S9 output on the S9 on the receiver or so. And if we take a look, the S meter didn't move, but we can hear a slight tone. We turn the signal generator off, went away, back on. So there is some signal getting through. So the receiver's not completely dead, it is converting, so that's all good news. Let's see what it takes to actually get an S9 signal. Alright, so there we have something just a little bit above S9 on the meter. And we take a look at the signal generator. We're all the way up at minus 22 dBm. So there's about 50 dB larger signal than there needs to be normally to get an S9. So the signal is obviously greatly attenuated going through the receiver path. Now the one thing I want to do is take a look and see if that 50 dB or so of attenuation is band dependent or frequency dependent. Now the reason we want to do this is twofold. If we find that the amount of signal level it takes to get to S9 varies, kind of gradually from, one end of the frequency range of the radio to the other, say from 1.6 megahertz up to 30 megahertz, it varies kind of gradually. That may tell us that the fault is maybe some kind of a break that is causing a small, like in-series capacitor that maybe at high frequencies isn't attenuating as much as it is at low frequencies. The other thing it might tell us is if we find that there's a dramatic difference in the signal level that results in S9 on a band-by-band basis, it may tell us that there's a problem in the pre-selection bandpass filters that exist between the antenna connector and the front end of the radio. But if the amount of signal it takes to get to S9 is the same across the whole frequency range of the receiver, then that tells us that the loss or attenuation that we're getting is somewhere within the circuit where it's not frequency dependent at all. So that'll all help us narrow down where the problem is. Let's see, at the same minus 22 dBm we're getting about an S7, S8 signal level here, so slightly frequency dependent at the lowest frequency band, amateur radio band anyway. Let's work our way up and see what it looks like going the other way. Let's see, at the 3.5 megahertz, that same minus 22 dBm is giving me S9. About the same at 10 megahertz. And about the same on 14.2 megahertz. And I walk through the rest of the bands for 18, 21, 24 and a half, and now 28 megahertz, all about the same. So no real change, no dramatic change in the amount of signal required to reach S9. So that tells us that the problem I have in the receiver is not necessarily in a particular filter or a frequency selective portion of the circuit, but the loss is kind of consistent across the entire frequency band. So that kind of helps us track down where the problem might be. All right, so let's trace the overall RF path through the transceiver here to understand what's going to be frequency dependent and what paths are not. So coming from the antenna port on the back, we're going through the little SWR sense board here, and then up into this unit here. This is the low-pass filter unit that's typically in line for transmit, for the transmit low-pass filters, but there is a path from the antenna port here to another line going out to the RF board. There's a little relay that disconnects the antenna from the receiver when we're in transmit mode. So we'll have to go through that path here first, and then this coax runs back through the receiver into the back. Alright, that coax comes out into the bottom of the receiver here into this unit right here, which is the RF unit. The RF unit underneath this can houses a bunch of pre-selection or bandpass filters for the various bands. So the signal comes in here, goes through a little bit of switching and filtering. There's some pin diode switches and things like that here. Then we go into the bandpass filters, and we don't think there's a problem with any of those because we're seeing the same response regardless of the band we're on. And then after we come out of the filter, we go in through essentially the first stage of mixing. Once we come out of here and go into the mixing, then everything from here on in through the IF path and everything else is going to be at a fixed frequency regardless of what frequency we're operating at. So that's also a common path. So I like to kind of go back and see if we can kind of draw a line maybe at this point here before we get into the IF, maybe before the first mixer, and see if I put a signal in here. Do we get a good signal in the receiver, meaning that from here through the IF path we're okay, and the problem is on the other side of this between here and the antenna? Or if we inject a signal here and we don't get a good response, and that tells us that our problem is somewhere in the IF path and the processing throughout the rest of the receiver. Now here's a portion of the schematic of the RF board. The RF receive signal antenna comes in here. That's the coax I showed you in the corner of the bottom of the receiver. It goes in through a couple of relays. There's some pin diode switching here, a bandpass filter, and then we go into this set of band-specific bandpass filters, like the pre-selection filters. And then after all of that, we go through another IF transformer, some more pin diode switching before we get into essentially the first mixer. So what I want to do is come in here and inject a signal at this point here. Alright, so those diodes we're looking for are D1044, D1045. If we look at the board layout, those two diodes are sitting right here, and they're kind of mounted on end, so I should be able to get to one end of those to kind of just touch a probe to inject a signal and see what we have. Okay, those two diodes that we're interested in are let's see, located right here on the RF board, and they're right there. And in fact, those are the two cathodes, so it should be easy to go and touch there with my probe. What I'm going to use is just this little homebrew contraption here. It basically is a piece of 50 ohm coax with a probe set out at the tip at the end, and a ground clip over here. That just comes off into an SMA connector. Now what I want to do is add a DC block. That's what this guy is here, and it's just a series capacitor to ensure that if there is any DC on that signal, it doesn't get fed back into my signal generator, which is connected to the other end. Now I've adjusted the signal generator to minus 73 dBm. Now that's not exactly what we're going to be getting at the probe tip here because we're not terminating into 50 ohms, but it ought to be close enough that if we're going to get something close to an S9 signal level, we'll get that. And certainly it'd be obvious if we're 50 dB off. So let's see what we get. Now the reason we can apply minus 73 dBm to this point in the circuit is that because between here and the connector on the back of the rig, there aren't any active circuits, no amplifiers. The only thing that we've got between here and there are some relays, some pin diode switches, some filters, some coupling transformers and coupling components. So under normal circumstances, the loss between the rear panel connector and this point here should be relatively small. So we should have about the same signal level. Now it's not going to be exactly the same because the circuit impedance is going to be a little bit different and there are going to be some losses along the way, but there isn't any gain or amplification along the way here. So I think we're safe applying that same minus 73 dBm at this point in the circuit to check out from the IF stage through the rest of the receiver. Okay, ground clip is connected. Let's touch the diode here. Oh, that's very encouraging. That's minus 73 dBm being applied just at the tail end of this set of bandpass filters, and that looks pretty good. Let's take a look what's going on the S meter. Okay, let's reach in here and touch those diodes again. Look at that. Get basically right at an S9 signal level. Exactly what we ought to have. So that tells us that the mixing stage, all the IFs, all that kind of stuff seems to be working just fine, and the problem is somewhere between that point and the antenna connector. So let's start working our way backwards. Okay, let's jump over the other side of the RF board and see if we can eliminate the RF board entirely. You know, I typically like to look around where things are going on with switching diodes, because things like pin diodes and switching diodes can oftentimes be points of failure. And there's a couple of them right here ahead of this coupling transformer going into the bank of filters. There's also another couple of switching diodes here. So let's just bite the bullet and go all the way into the input connector here and put a signal in here, because if we get that same S9 signal level here, then we've kind of eliminated all of this as being a potential problem. So this is where that receive antenna signal comes in to this board. So let's pop it out here, and I'll inject the signal right into that connector. All right, got my probe ready to go in there. And that sounds pretty good. Let me take a quick look at the S meter. Yeah, and then we've got our S9 signal there as well. So we've eliminated the entire RF board as a potential source of the problem. So we're kind of zeroing in. There isn't too much between that board and the antenna connector. So let's see how the receiver gets its signal from the antenna when it goes through this low-pass filter unit. Now the low-pass filter unit has got all these low-pass filters that are used only in transmit mode. In the receive mode, the signal basically comes in through the antenna port and out through the RX port here. So here's a zoom in on that portion of the schematic. Our antenna comes in here, and normally in receive mode we go through this relay. The relay contact would be closed, and then we go in through this pi filter and out to RX out. This is that coax that runs off to the RF unit that we just tested. So there's not a whole lot that can go wrong here. There could be a problem with the relay. There could be, that would be open when we're in receive mode, so we'll check the switching voltages to see what that looks like. There was also this transient device here which could be shorted. One or both of these caps could be shorted. The inductor could be open. So those are the only things that could really go wrong, but in this path that would attenuate the signal from the antenna to the output to the rest of the receiver. Alright, so let's pop the cover off of this low-pass filter unit so we can see what's going on inside between transmit and receive mode. Now let's test things that are easy to get to first. Let's first check to see if the relay coil is getting properly switched between transmit and receive mode. That's controlled by this transistor here and a couple of signals off of one of the connectors over here. So let's make sure we got the proper switching signals available to us, and that the voltage across the relay is being turned on and off. Okay, this is the relay in question, and this is the switching transistor. That's pretty easy to get to. And then there's a couple of leads on this connector here that provide us with the 13 volts supply voltage and the transmit switching signal. Now I'm going to be switching the rig between transmit and receive. And even though I'm in single sideband mode with no microphone connected, just to be safe, I'm hooking up the output of the radio into a dummy load, just in case there's any power being transmitted at all. So let's take a look at our voltages. So our 13 volt supply to the circuit should be right here, and that's 13.5 volts, so that's okay. This voltage here is reading about 2 millivolts. If I switch to transmit mode, it jumps up to 4.2 and then goes back to 0 volts. So we have our proper control voltage for switching. Let's see if that transistor is doing what it ought to do. So the collector of that transistor is right down under here. We can see that's sitting at in receive mode at 13.38 volts, so that should be enough to turn the relay on. I go to transmit mode, drops down to just 15 millivolts. So we are getting the proper switching voltage at that relay. However, as I switch between transmit and receive, I can't hear that relay clicking at all. Now some relays are actually very quiet, and sometimes you can feel them, and I don't feel that relay switching. So I suspect that that relay itself is faulty, and that it's just not switching when we turn the coil on. But let's do one test to be sure. So now I've gone in here and just tacked a little jumper wire across the contacts for the relay. And let's hook up the receive signal path and inject our minus 73 dBm signal in through the connector on the back of the transceiver and see if the receiver behaves normally. Moment of truth. Let's turn on the output from the signal generator. There we go. Got our S9 signal. Turn the volume down here. So we got our S9 signal at minus 73 dBm coming right in through the normal antenna connector, and all we had to do was jumper the contacts for that relay on the low-pass filter board. So I think it's time to take a look and see what that part number is and order that part. All right, according to the schematic and actually the part number printed on the relay itself, it's a TC-112NV. It's the manufacturer's part number. And looking in the service manual for the FT1000, it's a Yaesu part number M1190104. So I'm going to order that part up from Yaesu, and hopefully when that part comes in, we'll replace this relay and get the radio all back up and running. Alright, through the magic of video, here we go. We have the replacement part from Yaesu to replace this faulty relay. So all we need to do is pull this low-pass filter board out. And that's just a matter of removing these 4 coaxial connections. They just pull out, actually 5 coaxial connections, and then 1, 2, 3 multi-pin connectors. And there's 4 screws and the whole board comes out. And some quick work with my vacuum desoldering tool. Should be able to get this relay out of here. We'll insert the new relay into the board. And for the first pin or two, I'll keep my finger under the board to hold the part in place until the solder can hold it in there for me. And we'll clean off the solder flux with a little isopropyl to make them nice and clean. And we'll reinstall the board. Reinstall all of the connectors. And before I button it back up, we'll do a quick little test run here. Turn the rig back on. We're tuned again to 7.2 megahertz. Let's turn the signal generator on at minus 73 dBm, and boom, we've got our S9, a little bit higher than S9 signal. 160 meter band, we look okay. In the 80 meter band, we look okay. And I ran through the rest of the bands, and up here at 10 meters, we're looking okay as well with a minus 73 dBm input. So it looks like that relay fixed the problem. Let's button the radio all the way back up again. We'll start with the bottom cover, and then it screws. And after flipping this tank over, we can put the top cover back on here. Alright, got the radio up here in the shack, just checking out the receiver. Looks like it's working normally here on 40 meters, and checked out the other bands here as well. Signal levels and comparing between that and my 870 look pretty comparable. So we think that relay was it, and thanks for watching the repair. If you liked what you see, give me a thumbs up. If you haven't subscribed already, please do so. And thanks again as always for watching, and we'll see you again next time.
Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. A couple of months ago, I bought something called a Tinkerboard. And to be honest with you, despite, I think it's now 3 months worth of effort, I can't get the darn thing to run for more than a day or two, and sometimes not at all. So at this point, I don't recommend you buy one. Having said that, I'm going to make a last effort to get the thing to work. Just to sort of go over what I've used. I've used 4 different monitors, 4 different SD cards, multiple USB cables with micro on one side and the standard on the other to power the thing. 4 power supplies, all rated at 2 to 2.5 amps at 5 volts. Different HDMI cables, different settings on the monitor. Pretty much have tried everything I could think of to make it work, and up till now it hasn't. It's had a number of issues, including I've got it mounted because this is what my last ditch effort is. Kind of getting ahead of myself, but we'll get to this in a minute. This is the Tinkerboard, and I've mounted it on a power supply. Here's my thinking, and I haven't tested it yet, so we'll see how it goes in just a few minutes. So I'm suspecting, despite the 4 power supplies and all of them rated at more current than the thing is drawing, that perhaps it was hearing noise. Maybe there's some issue with the USB port that's on it. What I've done was to get a power supply from an old computer. This has a 5 volts at 16 amps. Plenty to power it. And I'm going to go through how I've converted this computer power supply from master cooler into basically a desktop or bench power supply. So the point of this episode is, how do you make a computer power supply into something that you can use in your ham radio station? Also, is it something that can be used to power the Tinkerboard? So I pushed it off to one side. I plan to mount other stuff on here. Is this the way I'm going to use it forever? No, it's mostly to see if I can get the darn thing to run. I've become so frustrated with it, I didn't call it Tinkerboard. I gave it a much more distinctive name. The HDMI in and out, despite the times when even at the times when the thing would run, they didn't function. I bought Raspberry Pi camera, that doesn't function. This heatsink that's on here is a little piece of double sticky tape. It frequently comes off. So to try to resolve that problem, I mounted a little blower on this end, connected it to 12 volts. That's going to blow across, hopefully, the heatsink and keep the thing cool. The processor that's on here runs really hot. I haven't put a thermometer on it, but it's way the heck up there. That may be part of what's going on. I don't know. It may be shutting down thermally. Tinkerboard has 4 USB in, Cat5, HDMI out, ribbon HDMI in and out, and an 1/8 inch jack that can be either audio in or audio out, if I understand it correctly, and then the micro SD. All right, let's run the video. I'll show you how I converted this thing. It's interesting wiring on the inside, as it turns out, and then at the end of that we'll come back and power this thing up and see what happens. All right, let's watch a few minutes of video on making a power supply, or making a power supply. Okay, so it says 276 watts at 12 volts, which would be 23 amps. So that would supply power to most transceivers. There's a green wire that's on this multi-pin connector, not that one, but that one, that when taken to ground turns the power supply on. So it's like the front panel switch grounds that green wire. So what I'm going to do is I'm going to undo it from the bundle, and I'll just take it to ground, leave it permanently on. The switch that's on the outside of the cabinet will work. So if you have one that doesn't have a switch, use that green wire. Just take it to ground through the switch. Okay, now comes the surprise. Let's see what's on the inside. Looks like there's just 4 screws on what amounts to the bottom of the power supply. And I'm curious about this gaggle wires because, what do they all go to? A terminal strip, or what's on the inside? And doesn't look like the fan can be unhooked or unplugged. All right, it almost appears that they all go to the same spot on the circuit board, so I'm really curious about what that looks like. So maybe this would be time to pull the circuit board out and see where all those wires go. Are they all connected together? Are there separate runs, separate power supplies, separate capacitors? At this point, I don't know. I do know there's too much wiring, so best for me just to get a bunch of it out of the way. There are 3 colors I'm looking for. There's orange, yellow, and, well, actually 4. Orange, yellow, red, and black. There's a 3.3 regulated supply. I don't think I have a use for that, so I'm just going to ignore it. There's 12 volts regulated and 5 volts regulated, and then a ground. So those are the ones I'm going to go for. The question is, do I need all those wires? And at this point, in looking at the wires, they look like number 20, which on a good day, short run, is probably good for 4 or 5 amps. So in theory, for 23 amps, I need maybe 5 wires. I think I'll increase that a bit because the wires, they appear to be labeled number 20 AWG. I've in the past found some that were not what they were spec'd out to be. So let's cut these things out of the way, get them to a length that's manageable, and I think then I'll lift that power supply out. It looks like there's at least 4 screws that hold it in place, maybe one in the middle. And the darn fan does not unplug, so I may end up cutting it out of the way because it's just going to be in the way the whole time. In cutting these right now, I'm making them about 1 foot long, so in the end they're probably going to be just a few inches long. The orange are the 3.3 volts, which I don't need. The yellow is 12 volts, and the red is the one I'm really going for right now, and that's the 5 volt. And black is ground, and that'll be the easiest to deal with because I can take that bundle to ground. Likely the circuit board is also grounded, so the black wires may be redundant, but for noise I'm going to ground them. Okay, so I've got red, yellow, orange, black, and a green wire tucked in a bundle that and now we find out. And look at that. They're pretty much just solder together. That trace has handled a lot of current. 23 amps worth. Surprises me. Well, 12 anyway. And what do I do with the back end? Okay, time to start cutting wires. I'm going to mount terminals through the holes that are the ventilation holes. I can probably line 3 of those up in a row and make it look halfway decent. I happen to have a green one which will be, I think I'll make that 12 volts, a black one which will be ground, and a red one which will be the 5 volts. And I think I'm not going to use all the wires because there's no point to it. Pick a number 6, 7, 8. I might just do 8 and bundle them together. I think what I'll do is I'll put them into a pigtail, connect like a number 12 wire to the opposite to the pigtail, so that the bundle of 8 will connect to a really good cable that I have, a really good wire that I have. It's actually a cable, and I'll do just some big glob of I'll do some big wrap with all the wires. I don't need all these ground, they're just a waste, so I'm going to cut a bunch of them out of the way. And I'll cut them shorter when I get in there. I don't have the right cutters with me. And this is the 12 volt one, so I'll grab about 8 of those. Cut away the rest because they're not needed. And again, I'll cut those to a manageable length and strip the ends, bundle them together, wrap them with some number 12, and make like a pigtail out of it. I'll put some heat shrink over the solder connection because it's going to be messy no matter what I do. I've got some alpha wire number 12 AWG, which is a really good high temperature cable that'll handle the current with no 23 amps. It'll handle it fine. Okay, I've got them bundled together. Not a pretty soldering job, so I'm going to hide it with some heat shrink. In fact, I'm going to do it with 2 layers of heat shrink. I'm concerned that a wire might poke through an individual strand, so see what I'm doing here. So again, there's 2 layers. The outer heat shrink is the kind with a glue on the inside, and it's really thick, so there's no way a wire is going to, or a strand is going to poke through that. Alright, I've got them bundled together. I've wrapped them with nylon straps, wire ties. Kind of pushed them out of the way because I've got to keep clearance for that fan, and so I'm going to tuck them underneath a small circuit board. Try to route them in a way where they're not going to make contact with anything, and they're not going to be touching the heat sink in the power supply or the blades of the fan. I did also, when I had the circuit board out, drill 4 holes to mount the tinker board. Not a great job of drilling holes, but anyway, it'll be good enough for this. Okay, I'm going to make sure I've got clearance for this fan, that it will spin. And you can see I've mounted the 3 terminals that were just, they're insulated from the chassis, so they're poked through a hole, and I just enlarged one of the vent holes, or 3 of the vent holes, and pushed them through. Okay, I have just now put into the GPIO pins 5 volts on 2 connectors, ground on 1, plugged in an HDMI cable that I know is good into a monitor that I know works on HDMI. I've used Win32 to upload the latest version of the Tinker OS operating system. Turned it on and it worked. I'll let you know after several hours whether or not it continues to work, and maybe I'll put a comment. That appears to be I've got a receiver going, you can hear it in the background. That appears to be the problem that I was having. It may have been that the power supplies I was using or the way I was connecting it to the Tinker board just won't work. So I'm into 3 pins, 2 are red, 1 is I think black. Red ones are the positive, of course, black is the ground. And it seems to be working okay. Also, the little blower that blows across the top of the heatsink seems to be doing a job. Just a quick test of it, the heatsink is much cooler than it was before. Anyway, that's a video on basically on how to convert a computer power supply into a bench power supply. See you the next time. I'm Jim, W6LG for Ham Radio Base. I'm Jim, I'm Jim, W6LG for Ham Radio Basics. Thanks for watching. See you the next time. Oh, and please subscribe. Thanks.
In today's video, we're going to talk about tuning a simple antenna duplexer with a spectrum analyzer and tracking generator, as well as tuning it with a VNA or vector network analyzer. But first, let's talk about what a duplexer is. A duplexer is a device that permits full duplex transmit and receive through a common antenna using relatively closely spaced signals. A diplexer, on the other hand, typically will separate frequencies by band, maybe a VHF and UHF. But a duplexer typically works within a common band where the frequencies can be very closely spaced together. This is often used in very common applications like cellular telephones and things like that, as well as public service radio and amateur radio repeaters. Now, because the transmissions occur simultaneously, the duplexer must ensure that the transmit frequency doesn't get into the receiver, and then the received signal coming in also doesn't get into the transmitter. And because these signals are very closely spaced, that places some pretty strong requirements on the filter properties and the band pass and band reject characteristics of the duplexer. Now, there are different types of duplexers. Probably one of the simplest types is a band reject or notch type filter, where essentially the transmit frequency is notched, so there's a lot of rejection in the receive path, and vice versa, the receive frequency is notched in the transmit path. So that ensures the transmit signal doesn't get into the receiver and the receive signal doesn't get into the transmitter. The problem with band reject filters is that the passband characteristics are relatively broad. So if you're working in a dense environment, you might allow other signals to get into the receiver that might overload the receiver. So the band reject filter, while it's simple, and it's the example that I have here that I'm going to demonstrate, it's not the most desirable, but it's certainly the easiest to tune, so that's why we're going to use it in this video. There's also bandpass type filters. The bandpass type actually sets a narrow bandpass filter around both the transmit and receive paths with a high rejection for out-of-band signals, and that's typically the preferred type. And then also there are duplexers that combine both of them. They're both a bandpass and band reject in the same device, and they're more complex to tune. And if I ever get a hold of one here to demonstrate, I'll show tuning one of those combination type devices as well. But for today, we're going to just show tuning a band reject filter with both a spectrum analyzer and with a VNA or vector network analyzer. This is the duplexer we'll be using for today's video. It's a simple band reject or notch type duplexer. So we have an operating frequency pair, a high upper frequency and a lower frequency, and they go through to a common antenna port. On the high side, we will pass the upper of the frequency pairs with very little attenuation, and we'll notch out the low frequency of the pair, and just the opposite occurs on the low side. The adjustments are done by essentially tuning each of these rectangular blocks, which are kind of resonant cavity notch filters, and there are little adjustment screws at the end of each of these. A duplexer like this is a passive device, so the response through a given path will be the same regardless of whether we're sending a signal in that direction or in this direction. So it almost doesn't matter really which side we hook the tracking generator up to and which side we hook the spectrum analyzer up to. It is important, though, in many cases, to ensure that you terminate the unused port when you're tuning one side. We've got the tracking generator output connected to the high path port, the antenna connected to the spectrum analyzer input, and we've set up the sweep to encompass the notch that should appear in that high path. Now the sticker on the unit indicates that the low path, or the low frequency, should be 314.75 megahertz. So I've got that set up as the center frequency of my sweep, and I'm looking at a 100 megahertz span. Now what we can see on the analyzer is essentially the notch. In this case there's 3 little notches because of the 3 cavities that are not properly tuned. Right here at the center is where we actually want that all these things to line up. So we'll just simply adjust each of these screws to make that happen. It doesn't really matter where you start generally, so we'll just start on the end here, and I'll start adjusting this one, and we can see that the notch that's all the way over on the right is moving over. So let's move that over until it kind of lines up right about in the middle, and we're probably right about there. Let's adjust the second one here to see if we can make any improvement in that. Let's see, if I move it this way, you can see I'm kind of extending it out to the right, so let's kind of bring that back. And if we go too far, we can kind of see we're extending it the wrong way, so let's try to center that back up and bring it into the center. And then we'll grab the third slug here, if I get the screwdriver in there, there we go, and bring that one down. So now I can see I've kind of adjusted that probably about as best as we can do, and we can see we're driving right down in here. Now the wide band of fuzz I see here indicates that I'm really driving down into the noise floor of the analyzer here. So let's see if we can do something about that. So right now the resolution bandwidth on the analyzer is 1 megahertz. So if we lower that, let me go to a coupling menu and uncouple the resolution bandwidth and start lowering that down. If I bring that down to say 30 kilohertz or even 10 kilohertz, you can actually see now that I'm sweeping a whole lot slower, but I've also driven that notch a little bit deeper down. And if we actually take our span, now let's reduce that down to say 50 megahertz, so I don't have to sweep quite as far. Now I get a little bit faster sweep. It's still taking about a second to do the full sweep, but now I can actually see that noise is being dropped down quite a bit. Compared to the passband characteristic up here, I'm down about 90 dB. Now I can see that the bottom of this notch isn't perfectly flat, so that tells me I probably don't have each of these cavities perfectly lined up. So if we tweak on them a little bit more, I was able to kind of make that a little bit flatter, so I'm probably a lot closer there now. Let's see, with that notch right there. But I can't really do much better than that with the noise floor where I have it. Now I've wound up with a notch that is literally about 90 dB down from my passband characteristic up here. So that's actually pretty good, and that's probably about as deep as you're going to be able to go with most spectrum analyzers with a tracking generator. You're just not going to have enough dynamic range to see any more. Now the issue that I've got here is that I've got a relatively wide notch here, and the reality is that the notch actually extends down below what I can actually see on this analyzer here. So actually you can get more rejection and actually fine-tune each of these cavities even more to line them up to deepen that notch even further, which would give me more and more isolation between the transmit and receive path. But I'm typically limited when I do that with a spectrum analyzer and tracking generator. So let's take a look at how much better we can do with the VNA. On the spectrum analyzer we left it with a 50 megahertz span and a resolution bandwidth of 10 kilohertz. So I set up the same 50 megahertz frequency span on the VNA and a 10 kilohertz IF bandwidth. Now it might be tough for you to see, we'll zoom in on this in a moment, but this lineup right up here is 0 dB, so there's my passband characteristic like we saw on the top of the spectrum analyzer display. And this line right here is my 90 dB down. We can see we're actually better than 10 dB and close to 20 dB better. But now I can actually see I do have still have a little bit of width here, so we actually can make some improvements in tuning each of these cavities and lining them all up and drive that notch even deeper. Let's see if we can tweak these filters a little better and align them up and drive that notch a little bit deeper. So we kind of bring these all over. Let's see, we'll leave that one about where it is so we can drive some of these other ones a little bit closer to it. And bring that one down here even more. All right, I've tweaked these around a little bit, and it's probably about as close as I'm going to get. If we take a look now, we're kind of hitting the noise floor, or getting closer to the noise floor of the VNA here. And I'm looking at, in the neighborhood of about 110 dB down. So I've just gained myself another 20 dB in terms of improving that measured notch that we were seeing compared to the spectrum analyzer. I made one small change here. I reduced the IF bandwidth down to 1 kilohertz. The sweep speed's gotten slower, but now I can actually see that notch is actually closer to about 120 dB. And I see it's coming down pretty much to a point, which means I've got each of those cavities pretty much lined on top of each other. Probably not going to do a whole lot better than that, but 120 dB of notch, of rejection versus, the only thing we could really see on the spectrum analyzer was about 90. So that's a 30 dB difference, a factor of 1,000 now, in terms of the difference that we see in the rejection of one signal through one path or the other. Now, of course, a VNA brings a lot more to the party than just improved dynamic range. In this particular case, for a notch type duplexer, the dynamic range improvement is really what we gain. When we start getting into the more complex types of duplexers, such as the bandpass type, or those that include both bandpass and band reject in the same cavity, there's a lot more adjustments to make. And you may want to look at more than just, in this case, like an S21 or a through measurement. You may also want to be looking at, S11 or return loss for a given path, or maybe both directions simultaneously, because a lot of these other more complex duplexers will include adjustments not only for the bandpass characteristic, but for the notch characteristic, and even for the insertion loss, which will also adjust the Q of, say the bandpass side or something like that. So by being able to look at both reflection and transmission properties at the same time with a VNA can be a lot more insightful and make it easier to tune these more complex duplexer types. I hope this video has given you a bit of insight into what a duplexer is and how you tune it with a spectrum analyzer and tracking generator, as well as with a VNA. If you like what you see, give me a thumbs up on the video. If you haven't subscribed to my channel already, please do so. And thanks again for watching. We'll see you next time.
Hi, I'm Jim W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain Lookout. One of the videos I did last month has been really popular, and I've gotten a ton of email requests for information about my light bulb dipole that I used on FT8 to work a guy, I think it was like 700 miles away. A lot of confusion about how I hooked it up. To get to the point of how I made it, the light bulb dipole is a dipole, and I'll show you why in just a minute. I found this square frame, and I found it in a craft store. And so I bought one thinking I would use it on this project. I put on 4 rubber bumpers that I happen to have in my junk box off of something else. Typically they are porcelain, and in fact they're often called a porcelain keyless socket. It's a light bulb socket, like would have been in many closets in many homes, screwed to the ceiling, chain coming down, you pull the chain, light comes on. That's a keyed socket. This one is keyless, it doesn't have the chain. In any case, a portion of it is porcelain, ceramic, something, be able to take the heat. This one I found at a True Value hardware store. I think it was $2 or $3. This V arrangement I also found in a True Value hardware store. I think it was more than the socket. I think it was $7, which was kind of a rip, but anyway. So how did I make it into a dipole? And as I said, it really is a dipole. I'm feeding the outside part of this part of the socket on one bulb and the center on the other. I know that's confusing. So anyway, why the dipole? Well, I thought it would work better, and as it turned out, it did. So I bought one of these. As I said, True Value had that. I think it happens to be a Leviton. I drilled out the rivet the head of the rivet with an 1/8 inch screw or a drill bit. And then on the, then I had to pry this part off the bottom. So basically I was able to sort of pry it loose with a screwdriver. Once that was off, then the two pieces could come apart. And this was one piece, there's nothing in it, and I'll put up a picture of the other piece. So with the socket attached, I'm feeding this outer ring with the shield of the, doesn't matter, but I'm having to be feeding with the shield of the coax. The center is being fed with the center conductor. And what I did to make this into a dipole was to split this sort of brass looking piece. I think it's plated. It may be brass, but I don't know. So I took some side cutters or sheet metal tin snips and cut out a section and then connected a wire so that I'm feeding just the center on this socket and not both at the same time. This is one of those projects that is good for a club to do, or perhaps some newly licensed guys, or if you want to demonstrate it for those who are going to be taking their exam. It's a way to talk about Ohm's law in a very practical way. You can actually see things light up. If you're going to do this for your home station, stick it in a window or run it outside and see how far you can communicate with it. And the mode to use really is FT8, because when you listen with this thing for an antenna, to say you don't hear much is an exaggeration. You really don't hear anything, but it's able to dig out signals and make contact. So one comment that I had from a neighbor who is an engineer who thought that I had made some connection to the house wiring. No, not even remotely. It's dangerous. Just connect it to your transceiver. Be very careful. Keep an eye on the SWR. Use an antenna tuner. Realize that when the bulbs are cold, the resistance is very different from when they're white hot. And as you might suspect, the resistance goes down. So that's my light bulb dipole. I've used it a few times. I made a bunch of contacts with it. I was truly amazed as to how far it would work. In any case, give it a try. It's kind of fun. It's not very expensive. That's it for today. I'm Jim, W6LG for Ham Radio Basics. Thanks for joining me. If you have a question, put it below. See you the next time. 7-3. Hi, I'm Jim, W6LG. Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. Been kind of busy the last few weeks, and a couple of weeks ago, I think it was 2 weeks ago, we had to evacuate. And that's what I want to talk about today is, what do you do? It was about midnight. I'm taking a drug called Lasix, and if you've taken that, you know you have to get up during the middle of the night, more than once likely. So got up to go to the bathroom, and went into the family room. There's a bathroom off of the family room. Totally oblivious to what was going on around me. It was pretty windy. I would say it was blowing 65 miles an hour. And the lights blinked. And the lights blinked. So I turned on the scanner, and much to my horror and shock and oh my, the local sheriff's frequency, they were doing evacuations of a road that is not far from me, kind of parallels my road. And it's there's a little bit of a canyon and then this road, and the road loops around. And what the heck? So I looked out the window, and the sky, it's midnight. And in fact, it's right at midnight. I could see flames in the distance. I could see the bottom of a smoke cloud, It was being well lit up. I could see the outline of trees because of the fire burning, and thought, oh my, we're in trouble. The wind was blowing our direction, and from what I could tell on the scanner, the fire was spotting our direction, and in fact it was. So it was kind of long and narrow and spotting in front of it and coming our way, which is the reason for evacuations in our direction. So I woke my wife up and said, we got to get out. And about the time I said that, the power went off. What do you take? Power's out. I've got flashlights. The phones may not have working. There was no reverse 911 call. When we plugged in a phone that doesn't require power, there was a dial tone. I had been involved in emergency communications in a number of disasters, won awards for it, honored by the Board of Supervisors. I've been a county building inspector, county tax assessor, a member of the Planning Commission. I know better, but I wasn't ready. So what did I take? Well, needed my medications, can't do without those. Probably could get things refilled, but some of them I have to take on a schedule, and there's not much margin for error. I'm currently on oxygen part of the time, so we loaded in 3 oxygen cylinders into the back of the Honda, and some clothing, So I took a couple of shirts, a couple of pants, and the rest of it. Some water. Feel like I have an obligation because of my license to have equipment in an emergency. So I took a handheld and a scanner and listened on the way out of town. But frankly, we were not prepared. It was windy. It didn't occur to us that there would be a gigantic fire. In that fire, about a dozen homes were lost in that fire. At the same time, another one started in another part of the county. That one consumed, I think, 30, 40 houses. In the Bay Area, the disasters was just hard to imagine. Something like 6,000, 7,000 houses destroyed. 40 plus people died as a result of the fires. So what do you do? I think what we did not do, or we were not prepared in the sense that we hadn't packed the night before, or maybe the day before. It was windy. In this case, a power line came down, either a tree came down or a power line came down, and that sparked a fire. And right at the beginning of a road, and immediately took out a guy's house. I'll try to include a picture. I shot a couple pictures on the road. So what's the point of the video? Let's put up a couple of things that you think that you must take. What are the things we have to have? You can get bottled water probably, but you need some en route to where you're going. What else do you need? Well, you need medications. As you get to be old, it becomes a requirement. In my case, I have to take these things. There's just, if I don't take them, I'm in deep trouble in a big hurry. And there's about a dozen meds. The oxygen I had to have, but clothing, some food. You better take some money. If you've got any cash laying around, you better grab it, because it's not going to be there when you get back if your house does burn. That's another thing. To finish this off, we decided and said that as we went down the road, if the house burns, the house burns. Yeah, we're going to hate that. It's going to be terrible, but if it happens, it happens. And fortunately, it did not happen. The fire department did an amazing job and literally stopped the fire around several. They were able to protect many, many structures. So the loss of houses was way smaller than it would have been. They did an amazing job, as did the sheriff's department, who brought in animal control, if you can believe that, because I listened to the call signs. They brought in Placer County sheriff's deputies and deputies, I think, from another county who would not be familiar with the area, or maybe they lived here, worked Placer County, to help with the evacuations. Literally, they were running from door to door, listening to the scanner. I could hear deputies being out of breath and being told by their dispatcher, who did a marvelous job, geez, they were really good. To get to this house, they can't get out. The flames are blocking the road. Sheriff's deputies went through the flames, recovered the people, left. So, what do you think we should take? What would be, pick out 3 or 4 things that you absolutely think you need to have. Look at what somebody else has posted in front of you. Let's create a list, sort of a checklist that we as amateur radio operators should take. If you got a go box, maybe that's high on your list. I would think it would be. Anyway, bullet those items, like number them so I can find them, like 1, 2, 3, 4. Don't put 20 things. It just becomes too much. Put 3 or 4 things that you absolutely positively would be taking in the event that something goes wrong. We got lucky and that they stopped the fire. Anyway, that's part of what's been happening around here. So please do post a message. I'd be happy to hear from you. I'm sure others would too. If you have a question, put that below. Please do subscribe. I'm trying to get to 10,000 subscribers. It's just a personal goal by the end of the year. Anyway, thanks for watching. I'm Jim, W6LG, on Wolf Mountain in Northern California. And I think there's a fire map, if you Google it, where you can see the outline of the fire. And it's pretty interesting. If you zoom in, I think CAL FIRE has it. If you zoom in, you can see literally they were able to stop it around houses and structures, garages and things, maybe not, but houses they saved one after the other. Absolutely amazing. All right. Thanks for watching. See you the next time. Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. 2 days ago, I published a video about evacuating, and it's had more than 1,500 views and more than 200 responses. In the video, I described what happened with us and why we had to leave and that we weren't prepared, and asked for ideas about 3 or 4 or 5 things that you probably should have ready to go. The actual list will be longer, but give me your best 3, 4, or 5 things, and try to cover things maybe that somebody else hasn't mentioned. And I've gotten really good emails, just some great ideas. So I'd like to go through those real quickly, and we'll create a list of items, and I'll publish that below the video. And we'll add to that. So this is going to be an ongoing process. What kinds of things should you have ready to go? And along those lines, since we're licensed, many of us that are watching this video are licensed amateur radio operators, we probably should have a go box, go bag, go kit, radio box, something prepared and, as the name implies, ready to go. So that's going to be a subsequent video. Sherry, who lives in Oroville, she's had to evacuate 4 times. She says she now has water, healthy snack bars of some kind, cell phone charger, duplicate meds, change of clothes, and photos. And if you're not familiar with Oroville, take a look at the Oroville Dam. Tom Ramberg, OH6 VDA, also JW6 VDA, sent the URL for the fire map in case you're curious about what that looked like. It's calfire.ca.gov, and then it's /general, and then /fire maps. And fire maps is one word. Chad, W4CHD, asked if he could share my video with others on Facebook. Please do that. It's all good. So any information we get, any help I can get is good. Cosmos makes a point. I'll mention his email. He points out that whether you believe in climate change or not, you need to be prepared. So climate change is not the issue. Whether you're on one side of that or the other, the point is we need to be prepared. Ethan Poole pointed out in his email that the extraordinary efforts made by first responders saved a lot of lives. Yeah, we lost a lot of lives, but it would have been even greater. And in my area, that would have been the case for sure. AIO listed the following items: scanner, radio, I think he probably means UHF, VHF, money, credit cards, food, my glasses, everybody in my family. It's a good idea not to leave somebody behind. It has happened, though. Jeff Minnick says meds, water, NHT, a Go box, and again, the Go box we'll cover in another episode. That may actually be several. I've got some pretty strong ideas about those things, and on the examples I'm going to use, it's going to be an inexpensive Go box, something that can be done for not a lot of money. Let's see. In one of the emails, Tony Cantrell says to have extra fuel. What I think he really means is to keep the tank of your car filled all the time, so that you're not down to a quarter of a tank and you have to evacuate and you can't get to where you need to get to because you're running out of gas. And that has happened. I'll kind of skip over this one, but one guy lists a bunch of things to take, and he lists his wife is at the bottom of the list, and another guy responded with, better move your wife to the top of the list. C. White says medications, cash, bank cards, 3 days of clothes. He recommends a GPS, portable ham radio equipment with extra batteries. The extra batteries thing is a very good point. That hasn't been mentioned so far. Michael Montgomery, who's a police officer, if you have a chance to read his paragraph to me, do that. It's really, really interesting. Basically, it can be summarized in that he says, you, me, must be prepared. That way, responders can attend to those with the greatest need. Seventh Depth of Field mentions a Pelican case that's a top loader that he likes a lot. So it is part number 1430, top loader case. Says it's $76. You might want to take a look at that. There are lots of alternatives to that kind of thing, but Pelican's hard to beat. Fanger wrote to me that he would carry as much water, food, clothing, tools for cooking. Just another guy wrote, living under the constant threat of fires, we have to devise an evacuation plan. He's quite right, and that's the point of this video, is we need to do that. His items would include the deed to his house. I think that you don't have to have that, but that's based upon my county government experience. Insurance paperwork, health insurance paperwork, baby pictures, pictures that are hard to replace. Medications, food that you can eat while traveling. He mentions a new one, which is pet food. Again, keeping the gas in the car filled, a Go kit. He also mentions those little GMRS or MURS or FRS handy talkies that you can buy at Amazon. They're not very expensive. Some of those so that non-ham radio operators can communicate. He also recommends the American Red Cross website that has information on getting ready, and I'll put it in the video. It's readyforwildfire.org. Reaper indicates medication, a bag ready in case of emergencies, extra pair of pants, important documents, and by that he means any kind of lease agreements, deeds, any other documents that are kind of hard to replace, clothing, communication gear, and he goes into his list of things that would be in a Go box, and they're excellent. But I'll cover that in the next video. And lastly, he says, always keep your car ready to go, full of fuel, and he's right. Deborah Neighbors asked if I could recommend some basic ham emergency communication equipment for our Go box. I will do that. I'm not going to mention specific transceivers. There are lots of choices. Fortunately, God, are we lucky that there's all kinds of things. But I will discuss in general terms the kinds of transceivers and things that I think that you should think about taking. BT Shop says some food and water, important medications, knife, fire starter, first aid kit. Now that's the first person that's mentioned a first aid kit, and I think that's hugely important. You may not need it, but you may come across someone who does. So if you ran across somebody like me who suffered an injury, a cut, having some gauze or bandages or something to seal the wound could save that person's life. So he mentions first aid kit, radio, Go box, we know, cache, important documents, family photos, and again, that's probably a good idea. Other folks have mentioned loading the family photos to the cloud, into some cloud server. That's an excellent idea, so that you have redundancy, or perhaps putting them on a NAS or some kind of hard drive backup, like a passport. So you could grab that passport, put it in with your stuff, and get out. Ray Bush mentions a fully self-contained ham radio station, 160 to 70 centimeters. I'm not so sure about that. It'd be nice to have the bands that are important that you might use in an emergency. I don't know that 160 would have any use. 80 might, 40 probably would, 20 probably would. Excluding the work bands, which I would think wouldn't be of much use. 10 and 15 meters, probably not. 2 meters, yeah, for sure. 70 centimeters, probably. In a lot of, we don't have 70 centimeters here because of the radar gizmo down the hill from us. Medication, wallet, mobile phone, my laptop. And that's the list that I've gotten so far. They're all excellent ideas. I'll list them at the bottom of bottom of this video, and let's add to that. So let's try to make it concise and see what else we can add. To continue along these lines, I'm going to do the Go box. I've got a video about half done on the dipole antenna, how it works. I'm going to maneuver that just a bit towards the emergency thing. Dipole is a great antenna in many emergency situations. While it may sound like it's not, it can be a lifesaver because it is so efficient. In any case, thank you very much for all the folks who viewed the videos, and for those who wrote in. It's great information. There's probably something major that's been missed, so if you can think of what that is, please let us know. Thanks for watching, and again, if you see something that we've missed and you want to add it to the list, please get a hold of me through YouTube by posting a message. If someone asks a question and you have the answer, please go ahead and answer. Thanks a lot. 73, I'm Jim, W6LG for Ham Radio Basics. See you the next time. Thanks a lot.
In today's video, I want to show you a really neat accessory that I found for this Yaesu FT817 all-mode HF, VHF, and UHF transceiver. Great little radio. The thing that I've never liked about it is the power plug. The power plug on this rig is a short little coaxial plug. And to me, it always seemed like it's just a little bit flimsy. Kind of wiggles around here a little bit. And if you got this thing in a backpack or something like that, you're worried about breaking it because it's kind of a fragile little thing. And also, I've converted most of my 12-volt rigs to operate with power pole connectors. So I had to make this little pigtail up just to get connect up to the wires to my battery packs and things like that. So I found a neat accessory that actually solves some of these little problems. Oh, and here it is. It's a kind of a 3D printed housing that holds the pair of power pole connectors and the coaxial plug in a nice, neat, compact little housing. It's actually designed to be mounted right onto the back of the rig, and held in place where this ground screw is. In fact, on the rig itself, if you take a look, there's actually that ground screw kind of comes out with a little kind of raised cylindrical area. There's actually a spot for that in the back of this housing here as well. Let me show you how this goes on. You start by removing the ground screw from the back of the radio. Then, quite simply, insert the coaxial power plug into the connector, and make sure to line up the hole in the housing with the embossed raised area here for the ground plug. And put that all on there, and it actually fits quite snugly right under the back of the radio. Now, they also provide a longer ground screw, so you can replace the one that you've pulled out, and this will lock the housing to the back of the radio. And that's basically it. It makes a really nice, low-profile, rugged way of connecting up your power pole-equipped power cable to the rig and ready to operate. I found this little accessory for sale on eBay. It's made by a fellow ham up in Missouri, M0ODZ. I'll put a link to his store down in the notes below. Anyway, thanks again for watching. I thought you'd all appreciate that, especially many of you that I know are FT817 fans and owners. Thanks again for watching. We'll see you next time.
Hi, I'm Jim W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain Lookout. My favorite antenna, for a lot of reasons, is the dipole. It's simple, it works. In emergency situations, it can be strung up from as an inverted V, an upside down V with the center insulator attached to a pole, a tree, a fence post, all kinds of things. It is real forgiving in terms of its length. It doesn't have to be perfect. Pretty much anything will work, from house wiring to electric fence wire even. So, and that makes some changes, but this is a dipole, and I've mounted it to the top. As funny as it looks, I've mounted it to the top of an antenna analyzer. It's not pretty, but it'll make the point of what a dipole is. And in this case, instead of having something like this in the middle, I've just got a coax connector, and I soldered on 2 lengths of house wiring. How long is a dipole? Well, that's really easy. The formula that I use is not one that you'll see in a book. It is simplified just a bit so that I can remember it. And the formula, my formula for a dipole is 1, 2, 3, 4. That I can remember. One side is 234. 1, 2, 3, 4. One side is 234 divided by the frequency in megahertz. So I cut this a little bit long. It is about 20 inches. So the if I take 234 and divide it by 1.75 feet, it's the number of feet into 234. Resonant frequency about 134 megahertz, so a little bit shy of 2 meters. Okay, so let's see where this antenna is resonant. It's got a couple of dips, so it's probably reacting with the other wires on the table. It's about 45 ohms at 137.7 megahertz. I said 133.7, so it's about 4 megahertz different, and part of that probably has to do with the insulation on the wire and its diameter. So let's see where it starts to go above 2 to 1. It's above 2 to 1 at about 156 at the high end and about 132 or 33 at the low end. So about 24 megahertz of coverage. On 2 meters, let's go to 144, it's 1.5, 148, it's about 1.6. So that's really pretty good. What happens if I add 100 feet of coax? And in this case, I've got on the table 100 feet of RG8X. What will happen to the dipole? It's going to change the SWR. Okay. So It's so broad I was having trouble figuring it out here for a second. So its resonant point is about 136 megahertz. 2-to-1 SWR now is down to 115 megahertz and up to, well, it won't go that high. So probably 180, 190 megahertz. So we added 100 feet of coax. The resonant frequency stayed pretty much the same, but its bandwidth became enormous. What does that tell us? Well, the feed line is really lossy, so the reflected power is decreased as it comes back into this box. In other words, the SWR here is one thing. The reading that this makes at the end of 100 feet of coax is very different. So we have a lot of line loss because this is RG8X. It's not good coax for 2 meters and above. It's not good coax for a lot of frequencies. So it looks to be really, really lossy because all of a sudden it shows a huge bandwidth. So when you install an antenna and the SWR looks really good, that may be good and it may not. Speaking of which, I want to show you this. Swing this around. This fancy looking box is my automatic antenna tuner. Instantly tunes the antenna, which is made up of 2 rods about, I think they're about 19, well, they're probably close to 20 inches long. Feed point is down here, and it instantly matches to the transceiver. I mean, instantly. So let's see how this looks. I'm gonna disconnect my dipole, such as it is, which would work, by the way, and it worked fine on 2 meters. Oh, speaking of which, if this is a dipole, and if we get an understanding about how this works, when it's configured like that, it's a vertical, right? So if we added more radials, it would look more like a vertical, bent and not very pretty, but it would be a vertical. When it's like this, it's a dipole. If we can understand how this works as a dipole, we can probably figure out a lot of different antennas. So let me bring up a video that I shot outside yesterday. It's far from perfect, but I took exterior Christmas lights, holiday lights, whatever you'd like to call them, strung them out on about 8 feet of fiberglass pole and transmitted into it. And if you watch this video closely, look at the bulbs in the middle that are at the feed point, and then look at the bulbs on the end that are red. And as shaky as it is, the filaments for the bulbs in the middle, I think they were blue, hardly light up at all. The green are lit a little more, the orange considerably more, and the red are really bright. So what does that tell us about how the voltage divides on a dipole? The bulbs at the end are bright, the bulbs in the middle are barely lit. So the high voltage is on the end, and the high current is in the middle. Now, why is that important? Well, it's important because it tells us a couple of things. It tells us what part of the antenna is doing most of the radiating, and it's not the high voltage, it's the high current. So a good deal of the power that's radiated by this antenna occurs in roughly the middle, about third of the way up. In other words, you can take an antenna, put some kind of capacity hat on the end of it, take off this end, and either put a trap here or some kind of capacitive loading, and still have a relatively efficient antenna for a dipole. Let's say you decide you need to feed this at the end. Okay, this is the low impedance, high current. This is the high voltage, high impedance. So if we combine this and put the coax connector down here, what does the impedance look like? Well, if we do the formula, it comes out infinite, but in fact, it is about somewhere in the neighborhood of 5,000 ohms, 4,000 ohms, in that ballpark. So we need to do transformation. In other words, if we're hooking up RG8X here, that's 50 ohms, we need to change the impedance or match the impedance with a transformer of some kind. Very easy to do, no big deal. It's typically a 9-to-1 or 10-to-1 transformation. Again, high current in the middle, high voltage on the end, high impedance, low impedance. If we feed it here, it's high impedance. If you can remember that, you can pretty much figure out any antenna. That's an exaggeration, but you can pretty much figure out a lot of antennas that we use on HF. This device, which was similar to one marketed by a company, I think they were in Florida, ran a lot of ads in some pretty well-known ham radio magazines, and I made a copy of it. So I've still got batteries going in that camera. Let's look at the SWR. Again, this is an automatic matchbox. It will immediately tune. There's some parts on the inside. If you put an ohm meter on it, it appears to be open. So let's just set it on the table here. Well, I'm at 175 megahertz and it's 1-to-1 or darn near it. Let's tune down. I'm at 143 megahertz and it's 1-to-1. Isn't that amazing? It works great. I've got a great SWR on all frequencies. There is a point to this. There's 128 megahertz. It's still 1-to-1. Let's go down to 10 meters. It's still 1-to-1. It instantly tuned. Here's 14 megahertz. It's 1-to-1. And in fact, if I'm turning the knob, and it's 1-to-1 everywhere. No matter what frequency I go to, it's 1-to-1. So, how does this magic box work? It automatically tunes. It says right on it that it's rated at 100 watts. So you get a very good SWR. The manufacturers of these kinds of antennas have done them as dipoles and as verticals. If you hook this up and you listen with it, you'll hear a few signals. But what is this? How does this work? Well, if I take off the cover and you look inside, you're going to see about 50 resistors. Yeah, it's a dummy load. It's a dummy load, and the resistors are connected to these two rods. One through a grommet, the other one, the case, is connected directly to the rod. So it produces a 1-to-1 SWR on any frequency, I think. Well, it's going to get weird when you get up to gigahertz, but on all HF frequencies up through VHF, probably even 70 centimeters, it's going to be 1-to-1. So when you see your SWR being low, it may be because you've got huge coax feed line losses. It may be that your antenna is not very efficient. So these are things to be aware of. When a company advertises an antenna that tunes everywhere with a low SWR, be really suspicious. An efficient antenna tends to be fairly narrow in its performance. It has a high Q. This thing is nothing more than a dummy load. And in fact, I'm not sure which would work better, my light bulb dummy load or this thing. What have we discussed today, and what's coming up in the next video? Well, we've discussed that high currents in the middle on a standard half-wave dipole. High voltage is on the end, and because it's high voltage, it's high impedance. At the high current place, that's where most of the radiating is done. It's not on the ends. Thanks for watching. I hope you've enjoyed this. If you have a comment, please post it below. If you've enjoyed this episode, please do subscribe. I'm trying really hard to get to 10,000. and subscribers, and I think I'm at 8,100 plus. Last couple of videos have had a lot of views. Anyway, thanks for watching. I'm Jim, W6LG for Ham Radio Basics 7.3. Thanks. Bye-bye.
In today's video, got another vintage tech episode, and this time we're going to take a look at this Sedcore TC162 tube tester from the early 1970s. Now, the professional quality tube testers of the day can be broken down into two major categories. The more comprehensive types that would measure the mutual transconductance of a tube, and the simpler devices like this one here that measures cathode emission. Now, while both types are very useful to help you to identify bad tubes, no tester is actually going to be suitable to actually tell you whether a particular tube will work properly in a given circuit, whether it's a radio, a television, or something like that. And the reason for that is because no tube tester puts that particular tube under the same operating conditions that a particular circuit would do. So really the best tester for any given tube, if it's questionable, is the device it was designed into. But on the other hand, a tester can be useful to help you identify bad tubes. If a tube has got some shorts between the pins or the electrodes, if a tube has got some grid leakage, or if it's got low emission, things like that, that can help to rule out a tube. But even if a tube tests good on a tester, where it doesn't have any shorts, the grid leakage is low, that type of a thing, it's still a possibility that it may not work in the circuit that it was intended for, but at least it helps you to rule out obviously bad tubes. The Sedcore TC162 is a emission type tube tester, as I mentioned, but there's additional measurement functions that it has. The shorts measurement function allows you to measure for shorts between any of the pins that are supposed to be isolated from each other. Now, in this case, a short is defined by a resistance between the two pins that is anything less than 300 k ohms. The emission function basically sets the tube up into a diode configuration and measures the tube performance at near the full rated cathode current. The life test is used in conjunction with the emission test, and it can also be called a filament voltage sensitivity test. And the idea is that when you push the life test switch into the test position, you look for how much the emissions drop for that given tube. And this is a pretty good indicator of how well worn a tube is or how close it is to its end of life. And finally, we have the grid leakage test. And the grid leakage test on this particular tester is actually very, very sensitive, more so than a lot of testers that are out there, and really gives you a good early indication of tubes that may not work in some very sensitive circuits like AGC circuits. So certainly any tubes that show shorts on any of the pins, they're ones that definitely have got to be got tossed out. I found that tubes that have got low emissions, that are kind of getting towards the questionable area, are often not going to work well when actually used in the application. So that's a pretty good indication that it's time to replace that tube. And then certainly tubes that have got high grid leakage, and are also candidates that with tubes that really need to go. But as I said earlier, if the tube passes all of these tests, there's still a possibility it may not work in a particular circuit, but at least you know that it's not obviously bad. So it is just a screening tool, but not an absolute go, no-go type of a test. This tester was actually built in the late 70s, so it's a kind of a late model in terms of a tube tester. And one of the advantages is that it's solid state. You'll notice there's no vacuum tubes in the schematic. There's a number of switches and a multi-tap transformer, and then a JFET is used in a kind of a balanced bridge configuration here to actually drive the meter for the emissions and the grid leakage tests. An important accessory with any of these tube testers is the setup book. The setup book lists all of the tubes that can be tested by the tester and the configuration for all of the setup switches in order to test that particular tube. Now, before we go ahead and actually use it, we'll follow the advice of my friend Dave Jones from Down Under. Don't turn it on, take it apart. Well, I can't do the Australian accent, but we can take it apart and take a look and see what's inside. Okay, with all the screws taken out, we can lift the panel out of the housing and see what we've got underneath. Okay, so here we go. Here's our array of tube sockets all hand wired up and ready to go. Our transformer is here. that provides not only the power to use for the emissions test and the grid leakage test, but also provides the various filament voltages, and they're all selected by this first switch over here. The next switch here with the ring of resistors going around it is the one that selects the test current for the emission test. And then the next switch here selects which pin is actually being used for testing, either for the shorts test, and also which pin is essentially the control grid that is actually used for the emission and grid leakage test. And then finally we've got our mode switch here to go the shorts, emissions, or grid leakage testing. The life test switch is down here, and then this row of switches along here are the pin elimination switches. There are some tubes that pins have got to be omitted out of the test circuit in order to read properly, so that's what those switches do. And the setup book kind of details all of that. And of course the circuit board over here houses that circuit that I showed on the schematic. And there's a couple of diodes and a JFET on there are the only semiconductors. The rest of it is just a couple of resistors and capacitors. And it's bolted right to the back of the meter. And that's essentially what's inside this tester. You know, again, it's all solid state, so there's no warm-up period associated with the tester itself, but of course there is for the tubes that you're testing. So let's put it back together and actually go test some tubes. Now, the first thing you want to do before you even plug any tubes in is turn the tester on and adjust the meter 0 to zero out the meter. Let's start off by testing this 12BY7A, which is also known as a 12BV7 and a 12DQ7. So if we take a look and locate that here in the book, here's the 12BY7A row right here. This indicates that pins 6 and 9 need to be switched out, that the filament is set to 12, the load switch is set to C, and the setup switch is set to 2, and we'll insert the tube into socket 3. Okay, so we'll lock out pins 6 and 9. The filament is a 12-volt filament, so we'll select the 11 to 14 position here. The load needs to be set to position C and the setup to position 2. And now we're ready to put the tube into socket number 3. Now with the tube in place, let's start by doing the shorts test. For the shorts test, you go to the shorts function, and the tube is going to start warming up, and we'll repeat this test later after the tube has warmed up also. And the idea is you rotate the setup switch and watch the shorts indicator light right here. Now you might get some momentary flashes, and that's okay. And sometimes you get a very slight flicker, and that's okay too. But if in any of the positions that short light illuminates continuously, that indicates that we've got a short of 300k ohms or less on any of those pins. And this is essentially passing that shorts test. We'll return the setup switch to position 2 as indicated in the book, and we'll look at the emissions test. Now, the emission test here is solidly in the good range, and that's a good thing. If we want to run the life test here, we can push the life test switch over and see if we get a drop in that emissions, and it looks like it's staying pretty steady, and it should, because this is an unused tube I just pulled out of the box. So we passed the emission test, and we'll go to the grid leakage test. The grid leakage test, we want to look on the lower scale here, and we can see that sitting right at the very bottom, which indicates that the grid leakage is well above 300 megohms. So this tube is actually quite good. Now you may find with some tubes that as they warm up a little bit longer, that grid leakage will start to come up. But this is a new tube, and this looks like it's okay. Just before we finish up, since the tube has had a couple of minutes to warm up here, I'm going to switch back to the shorts test here and repeat the shorts test. And again, looking for any kind of a solid indicator on the shorts indicator, because sometimes some of these shorts can be thermally induced. So I would say that this tube has passed the test here. It's got a good likelihood that it may be okay and can be used in the circuit, but it's not an absolute certainty. The next tube we'll take a look at is a 6BE6. If we take a look in the book under that one, we can see that none of the pins need to be eliminated. And we're going to go to a 6-volt filament, load of D, the setup of position 1, and socket 4. Okay, so none of the pins need to be locked out. We can just pull the reset switch to bring all those pins up. Go to a 6-volt filament and the D on the load, and setup number 1, and we insert ourselves into socket 4. So let's start by doing the shorts test We'll go into the shorts position here, and again watch our little light as we rotate around to see if we have any shorts in the tube, and I don't see any here right now, so that's a good thing. Let's go back to 1 and take a look at the emissions. Emissions actually look pretty good, so that's a good thing here. We could run the life test here. I pull that life test switch over. I don't see the emissions dropping very much, so I think we're okay on that. Now let's go to grid leakage. We'll take a look at the grid leakage test here, and that looks pretty good as well. So this would indicate that, hey, this tube is probably pretty good. Now again, I mentioned that some tubes, the grid leakage can start to increase as the temperature comes up. Now I've left this thing on the grid leakage position, and look at what's happening with the meter. So this is one of those things that if you were tested this tube a little bit too quickly, you might have missed the fact that this leakage is starting to come up now here. Now we've quickly gone out of the good range into the questionable range, and now we're in the bad range. So this tube, if you just spent a minute or two testing it, you might have not seen that the grid leakage actually gets bad when the tube fully heats up. So this is actually a bad tube and probably would not work very well in most circuits. Now sometimes when you look up the tubes, you might find, like this 6BH11, that there's actually multiple lines for setup. And what that means is that particular tube has got multiple sections. This one happens to be a dual triode pentode tube. So each setup condition here is to test each section of the tube. So you essentially have to test the tube 3 times with those 3 switch configurations. Now one thing that I didn't mention is this guy right here. This is actually a plate cap. For a lot of tubes like this 6146, the plate connection is actually made on the top and not through one of the pins. So after you stick the tube in the socket, you need to attach the plate cap to that as well before you begin testing. I hope you enjoyed this vintage tech video about this Sencor TC162 tube tester, a really nice solid state unit from the early 1970s to help give you an idea of whether some of the tubes you're looking at are any good or not. Again, no tube tester can tell you whether the tube is actually good enough to work in a particular application because it doesn't test it under those same conditions, but a bad indicator is usually going to be an indicator that the tube is not going to work well. So it is essentially one screening method that you can use for tubes in your tube base gear. Thanks again for watching. If you like what you see, give the video a thumbs up, and if you haven't subscribed to the channel already, please do so. And thanks again as always for watching. I look forward to your comments. Bye-bye. Probably the most common bipolar transistor amplifier is the common emitter amplifier operating in Class A. So today's video, we're going to talk about some design tips and shortcuts for Class A common emitter amps. When designing an amplifier, you usually have some goals and constraints. The most common, of course, would be how much gain do you want the amplifier to produce? That will certainly enter into the design process, but other things will as well. In terms of what kind of input impedance do you need to have? What kind of output impedance do you need to have? Or what kind of load are you going to drive? How much power supply voltage do you have available to you? And how much power dissipation, do you want this circuit to draw? All of these things will have an impact on how you do your design. Now, before I get started here, I also want to mention that there's a couple of related videos here that might be helpful for you along with this video. Number 185 that talks about transistor bias circuits and dependence on current gain or beta of the transistor and how to minimize that dependence. Really helpful video here. We'll talk about the implications of that next. Number 113 and 14 talk a little bit about the transistor bias point and class of operation. As I mentioned, we're going to be talking about a Class A amplifier here today. And also the common emitter, common base, and common collector amplifier just configurations. Again, we're talking about the common emitter one today. And then video number 67 that also goes through some common emitter amp gain and frequency response calculations. They might be good follow-ups, and I'll put links to each of these videos down in the video description below. I've got a little common emitter amplifier built up on my breadboard here. Let's take a look at the test circuit we'll be using to look at both the DC bias conditions as well as how to configure the gain. So here's our common emitter amplifier. A couple of bias resistors, 33K and 3.3K, emitter resistor of 1.2. The collector resistor I'm going to vary with a couple of experiments, so we'll leave that one just labeled R3 for now. a 47 microfarad bypass cap for the emitter that we'll put in optionally later on for some of the experiments, and then I'm AC coupling in through a 2.2 microfarad cap. Now, to generate the signal when we do some of the gain calculations, I'm using a sine wave function generator running at 50 millivolts peak to peak with at a 10 kilohertz frequency. I've got that running out to a BNCT located right at scope channel 2 with a high impedance termination. We can see that right here. And then coming out of there, I'm going to go into a 10x attenuator or a 20 dB attenuator, and that's located right here. That's followed up with a 50 ohm terminator. The 50 ohm terminator is going to do two things. It properly terminates the line, which at this frequency we don't really care about, but what it also does is ensures that the 10x attenuator sees the load it's intended to see, so it really is a 10x attenuator. And then I just follow that with a little BNC to alligator clip adapter to bring the signal into my test circuit. Now you might ask, why am I doing this 10x attenuator? Well, I want to drive this signal, drive this amplifier with a very low level signal, in this case just 5 millivolts peak to peak. Now if I probe that directly with the scope, the trace on the scope would be pretty noisy because you get 5 millivolts peak to peak. You want to probably set the scope to 1 or 2 millivolts per division, and things get just pretty noisy there. So what I'm doing is I'm going to drive that signal into the scope at a higher level, and then just adjust the attenuation factor on the scope to 0.1x, which is 1 over that. So the scope will still read the voltage that's being applied, but the actual voltage that's actually going in the scope is 10 times higher. Just a little bit of a trick to be able to get a nice clean low-level signal or representation of a low-level signal that we're going to apply to the input. So that's going into channel 2. Channel 1 I'm probing with a 10x scope probe at the collector, at our output of the amplifier. So with these two, we'll be able to look at the input and output of the amplifier and calculate its gain. Now the first consideration is always the DC bias condition for the amplifier. For a bipolar transistor, it's always a good idea to design the bias circuit so that you have a few hundred millivolts across a degeneration or emitter resistor. And the reason for that is it gives you good bias stability versus beta variation. As you know, current gain or beta of a transistor is pretty unpredictable. Or a given transistor that can vary pretty wildly. So by designing the bias circuit to be independent of beta, you'll get a very consistent operation of the amplifier for different transistors that you might swap in, or if you want to replicate the amplifier again. Again, video number 185 covers that in good detail. Now you'll get that couple of hundred millivolts across the emitter by properly setting up the base voltage, and that's typically done with a resistor divider at the input. Now if we're going to have a few hundred millivolts here, we're going to have 6 or 7 tenths of a volt above that sitting at the base. So typically 1 to 1.5 volts or so sitting at the base will give you a good amount of degeneration voltage and good bias stability for the amplifier. Now the values of the resistors will often be driven by the currents that we need to drive in the bias string and through the collector. And oftentimes that's going to be driven by one or two requirements. Usually it's driven by what does the output impedance have to be. For low power circuits, this might be a relatively large value resistor. That means we're going to be running some lighter currents through here, so all the resistors will be high. Or if we're driving a low impedance load, the collector resistor might have to be low as well, so that we don't get too much gain reduction when we hook up to the next stage. So your application is really going to drive what this approximate value is going to be for your collector resistor. So once you've got that kind of narrowed down a little bit, the next thing to decide is what bias voltage we want to sit at the collector. Now if you want to design the amplifier to have a large output swing, you need to give the amplifier enough headroom to drive the positive and negative peaks of your signal. Therefore, this bias voltage should be sitting somewhere midway between VCC and either the base or emitter voltage. If you do a midway between the base and emitter voltage, that'll give you the maximum swing, but just keep in mind, if you drive that collector voltage too far down towards the emitter, you'll get close to saturation and you're also going to increase distortion. So a good idea is maybe pick an operating point or quiescent point that's midway between VCC and the base voltage. That'll give you a lot of room for swing and start to get away from that area where you might get some additional distortion or run the risk of saturating the transistor. Now, an interesting little trick I'm going to show you later is that oftentimes the voltage you drop across this resistor is going to directly determine how much gain you have. But stay tuned for that. That's kind of a cool little trick. So once we know our approximate value for R3 and where we want it biased, that kind of tells us what our collector current is going to be. If we know what our collector current is going to be, we know that the emitter current is virtually the same as that. So if we want a couple of hundred millivolts across this, we can then use Ohm's law to calculate about what that resistor value needs to be. So now with the collector resistor and the emitter resistor calculated, what do we do about our resistor bias string? Now it's a good idea to make this bias string also independent of beta. So what that means is we want the base current that's going to be coming down through R1 and into the base, we want that base current to be pretty small with respect to the current flowing through the string. And a good rule of thumb is to make the current flowing through the string at least 10 times greater than the base current. Now a couple of little tricks here as well. Since the beta of many bipolar transistors is on the order of about 100, we just know that we want this current here to be about 1/10 of the current going in the collector. That will ensure that we've got at least 10 times the base current flowing through the string, and therefore any variations in base current is not going to make a big change in the bias voltage here. Of course, you could make the current in this bias string much larger than the base current, but then you got to start thinking about how much power do I want to burn just in setting up this bias. If the circuit's designed to go into, say, a low power application like a battery powered application, you might not want to burn a lot of extra current going through these resistors unnecessarily. So usually the choice of these resistors and the choice of this current is a trade-off between bias stability and power dissipation in the amplifier. Let's take a look at how I've got our test circuit biased. So if we take a look across the 1.2K emitter resistor, I've got about 509 millivolts there. That puts the base at about 1.09 volts, and puts the collector, in this case, at 9.93 volts. I've got a 4.7 k ohm resistor in the collector here. We're going to change that out for a different value later on. So this bias might seem a little high based on the recommendation I made earlier, but I'm not necessarily looking for maximum signal swing here. We're just going to do some experiments to talk about gain in a little bit. There's two configurations we'll talk about for gain calculations. One with emitter degeneration, where the emitter resistor does not have a bypass cap, and one where the emitter is bypassed. And now the difference is that the emitter bypass calculation is going to give you a higher gain, but also generally higher distortion. Without the bypass capacitor, we're generally talking about lower gain applications, but very precisely controlled gain and some pretty low distortion as well. Now, as long as we have several hundred millivolts across the emitter resistor, the voltage gain of this configuration is actually quite simply given by minus RC over RE, that resistor value divided by that resistor value. So very easily determine the gain just by a ratio of two resistors. This is because with that couple hundred millivolts here, the contribution of the incremental emitter resistance, or RE, or 1 over the transconductance, is negligible. So it kind of drops out of the equation. And I say this is approximate because there will be some small error, but generally well within just a couple of percent. Now in our case, the collector resistor is 4.7 k ohms, and our emitter resistor is 1.2 k ohms. So take that ratio, it says our gain should be about 3.9. So let's take a look and see what that is. Now on the scope I've got two different waveforms. The blue waveform is actually channel 2, and that's on a 1 millivolt per division scale. So that shows us our 5 millivolt peak-to-peak input signal. The yellow trace is channel 1, that's our output at the collector, and that's on a 10 millivolt per division scale. Now I'm actually using the scope math capability to actually calculate the gain for me to make my life a little bit easier. Let's take a look at that. The scope is measuring the amplitude of the output voltage, about 20 millivolts peak to peak, and the input voltage just a little over 5 millivolts peak to peak. So I could just do the math on that, but why not? Let me have the scope do it for me. So I've set up a math function to have the amplitude of the output divided by the amplitude of the input. That gives me a math trace, this red trace, which is essentially equal to the gain. So I just set up one more measurement to measure the mean of that math. And we can see that's showing me that same 3.9 volts per volt that we calculated that this gain ought to be. So now let's swap out the 4.7K resistor for a 20K ohm resistor. And if we do take a look at that and calculate what that gain ought to be, so if we have 20K divided by 1.2, that gives us a gain of about 16.7. And we take a look at the scope, and this is showing our gain of about 15.2. Certainly well within just a few percent of the 16.7 that we calculated. And again, that was using nominal values for these resistors, and there's some tolerance there we didn't take into account. So that's certainly close enough. Therefore, we can see that for the case of emitter degeneration, the voltage gain is pretty closely predicted by simply the resistor ratio of the collector resistor to the emitter resistor, minus RC over RE. As I mentioned, this configuration is really good for relatively low gain applications, because it's tough to get a lot of gain when your gain is controlled by this resistor ratio, and we've got already a couple of hundred millivolts tied up across that resistor. So for high gain applications, you typically will bypass the emitter resistor. And this will give us higher gain, a little more distortion, but can get some pretty reasonable gain out of this circuit. Now what's really cool is that the gain calculation, while it can be complex, can boil down to a very simple approximation here, where the voltage gain is simply equal to the voltage across the collector resistor divided by this parameter called VT, or thermal voltage. All you have to remember is that VT is 26 millivolts at room temperature for silicon bipolar transistors. So it doesn't vary too much with temperature because it's proportional to absolute temperature. So even around normal operating conditions, 26 millivolts is a good approximation. And this will predict the gain to within about 10% for small signals, where I would define small signals with the input voltage or the variation of base emitter about 10 millivolts or so. And that's the condition that we're playing with here. So let's actually go verify that. Pretty cool simplification. All right, so I put my 4.7K collector resistor back in here again. I'm going to shut off the signal generator and measure the voltage directly across that collector resistor. So we're seeing about 2.051 volts. So let's calculate out what that gain should be. So we have 2.051, and we'll divide that by 0.026 or 26 millivolts, and that gives us a gain of about 78.8. Let's go see what the scope tells us. And we'll turn the signal generator back on, and let's insert the bypass capacitor around the emitter resistor. And readjust the scope because we got much higher gain here now. And let's go zoom in and see what the scope is telling us for the gain calculation. We said the gain was going to be about 78, and we're seeing about 75. And again, this is an approximation, going to get you to within about 10%, and we're well within 10% for that calculation. Let's do the same thing for a 20K load resistor. So we'll swap out the 4.7 for 20K. And we can see that my signal's gotten a lot larger here again. Now let's go first and measure what that voltage drop is across that 20K resistor. And it looks like we're sitting at about 8.25 volts. Let's calculate out what that gain ought to be. So if we say 8.25 divided by 26 millivolts, and we should see a gain of about 317. And let's see what the scope is telling us here. And there we go. So 295 or so. So that's just about 10% low, which is again about what we expect. We're only going to be within about 10% with that approximation. But that is a pretty cool approximation for gain and a very simple calculation. Just measure or figure out the voltage across my collector resistor divided by 26 millivolts, and that gives you the gain. Pretty cool. So where does this approximation come from? Well, let's start with kind of the Ebers-Moll approximate gain equation for small signal common emitter amplifiers, where the voltage gain is given by minus the transconductance times the collector resistance. The transconductance GM is simply equal to the collector current divided by VT, our friend the thermal voltage, 26 millivolts. Now also we've got this parameter called RE, the incremental emitter resistance. Incremental emitter resistance is just 1 over GM, or VT divided by IC. And if we take a look at it, then This gain equation is basically the same thing as saying AV is equal to RC over RE. Gee, that looks awful familiar, right? That's the same gain equation we used right here. So really it's the same gain equation, just represented differently. We talk about it in terms of GM. But now if we actually just do some substitution of things here and say, well, if the gain was GM times RC, GM is IC divided by VT. So if we kind of expand this out and say 1 over VT times the product of IC times RC, we can then say that IC times RC is just the voltage drop across the collector resistor. So we just put that here, and voila, AV is equal to, the minus sign belongs in front of all of these things here, of course. Okay, but the AV is equal to the voltage across the collector resistor divided by VT. Just a really cool simplification. So I hope this video has given you a little bit of insight into some of the shortcuts of gain calculation and some of the tips and tricks in terms of setting up the bias conditions for a common emitter Class A amplifier. If you liked the video, please give me a thumbs up. If you have any comments or questions, please list them down below. I'll try to get to them. And thanks again for watching. We'll see you next time.
Whiskey 6 Lima calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Hi, I'm Jim, W6LG for Ham Radio Basics. I was on the air and a guy called me. The guy's name was Tim. And Tim said he had a new ICOM 7610 and could I give him a few minutes to run a couple of quick checks on it. And we did. The call sign of the station I was working was M0ODZ. Didn't exactly ring a bell, but I had heard it before and didn't have QRZ running, so we chatted for a while, and it turned out the guy I was talking to was Tim Duffy, K3LR. Tim's a heck of a nice guy, and the 7610 from ICOM sounded terrific. There really was nothing that I could criticize about the way it sounded. We talked for quite a while. As it turned out, they recorded the contact, the folks at DX Engineering. So I'd like to share with you a few minutes of that video of Tim Duffy and the new 7610. It's a pretty amazing transceiver, and apparently they're a little hard to get right now. Anyway, let's watch a few minutes of the video recorded at DX Engineering.
6LG over to N8DXE. And
W6LG from N8DXE. We actually, this is the DX Engineering Employees Club station, and so we just got our first shipment of these radios yesterday, and we were so busy sending them out all over the country that we didn't get a chance to light one up here until this morning. So that's this is part of that first big shipment we got here, Jim. Go ahead.
yeah, good. Well, if it's anything like the 7300 gun, it's ubiquitous, I guess. If you recall the 706 Mark II, all the variations of that, they must have sold 100,000 of those things. I think the 7300 is probably getting there too, literally all over the world. That sounds good. I don't hear any distortion, nothing in the background. Audio quality is excellent. So I can touch the screen on my K3s, but it doesn't do anything. So what? So I'm at a loss. Go ahead.
Well, the K3 is a very nice radio, and of course made in the great state of California. But this is really something else. You never know what to expect. You hear all the marketing hype, and this thing just looks like it's living up to all that, Jim. And just tuning around here for a few minutes on 20 meters and getting used to the filtering. And but so many things are adjustable just by hitting the screen on how you switch between VFOs and being able to blow up the spectrum area so you can do a closer analysis. Just lots of good things. So really looking forward to it, you know, the 7300, you're right, it was a game changer because it too is an SDR, just like the 7610, and guys have been clamoring for this. So Christmas came a little early here in Talmadge, Ohio. W6LG from N8DXE.
N8DXE W6LG. Your transmit bandwidth is at more than 3. Sounds like about 4. Go ahead.
Huh. That's interesting because it shows 2.9 here, but it may have something to do with some of the settings that are just out of the box. So we will check that, Jim.
Yeah, well, I'm not complaining. I've just turned on the pan adapter to take a look. It sounds really good. It really does. What mic could be paired with that?
This is the Heil, I think it's the 781. So it's one of the fancy Heils.
That sounds excellent. Good. I love this new stuff. When you and I started at this, we never dreamed we'd have boxes in front of us to do the kinds of things the 7300 does, let alone the 7610.
Well, you're absolutely right about that, Jim. You know, being a high school kid and just lusting after a Drake C line or the smoothness of Collins S line, you know, that's we didn't think it would ever get any better than that, right?
You know, I was licensed in 63 in the late 60s. Well, in high school, 67, 66, I guess. I worked in a radio store selling ham radio equipment in Burbank, California, and did love the Drake stuff, which is why I bought a bunch of it later on in life. Back to how you sound. It sounds great. You are peaking 40 over. I assume there's a Yagi out in the parking lot. You got it pointed towards California.
Yep, sure do, Jim. Yeah, this is a Skyhawk that we make here at DX Engineering, so it is headed your way. And we have a beautiful Roan 65 tower with a stack of Yagis on it so that customers can get on the air, and employees, and we can have fun on lunch breaks and after work. And so it's a first-class station here. And of course, DX Engineering is inside Summit Racing Equipment, so we got the best of both hobbies. W6LG from N8DXE.
N8DXE W6LG. Yeah, sounds like a great place to work. Are you hiring? Just kidding. But what a wonderful thing that is. Are you running an amplifier? Because literally you're 30, 40, sometimes 50 over.
Yeah, we've got, this is an ACOM 2000, but we've got it ratcheted back, so it's not really going full bang at you. But yeah, this particular RF chain had the ACOM 2000 in there.
Yeah, one of the best amplifiers in the world. Built like a brick, you know what? Should last forever. And it sure sounds like it. Boy, that is as clean as a whistle. I'm looking at the scope as best I can, and everything looks really good. Well, considering the ACOM 2000 following it. And the Skyhawk, I got a buddy in the Crimea. Used to be UK5 MAF, DY5LK, R7 Kilo Zulu is the new call. Stan. He's got a Skyhawk, and it's a marvelous antenna. It just works and works and works, and I've, on sometimes a dead band here on the West Coast, I've been able to meet him on Skype and then meet him on the air a few times. I'm primarily a DXer, not much of a regular, as you might be able to tell. And I've got some pictures on QRCode.com. Do you have a computer handy?
Yeah, we have a computer handy, so we'll take a look at your QRZ page and see what you're all about, Jim.
N8DXE W6LG.
Okay, so that was my conversation with Tim Duffy at DX Engineering and the new beautiful 7610, which sounded really good and looks even better than it sounds. At the end of this, I've got something else coming up, and I'll stick around to the end because it's worth hearing. A couple of words about how lucky we are to have companies like ICOM, Kenwood, Yaesu, Elecraft, Flex that provide us with incredible equipment and a whole bunch of choices of fun things to use for a relatively small market, and for them to pioneer radios like the 7610, the Ecom 7300, for example, the one I use, the Elecraft K3S. For us to have that available is really amazing. The other side of that is dealers, and DX Engineering is an interesting company because they really have set the standard for customer service. And everybody I know, and I have not ordered from them, I don't think I've ordered anything. I hardly know them. I haven't been there. I've been to a lot of other stores when I was selling something I was manufacturing. But I think if you noticed how Tim described the station, that it was available to employees to use, and it sounded like he was encouraging them to use it during lunch and probably get familiar with the equipment. Brilliant. Roan 65 out in the backyard, the really neat antenna at the top of the tower, and an ACOM 2000 to push out a really big signal. What's the point? We're lucky that we have manufacturers like we do, and I think I've left a couple off, but you know what I mean. Then to have a dealer that really puts customer service as number one. At the end of that contact, and here's one of the most remarkable things that's ever happened to me, ever, on the air. Finished with Tim, or was finishing with Tim, and a W9 called. And he called me a couple times, and we kind of got lost in the noise, and then we made contact. At first I thought it was my neighbor W9GR, but this guy was really weak, so I had a feeling he was somewhere other than my backyard. And it was Harry W9BR, and he asked if I could participate in a very special situation. And that was this group in Illinois had set up a station to grant a dying man's last wish, and asked me if I could participate in that and be his first contact. In the next episode, we'll talk a little bit more about that and what happened that day. So, started off like any other day. Then I talked to DX Engineering, which was a lot of fun with the new 7610. And then to put things into perspective, I had the pleasure of meeting WA2EQJ. This group is so good that they sent me a certificate. And I think this was, everybody who made contact, I think, or participated probably got this. An amazing group of guys and women who did this. Anyway, next episode we'll talk about it and what little I know about it. But this is remarkable amateur radio. So we have remarkable manufacturers, dealers, guys like this. Amazing. All right. If you've enjoyed this video, please subscribe. And I've got a bunch of things in the works. Upcoming ones, for example, on what control in the front of your transceiver are you likely never using? You'll be surprised. Anyway, I'm Jim, W6LG for Ham Radio Basics. Thanks for joining me. See you the next time, and probably never have another day like December the 5th.
Whiskey 6 Lima Golf calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
So here's what happened last week, and it's a once-in-a-lifetime thing. W9BR called me, and he actually called me a couple of times, and he wasn't real strong, but I heard him. And at first I thought it was my neighbor, W9GR, Dave Hirschberger. It turned out it was Harry, W9BR. And Harry asked me if I could help fulfill a dying man's last wish, and that was to get on HF and to make some contacts. So of course I said, yeah. And when and where do you want me? He said, right now, and let's go to 14235. That's on 20 meters. So we met there. The most amazing group of hams that I have come across ever were there at a VA facility in Chicago, Illinois. To help out, I have to look, gentleman whose name is John, and John Nugent, WA2EQJ. John's in the a facility in Chicago, and they set up a portable transceiver like an ICOM 706 or ICOM 7000, an antenna outside, microphones, power supplies, tables, chairs, had a big crowd, and got John on the air. And I was his first contact. And we talked for several minutes, and I got other guys that could hear him to say hello. The hams in Chicago that did this is the, let's see if I get this right here. Let me look on this side. The Lake County Races Aries group in Libertyville, Illinois. And they are so good at what they did. It's truly amazing. For example, I got this in the mail yesterday, and it's going to go on my wall. It's a certificate of appreciation for meeting John on the air, and certainly wasn't necessary. I was more than happy to do it. John did pretty good. He's on oxygen and needed some help, but his family was there to help him. And we had, I think, about 10 contacts come through and say hello. So these guys fulfilled a dying man's wish, got him on HF. And again, his name is, the gentleman's name is John Nugent, Nugent, WA2EQJ. It was a pleasure to be a part of it, and hopefully he got some pleasure out of it. Anyway, day started off with by accident meeting Tim Duffy, which was a real pleasure, nice guy, and then finished with this from the Lake County Races Aries group, setting up a station for John Nugent. In doing that, it was not only to help out John Nugent, but it generated a lot of publicity, which is good for amateur radio. It was carried in a lot of newspapers. My name appears in those articles as Jim in Grass Valley, and since I knew I was playing to an audience, I did my best to explain ham radio to those that were listening. And for example, I discussed 73 and where it came from and what it meant, because I knew at the end I'd be saying 73 to John. Anyway, won't forget it. Great group of guys. What I'll try to do at the end of this video is post a list as best I can. I'll add to that because it was a big group of guys. And I think one or two ladies also helped out. Maybe a daughter or a granddaughter were part of it. Anyway, if you ever have the opportunity to help someone out like this, I encourage you to do it. It's an amazing experience. Anyway, what a day. December the 5th, 2017 starts off with kind of a neat thing. We're checking out a new ICOM 7610 with DX Engineering, and during that, or at the end of that, I get involved in a guy's last wish. So that's the story that goes with what happened on December the 5th. If you've enjoyed this video, Please subscribe if you are aware of this or have something to contribute to it, or if you know these guys, please thank them for what they did. What can't even describe how impressed I am with Lake County. Anyway, for now, 73. Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. That's Orrin, K9KEJ. Orrin is a world-class fisherman. He's been inducted into a Hall of Fame. He's also worked and confirmed over 320 countries. Orrin will tell you that DXing is like fishing. You need to know when and where. And in 10 seconds, I'll give you some tips that will help you figure out when and where you can fish for DX.
Whiskey 6 Lima calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Okay, local time's a little bit after 6 o'clock. Zulu time, that would be 1400 UTC. Gone to DX Heat. I'm going to select phone only. DX Heat is a DX cluster, and I'm selecting also 20 meters only, since that's the band that I specialize in. You can select all or other bands, whatever you want to do. You can do it. It's a very flexible website. So, and I'm going to pick out Europe only. I just want to see the posts that are of Europeans, and you can also select who's put up the post: Europe, North America, South America, Asia, Africa. We'll leave it wide open for now and see what's happening. If you are not sure what country is being displayed as DX, you can click on the flag and it will tell you. Now here's NX7TT. He's posting DX. It's a bit early. Not much from North America, so wherever that guy is, he's hearing stuff. So let's just select North America, see what comes up. Okay. Go back up to the top. Again, there's NX7TT, K4 a little bit, well, yeah, a little before that, an hour and a half, hour and 3/4 before that. And that's really it. There's OH0Z, Alien Island. That could be Marty, OH2BH and friends. They're often there. So let's go see what propagation looks like. I'm going to go to eham.net, click on propagation, because I want to look at the solar flux, the A and K index. And I look at those every day. The solar flux is 72, the A is 4, and the K is 0. Says G level, moderate geomagnetic storm. Likely. That may be what's happening now, because there's not a lot of DX being posted. So again, I look at this every day, several times a day, so you can't just look at the cluster and see what's there. You need several resources. So one for sure is a cluster, and there are several to choose from. Let's take a look and see where OH0Z has been posted and see what bands they've been on. It's sort of a de-expedition. So we have Alien Island, Europe Zone 15, sunrise, sunset. Looks like they're being heard pretty much in all the bands. So there's 20, and also it gives you spots by year. So that's interesting if it's one that's on frequently, as this one is. And here's a distribution of what continents, and you can see North America is being heard pretty well. And here's a listing of spots for OH0Z by different guys. Anyway, so this is one of many resources within DX Heat for doing research. Now here's DX spots that are submitted by OH0Z, and who they have spotted. And again, I think that's Marty Lane OH2BH. So I'll
put in his call. I'm curious to see where he is since he's posting DX and really nobody else is. Oh, here we go. Daytona Beach. Oh, on the air via Maine or Georgia. Well, if he's on the air from Maine remote, he's got a big advantage over me. You can almost see Europe from there, so that explains it, especially if he's got a lot of big antennas. So he's got a super setup where he can operate remotely via Maine or Georgia, which is a neat thing.
Well, there are some tips on fishing for DX, and there are lots of others. None of these things are absolute. They're guides. They'll help you out. They're going to show you what band and what time of day. I think the most important thing that you can do in using those tools is listen. And listen and listen and listen. And when you see stuff being posted, go listen. It's really important to figure out how things work and what times the bands are open and where you might be able to talk to. And if you have a guy like K9KEJ in your neighborhood who's actively on the air, ask him for some help. You might get some really good tips. And as I said, there's a lot more than the ones that I showed you, but those are a few that I use pretty much every day. Thanks for watching. I'm Jim, W6LG for Ham Radio Basics. Go fish for some DX.
All right, it's a little after 6, so let's go to dxheat.com. We'll click on the DX cluster. And I've got it set up for 20 meters. The way to do that is, well, first of all, there's the modes. So I've got, right now, phone only. And I picked 20 meters only. If I wanted all bands, I could click all, and it'll show DX on all those bands. But I'm just interested in 20 meters, so let's do 20. And the next thing to pick down here is what DX are you looking for. Right now I'm not looking for North America, so I'm going to click none, and I want Europe. Let's say Europe only. So, and further down is the source of the DX, and I'm going to leave that for all just for now. Understanding that, well, here's a guy in Canary Islands posting a guy in Hungary who's portable. So let's see what's here. Well, I don't see stuff being posted by guys in the US, so let's narrow this down just a bit. So let's go down here and we'll say North America only. My local time is 6 a.m. Zulu's 8 hours past that, so I guess that's NX7TT. Station he posted it is in Slovenia. If you don't know what country this is, you click on the flag. Here's that could be Marty OH2BH Alan Island, which is pretty rare. So let's see what's going on. Something must be with the propagation. So let's go to eham.net. And on the left-hand side, I'm going to click on propagation. And here we go. SolarFlux 72 estimated A index of 4. K was 0. That's actually pretty good. Space weather for the next 24 hours predicted to be moderate. Geomagnetic storms reaching G2 are likely, so that may explain it. Conditions may be terrible. Oh, we've looked at the cluster, at least one of them. There's others. Going back to this one, it has a lot of neat features. Let's see where let's say this is a DXpedition. We want to see where they are. So let's type in OHZ
M0ODZ. Okay, Alien Island. Europe. Spots by band. 20 meters have been pretty good. And let's see here. By continent, Europe, North America, pretty well heard. Spots, WhisperNet. Here we go. All right, so let's well, this is a very different story than what we're seeing on the cluster. Make sure I got the right time here. Got to update this. Okay, excellent. This is telling us a lot. Let's scroll down the page a bit. And let's now what this tells me is very different from what the DX cluster is saying. Guys on the East Coast, here's the gray line. And oftentimes that's a good path. So that line between, in this case, the nighttime, daytime, right in this path, it's called the gray line. And you can see that the guys that are beaconing, thank you for all of that, on the East Coast are being heard in droves on in Europe, and that's Canary Island down here. And even into, don't know if those lines connect. I don't think they're being heard into India, but let's zoom in just a bit more. And you can see the number of guys who are generous enough to provide a beacon signal. And there's tons of them. So let's go to California. And this just sort of proves that the gray line really does work. Of the few guys in California, they're not being heard, or on the West Coast, they're not being heard in Europe yet. Well, there are some tips on fishing for DX, and there are lots of others. None of these things are absolute. They're guides. They'll help you out. They're going to show you what band and what time of day. I think the most important thing that you can do in using those tools is listen. And listen and listen and listen. And when you see stuff being posted, go listen. It's really important to figure out how things work and what times the bands are open and where you might be able to talk to. And if you have a guy like K9KEJ in your neighborhood who's actively on the air, ask him for some help. You might get some really good tips. And as I said, there's a lot more than the ones that I showed you, but those are a few that I use pretty much every day. Thanks for watching. I'm Jim, W6LG for Ham Radio Basics. Go fish for some DX. Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. That's Oren, K9KEJ. Oren is a world-class fisherman. He's been inducted into a Hall of Fame. He's also worked and confirmed over 320 countries. Oren will tell you that DXing is like fishing. You need to know when and where. And in 10 seconds, I'll give you some tips that will help you figure out when and where you can fish for DX.
Whiskey 6 Lima Golf calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Okay, local time's a little bit after 6 o'clock. Zulu time, that would be 1400 UTC.
we'll click on the DX cluster. And I've got it set up for 20 meters. The way to do that is, well, first of all, there's the modes. So I've got, right now, phone only. And I picked 20 meters only. If I wanted all bands, I could click all, and it'll show DX on all those bands. But I'm just interested in 20 meters, so let's do 20. And the next thing to pick down here is what DX are you looking for. Right now I'm not looking for North America, so I'm going to click none, and I want Europe. Let's say Europe only. So, and further down is the source of the DX, and I'm going to leave that for all just for now. Understanding that, well, here's a guy in Canary Islands posting a guy in Hungary who's portable. So let's see what's here. Well, I don't see stuff being posted by guys in the US, so let's narrow this down just a bit. So let's go down here and we'll say North America only. My local time is 6 a.m. Zulu's 8 hours past that, so I guess that's NX7TT. The station he posted it is in Slovenia. If you don't know what country this is, you click on the flag. Here's that could be Marty OH2BH Alan Island, which is pretty rare. So let's see what's going on. Something must be with the propagation. So let's go to eham.net. And on the left hand side I'm going to click on propagation. And here we go. SolarFlux 72 estimated A index of 4. K was 0. That's actually pretty good. Space weather for the next 24 hours predicted to be moderate. Geomagnetic storms reaching G2 are likely, so that may explain it. Conditions may be terrible. Oh, we've looked at the cluster, at least one of them. There's others. Going back to this one, it has a lot of neat features. Let's see where let's say this is a DXpedition. We want to see where they are. So let's type in M0ODZ. Okay, Alien Island, Europe, spots by band. 20 meters have been pretty good. And let's see here. By continent, Europe, North America, pretty well heard. Spots, WhisperNet. Here we go. All right, so let's well, this is a very different story than what we're seeing on the cluster. Make sure I got the right time here. Got to update this. Okay, excellent. This is telling us a lot. Let's scroll down the page a bit. And let's now what this tells me is very different from what the DX cluster is saying. Guys on the East Coast, here's the gray line. And oftentimes that's a good path. So that line between, in this case, the nighttime, daytime, right in this path, it's called the gray line. And you can see that the guys that are beaconing, thank you for all of that, on the East Coast are being heard in droves on in Europe, and that's Canary Island down here. And even into, don't know if those lines connect. I don't think they're being heard into India, but let's zoom in just a bit more. And you can see the number of guys who are generous enough to provide a beacon signal. And there's tons of them. So let's go to California. And this just sort of proves that the gray line really does work. Of the few guys in California, they're not being heard, or on the West Coast, they're not being heard in Europe yet.
Well, there are some tips on fishing for DX, and there are lots of others. None of these things are absolute. They're guides. They'll help you out. They're going to show you what band and what time of day. I think the most important thing that you can do in using those tools is listen. And listen and listen and listen. And when you see stuff being posted, go listen. It's really important to figure out how things work and what times the bands are open and where you might be able to talk to. And if you have a guy like K9KEJ in your neighborhood who's actively on the air, ask him for some help. You might get some really good tips. And as I said, there's a lot more than the ones that I showed you, but those are a few that I use pretty much every day. Thanks for watching. I'm Jim, W6LG for Ham Radio Basics. Go fish for some DX. Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. I'm going to solder on a coax connector, and I'm probably going to crimp another one to show you the difference between soldering and crimping. And I'm going to do the soldering in a way that you may not have seen before. Oh, stand by. Back in 10 seconds.
Whiskey 6 Lima calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room. A friend of mine puts on coax connectors in kind of a different way, and I'm going to attempt to do it the way he does it. And what I'm doing right now is taking the jacket off of some RG213. The jacket is the plastic coating on the outside. Pull that out. And this is, again, RG213. And let me pull this jacket off. What my friend does is to use a solder pot. And it sounded kind of crazy, and here's why. The solder pot's at about 600 degrees. He dips the cable into it. The solder pot's 600 degrees. The dielectric has a melting temperature of around a couple hundred, well, yeah, a couple hundred degrees Fahrenheit, maybe a little bit higher. So what I thought I would do is give it a try, and we're going to do it with the camera running and see what happens. So I hope it doesn't splash up and ruin this camera. I'm going to do a different cut on the end of this coax. I want to get a clean cut. So the other thing I'm going to do, and again, this is a test to see how it works, I'm going to apply flux to the shield. And the reason for that is, in looking at it, it looks a bit tarnished and not entirely bright and shiny. The reason for dipping it is to tin the braid, so that when you screw on, and basically that's what you're doing, when you screw on the coax connector, it's off. And here's my coax connector, which is the top flight CNC machine connector. And it's got a gold-plated pin, Teflon. It is silver-plated. It could be nickel, but silver is a little bit easier to solder. You can see, I can get it back a little further.
there are 4 holes typically in the coax connector to pass solder through to the shield, which is pretty hard to do. One thing that's often forgotten is to put on the barrel, so I'm going to shove that on there. And the reason why this is threaded is not to accept the shield, but to accept an adapter, like a UG176. So, for the camera. Okay, I've put on a good coating of flux. And here goes nothing. Again, the melting temperature of the dielectric is a couple of hundred degrees. The melting temperature of the solder is above, it's like 570 degrees. And I'm going to see what happens. And then, again, this is, move that out of the way. This is how my friend does it. So let's see what happens. I'm going to do this with, here we go. Before I do that, I'm going to try to pick up some of the contaminants and stuff so it's nice and shiny. Okay, there we go. Looks pretty clean. All right, here we go. All right, didn't go deep enough, but it may be enough. It looks like it melted the end of the dielectric, and I'm going to need to trim off some of that. So let's see what it looks like. Okay, here's what we have so far. Going to have to pull back on the shield just a bit. In trimming it the way I did, I sort of bent it inward. The dielectric did melt here. Okay, here's what's happening. The dielectric is now so hot it's almost fluid, liquid. The cable, the jacket is hot to the touch. I'd say it's well above 100 degrees. And the dielectric looks, it looks a bit iffy to me. And it's changed the dimension of the shield, mostly because I pressed on it kind of hard. And I don't know how else to cut it because the shield is so tough. It's not going to show on camera, but the dielectric has melted. It's still smoking just a bit. I'm not convinced this is a good way to go. So the other way to do it is the more traditional way, and that would be not to tin the wire, not to tin the wire, not to tin the shield. And looking at this coax connector from a commercial company, you can see that this one is cold, and in fact it's loose. That one's also cold. That one's about half cold. There's an easy way to do this, so let's talk about that. I can push solder through it and show you that I can solder it, but it's not going to be pretty when I get done, and it's not going to be very good either. So let's crimp on a connector, and doing that is tons easier. I'm pulling on I was pulling on the wrong end of this cable, and guess what? Look at this. Now again, this is a commercially made cable sold by a major ham radio dealer, and inadvertently I pulled on the coax connector, trying to pull it off, and you can see it never made a good connection to the shield, to the body of the shield. Never made a good connection to the body of the coax connector. Look at that. Look at that. Honestly, I didn't plan on doing that. That really makes my case that the way to do the coax connector is to crimp it. again, I was pulling on this thinking I was pulling on the one I had not soldered. And in doing that, and I discussed how the solder connections look cold, and pulled this darn thing right apart. Look at this. This is the shield. There's virtually no solder on there. So what do you think? Do you think you want to solder? Or do you think you want to learn how to crimp? Crimp tool, like the ones I was selling, I'll put some of those on eBay if you're interested. I'll tell you where they are. A good crimp tool is one that's heavy and it's laminated. Crimp dies there are different grades of crimp die, but most of them are pretty good. Crimp connectors, it's a whole different story. It needs to be a good crimp connector. All right, this is sort of an unplanned exit to a video on how to solder on a PL259. Complete fail because I destroyed the cable pulling on it. Well, let's see. Here's another look at this thing, because this was the other end of that cable. It was quite a bit longer than this. I cut it off to put on my own connectors because I didn't like these. But here's how it looked before I pulled on it. And you can see that one in particular is about 3/4 not shiny. And so what I was doing was, off camera, was like this, and I don't know if this one's going to go that way or not. I'm just not that strong. Well, son of a gun. Look at this. Hope the camera, this is still recording. Look at this. A commercially made cable. I'm not going to tell you who I got it from. I just pulled it apart. And again, I'm not that strong. I can explain that to you another time, but look at this. Okay. Do you really want to buy a commercially made cable where they've soldered on the coax connector? Let's end the video here. I don't know how many minutes I've got into it. That camera says 11 minutes. People who watch YouTube videos usually watch about 6. I mean, the coax is decent. It's, man, that's something. I'm stunned. So we'll leave it at that. I've got to rethink the next video, but this is not good. The only thing that made this work was the way the connector was installed, and that it has a bit of a thread, and it was threaded onto the shield. So that was the mechanical connection. It was not a solder connection at all. So it's garbage for sure. And that's name brand stuff, Midwestern manufacturer. The coax is RG213, not a foam dielectric. A foam dielectric is even harder to solder because it really does melt easily. All right, I've got to rethink this. Stay tuned for the next episode. I'm Jim, W6LG for Ham Radio Basics. I'll try not to break something in the next one. Thanks for watching. If you enjoyed this, please solder. If you've enjoyed this, boy, I'm really hung up on the soldering. If you've enjoyed this, please subscribe. If you have a comment, and I think this is going to generate a lot of comments, please put it below. This wasn't fake. This was purely by accident. And we'll do a crimp connector next. Man, not good. All All right, 73. I'm Jim, W6LG for Ham Radio Basics. Thanks for watching, and I got to go sit down. This is just more than I can handle. See you later. Bye. It's crap. What the...
The Smith chart is a graphical tool that is very useful to help solve a wide variety of RF and microwave complex impedance matching and transmission line problems. In this short basics video, we're going to take a quick look at how complex impedance is represented and illustrated on the Smith chart. The Smith chart is comprised of a series of concentric orthogonal circles that represent the real part and the reactive part of a complex impedance. Complex RF impedances are typically represented by a real part and a reactive part. On the Smith chart, the real part is represented by a series of concentric circles. The horizontal line through the center represents like a pure resistance with no reactive component at all, and the center of the chart represents the system impedance. Both Smith charts are printed in a normalized fashion, meaning that the center will show 1.0 instead of 50 ohms, which is a very typical RF system impedance, so that the chart can be used for other system impedances besides 50 ohms. But in our case, we'll just represent it as Z0, or the system impedance. In order to get back to actual impedance values, you would need to multiply the values obtained on the Smith chart by your particular system impedance. As you move to the right along the baseline axis, you go higher and higher in resistance until you get all the way out to the outer circle, and that represents an infinite impedance or an open circuit. Conversely, as you move to the left, you'll get lower and lower real components until you get to a short circuit. So a short circuit from an RF standpoint is represented at this location in the Smith chart, and an open circuit is represented here. The reactive component of a complex impedance is represented by this set of curves. This is actually a series of circles, but we're only showing the portion that lie inside of the Smith chart here. But the reality is it is a series of circles that expand around and beyond this outer perimeter. Inductive reactance is represented by curves above the baseline, and capacitive reactance is represented by the curves below the baseline. Now that we know what these circles and arcs represent, if we actually look at the Smith chart, you can actually now see them. You can see the circles here that all kind of are tangent to the open circuit here all represent values of R, and then all of these arcs that are leaving, or that terminate, if you will, at the open circuit point are the inductive reactance and capacitive reactance circles. So we can represent any value of R plus JX by any point within the Smith chart. In order to help visualize the impedance on the Smith chart, we're going to use the vector network analyzer and this relatively large overscaled circuit, which consists of a large variable capacitor, a variable inductor, and a series of switches that allow me to put the inductor or capacitor in series or in parallel with the load, which I've also got as a potentiometer, so we can adjust the real part as well. And here's the basic schematic of my demonstrator circuit. It's a variable inductor and a variable capacitor that can be switched into circuit with this double pole double throw switch, so we can select either L or C. And then this double pole double throw switch allows us to switch the variable element in series with our load, or by flipping the switch in the other direction, we'll put the variable L and C in parallel with our load. Therefore, we can represent each of these four situations: a series capacitor, series inductor, shunt capacitor, and shunt inductor with respect to our load. This demonstrator was built with some very large scale components, so it could be used effectively in front of a live audience at ham radio meetings and things like that. So as such, it's really only usable up to a couple of megahertz. Let's start off by putting a series capacitor with our load. Now if the capacitor is very small and the frequency is very low, this is going to look more and more like an open circuit. And as the capacitance goes up and the frequency goes up, the capacitor becomes more and more out of the circuit, and essentially we're going to see mainly our 50 ohm load. So let's take a look at it on the VNA. I'm sweeping frequency from about 300 kilohertz to 10 megahertz. I've got the capacitor dialed to its minimum value, which is on the order of 70 to 80 picofarads. So we can see at 300 kilohertz we're looking very close to an open circuit because the capacitive reactance is quite high, so we don't even see that 50 ohm load. At 10 megahertz we're going to, the impedance is actually getting lower because at 10 megahertz 70 picofarads is reasonable. It's a couple of hundred ohms. As I turn the capacitance up, we can see ourselves tracing across or tracing around, and notice that we're essentially tracing around the constant resistance circle. Okay, in this case the 50 ohm constant resistance circle, because we're not changing the 50 ohm resistance. We're only changing the series capacitance. So we're only changing the the JX portion of the R plus JX equation. So it's very easy to see how that we're tracing ourselves around that constant resistance circle. Now if I go and adjust the 50 ohm resistor that is at the termination, we can actually see that I can change the entire shape of that curve by moving it to other constant resistance circles. So now I've got it dialed into about 25 ohms, and now we're dialed into about 10 ohms, and we go up to a higher impedance. We can kind of see there's, that's I guess our 70 ohm line. Let's see if I can bring it back to 50. And there we go, got it on 50 ohms again. Now let's throw this switch and put the variable inductor in series and see what that looks like. Okay, now I've got the inductor in series. I've got the inductor dialed down to its minimum value, which is about a half a microhenry or so. And again, at a half a microhenry, there's very little inductive reactance at 300 kilohertz, so our marker 1 is sitting very close to our system impedance of 50 ohm resistive. And at 10 megahertz, we're seeing a little more inductive reactance due to that inductor value. Let me dial up the variable resistor or variable inductor here, and again we can see ourselves tracing around that constant resistance circle as we bring the inductance higher and higher. Now adding a series inductance or a series capacitance might be a portion of what you're doing when you design an impedance matching network to adjust yourself from some complex impedance to the normalized system impedance. However, the other piece of it is you might add a shunt capacitor or shunt inductor. Now how is that represented in the Smith chart? Let's take a look at that. When adding these elements in series, you're simply adding the reactive component to the real component. However, if you're going to be adding elements in parallel, it's a more convenient to typically talk about admittance. And that's where you're adding the conductance components to the susceptance components, or one over the resistance and one over the reactance. So there's actually a complementary series of curves on the Smith chart called the admittance curves. Now these admittance curves are really the same exact curves that we looked at for the impedance curves, except rotated 180 degrees. If you take this chart and you spin it around 180 degrees, you have these charts back here, and that's how they're derived. So these circles now represent constant conductance values, and these arcs represent constant susceptance values. Let's take a look at that on the VNA, and we'll start off by putting the shunt capacitor in parallel with our load. With the capacitor at its minimum value, it's going to essentially look like a very high impedance, so we're going to see mainly our load. And as we increase the capacitance value and as we increase frequency, we're going to start reducing that impedance, and we'll see how that is represented on the Smith chart. So now with the capacitance at its minimum value, we're basically sitting right at our system impedance, but as I increase the capacitance value here, we can now see ourselves tracing around, what we can imagine is our constant conductance circle for that 50 ohm load impedance. Now similarly, we'll switch in a shunt inductor, and as we bring the inductance value higher and higher, that inductive reactance that's shunting the load is getting higher and higher, and therefore becoming less and less a part of the circuit, and we start approaching our system impedance. At low frequencies, the inductor looks more like a short circuit, so we're kind of approaching our short circuit over there. And again, if we adjust our load resistor, instead of being 50 ohms, we can actually see how we're going to be tracing around other constant conductance circles other than the 1/50 ohm conductance circle. Now, you may have noticed that all the Smith charts I've shown you don't have the admittance curves on them. They only have the impedance curves. Of course, we turn the chart upside down, and now these curves are all the admittance curves. Now, you don't really have to do that. The axes are labeled both ways with the impedance and admittance components, and there's actually a little bit of a graphic trick to do the conversion between them. Let me show you a quick example. Let's say the impedance that I have that I want to convert to admittance is normalized to 1.4 plus J 0.8. To convert this to the admittance, we simply take a compass and we draw from the system impedance, center, through that point and all the way around the Smith chart. And then take a straight line from our impedance component through the center and cross the circle on the other side. And where we cross on the other side, that becomes our admittance component. So the conversion from an impedance of 1.4 plus J 0.8 to admittance is 0.54 minus J 0.31. Very simple, no math, real easy to convert between impedance and admittance on the Smith chart. I hope this video has given you some insight into how complex impedance is represented on the Smith chart and how to convert from complex impedance to complex admittance. In future videos, I hope to deal with topics such as reflection coefficient and SWR and how they're represented and computed off the Smith chart, as well as developing impedance matching networks and also the effect of transmission line length on the impedance seen by a transmitter when looking into a load. Anyway, thanks again for watching. If you like what you see, give me a thumbs up. If there are other topics regarding Smith charts that you'd like to see videos on, let me know, and I'll add them to the list as well. Thanks again for watching as always, and we'll see you next time.
G3 Victor Mike, Whiskey 6 Lima Golf, W6LG.
Whiskey 6 Lima Golf. Calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Germany 3 Victor Mexico G3VM CQ. CQ20 from Golf 3 Victor Mike, Germany 3 Victor Mexico CQ.
G3 Victor Mike, Whiskey 6 Lima Golf, W6LG.
W6LG, thanks for the call. You're 5 and 5 here, 55 I think, but I'll give you another report on the next over. Okay, name is Dan, Delta Alpha
Hello.
AM, and location here is in Bristol. Whiskey 6 Lima Golf, Golf 3 Victor Mexico, roger?
Roger. QRX, standby 1. Okay, there we go. G3 Victor Mike, Whiskey 6 Lima Golf. Good morning from California. My name is Jim, Japan, India, Mexico. Jim, I initially called you with about 70 watts, so hopefully this is better. I'm sorry. I didn't catch the name because I was flipping switches. G3 Victor Mike, W6LG. Jim near Sacramento in California, over.
QSL Jim, no problem. W6LG from Golf 3 Victor Mike returning. You're 5 and 9 plus 10 on that last over, which was a massive difference, Jim. It was like your audio came up by about 100%, to be honest. It was a massive difference. So yeah, the amplifier is working very well. I'm just testing out first contact. I've just taken in an Icon 756 Pro 2 as a trade-in deal today, so I've just brought it home with me to try out here. I always try radios that I've taken in for sale on air for a good sort of week before I list them to make sure they're okay for selling on, Jim. So it's just a Pro 2 here. And the antenna is a 3-element ultra beam, not very high, at about 30 feet, because I've got an 80-foot tower, a 4-section tower, but it's in its low position at the minute because all the wind we're having over here, Jim. W6LG, Golf 3 Victor Mike.
Okay. And the name is Dan, is that correct, over?
Yeah, QRCode Delta Alpha November. QTH is in Bristol, Jim. Roger.
Okay, still was messing with stuff. All right, very good. I've got my process up to high 2, and I'll turn that down a hair. You're 5 by 9, occasionally 5 to 10 over 9, quite a strong signal, and I'm pretty much beamed at you. Dan, my name is Jim, as I said. I'm near Sacramento, the capital of California, south of an old Cornish gold mining town called Grass Valley, in the foothills of the Sierra Nevada. Using 2 4-element Yagis, 8 active elements on 20. The Yagis are about 20 meters apart on separate towers. The transceiver is an Elecraft K3. Amplifier's homemade. It's about, I'm kind of guessing now because I haven't looked, somewhere around 4 to 5 degrees C with some light rain and broken clouds. And we desperately need the rain, so it's not a bad thing. Back to you, Dan. Nice to hear you. One of the first signals I've heard over the North Pole is you. G3 and the Pro, I think you said it was a 3. The Pro 3 sounds great. G3 Victor Mike, W6LG.
QSL Jim, W6LG from Golf 3, Victor Mike returning. Yeah, okay, I'm just looking you up on QRZ actually. Only on my iPhone because I haven't turned the computer on here in the shack because I wasn't planning on staying out here too long. I just wanted to make sure the radio is working before I go in the house and see the XYL and the children who are now home from school, so I can't hold it too long today, Jim. But looking you up on QRZ there, I think I've seen your YouTube videos before. I can't remember what I've been looking at before, but I'm sure you've come up on YouTube before. Your face seems familiar, so I'll have to research that. I'm not too sure what I've been looking for, but obviously something there that triggered my memory to your station there to see all your gear in the background. And okay, your antennas slightly more complex than what I've got here. Just the ultra beam, like I said, very low, 30 feet at the minute, so not very high at all. And I'm beaming about 310 degrees, which I've taken a guess, which is going to be roughly towards you, Jim. But you're very loud, very strong, so I mean, if you want to keep the frequency, Jim, you're more than welcome, mate. W6LG from G3VM in Bristol, over.
I've got to leave for a medical test in a few minutes, so I'll probably tune around the band for a while. Well, great. It's 2 real simple Yagis, 204BA type. Boom length is slightly less than 8 meters, so nothing really fancy, but fed with hardline and phasing line, so which I didn't adjust when I first called you. Anyway, rig sounds fine. Hope you make the sale when the time comes, and pleasure to hear you here on 20 meters. Happy New Year to you and your family from mine. Go see the kids. G3 Victor Mike, nice to meet you, Dan. And I've had pretty good luck with YouTube and a number of views, about 80 videos, and some of them either approaching 100,000 or over 100,000, which really surprises me, frankly. Dan, again, 73, nice to meet you. G3 Victor Mike, 73 from W6LG.
QSL Jim, W6LG, G3VM with the final. Nice to work you on air, Jim, and hopefully it won't be too long until we work again. And good luck with the medical appointment, mate. W6LG from Golf 3, Victor Mike. Look forward to the next one, Jim. Take care.
All right, good afternoon, Dan. 73.
73, mate. Take care.
Bye-bye.
QRZ, Bravo 1, Neil Jones, Julia, CQSA time.
Whiskey 6 Lima Golf.
Whiskey 6 Lima Golf.
Whiskey 6 Lima Golf. Calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
For me, it's a big Thursday.
Hello.
To you always. Thank you very much, and a big you. 7-3. QRZ, Echo Bravo 1, Neil Jones, Julia, CQSA time.
Whiskey 6 Lima Golf.
Whiskey 6 Lima Golf. Have a good evening. Good morning to you. I think you are 5 by 6. 5 by 6 at the moment, QSL, yeah.
Okay, I'm sorry, Alex. Nice to hear you. 5 by 9 into Northern California. Propagation appears to be just okay today. Anyway, great to hear you. EB1DJ, W6LG, over.
Roger, QSL 509 in the last over, accompanied with a little bit QS Baker. We carry a few days with a very depressing condition, but a lot of QS being all H1, but I think it's improving the sound spots at the moment. Okay, Jim, thanks for calling 73 and have a good time. W6 Lima Golf, Echo Bravo 1 Delta Juliet.
All right, thanks a lot, 73, and great to hear you. B1DJ, W6LG. Bye-bye.
Thank you, bye-bye. QRZ, leaving a stateside, Echo Bravo 1 Delta Juliet. W6 London, Germany, Delta Fox 2 Blue Ocean.
Whiskey 6 Lima Golf. Calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Atlante, CQDX, India Zulu 2, Zulu Sierra Foxtrot.
So.
Okay. India Zulu 2.
It's completely changed. I was 2 S units louder than tapped for an hour maybe, and now we're equal, so I've lost the skip already, Tom. The northern topography is not helping. It's much better being in Italy when the sun has set. And I hear many Italians working the DX, and we have no conditions anymore. So that's the typical credit you have to pay when being located a little bit further up to the north, Tom. Plus, I'm missing about an S unit due to the retracted tower. Anyhow, I thank you very much for coming back to the shout tone, and wish you and yours a happy, healthy, prosperous 2018. And looking forward to finding you on the band again before too long. 73's Tom, and until the next time, Willie Kilo 6 Florida in California. Delta Fox 2 Blue Ocean signing. 73's, bye-bye.
73, thank you.
W6LG.
Oh, okay, 6LG is still... Hi, Jim. Yeah, the antenna's down at the 51-foot level. Strong winds here, and I had to avoid that we might take some damage. I'm not paying the credit for that, just an S unit more, but losing the tower and the antenna, so... the antenna is at 51 feet now. Normally it's at 75 and a half, and the houses surrounding the antenna, of course, delivering some kind of an absorption, but you're still coming through very nicely. I think I saw the needle being pumped up into the red a bit, and I'm way past my sunset already. W6 London, Germany, Delta Fox 2 Blue Ocean.
All right, good morning to you, Tom, and also to the other Tom, if you can hear me, WK6F. Hello from Grass Valley. I'm going to make it short because I have to leave in a few minutes, but great to hear you, Tom. 5x959. Not a lot of signals over the North Pole, but just talked to DJ4 OA up the band a little bit, and he was also S9. But he was beginning to go down from the peak in the opening. Temperature here around 5 degrees C with some light rain. Looks like we're going to get rain off and on today, and hopefully sometime next week. Been quite the beginning for 2018. 73, thanks for letting me break in real quick. DF2BO W6LG.
Okay, very good, Jim. Yeah, well, Wolf is even west of me, so he has lost the skip. He has a much smaller antenna, Jim, and I had a good peek into the west coast 30-40 minutes ago, and the band is completely down, but you're still making it, and so did WK6S. Still cutting through very nicely, and we're a bit more than 20 minutes past sunset, and in Delta Lima conditions are completely fading away as soon as the sun has set in the southern topography in Italy, Spain, etc. It's much easier to walk an hour, 1.5 hour past sunset during the winter months. We here in Delta Lima cannot do that, Jim. It's just not possible.
Anyhow, you're peaking a 9 here, and thank you for the 5 and 9. Jim, you take care. My very best 73s. You have a good day over there in Cal, and good evening from my side. W6LGDF2BO.
Okay, Tom. Yeah, you're beginning to fade, and so I think it's the end of the opening. Thanks, Tom.
Whiskey 6 Lima Golf. I know the call sign, and I'm just thinking, Jim.
Whiskey 6 Lima Golf. Calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Hang up with you again soon. Take care, buddy. All the best. KP3 Alpha Golf Zulu. Germany 0 Alpha Whiskey Victoria 73J. 73 Red.
W6LG. Whiskey 6 Lima Golf.
Whiskey 6 Lima Golf. Whiskey 6 Lima Golf. I know the call sign, and I'm just thinking, Jim. Good to hear you, Jim. I think the band's starting to go. A lot of heavy QSB coming in, Jim. But great to hear you, Jim. I hope you're good. I hope you had a good New Year. W6LG, Germany 0 Alpha Whiskey Victoria.
Okay, Rick, great. G0AWV, W6LG. Well, yes, I did, and I hope you did too. Happy New Year. Last time we worked was probably November. Anyway, you are 5x8, occasionally S9. There is some QSB, and as you said, the band is beginning to go out. It's not as good as it was 30 minutes ago. Our sunrise occurred about 45 minutes ago, so it's a fairly short opening today. Rick, at this end, 2 4-element Yagis for 20 meters, 8 active elements on 20, Elecraft K3, and a homemade amplifier. Anyway, great to hear you. I wish propagation was better, but there's just a few signals coming in over the North Pole. G0 Alpha Whiskey Victor from Whiskey 6 Lima Golf, over.
Yeah, superb, no problem at all, Jim. And you're coming in here 5 as well. You're always a very, very big signal in here, Jim. And never have any problems hearing you. I know the band is definitely, I think, on the shift now. And it generally does at this sort of time. So, but there you go. Great to hear you, Jim. And I've seen quite a few of your videos, which are always great to watch. Always lovely hearing you on the air, Jim. Always sounding great, and always happy to say hello. Thanks for calling in, and I'm wishing you and your family all the best for 2018, Jim. Look forward to many contacts, and I hope the band starts to open up a little bit and get a little bit better as we head towards spring. Whiskey 6 Lima Golf, wishing you all the best for now, Jim. Germany 0 Alpha Whiskey Victoria.
All right, Rick, thank you very much. And yeah, it's one of those things, good days and days that aren't so good. Anyway, great to hear you. Thanks for the compliment on the videos. I'm recording video of our conversation right now. If it works, I'll be putting it up as part of a series of contacts, DX contacts. All right, take care, Rick. Nice to talk to you. See you on another day. G0 Alpha Whiskey Victor 73 from Whiskey 6 Lima Golf. Bye-bye.
Yeah, thanks a lot, Jim. Just to let you know that the equipment sounds great, and should I change your mind, right? Still on the ST1000 MP Mark 5 field. Using a solid state linear from ICOM RC2KL 400 watts here to the 2-element book one. You take care, and I'll look out for your video for sure. That'll be quite fun to hear myself on that. Take care, Jim. All the best for now. Whiskey 6 Lima Golf. 0 Alpha Whiskey Victoria, off and clear, 73.
All right, thanks a lot, Rick. And the only problem I'm having is there's that solar wind. It's up and down often way above S6, S7. So we're dealing with that as just about.
Kilo Papa. Echo Alpha 3 Alpha Kilo Papa. Calling CQDX 20 meters and leaving.
Whiskey 6 Lima Golf. Calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Kilo Papa. Echo Alpha 3 Alpha Kilo Papa. Calling CQDX 20 meters and leaving. Over.
Hello, John. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
W6 LG, my dear friend, thank you very much for your call. Big signal from you. I heard you, 30 or 40 minutes ago, Tim, with a very good signal. Right now, you're thinking between 10 to 15 dB over S9 easily. So appreciate every time you call me. Back to you, Tim. How are you? Whiskey 6 Lima Golf. Echo Alpha 3 Alpha Kilo Papa.
Okay, John. Very good. EA3 AKP. W6LG. EA3JE is about 1.5 to 2 kilohertz below U, so there is some QRM. Readability 4, strength 9, 4 by 9, and actually you're about 20 over. You may want to slide up 1 or 2. That's up to you, of course, John. But anyway, I thought I'd let you know. Weather here, it's about 5 degrees, some fog, and occasional rain. I let go of the microphone, and I hear the guy below us, who is quite strong. Anyway, it's raining a little bit, and looks like it will rain off and on for the next several days, which is good for us. EA3 AKP W6LG, over.
W6LG, Echo Alpha 3 Alpha Kilo Papa. Thank you for the full by 9, Jim. Thank you very much. And I'm not running a lot of power, Jim. Yes, I heard Lou transmitting very close to my frequency. Well, Jim, thank you for the information about the weather. 5 degrees centigrade and rainy. Here we are expecting some rain. It's very dry. The temperature is not bad. It's really warm for this season, 12 degrees centigrade, Jim. So that's the story, my friend. And I heard you also 45 minutes ago with the same signal, 10-15 dB over. Whiskey 6 Lima Golf, Echo America 3 Alpha Kilo Papa, over.
Okay, very good. EA3 AKP. W6LG, and of your beautiful OptiBeam antennas, and our friend Tom, DF2BO, during one of his visits to your terrific location there. He's quite the nice guy. John, I'm using 2 4-limit Yagis, real simple Yagis, 204BA type on separate towers, side by side, about 20 meters apart, and Elecraft K3, and the amplifier is homemade. Anyway, take care, my friend. Nice to talk to you. If you do chat with Tom, I did upload a video. It's off of YouTube right now, but I'll be putting it back up of me and Tom on 20 meters day before yesterday. EA3 AKP, over to you, W6LG, over.
W6LG from EA3 AKP. Thank you for your help, team, with Delta Fox 2BO's QSO. Will be always my pleasure. I told you this before in some of our previous QSOs that I watched some of your other videos. Some of them talking about technical things about radio, which is very interesting, and you explained very, very well, Tim. Congratulations. Okay, that 4x4 Yagis doing a great job for you. You're always very loud, one of the strongest signals from the West Coast coming through, Jim. Well, Jim, thank you very much for the nice QSO. I'm always very glad to hear you. Thank you for visiting my page, Jim. And yes, Tom came here several times to install antennas and so on. We are close friends for many, many years. So that's the story. Keep warm. There in your community, the West Coast of here, where, like I said, we're expecting some rain. It's very dry, Jim. Whiskey 6 Lima Golf, EA3 AKP, over.
Okay, very good. EA3 AKP, W6LG. All right, yes, and I will. I'm pleased that you watched a couple of videos, and I'm trying to upload some more, so hopefully I'll get better at it. Take care, my friend. Nice to talk to you. Thank you so much. Always fun to chat with you. EA3 AKP 73 from Whiskey 6 Lima Golf. Thank you, and 7-3. Bye-bye.
Lima Golf. I tell you, your signal is coming through still very loud and clear, and your IMD is always very good, according to my little spectrum analyzer from the IC7300. So also congratulations for that, Jim. And thank you very much for the enjoyable QSO. Please regards to your family, best wishes, and well, we keep in touch. You know that we meet very often here and there, but basically here on 20 meters where it's easy to hear your signal and your voice is strong. Jim, regards, my friend. Thank you for the QSO. Whiskey 6 Lima Golf. Over.
All right, 73, John. Always fun to talk to you. See you later, W6LG QSY. Bye-bye.
CQDX stateside, CQDX North Africa, Italy Zulu 4, United Florida, Germany, CQDX stateside.
Whiskey 6 Lima Golf calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
CQDX stateside, CQDX North Africa, Italy Zulu 4, United Florida, Germany, CQDX stateside.
Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Okay, Whiskey 6 Lima Golf. Thank you so much. Good morning. My name is Luca. Back to you.
Good afternoon, Luca. You're 5x959. Luca, my name is Jim. Japan, India, Mexico. Jim, you have some noise in your audio, just to let you know. I'm not sure if it's a loose connection or what I'm hearing. Back to you, Luca. IZ4 UFG W6LG. Over.
Okay, Whiskey 6 Lima Golf. Jim, thank you so much. Your report fantastic 59 plus 20, very strong in the north part of Italy. I am working with 1 kilowatt in the Delta Loop monoband 1 element and ICOM 7300. Back to you, Jim.
Okay, very good. I'm using 2 4-element Yagis, 8 active elements on 20 meters. Yagis are about 20 meters apart. Transceivers and Elecraft K3, and a homemade amplifier at 1 kW. Luca, nice to meet you. Happy New Year. Terrific signal. You're also peaking about 15 to 20 over 9. 73, my friend. IZ4 UFG from Whiskey 6 Lima Golf. Over.
Okay, Jim. Thank you so much. My best 7-3. Good weekend to you and your family, and greetings from Italy. Ciao, Jim. Bye-bye.
Arrivederci. Ciao, ciao.
CQDX 20, CQDX 20, CQDX 20. Hello, 20, CQDX 20.
Thank you very much, my dear friend. Yeah, the band is very, very poor here. Unbelievable.
Whiskey 6 Lima Golf calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Thank you very much, my dear friend. Yeah, the band is very, very poor here. Unbelievable. Hey, thanks for the contact. 73, have a great weekend. Muito obrigado. QRZ Ocean, November 7, Tango, Quebec.
Owen 7 TQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Whiskey 6 Lima Golf. Hi, Jim, and happy New Year. Good morning, and you're 5'9", over.
Yeah, you're 5'9" plus. Nice to hear you, Roger. What's new? Over.
Well, nothing. A new year, poor band conditions, and we are praying that it improves, Jim. Over.
Well, yes, I hope so, but I think we've got another year to the bottom. In any case, you're 5x9 right at S9. Nice to hear you. As usual, a very good signal over the North Pole. Temperature here about 5 degrees C with some light rain. ON7TQ W6LG.
Well, temperatures is okay, I think, Jim. Yeah, same thing here, actually. We got, well, what is it, plus 7 C at the moment. A couple of weeks ago, we had quite a bit of snow and low temperatures, but, well, it's pretty okay at the moment. We are not complaining. And, well, we are actually not too active on the radio at the moment with the other project going. Look at my QRZ page. You will find out where we are working at. So, anyway, hey, wish you and your family all the very best for the new year. Have a great weekend. And thanks so much for calling me. It's a pleasure. 6LG 17TQ. Thank you, sir.
But nice to hear you. Terrific signal. Roger, I'm using two 4-element Yagis for 20, about 20 meters apart, Elecraft K3. 73, Happy New Year, best to you and your family. Look forward to working you many times, I hope this year. 73, my friend. All-in-7TQ, W6LG. Thanks, Roger.
Okay, fine, Jim. And we hope to work you out of Mozambique in the month of May. We will be Charlie 8 Tango. 73, my friend. Take it easy, buddy. Bye-bye.
Yeah, see you there for sure, 73.
Thanks. November.
Is the frequency is, one more time, is the frequency is W6LG.
Whiskey 6 Lima Golf calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf. CQ, CQDX beaming JA, Whiskey 6 Lima Golf. W6LG calling CQDX, CQ, CQDX. CQDX calling CQDX. Beam towards Japan, Whiskey 6 Lima Golf. Whiskey 6 Lima Golf calling CQ, CQDX. CQ, CQDX calling CQDX. Beaming JA, Whiskey 6 Lima Golf. Whiskey 6 Lima Golf calling CQ, CQDX. CQ, CQDX calling CQDX, beaming Japan. Whiskey 6 Lima Golf, W6LG listening.
Juliet Alpha 0, Delta Charlie Queen.
Hey, good afternoon. JA0 Delta Charlie Queen. I think I got that right. Yeah, Delta Charlie Queen, Whiskey 6 Lima Golf. Takashi, nice to hear you. 5x959, my name is Jim. Japan, India, Mexico, Jim. And I'm in California. JA0 Delta Charlie Queen from Whiskey 6 Lima Golf. Dozo.
Returning, Jim. Very good morning to you. Or I should say good afternoon or good evening over there. Thank you very much for coming back to my call. And maybe it's just a good condition, but you are much stronger than you usually are. Your condition is very familiar for me. Anyway, you have 5 and 9. 5 and 9. It's into Nagano, Japan. Yes, my handle is Takashi, Tango Alpha Q Alpha, Sierra Hotel India. Takashi is my handle. Also, I'm glad to know that my signal is 5 and 9 over there in California. Here, it's cloudy, but sometimes we are able to see sunshine among the clouds. Temperature about only 0 plus minus 0 degrees C out of the doors. How copy over there? Jim-san, W6LZ, Juliet Alpha 0, Delta Charlie Queen. Microphone back to you.
Okay, Takashi-san, nice to meet you. Anyway, yeah, you're 5x9, 59. I've got two 4-element Yagis, 8 elements in total for 20 meters, pointed towards JA, and some phasing lines to one of them. The Yagis are about 20 meters apart. Transceiver's an Elecraft K3, and I'm using a homemade amplifier. So what is your antenna? JA0 Delta Charlie Queen. Nagano Whiskey 6 Lima Golf near Sacramento. Over.
Solid copy, W6LZ in Sacramento, Juliet Alpha 0, Delta Charlie Queen in Nagano, returning 100% copy. Your signal is coming in here remarkably. Always 5 and 9, your last transmission. Now I know, your gears are excellent. Sounds good. K3, it's also a familiar transceiver for me. Anyways. Okay, microphone back to you, Jim. W6LZ, JA0 Delta Charlie Queen. Put it back to you.
Okay, arigato, Takashi-san. Nice, strong signal. J0DCQ. Nagano Whiskey. Nagano. I'm not saying that right. I'll try the next time. W6LG. Very good.
Okay, I enjoyed talking with you also. If I could speak English more fluently, I could have more delighted you. Anyway, okay, thank you so much. Wonderful QSO. Whenever I have a time, I'm on the band. If you can hear me, please call me again. May I say sayonara, W6LZ, JA0 Delta Charlie Queen. どうもありがとうございました。Catch you later.
Okay, I did understand every word with no problem, Takashi, so thank you very much. Thank you. I've really enjoyed it. I see you're also Alpha Italy 6, Florida, England. That's poor phonetics, but I think you understand. 73, my friend. Take care. Hope to see you again soon. JA0 Delta Charlie Queen, sayonara. W6LG, arigato.
Oh, you spoke fluent Japanese. Your Japanese sounds really natural. So, sayonara.
Bye-bye. Whiskey 6 Lima, calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima, Golf. Whiskey 6 Lima, Golf.
DW6LG, and I'm running about the same power you are with Gulf Sierra 35 Bravo transceivers and Elecraft K3. I'm using 2 4-element Yagis for 20 meters, 8 active elements on 20. That are 20 meters apart and side-by-side locations on the top of the mountain. Not as high as the last guy you were talking to, about half his elevation. I'm at 2,200 feet, about 700 meters. So great to hear you, Dan, and won't hold you. Lots of guys are calling and would love to make contact with you because you are so strong this morning. Your Yagi is just putting out a potent signal. That's 58DW6LG, over. Yeah, okay.
In my previous video, we took a look at the Smith chart and how the impedance and admittance components are represented on the chart and how to convert between them. Today we're going to take a more practical look at the Smith chart and plot an impedance and look at some of the additional scales on the Smith chart to figure out how to extract the reflection coefficient, VSWR, return loss, and more. And then we'll really get into some of the magic of the Smith chart and better understand transmission line effects and what that does to the impedance that's seen looking into the line. So for our example, let's start with an equivalent circuit like a load that looks like a 33 ohm resistor followed by a 220 picofarad capacitor operating at 14.2 megahertz. So we can very simply convert this to an R plus JX type format by converting the 220 picofarads to its capacitive reactance, and we wind up with a load impedance that looks like 33 minus J51. It's a minus sign because it's capacitive. Now, in order to plot this on the Smith chart, we need to normalize this quantity to Z0, or our system impedance. So we're going to take our 33 plus J51 and simply divide it by Z0, and that gives us this normalized load impedance, I'll just call ZL, which is 0.66 minus J1.02. So let's go plot this on the Smith chart. Alright, we want to plot 0.66 minus J1.02. And being a negative J, being capacitive, we're going to be in the lower half of the Smith chart here. So we start off by looking at the 0.66 real component, and that is basically right next to this line right in here. And then we're also going to look at the intersection of 1.02 on the capacitive side of the reactance scale. So that plots us right here. To verify our point in the Smith chart, I took a 33 ohm and 220 picofarad capacitor, soldered them in series across this SMA connector. We'll connect this up to the VNA and verify what that point looks like on the Smith chart. And with the VNA set to test at 14.2 megahertz, we can see our point here, and that's showing 33 ohms and minus 51 ohms of reactance. And that basically matches, if you look at this point here with respect to the center of the chart, we're right in the right spot. So we've computed that correctly. Now once we know the load impedance, we could, if we wanted to, calculate the complex reflection coefficient. Remember, all these values are complex values, so this is not an easy computation. We could get the magnitude or reflection coefficient, often called ρ, just by taking the magnitude of that complex value. We can compute the voltage standing wave ratio, or VSWR, the power reflection coefficient, or the return loss. That's a lot of calculations. Or we can actually very simply just read them off the Smith chart. Let me show you how you do that. With our normalized load impedance plotted right here, we simply take a set of dividers, or even just a ruler, and measure the distance from the origin or center of the chart to our load impedance, and transfer that measurement down to these lower radial scales. And these scales have got a number of different axes. Let's take a look at them. Right, we transfer that radial distance from the center line here out here to the left, and the lower scale is the one that says reflection coefficient E or I. That's our complex reflection coefficient, and we can see that crosses right at 0.54. That's the magnitude, or rho, of the complex reflection coefficient. But how do we get the angle? If we take a look at the circumferential scales here, this one here says this is the angle of the reflection coefficient. So this scale right in here, that's going from 20, 30, 40, etc. And we take a close look at that, we can see that if we extend the line of our normalized impedance out to that scale, we can see that we cross right at about 76 or minus 76.4 degrees. So our complex reflection coefficient is 0.54 at an angle of minus 76.4, and our rho is just 0.54. So the next axis up is our power reflection coefficient. That's simply just the square of gamma. So that is about 0.3, actually closer to probably 0.29. We can kind of see it's crossing just to the right of 0.3 here, which means that basically 30% of your power is reflected, if that's what your load looked like at the end of a 50 ohm transmission line. We go to our next one up here, we look at our return loss. That's about 5.25 dB. The next scales up are for SWR. The top one is linear. That crosses right at about 3.4. So our SWR is 3.4 to 1, and represented in dB, it's just a little over 10 dB, about 10.6, 10.7 dB or so. So very easy to yank these parameters right off the Smith chart without doing any calculations. Next, we'll take a look at transmission line effects on the Smith chart. And what do I mean by that? Well, when you add a transmission line at our system impedance, like a 50 ohm line in this case, between the source, being a generator or a transmitter, and the load, a couple of things happen. The VSWR seen by the source looking into that transmission line is constant, regardless of that line length. And that's, of course, ignoring losses, which we're going to do in this case here. But the impedance looking in that line seen by the source changes with the line length. Let me say that again. The VSWR stays the same, but the impedance changes. You might say, how does that happen? Well, here's an example of how two impedances can give you the same SWR. If you had a simple resistive load of 25 ohms or a resistive load of 100 ohms at the end of a transmission line, or just at the output of a generator, both of those will result in an SWR of 2 to 1. So this, just one example illustrates the point that you can have different impedances that give you the same SWR. The same holds true for complex values of Z. So the calculation of that input impedance as a function of line length is pretty ugly, involving hyperbolic tangents and all that stuff. But with the magic of the Smith chart, this is a piece of cake. Let's go take a look at what I mean. Now, any circle on a Smith chart that's drawn concentric with the center represents a constant VSWR, or constant return loss, no matter where you are on that circle. And as you can imagine, any point on that circle represents a different impedance. So this impedance right here that we plotted earlier has got the same return loss, the same SWR as any other impedance represented on that circle. Now, rotating around the Smith chart represents either adding or subtracting line length. So a complete trip around the Smith chart represents a half wavelength of transmission line length. Therefore, the input impedance looking into that transmission line is equal to the load impedance whenever the line length is a multiple of a half wavelength, or another way to say that is an even multiple of a quarter wavelength. Now that's regardless of the line length and the load. So it could be a 50 ohm line, it could be a 100 ohm line, it could be a 75 ohm line. As long as that line length is a half wavelength or multiple half wavelength long, the impedance looking into that line is equal to the load impedance. Now, so therefore, halfway around this chart represents a quarter wavelength line. And this is kind of a special line length because it does some interesting transformations to the impedance. A quarter wavelength around a line that is open at the far end will look like a short looking at the near end. And vice versa. A quarter wavelength line that is shorted at the far end will look like an open at the near end. So really interesting impedance transformation. This is used for what are called quarter wave transmission line transformers, and we'll talk about that in a future video. So for any impedance, if you draw a circle through that impedance, you can show how that impedance varies with line length. So here's our initial impedance, ZL, and if we draw a circle that coincides with that radius, we've got our constant VSWR circle. And of course, where that crosses the zero reactance line, we drop a perpendicular line straight down. Here's the measurements that we transferred earlier down to this axis to determine SWR, return loss, etc. Now let's look at the axes that help us with transmission line issues. You'll notice these two labels over here. This one says wavelengths towards generator with an arrow pointing in this direction, and this one says wavelengths towards load with an arrow pointing in that direction. You'll notice that they're both start at 0 here, and if we go halfway around, both of those axes now end up here at 0.25. So as I said, halfway around the Smith chart represents a quarter wavelength line length. So if we continue to go all the way around, we can see we start approaching, here's 0.48, 0.49, and then this would be 0.5, but we're back at 0, because when we reach a half wavelength, we've replicated the impedance that's seen at the far end of the line. So we can use this constant VSWR circle and these various axes to predict how this impedance will get transformed into a different impedance when you start adding or subtracting line length from that load to the generator. All right, so here's our example. Again, we're going to continue to use our test frequency of 14.2 megahertz, right smack in the 20 meter phone band for us radio amateurs. And I've got a piece of coax here that has got a coax velocity factor of 0.66, which means that the speed of the wave through that coax is 66% of the speed of light. And the length of that is just about 1 meter. So let's figure out how many wavelengths long this is. So in free space, we want to calculate the free space wavelength of our 14.2 megahertz signal. That's 300 divided by 14.2 gives us 21.13 meters. Now to determine the length of coax, we can just multiply by the velocity factor. So we know that the length of coax that would be a 1 wavelength long would be 13.95 meters. But I've only got 1 meter of that, so we simply can invert that. And now I know that that 1 meter length is 0.0717 wavelengths long. So let's go to the Smith chart and see how to predict what that input impedance will be looking into that transmission line. Okay, so our original known load impedance is plotted again right here. And again, we're going to follow this axis now clockwise around because that's where it says we're going to go wavelengths towards the generator. So as I add transmission line length, I'm essentially moving the generator further away from the load. So I'm rotating in this clockwise direction. So we just need to rotate essentially 0.0717 wavelengths. So how do we do that? We extend again this line down here. we can actually read from that appropriate scale how many wavelengths when we're starting from. It's just a starting point. We'll call that 0.356 wavelengths right here. So we want to essentially add 0.0717 to that. So we want to wind up at a reading that is 0.0717 wavelengths away, or at 0.4277 on that scale. So we put a little tick mark there, draw another line right back up through to the center of the Smith chart, and where it crosses our constant VSWR line, that is the input impedance looking into that 1 meter length of line. Let's verify that on the VNA. Yeah, but first we need to actually determine what that impedance is. So we just essentially can read off the scales here. We're at about 0.355 on the real or resistive circles, and we're at about minus 0.44 again capacitive on the reactance circles. And so if we unnormalize that, multiply both these values by 50, we get an impedance of about 17.8 minus J22 ohms. Now we can go to the VNA. So here's our measurement with the load directly connected to the VNA. So let me disconnect that load, and I'm going to add connect it to the end of the 50 ohm transmission line, 1 meter length long, and then connect the transmission line to the input of the VNA. And there's our point right there, and we're measuring, we can see that, about 18.2 minus 22.6, and we were predicting that to be 17.8 minus J22, so that's pretty close. Now, a more common use case probably in amateur radio world is kind of almost going the other way. Well, with an analyzer or something like that, you may measure the input impedance at the transmitter, looking into the coax that the transmitter sees. So you're already some distance away from the antenna. So if you know the line length, you can then use the same trick we just did to rotate towards the load instead of towards the generator, so we can understand what the actual impedance is at the feed point of the antenna. And then you can design a matching network to place at the antenna feed point. And by doing that, it keeps the SWR on the transmission line near 1-to-1, and that minimizes loss. You certainly could just design a matching network to match the input impedance of the transmitter. It doesn't change the SWR on the line, but it does allow the transmitter to put out full power. So again, going the other way is probably the more common use case in amateur radio use. So we took a look at how to plot a complex impedance on the Smith chart, how to determine complex reflection coefficient and SWR return loss, and then also how to take a look and see what the impedance looks like with different connected line lengths to that load. As always, all of these notes will be available in a PDF file, and a link in the video notes down below. If you like what you saw, give me a thumbs up. Please subscribe if you haven't done so already. I'd love to hear your comments in the comments section, and thanks again as always for watching.
Many of these are old. This one's World War II war surplus.
Whiskey 6 Lima calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. Going to do an experiment, and going to be kind of a repeat of one I've done in the past that got a lot of criticism. I'm going to connect, or have connected, approximately 30 coax connectors. And just to be really clear, many of these are old. This one's World War II war surplus. Same with this one, same with this one, same with this one, and they've been outside and used. I'm going to string them together and hook them up to this switch, and it's going to go these two switches, and it's going to go between these two switches here. And I'm going to turn on this signal generator, which puts out 50 microvolts, and see what the loss is using my pan adapter. So my pan adapter is calibrated in dB, which may not be the easiest thing to understand, but Turn this off. But I'll try to convert the dB to loss, maybe percentage of loss. So how much loss is there on 20 meters? And this time, how much loss is there on 6 meters? Then I'm going to hook up 100 feet of coax from here to here and see what the loss is on 6 meters and 20 meters. Also, I've got FT8 going on the Yaesu 450. The antenna's disconnected, but I'll reconnect it. Got that going late last night. So in a subsequent video, we'll talk about putting a Yaesu FT450 on FT8, and we'll see how that works. Looks like a lot of fun. Anyway, let's see what happens. Get the receiver to 20. 14,200. Going to go down just a bit so I'm not 0 beat. Not sure where to put the scale, so looks like 84, 85 dB. See if I can change the scale just a bit so we're a little more accurate in the reading, because now we're down to 1 dB is going to make a difference. Let's see. Okay, there we go. Well, right at 84 dB. So minus 84 dB on 20 meters. Now that's connectors in line. No connectors. Connectors in line. And so it's minus 84 dB whether the connectors are in line or not. So there's no difference. Let's go to 6 meters and see what happens on 6. Okay, here's 6 meters, minus 87 dB without the connectors, minus 87 dB plus a little with the connectors. So again, there's no difference that I can measure. It's minus 87 dB in either case. So the connectors don't attribute to loss. Let's try coax and see what it does. And again, it's 100 feet of RG8X. We'll go back to 20 meters, which was minus 84 dB. Okay, there's about 1 dB difference. So minus 84 versus minus 85. It's about a 22% loss for in the coax. So if you put in 100 watts, you're getting 78 out the other end. Here's 6 meters. The loss is roughly double, about 40%. So it's minus 87 versus minus 89. So there was about 40% loss, and both those are assuming that the SWR is low. As the SWR goes up, as we've discussed before, those losses also increase. Anyway, if you enjoyed the video, please subscribe. If you have a comment, please put it below. Right now we're at about 10,000 subscribers and growing pretty rapidly. So thanks for watching. See you the next time. I'm Jim, W6LG.
In today's video, I'm going to take a look at how to use the Smith chart to design an impedance matching network, in this case an L network. We'll use that to take our complex load and transform it into the system impedance, in this case 50 ohms. The L network is a very simple two-element matching network. It's called an L simply because of the shape or the arrangements of the components in a schematic. Will typically consist of either a series element and a shunt element. That shunt element will either appear across the load or across the input, depending on the nature of the load that we're trying to match to the system impedance. I've shown these as LC matching networks, but you really can also build this with 2 inductors or 2 capacitors arranged in either direction. So let's go take a look at the approach. You may remember from video number 274 that adding an inductor or capacitor in series with a load will rotate us on the Smith chart along the constant resistance circles, which are these red circles that are all tangent to the open circuit point on the Smith chart here. Adding a shunt inductor or capacitor, or adding a capacitor and inductor in parallel with a load, will rotate us on the Smith chart along the constant conductance circles, which are these blue circles that are all tangent to the short circuit end of the Smith chart. So which way do we rotate along these circles? There's actually a little bit of a trick that I use. When we're talking about adding inductors, either in series or in parallel, that always rotates us up through the real axis being the center axis here. So we can see adding a series inductor rotates us up in this direction along the constant resistance circles. Adding a shunt inductor rotates us up along the constant conductance circles in this direction. So you can think about this as adding an L that's elevating us up and rotating up on the Smith chart. Now, as you might imagine, adding a capacitor will rotate us down. So whether that capacitor is in series with our load, we're going to rotate down on the resistance circles, or that capacitor is in parallel or a shunt capacitor, we're going to rotate down along the constant conductance circles. And again, C for crashing down or going down on the Smith chart. So it's a pretty easy way to remember how we move around on the Smith chart by adding a series or shunt inductor or capacitor. Now, while the L network is very simple and easy to design, one network configuration can't be used to match all possible load impedances. So this set of yin-yang drawings here of the Smith chart basically show you what impedances can be matched by each of these four configurations of the L network. Now you may notice that for some impedances, like let's say our impedance was down in this area, that could be matched by either a series C and shunt L, or by a shunt C and series L, because either one of those are in the unshaded areas. So when you have two possibilities, which one do you use? Well, there could be a number of configurations. If you look at, as I described, a load that is down in this area that could be matched by either of these two networks, you might say, well, this one is essentially a high-pass network, this one is a low-pass network. So this one might be favorable because it might help to reject some higher order harmonics that might be coming from your transmitter. But at the end of the day, it comes down to personal preference and even maybe what components you have on hand. And of course, let's not forget that the L network can either be all capacitors or all inductors. And I've got similar diagrams here to show you what impedances can be matched using these configurations. They're not as commonly used because the range of load impedances that can be matched is smaller, given the smaller area here contained in the unshaded area of these Smith charts. Here's our design process. We first plot the load impedance wherever it is on the Smith chart. And then working from that, we want to add a series or shunt L or C to rotate along the constant resistance or constant conductance circles until we reach either the unity resistance circle or the unity conductance circle. And then we record how far we've moved in either reactance or susceptance to get there. Then we add a series or shunt inductor to rotate along the unity resistance or unity conductance circle to reach the center, and record how far we went in that case. And then from those movements or the lengths of those arcs in either reactance or susceptance, we can then compute the capacitive and inductive reactance at our operating frequency, and use that to compute the actual capacitor and inductor values. And it may sound confusing. Let's actually go do it in a real example, and you'll see it's actually not that hard. I'm going to be using the same 33 ohm and 220 picofarad series combination load that I used in the previous video to kind of show how to plot the impedance. And we're going to impedance match that one. Now, in order to be able to put my L network together, I've inserted in series here just a little fixture that allows me to put a component in series and a component in parallel with our given load. So we can actually see the results of this on the VNA. Now, as shown in the previous video, here is our load impedance right here on the Smith chart. If you really pay attention, you may notice that this plot is actually ever so slightly to the left of where it was when we did it in the previous video. And that's because we've effectively added a little bit of transmission line length by adding that fixture in place. So that kind of rotated us a little bit over, but not so much that we're going to worry about here. So that's our starting point. We want to get from there right to the center of the Smith chart right here. Using the previous yin-yang diagrams, we've selected this network here because that will take and properly match this load impedance location. So we're going to put first thing we're going to do is work from our load back. So the first thing we're connecting to a load is a shunt inductor. So the shunt inductor means that we're going to ride up along the constant conductance circles here. And we want to do that until we hit this constant resistance circle. Okay. Now I also want to do it with a series capacitor. So if I rotate up here, the first place I hit that unity resistance circle is right here. So I could rotate up here and then rotate that way to get to the center, but that would mean adding a shunt L and a series L. I actually want to do a shunt L and a series C. So we're going to rotate up from here until we hit the unity circle up on this side. So how far did we move? If we look very carefully, we can see that the susceptance at this point is a value of 0.069. It's right adjacent to this 0.7 susceptance line. So we're going to move 0.69 to here, and then if we look again carefully up to this end, we're on the 0.5 susceptance line. So the total distance that we've moved is 0.69 plus 0.5, or 1.19. So if our susceptance, our normalized susceptance that we moved is 1.19, the inductive reactance is essentially going to be 1 over that, and then unnormalized times 50. So our our inductive reactance of this shunt element is 42 ohms. So to calculate that back using our operating frequency of 14.2 megahertz, we can compute an inductor of 471 nanohenries. All right, I've wound an inductor to be in the neighborhood of 470 nanohenries. We can stick it in the tester and see what we have here. 465, that's pretty close. In fact, if we squeeze these windings together a little bit more, we can kind of tweak that value a little bit. And now we're at 482. So what we'll do is we'll stick it in and actually stick it in the fixture to do the impedance match and tweak the value there. Okay, now we're going to want to rotate up. We're not going to see the rotation, we'll just see the movement, but we want to wind up on this unity circle here, the one that goes right through the center of the Smith chart there. So let's stick my inductor in parallel with the load and see where we are. Actually pretty close. We're a little bit shy, which means I need to actually reduce the inductance value ever so slightly. So let me spread those windings out a little bit here, and boom, we line right up on that line. So we've done that first arc now on our matching network. So now the other piece is to add our series capacitor to bring us from this point down to our matching network. And if we take a look at our reactance component, our reactance component here is sitting right about 1.1. So we can unnormalize that. So 1.1 times 50 gives us a 55 ohm capacitive reactance, and then we can use that to compute the actual capacitance value at our operating frequency of 14.2 megahertz, and it gives us a capacitance of about 200 picofarads, just a little bit more. So I've taken a pair of 100 picofarad capacitors and just soldered them in parallel. Now let's put that in series with our network to complete the L network, and that should rotate us right into the center of the Smith chart. Alright, so I'll pull the little 0 ohm jumper out that I have in the series position on my fixture and replace that with my 200 picofarad capacitor, and lo and behold, if I get this connection here to go right, it's a little more reliable there, there we go. And there we go, we find ourselves actually very close to the center of the Smith chart. Of course, these components are not ideal, and as I touch them I'm going to move them around a little bit, but you kind of get the idea here that a simple L network rotating on a couple of arcs by adding series and shunt elements, we're able to take this impedance, which was way out over here on the Smith chart, and match it to our 50 ohm system impedance. Now, for those that were curious of what that looked like, here's my load that we started with here. This is the 470 nanofarad shunt inductor, and here's our 200 picofarad series capacitor. So we use the Smith chart to design this style of network here. Now, of course, we could have also used it to design this style of network by starting off by doing a series inductor and then adding the shunt capacitor, or even using this network down here. Either one of these configurations of a pair of inductors would have gotten us there as well. I hope you enjoyed this video to take a look at how to design an L matching network using the Smith chart. If If you like what you see, please give me a thumbs up. As always, my notes from the video will appear as a link to a PDF file in the show notes on the YouTube page just below the video here. If you haven't subscribed to the channel already, please do so. I'd love to hear your comments down below, and thanks again as always for watching. In this video, I'm going to show you how to build the super simple code practice kit. The supplies you'll need to build this kit are a Phillips head screwdriver, a pair of diagonal cutters, a soldering iron and some solder, a sandpaper or emery board, and a 9-volt battery. The first thing to do is to take some inventory. Starting off with the electronic components, we should find two capacitors with a marking 104, and that's these two components here. Two 15K ohm resistors, and they will have a brown, green, orange, and gold band, just like these. The next are two 470 ohm resistors, and they'll have a marking with yellow, violet, brown, and gold band, like these two right here. And the two transistors. These are the metal cans with 3 leads. Next, make sure you've got all of the hardware. You should have a pair of 632 by 3/8 screws, 4 632 by 1/4 inch screws, one 832 by 3/8 inch screw, just slightly larger in diameter than the number 6 screws here. You should have 6 hex nuts, 2 spacers, the male and female 9-volt battery clips, and the plastic knob. And finally, make sure you've got the 8 ohm speaker, the stick-on rubber feet, and the printed circuit board. The first step is to break off the piece of the circuit board that becomes the Morse code key, and that's just grooved and makes it very easy to snap off. After you've separated the circuit board, some of these edges might be sharp, so you can take your sandpaper and smooth those edges if necessary. The first step is to install the speaker, and we start by putting 4 screws through the component side of the board surrounding the speaker. Then carefully place your hand across those screws so they don't fall out, and flip the board over. And then place the speaker in the middle of the 4 screws with the terminals facing the solder pads on the board. And take 4 of the hex nuts and start them on each of those screws until they're just touching the speaker. You can then put your hand over those 4 nuts, flip the board back over, and use the Phillips head screwdriver to snug up the screws. And just a quick tip here, don't make the screws too tight because you don't want to bend the speaker. Now before we start doing some soldering, some words of caution. The soldering iron gets very, very hot enough to melt metal. So do not touch any of the metal portions of the soldering iron once it's plugged in. And follow the instructions carefully when doing soldering so that you don't burn yourself. So periodically while you're soldering, it's a good idea to put a little solder on the tip of the iron and then to wipe it off either on the solder tip cleaner or the wet sponge that is provided. This keeps the tip clean and ensures good solder connections. We're going to start with the battery terminals. So hold the battery like this so that the positive terminal is facing away from you, and attach the 2 solder terminals to the top of the battery, and we'll use the battery to actually hold them in place while soldering them on the board. Now making sure that the battery positive terminal is going into the positive set of holes on the board, insert the battery terminals through the board and flip the board over to get ready to solder. Now the proper technique for soldering is to bring the soldering iron down so it's touching both the board and the terminal that you're looking to solder. Let that heat up a little bit and then apply the solder to the opposite side. When everything is heated up, it will melt and flow evenly around the lead and the terminal itself. And again, be sure not to touch it because it's going to get very hot. Repeat this for all 6 terminals sticking through the board. When done properly, each of those solder joints should be smooth and shiny all the way around. If it looks dull or pitted, then it's what we call a cold solder joint and should be reheated with a little extra solder until they're nice and smooth. Once you're finished soldering the 9-volt battery clip joints, you can turn the board over and pull the 9-volt battery off for now and set it aside. Okay, the next step is to locate the 2 15K ohm resistors. These are the ones that have a brown, green, and orange marking with a gold band on the end. And for each of those resistors, we'll take and bend the leads at a 90-degree angle, and then we can insert them into their locations on the board. You'll see a marking for 15K and 15K. So insert both of them into the board now. When they're properly inserted in the board, they should sit nice and flush, and then with your finger on the part you could turn it over and slightly spread the leads out on the bottom so that the part doesn't fall out when you turn the board over for soldering. And then we'll solder these 4 leads just like we did for the battery clips. With all 4 leads soldered, it's time to clip off the extra lead length. Let the leads cool for a few seconds and then bring your diagonal clippers in and clip off each of the leads. Now hold on to the wires so they don't go flying, plus we're going to need to use a few of these later on. So it's a good idea just to clip them all off, keep them in your fingers, and put them in a pile on the desk for use later on. Okay, so the 15K resistors are installed and soldered, and we've clipped the leads off. We're going to repeat the same process with the 2 470 ohm resistors and the 0.1 microfarad or 104 capacitors. The 470 ohm resistors are the ones with the yellow, violet, brown, gold bands. And we'll insert them in the board in the 470 ohm resistor locations. And we'll solder them in place. And trim off each of the leads. Follow the same process for the 2 capacitors. Okay, the resistors and capacitors are now done. Next we're going to start with the 2 metal can transistors. They're labeled 2N2222A. Now you'll notice these transistors, they have 3 legs, and there's a small tab on one portion of the can. So with the tab facing up, we'll install the 3 leads of the transistor and slide it down so that it's not quite touching the board, spaced up by about a 1/16 of an inch or so, like I've shown here. Install the second transistor the same way, spaced up by about the same amount, and then you can flip the board over and solder all 6 of those legs. Okay, next, take the 832 by 3/8 inch screw, stick it through the large hole at the end of this board with the silver side up. Turn it over and attach the plastic knob. I'm going to take the last 2 screws and insert them through the end of the keyboard here, and throw the red side over, flip it over, and slip the 2 spacers on top of those screws. Then take your board and position it over those 2 screws, and then we'll put the nuts on the other end. Now the final electrical connections we need to make are to solder the terminals of the speaker to these terminals on the board. And this is where we're going to use 2 of the spare leads that we clipped off earlier. I'll start by just putting a little solder on these blank pads on the mounting points. It'll just make it easier when we go to solder the wires on later. Now using your diagonal cutters very lightly or a pair of needle nose pliers, you can hold onto that wire, position it over the pad, and melt the solder to attach it. Then repeat this for the other terminal. And we just want to position these wires so they go over the metal pads that are on the board, and then use the cutters to cut off the wire about in the middle of the pad on both of them. You can then push the wires down until they touch the board and then solder them. Okay, almost done. We simply take the 4 adhesive rubber feet and stick them to the 4 corners of the board. Right, flip the board over, slide on your 9-volt battery, and lo and behold, you've made yourself a super simple Morse code practice oscillator. Congratulations.
GG for Victor, Zulu Victor, pedestrian mobile in Spain. This is Jim, Whiskey 6 Lima Golf near Sacramento in Northern California. Whiskey 6 Lima Golf calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Last week, at about sunrise my time, I was tuning 20 meters because there's a gray line that goes from California into Europe. Came across a guy calling CQ, and his call sign was G4 Victor Zulu Victor. As I turn the antennas towards Spain, he becomes even louder, and I hear him say EA5 stroke G4 Victor Zulu Victor. There was a little bit of QRM, and then that goes away, and I hear his complete call sign, which was EA5 stroke G4 Victor Zulu Victor stroke pedestrian mobile. It's a guy walking in Spain. Then on my receiver, the S meter's going to about S8. Made contact with Ken, and he offered to video his end of the contact using his cell phone, which he did and uploaded so I could get it. I take a transmission, which is what he recorded, and in that transmission I overemphasized pretty much every word because I knew he was making a recording and I wanted it to be clear. Anyway, I was S9 with him, and eventually he was S9 with me. So here's that recording done by Ken Cherms in Valencia, Spain, EA5 stroke G4 Victor Zulu Victor stroke pedestrian mobile.
Pedestrian mobile in Spain. This is Jim, Whiskey 6 Lima Golf near Sacramento in Northern California. Good morning, Ken. You are 5 by 8, 58 into Northern California. I'm near a small old gold mining town called Grass Valley in the foothills of the Sierra Nevada. Again, my name is Jim, a location near Grass Valley in Northern California. You are 100% readable and really quite strong. Ken, I'm using two 4-element Yagis that are side by side about 20 meters apart. Transceiver's an Elecraft K3 and a homemade amplifier. Temperature's been warm right now. It's about 10 degrees C. The high today is going to be an amazing 22, 23 degrees. Ken, 73 from Northern California. Your pedestrian mobile signal is amazingly strong. 73 Ken, EA5 stroke G4 Victor Zulu Victor pedestrian mobile. 73 from Whiskey 6 Lima Golf in California. Over.
Yeah, okay, Jim. Well, Jim, I'm still videoing it. I've got a minute on the video now, and just to show on the power, my power, which is 100 watts, and you should see that on the meter, and the 857, the trolley and everything. Thanks very, very much for the report. And it's a pleasure to talk to you again, Jim. You're coming through, absolutely romping through 5.9 plus. I'll try and get this video back to you, and look out for it on an email. Cheers, Jim. Whiskey 6 Lima Golf. This is Echo Alpha 5 stroke Golf 4 Victor Zulu Victor pedestrian mobile. Over.
Okay, you went over S9 that time. As the sun is coming up, it's not looking across the valley. I can see the transition from light to dark. So we're just now moving into that gray line, and you went above S9, that transmission. All okay. Yeah, please do that, and I'll put it into a YouTube video. I'm approaching 11,000 subscribers, and some of the videos have had a fair number of looks. One of them about 110,000 views so far. 73 Ken, you do a marvelous job. EA5 stroke G4 Victor Zulu Victor pedestrian mobile in Spain.
Apart. Don't break. Hey, Gads.
Whiskey 6 Lima Golf calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Jim W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. I'm trying to keep the background blurred because it's a mess, and it's a mess because I'm rearranging everything. My goal is to set up a microphone on a boom arm, and the reason for that is, well, there's a couple of reasons for that. One of them is so that when I operate, I can keep one hand, left hand on the RF gain, AF gain, and the right hand for typing into the keyboard. So the goal here is to kind of free up my right hand from holding onto the microphone, and the only way to do that is with a boom arm. So I've purchased one that I'm using right now. It looks like 90% of them that you see on Amazon, and that's where I got it. There's, first of all, I didn't pay much money for it, so I'm not going to complain about how much it cost, because for what I paid, I got what I paid for. The problem I'm running into is it just simply doesn't work very well, and the microphone, I've got a couple of mics. In some cases it doesn't want to keep the microphone down. In this case, this is a very light microphone, but the issues I'm running into are it doesn't want to hold its position, and the springs are noisy. And the other thing too is, without showing the mic, there's just a bunch of slop in it, and it drives me nuts. So I don't know what to think. I need to close talk the microphone for DXing, and that particular mic doesn't work all that well for that. It's got way too much gain. It's an Electret, very popular microphone, incredibly inexpensive. The boom arm, as I said, looks like about 90% of the ones that you see on Amazon, and it's got, let's see, 1, 2, 3, 4 exposed springs, and it's just not going to do the job. First of all, it's too short for where I have to mount it, because it's going to have to come over some of the equipment on the second shelf. I put it over here thinking, well, maybe I could use it for YouTube videos, but I don't want to, and there's a reason for that. And the reason is I don't want it in the field of view much. I know a lot of guys want to have a pretty microphone to show off their nifty mic that's looks like gold, but I don't want to do that. I want the microphone to be really out of the picture, not part of the picture. Also, I've had a bunch of issues with AC hum occurring once in a while on this mic, so there's a grounding problem. To make this mic work really well for close in, you need to use one of these things, and I don't want this in the field of view either, so I don't know. I've got my somewhere. I've got my Heil Gold Line microphone somewhere. I've got my Heil Gold Line microphone that may or may not work in this mount. I may have to use a mic clip to make that work. Something like, let's see if we get it in focus. Something like this guy. And so the mic slips in, and this is the one with. This is an interesting mic in that it has two cartridges in it. One is the HC4, the other is the HC5. What is kind of weird is the way they're mounted, and maybe it's genius, I don't know. So I'm going to pull this apart. Don't break. Hey, gads. Okay. Here's how, let's see if I can get this in focus, and maybe I'll shoot a picture of this. So here are the two cartridges. They're mounted on the top on double-sided tape. So this part looks like a standard dynamic microphone housing. There's no microphone in it, and then these two guys are mounted on the top. The difficulty with this is, let me put this back together.
Okay. Boy, is that fragile looking. The difficulty with it is you've got to talk into it this way. So I'm not sure I can make that work on YouTube. So I'd use a mic clip, and the mic clip is rubbing up against the switch. So this mic clip's not going to work. There's a switch mounted here. By the way, this is the second switch, and I just had this apart. I'm going to need to buy a third switch because it quit working. Becomes intermittent. So I'm going to have to use a different kind of mic clip with this thing, and then if I use it on the air, I'm going to have it like this. So, and probably some kind of windscreen over it. Not sure if that's going to work. For YouTube videos, again, I'm not sure if it's going to work. I can give it a try. Along those lines, I'll get myself back in focus here. The depth of field on this lens is about that much, and like I said, I'm trying to keep everything else out of focus because it's such a darn mess behind me. I've got a microphone coming that's fairly expensive, and I've got what I think is probably one of the better, if not the best, mic boom arm around, to the extent that the manufacturer of it actually measures the noise that the thing makes as you move it and gives you a graph of that, which I haven't seen yet, but it sounds interesting. So we'll see what that looks like. Again, I got what I paid for, so I can't complain. Well, I can complain, but this part is just, it's got about, I'd say 4 inches of slop in it, and they've used channels with like nylock nuts. Of course, they're all metric because it's made in China. And springs that are exposed. And what happens over time is, as you move the thing, the springs become really noisy. They remind me of a spring door, of a screen door that we had as a kid, and it had a big long spring on it. And then when you let go of the door, it made a lot of noise before it slammed shut. Anyway, for YouTube videos, I don't think this is going to work out, and I'll see what the audio sounds like. But for now, and if you've enjoyed this video, please subscribe. I'm Jim, W6LG for Ham Radio Basics. Thanks for watching.
In video number 276, we learned how to use the Smith chart to design an L matching network to match a load impedance of 33 minus J51 ohms to the system impedance of 50 ohms. And for a network such as a shunt L and a series C, we wound up with component values of about 470 nanofarad and 200 picofarads for our particular operating frequency of 14.2 megahertz. Now you may recall we chose this network based on this set of yin-yang diagrams here that said if our load impedance was down in this area, we could use a shunt L series C or a series L and shunt C network, and we chose to do this one. If we examine our yin-yang diagrams here, we can see that for the load impedance that we were talking about, there's actually 3 different networks, actually 4 different networks that we could use to match that impedance. We could use the one we chose, we could use this one over here, but also our load impedance fell into this area here, so we could use a shunt L series L or a series and shunt L. So rather than go through and use the Smith chart manually to show you each of those potential matching circuits, I'm going to introduce you to probably one of the best Smith chart simulator programs for the PC that I've come across, called SimSmith. Let's start off by replicating what we did on paper with the shunt L and series C network. SimSmith is a fantastic free Smith chart simulator that was written by Ed Harriman, AE6TY. Another great resource to look at is the YouTube channel of Larry Benko, W0QE. He has a whole series of tutorials on how to use SimSmith. and I'll include links to these down below. Now let's start off by just replicating the experiment we did on paper. So I've included my operating frequency of 14.2 megahertz here on the source, and here's our load impedance that we're starting off with, 33 ohms minus J51. And notice that plot's right down here. Remember, we're going to start off by replicating what we did earlier. So that is starting off with a shunt L. So I'll just grab the shunt L and stick it up here. And you notice that traces this trajectory up along essentially the constant conductance circles. And if I mouse over the value for the inductor, I can roll its value back and forth. And the idea here is to roll it up, in this case, up to our constant resistance circle that passes through unity. And that's pretty darn close. So now I want to add my series C. So I grab the series C, drop that in series here between the generator and the load. And you can see that we're just about at the matching point here. I simply just roll the value of that capacitor up or down, and boom. Very simply, we've replicated that same 470 nanohenry and 200 picofarad L matching network that we did on paper. Well, now that was really simple to get to that same result that we did on paper. So let's use this program to show us what the components would be for the other three possibilities of the matching networks. So let's start off by designing this network now, which would be a series L and a shunt C. So we'll go in here and I can just simply grab these guys and drop them down into the trash can here over here and start over. Now let's add a series L to begin with. And we see that's rotating us up here. Now since the next element we're going to add is a shunt element, we're going to go on these constant conductance circles. So I know I need to bring this point up to that constant conductance circle. So I'll just roll this inductance value until I reach the unity conductance circle right there. Okay, now I can add my shunt C in front of this network here. And we went a little bit too far there, so we'll just rotate our shunt capacitor value back, and boom, there we are, perfectly matched, and about 834 nanohenries and 157 picofarads. So real simple, we've been able to design 2 of the 4 matching networks. Let's do the other 2. Now the other 2 are purely inductant networks, a shunt L and series L, or a series L and shunt L. So let's go design each of those. Alright, let's do the one with a series L, shunt L first. So let's take the series L in series with the load here. And again, I'm going to do, remember L's kind of bring us up on the Smith chart, so I want to rotate up to the unity conductance circle here. So we need to change this inductance value until I reach that unity conductance circle right here. And now I'll add the shunt L component to the front of that and adjust its value till I get down to my match point. And there I am, impedance matched with an L network that's purely made of inductors, 300 nanohenries and 786 nanohenries. And lastly, let's do the network that starts off with a inductor in parallel with the load. And we're going to adjust that inductor value so that we hit the constant resistance circle down below the real axis here, so that when I add my series inductor, we can rotate up to our match point. And we can see using this style of network here, we've got about 2.9 microhenries and 619 nanohenries. So we can see it was very easy to whip through the 4 possible combinations of our matching network for that particular load, and have got 4 different sets of values of components. Now which one do you choose? Again, it may largely be determined by the component values you have available. In the case of this last matching network, I'm not real crazy about using a very large value inductor here because of the parasitics involved, so I probably wouldn't use that network. I might choose, for example, to use this network here because this is a high-pass network. Or I might choose to use this network here because this is a low-pass network, and that might help to reduce any harmonics that might be coming from my emitter or something like that. So at the end of the day, you have some flexibility in determining which of the matching networks you want to use for your particular situation. And using a really cool program like SimSmith makes it very easy to do this what-if type of analysis and develop a couple of different alternatives for your particular matching network. Again, I will put links to Larry Benko's excellent YouTube channel that has a lot of tutorials on this great program that was written by Ed Harriman, AE6TY. I also put a link to Ed's website as well, where you can download SimSmith for yourself. If you liked the video, give me a thumbs up. If you haven't subscribed already, please do so. And thanks again, as always, for watching.
In today's video, we're going to take a short look at this Whisper Light amateur radio beacon transmitter that I got from the fine folks over at Soda Beams in the UK. The Whisper Light is a low-power beacon transmitter that uses a protocol called Whisper, or WSPR. WSPR stands for Weak Signal Propagation Reporter. The WSPR, or Whisper protocol, was developed by Joe Taylor, K1JT, the Nobel Prize-winning astrophysicist out of Princeton, New Jersey, and utilizes a very slow-speed transmission technique that allows receivers to pick out this signal even if it's as much as 28 dB below the noise floor in a 2.5 kHz reception bandwidth. Now, because the protocol allows for reception of signals well below the noise floor, you can use a very low-power beacon transmitter like this device and be heard literally around the world. Radio amateurs around the world set up reporting stations or beacon receivers to pick up signals from low-power beacon transmitters like this and report their findings online. And you can go online and check any time to actually see where your beacon was heard. It really is quite fascinating to learn that the 200 milliwatt or less signal from this tiny little beacon transmitter can be received literally halfway around the world. Now, in addition to the official Whisper reporting network, purchasing the Whisper Lite also gives you access to a website called DXplorer. That was also put together by Soda Beams. Now, DXplorer pulls data from the official reporting network and displays it to you in a number of very useful ways to help you understand propagation from your station to other parts of the world. You can look at things such as propagation distance as a function of time of day over the course of several hours or days or even weeks. It also allows you to compare performance of, say, one antenna system to another to give you a better idea of which antennas are going to work better into certain parts of the world at certain times of the day. So lots of useful information to help you better understand where your signals can be heard, either from a beacon like this or when you get on the air with your regular HF rigs. Now, this self-contained little beacon transmitter is powered using a USB micro 5-volt power supply, and the only other connector is to the antenna. So before you use this Whisper Light to start sending your signal out to the world, you need to simply program it with a couple of pieces of information: your call sign, your location, and the transmit power that you're going to use. And those are the only three pieces of information that are transmitted by the beacon. This very slow speed transmission protocol takes just under 2 minutes to transmit just those three pieces of information. So to start, let's take a look at what the configuration utility looks like to set up the Whisper Light with your information. Now, there's a small app that's available from Soda Beams that allows you to set the Whisper Light settings. I'm showing the Windows app here, but there's also an app available for Android as well. In this case, I'll connect up to my device, and we can see that I've already got my call sign, my grid locator, the band I want to operate on, and the transmit power kind of indicated here. You can pick the transmit power anywhere from 5 milliwatts to 200 milliwatts. I've been running mine at just 100 milliwatts. You can also use an external amplifier and then indicate that as well. In this case, as I mentioned, you can operate from 20 meters down to 160 meters, as well as the experimental 630 meter band. I've been operating on 20. Once you've set up all of the settings that you want configured in your Whisper Light, you simply hit Save Whisper Settings. That writes this information then to the Whisper Light device. You can then disconnect it from your PC or Android tablet and then simply connect power to it and then connect up your antenna. There's a single button on the front panel that allows you to initiate the transmissions. Now here's some examples of where I've been heard with my transmitter here on the northeast coast of New Jersey. After just a couple of hours, we can see I've collected some reception reports from the continental US as well as in Europe, including Sierra Leone on the west coast of Africa and the Canary Islands. A little bit later on, checked again, I even was heard on Reunion Island, which is off the east coast of Madagascar in the Indian Ocean. And then checking again later on, also found a reception report from the coast of Antarctica. There are lots of resources available online for Whisper. It's actually been around for many years. This is the website for this particular device that I have, the Whisper Lite Classic. And I'll put links to all of these resources and more in the video description down below. Here's the DX Explorer site that I mentioned. It allows me to plot things such as this is transmission distance versus day and time. We can see from this plot that the 20 meter band that we're looking at here, 14 megahertz band, is active really during daytime hours. Right here is about 1900, that's about 2 p.m. East Coast time here. We can kind of see at night the band kind of goes away, during the day it comes back on again. So pretty interesting view there. You can also get a plot of a map that brings up all of the places where my particular station was heard. And this is over the last week. We can see there's the Canary Islands here. Been heard in Spain and other parts of Europe, and even up into Alaska from KL7L. This is the official WhisperNet reporting network. It's just whispernet.org, and you can put in information here about what station call sign you want to look for, and over what time period and over what band, and you can kind of see a map of where that particular station was heard and who it was heard by. Now also on the SodaBeam's website for the product, you'll see a couple of really good reviews, more so than I'm doing here. This Michael G0POT does a fantastic overview of the Whisper Lite and all the software, and there's some additional reviews that are available down here on the bottom of the page as well. And of course there's a wiki page for WSPR for Whisper that has got some additional information here, as well as the official WSJT Whisper homepage. Again, I'll put links for all these down below. But of course, being an engineer with access to some pretty cool test equipment, I wanted to take a quick look at the transmission protocol by capturing and recording a transmission from this beacon and taking a look at it. So let's have a look. Now, I recorded the 110 second long transmission using a Tektronix real-time spectrum analyzer, and here's a couple of views of that transmission. This plot down here is showing me the RF amplitude versus time, and we can see I've got the markers positioned at the beginning and at the end of the transmission, showing it's about 110 seconds long. In capturing that, we can take a look at the spectrum of the signal over time. And that's what this plot shows here. Some people call it a waterfall displot or a spectrogram. We can actually see that it's a frequency shift keyed modulation. The red spectrum line down here is showing me where the spectrum looked like at the location indicated by the active marker. And if I drag this marker through, we can actually see how that RF transmission changes versus time. The Whisper transmitter is essentially a 4 FSK transmitter, meaning that it shifts frequency between one of 4 states. And that can easily be seen in the spectrogram, but even better seen in the frequency versus time plot up here. This plot shows versus time the frequency deviation from center. I've got the center frequency dialed into 10.1402, in this case on the 30 meter band, and we can actually see the frequency deviation versus time. The scale here is plus or minus 5 hertz, so therefore at 10 divisions, each division is just 1 hertz of frequency deviation. And we can actually see now that we've got a 4 FSK transmission that's going on. This is an encoded transmission with forward error correction, so we can't pull out the data directly to see what's actually being sent. But what's contained within this transmission is my call sign, W2AEW, my grid locator, Fox November 20, and the transmit power that I was indicating that I was transmitting, or 100 milliwatts. But pretty amazing that we can take this 4 FSK transmission and send it around the world at just 100 milliwatts and have it be heard thousands and thousands of miles away. Well, I hope you enjoyed this short review of the Whisper Lite Classic Whisper Beacon Transmitter from SodaBeams. If you liked the video, give me a thumbs up. If you haven't subscribed to my channel already, please do so. And definitely check out the Whisper Lite if you're an amateur and want to go understand better the propagation characteristics from your location. Thanks again for watching. Be sure to check all the links and resources in the video notes down below, and we'll see you next time. Thank you.
The 2K3s are still side by side, and if you notice, they're really on the desktop as opposed to being elevated, and that way when I'm sitting there my feet are flat on the floor. My
Whiskey 6 Lima calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
just about finished reconfiguring my station. I've moved a lot of things around. For example, the 3 rotator controls are now in front of me instead of to the side. I've got the watt meters still in front of me. I think it's crucial that you have some kind of device that gives you an indication of output. So if something goes wrong, you've got a warning. Now those 2 watt meters have built-in alarm systems, so if the SWR climbs above a point I've preset, they can do a couple of things. They can alarm, or they can shut off an amplifier or turn off a transceiver. The 2 watt meters below those 2 digital ones are old Drake watt meters. Each one is in the line to a Yagi, so when I'm feeding the 2 Yagis at the same time, I can see that they're both getting the same amount of power. So and since they're analog, it's a lot easier. The switches are for selecting delay lines to one of the 2 Yagis, so I can switch in lengths of coax. For example, in that position, 9 feet of coax is added to just one of the Yagis. That's a homemade antenna tuner, kind of blocked by the microphone, but one knob is the upper Yagi, and the knob on the right is the lower Yagi. So those 2 knobs react with those 2 watt meters. I can adjust the impedance of both the Yagis, so the combination of the 2, I can kind of get it close to 50 ohms. I think it's more like 70 most of the time. Behind the microphone is my favorite antenna tuner that I don't want to give up. It's the MN2000, and so I've kept it all these years. That monitor is on most of the time. That's doing the cluster. The DX cluster. Those 2 boxes are relatively new to me. They're the devices for the new microphone. They provide the voltage and the preamp. The voltage, by the way, is just for the preamp. That's the monster antenna tuner from Nye Viking that matches not quite as wide a range as the MN2000, but it does a lot, and it's rated at 1500 watts RTTY. The 2K3s are still side by side, and if you notice, they're really on the desktop as opposed to being elevated, and that way when I'm sitting there my feet are flat on the floor. My left hand is really at the AF and RF gains. Right hand is on the VFO knob. I'm basically a DXer, so I want that VFO to be close to the tabletop so I'm not reaching for it. If it were up on that shelf, like up there, you wouldn't be tuning the band. I wouldn't be tuning the band all the time because my hand would get tired. So by having it down there, really at rest, my hand is on the VFO and I'm tuning the band. To the right of that is the Elecraft P3, which is their pan adapter. A time when 20 meters is dead, there's just no signals. That's the KPA 500, which is a 500 watt amplifier. On top of it is the KAT 500, which is a 500 watt antenna tuner. That's an old Drake speaker. That screen is connected to an SDR receiver that's connected to the IF of the second K3. So it gives me a picture of the band, and that is really handy. That computer screen does my logging. That happens to be log 40M, and I like that logging program. It works great, and there's a gray line on it. There are two Drake amplifiers, one of them highly modified. Actually, both are pretty much modified, and they are the ones I use most frequently. They're really built to last. The power supplies for both of those, both power supplies are actually homebrew now, and they happen to be underneath the desk. That's my station, and like I said, I moved some things around to accommodate the new boom arm because it attaches to the back of the shelf. I've tried to make it ergonomically a little better for me. I'm not too happy having the monitors as high as they are, but that's at this point the best I can do. If I had my choice, the two amplifiers would also be in front of me so I could monitor the grid current. So there's no perfect station, but it's been a fun project to do it. I learned a lot, had to get some extra things I hadn't planned on, but as a result I've actually made some friends in a couple of places. With respect to the boom arm, if you look at the picture with the white background on the right side of the screen, each of the distances from the elbow in rough numbers is 20 to 24 inches depending on how you measure it. But it's plenty to get, for me, to get over the boxes, that the Drake boxes and the rotator controllers. So I'm real happy with the way this is all worked out, and I think it'll serve me well doing voiceovers also. Anyway, it's I've made a number of tests into Europe and Africa and gotten very good results with respect to the audio. I hope you've enjoyed this video. This has been 2 parts. This is part 2. There may be another one coming up pretty soon covering some of the same territory, but a little bit of a twist, and we'll see how that goes. Anyway, thanks for watching. Please subscribe. If you've enjoyed this video, I know, it's a reach.
Mostly sunny in the morning, then
all right, thanks for watching. It says goodbye.
Whiskey 6 Lima calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Hi, I'm Jim, W6LG. Let's talk about ham radio. Actually, let's talk about AM radio and FM radio. When we evacuated because of the fire down the street, we left a lot behind and were not prepared to leave. The fire was unexpected, but it was in our not in our backyard, but close enough, about a mile and a half away. The things that we didn't take included some kind of AM, FM portable radio. And to that extent, a company contacted me that makes AM, FM portable emergency radios and asked if I'd like to see them and do a review, and I agreed. So this is the little radio that we got. It comes in a box that looks like this. It's kind of a nifty box. It is, there are 2 versions of this radio. I had them send both so that I could try both. I wanted to see which one would work for me. One was attractive because it had shortwave in it. So the choices are, there's an AM FM shortwave, that's model number 1, and model number 2 is AM FM and weather band. And actually, they're called, can't pronounce the name, TIV-DO. TIV-DO, if you're watching, think of another name. But so they have a model number called HR11. It's on Amazon. These came from Amazon. They sell for about $50. But they do a couple of really neat things, and so they're worth looking at and they're worth talking about because they provide some functions that other radios, I'm not aware of other radios doing the same kinds of things. And I'll do some close-ups of them, but it says goodbye. There's a green, seriously, it's a green and a red. One is shortwave and the other is weather band. So they both have AM, they both have FM, and that's where it ends. One does weather band, the other does shortwave. The shortwave is 3 to 23, yeah, 3 to 23 megahertz. I have yet to hear anything with it. There is not an antenna jack on it. It has a short whip. Might be okay if we were in Europe, but we're not. And at this point, I'm liking the radio with a weather band in it. And as a matter of fact, we have a storm coming our way. And I had it on early this morning, and it was warning us about the upcoming storm.
Today is 77, which occurred in 1992, and the record low is 30, which occurred in 1887. Sunrise today is
That's 162.4, which by coincidence, I'm looking at the transmitter. It's just down the road. I'm on Wolf Mountain Lookout. This
simulcast on radio station KEC 57 at 162.55 megahertz from Fairplay in El Dorado County, and on radio station WWF 67
There we go.
at 162.40 megahertz from Wolf Mountain in Nevada County.
and that's us.
Here
So
is an important winter weather message for the following areas in California: Motherlode and West Slope,
That's
northern
us.
Sierra Nevada. What? Snow expected. Plan on difficult travel conditions, including during the morning commute on Monday. Total snow accumulations of 5 to 8 inches, with localized amounts up to 17 inches, are expected.
whoa.
Where? Motherlode and West Slope, northern Sierra Nevada. When? 1 a.m. to 10 p.m. Monday. Additional details. Be prepared for reduced visibilities at times. A winter weather advisory for
Okay.
some means periods of snow will cause primarily travel difficulties. Be prepared for snow-covered roads and limited visibilities, and use caution while driving. The latest road conditions for the state you are calling from can be obtained by calling 511.
So the radio that makes this radio really valuable to me because it has a weather band in it, and everything is push buttons on the front. There's a keypad, volume up, volume down, change frequency, change channels, change bands. On the shortwave one, you can scroll through roughly 1 megahertz jumps from 3 up to 23. What makes these really interesting is what's on the side. And in this case, there's a slide switch on top, and in position number 1 is a flashlight, which is cool. Position number 2 supposedly blinks SOS, but it doesn't. And it says that that's a SOS emergency alert. Well, I don't think so. The flashlight's nice, the emergency alert not so much. Now, this makes a lot of noise. And I think if you were trying to be located, maybe that would help. I hope never to be in that position. It has a menu system on the that chooses a bunch of things, and including Bluetooth. You can connect to your cell phone, and it has a right about there a couple extra holes, and I think those are for the condenser or electret mic, and of course that's the speaker. So you can Bluetooth with your cell phone. Not sure why you would want to do that. I don't know. It has a micro SD slot, so maybe if you put it on Bluetooth, you could record the cell phone. You can put music on here, and it'll shuffle through the music. There's a headphone jack, and that works. I tried it. There's a micro USB connector, and that's really handy because that's where you can charge the phone. There's other choices, however. So you could plug one end of the cable, the USB cable, into this micro USB jack, and the other into your computer and charge the battery. And I have a battery pack that I could plug into there to charge the battery. Another way to charge the battery is this guy. There's a dynamo thing on the back. You turn the knob and it charges the battery, and that's pretty cool. But it gets even better. The other feature that I really like on this thing is it has the, if you will, the other end of that cable would have a connector like this. So you can take the cable that would plug into here, plug the opposite end that would go into your computer into here, push the switch down. The output of the dynamo now comes out this USB jack to charge your cell phone. And I tried it and it works. It takes a bit of cranking for sure. So when you plug your cell phone into here, immediately the battery starts to charge. If you don't want to drain this battery, then you can take the battery out and use the dynamo. And when you're cranking it, the cell phone says it's being charged. When you stop cranking, it is not charging. So that's a neat feature. So it gives you the ability to charge your cell phone, but you'd want to take the USB cable with you, and also to charge the radio. So if you, for example, are in your car, you could plug this into the cigarette lighter, charge it up, and have it ready to go. The battery that's in it is on Amazon.com. It looks like kind of like a camera battery or a cell phone battery. It's thin. The model number of the battery is BL5C. It's 3.7 volts. You charge it with 4.2. Usually when you charge a battery, you over voltage it a bit, so it takes some current. And price on Amazon Prime was I think $8 to $15, depending on which one you bought. So the good news is the battery is replaceable, and some of these things I've had in the past, the battery was not replaceable. There's also a solar cell, solar panel, if you will, up on top. This won't power your house. It really won't power the radio much either. It's very few milliamps. So what it will do is maintain the charge on the battery, but it won't take a battery from dead to fully charged. It simply doesn't have enough output, current output. However, if you park this in the sun and the battery's down just a bit or close to being fully charged, it will maintain that. The difference between where it needs to be and where it is, well, you can turn the dynamo and run it up. The two model numbers for these two radios, and these are roughly 5 by 2.5 by 1 3/4. Round numbers 5 by 2.5 by 2. And at first I thought, well, it's pretty small, but the speaker works okay. And the nice thing about this size is you can stick it in your pocket. So if you had to go somewhere, you could take it with you. It's pocket sized. And again, it has 5 volts out, 5 volts in, headphones, charger, dynamo. solar cell up on top to keep the battery charged up. Has a clock, an alarm clock, and a bunch of things I'd probably never use, to be honest with you. For example, it has its built-in MP3, and it has a way to shuffle through music, so I guess you could stack up music, but that's not going to be my thing. What would be handy for me is it can keep the battery charged. I can use this to charge my cell phone. It does have a built-in flashlight. I'm more likely to use that than the non-SOS SOS. Display is big, easy to read. The radio is about what you, in terms of quality of music and voice, about what you'd expect for a speaker that's maybe 1.25 inches in diameter. It's not great. It's not high fidelity. You can connect it to a separate speaker, but that sort of defeats the purpose of this little radio, and that you can stick it in your pocket when you need to. For example, on the night that we left, it was actually 2 o'clock in the morning. If I had had this, I would have taken it. If we had ended up in a shelter, this might have been our only way to find out what was going on. There's a place for a strap to go through here, like a hand loop strap. Anyway, this model number is the HR11W, W for weather band. This one in green, and that's all it comes in as red, is the HR11S for shortwave. I tried it last night and I couldn't get anything on it. I couldn't get WWV at 10 megahertz. I couldn't get WWV at 5 megahertz. Again, if I were in Europe, maybe that would pay off, where you got megawatt stations down the street broadcasting in the shortwave band. Here, there's really nothing close. Are these worth 50 bucks? Yeah, they are. And if I were having to leave again, or when the power goes out, I'm going to have these handy, especially because of the flashlight and the dynamo. I can charge my cell phone. I can keep that going. Of course, the first thing to go out during a disaster is the cell phone, but at least you have the opportunity to keep the battery charged. That's kind of where we're at with these two radios. They work fine. They sound okay. The audio quality is fair. The menu system is a little bit complicated, and there is a learning curve. They function as advertised. They do what they say they're going to do. FM, AM, shortwave, or weather band, direct tuning, which means you press the buttons, MP3 player, and it says lyrics display. So, okay, so it displays I guess if the MP3 thing has lyrics in it, it displays it. That's new to me. It shuffles. I hope it doesn't walk away on its own. Radio recording, mic recording, alarm clock, sleep timer, ebook, calendar, flashlight, SOS, hand crank solar power, 5-volt USB to charge your phone or other devices. And again, that's one of the really neat features. About half those things that I read off, I'm probably not going to use. Again, the packaging is spectacular. I like that. The company name is TIVDIO, TIVDIO. I don't know why. Thanks for watching. I'm Jim, W6LG. If you've enjoyed this video, I know it's a reach. If you've enjoyed this video, please subscribe. And I've got some other things in the works that really have to do with ham radio. So thanks for watching. See you the next time. 7-3.
Northwest winds 10 to 20 miles an hour with gusts to around 30 miles an hour. Monday night, mostly cloudy until midnight, then becoming partly cloudy. Lows around 42.
That's in the valley.
Northwest winds 15 to 20 miles an hour with gusts to around 30 miles an hour. Tuesday, mostly mostly sunny. Highs around 58. North winds 10 to 15 miles an hour. Gusts up to 25 miles an hour in the morning.
Yeah, it doesn't sound good.
For eastbound travelers, the forecast for Tahoe Basin today, mostly sunny in the morning, then
All right,
becoming
thanks for
partly
watching.
cloudy. Highs.
That says goodbye. And one of the episodes now has gone past 125,000 views, and for that I thank you very much.
Whiskey 6 Lima calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Hi, I'm Jim W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. Going to be doing a series of videos called The Art of the QSO, and by that I mean the way you carry on a contact could be really brief, might be 5973 and that's it, or it could be an hour conversation with someone. That would be, of course, the exception, but there are some things that you might want to think about doing or maybe changing in the way you carry on a contact or if you will, QSO with somebody. And so, based upon my experience since 1963, I'd like to describe to you some of the things that I think help during a contact and some things that you might think about not doing so much. I'm not going to be critical, I'm just making some suggestions. If you use them, great. If you don't, okay. What do I mean by the art of the QSO? It is an art. It's not something that goes on in a vacuum. And a lot of times, from what I hear on the air, a lot of times new guys and even some guys who've been around for a while, in many cases, they're not listening to what the other guy is telling. And I say guy, it could be a man, it could be a woman, I'm just generic guy. Could be what that other person is saying is not being understood. So it comes down to situational awareness. Pay attention to what the other guy is telling you. If he says you're 3 by 3, 3 by 5, could be 3 by 9. I'm missing about a third of what you're saying. You're really strong. Well, how does that happen? Well, there may be interference. There may be atmospheric noise. So the guy's signal strength is great, but the guy that's listening to it is missing words here and there. Could be static crashes, could be any number of things. The guy that you're talking to, or the guy on the other end of the conversation, assuming it's two people, says something to the effect that you're weak. You need to respond to that in a way that helps him out. Could be by saying your name more than once. My name is Jim, Japan, India, Mexico, Jim. So that he has at least 2 shots at getting it. What I hear happening is the guy who's been given the rather weak signal report doesn't seem to comprehend what that means. So he'll say something, well, hi, my name is Jim, I'm in Grass Valley. And he stops talking. He doesn't say over, doesn't give the guy a clue that he's turned it back to him or that he is receiving now. Again, I'm offering the suggestion, and that is that pay attention to the signal report that you get from the other station. It's crucial in how you respond. If the other guy says, oh, you're 5 by 9 plus 10, then maybe you can just carry on this back and forth where you're not exchanging call signs real quickly, you're just kind of saying a sentence or a phrase and the other guy says something in response. And that's fine, provided the other guy tells you that he's hearing you well. So pay attention to the signal report that you get. Try to be aware of the situation that you're in at that time. Is there a lot of interference? Is there a contest going on? For example, last weekend there was a DX contest. If you heard a guy calling CQ, a DX station, and let's say it was PD7DX, and you answer PD7DX, and you give him your name, your location, your signal report, all kinds of information about the weather, your antenna system, all that stuff. That's not good for him if he's in a contest. All he wants to hear from you, basically, is 5 by 9. And while we're on that subject, Many times in contests, the contesting station will just give a report, and the report is frankly meaningless. Everybody may be 5 by 9, and everybody that he talks to may give him a 5 by 9 report. So in this first little episode about the art of the contact, I talked about listening to what the other guy is saying and responding to it. You get a weak signal report, emphasize. If you get a really good signal report, maybe you can go to some kind of quick talk break-in operation. Think about that as you make contact with guys in the other parts of the world. Most of them are really nice people, and if you can carry, and that's true of most guys in ham radio are just neat people, and their stories are interesting. And if you get to dig into it just a little bit with someone, it can be fascinating. I've talked to a guy today for an hour, and I can tell you where he works and what he does, and it turns out we have a mutual friend, Raumut Amidan, AE3RM, who's a musician. It's great fun to talk to him, and again, it goes back to the art of the QSO, paying attention to what's going on, having a good time. Really, it is. It's an enjoyable thing. Please put a note below if you have some suggestion or some idea about the art of the QSO or what you do to make your contacts more enjoyable. Put it down so we can all read it and learn from it. That's it for today. I'm Jim, W6LG for Ham Radio Basics. Thanks for joining me. See you the next time, and please don't yell contact on during a de-expedition.
Whiskey 6 Lima calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. I'm doing a series of episodes or videos about the art of the contact or the art of the QSO, and things that you might think about doing to make your contact with another station more enjoyable. In this one, we're going to talk about where that might not apply and why. You need to really listen to what's going on. Oftentimes, I'll listen for quite a while to someone before I give them a call, if that's possible. By listening, I know what, let's say it's Victor 51 Whiskey Vinan, and he's on the air. He may be working one guy after the other. Vinan may be saying, W1ABC, you're 5 by 9, over. Or, as Vinan likes to do sometimes, he may be expressing an interest in the guy's name and call sign and wants to carry on a conversation with that guy for a while. Even though there might be hundreds of people waiting to talk to Vinan, it's his decision about how much time he spends with someone, and if he decides he wants to engage in lengthy contacts, that's his decision, and you have to honor that. On the other hand, if he's working in rapid fire, then you probably should pay attention to that and respond accordingly. For example, I worked at the expedition today, which is really rare, Spratly Island, and I think I was one of the first W6s, and for sure I was one of the first W6s this morning to work it. They're on an island. I'm not about to do much of anything other than tell them they're 5 by 9 and make sure they got my call sign correct. And that's what happened. I called and called. Finally, he heard part of my call sign, and I kept going until he finally got it all. He had the last letter turned around a bit, and so I explained it to him briefly by doing phonetics, what my call sign was, sent it back to him, and he confirmed my call sign. That's a situation where you're not wanted to engage in a long conversation. It's basically, how fast can you do this? In many cases, how you will respond to the de-expedition, especially if you're on split frequencies, might simply be, you're 5'9" in California, 73. He's got your call sign correct. You might just do that if he's especially strong. If there's some question, then repeat your call sign and say, you don't need to give his call because he knows what it is. So in your split frequency, everybody knows that's calling on that frequency what's going on. Just give your call sign, Whiskey 6 Lima Golf, 5'9" California, over. and he might respond with Whiskey 6 Lima Golf 59. While we're on the subject of signal reports, everybody that guy works is going to be 5x9. He doesn't have time to change anything or do anything different. He's just trying to go as fast as he can. And so you may want to give him an honest signal report, but if he's just working in rapid fire and he's really strong, it's perfectly acceptable just to say you're 5x9 W6LG 73. He's trying to make as many contacts in an hour as he can do, and oftentimes you can facilitate that by keeping your transmissions short. I heard guys answer T-Expeditions and they'll say, yeah, it's weather here is, and I'm using an HT37 and an SX111 from Hallicrafters, and they go on and on and on. Meanwhile, the guy, and this happened with a guy who's right now on a D-Expedition off of Mexico, and the guy went on with a lot of conversation, much to the frustration of the guy who's on the island. He just wants to make contact with that one guy and go on to the next. Anyway, this is episode 2 of what will be a series of episodes about the art of the contact. Plan to do several on topics. They'll be relatively short. Average view time in a video, YouTube video, is about 6 minutes, which means a lot of people hang up immediately. Some watch to the end. So if it's 12 minutes long, on the average they may have watched 6 minutes if half are quitting. I don't think half drop out. So I've tried to keep my YouTube videos, not successfully, I've tried to keep them to about 6 or 7 minutes long. Anyway, think about what's going on during a conversation. Keep in mind situational awareness, what's happening here. And sometimes if you listen before you call, you'll have a clue as to what's going on. And please don't yell contact on during a D-Expedition. All right, and along those lines, a group of guys who meet on a scheduled thing like the Salvation Army net, that is not typical. That is actually atypical, but they have their own pattern or way of doing things. That's fine for that group, but when you get outside that group, it's a different situation. Anyway, got to run. Thanks for watching. See you the next time. I'm Jim Heath, W6LG from Wolf Mountain. If you've enjoyed this, please subscribe. We're at 11,000 subscribers.
In today's video, we're going to take a close look at this Rig Expert AA55 Zoom antenna analyzer, really kind of geared towards the radio amateur who likes operating in HF and the 6 meter frequency bands. As the 55 stands for 55 megahertz, which is the upper frequency range of this analyzer. Rig Expert makes about 10 different models of analyzers that range from a max frequency of 30 megahertz up to 1400 megahertz, or 1.4 gigahertz. Now we should more accurately call this unit a multifunction antenna and cable analyzer, because it really is a lot more than simply an antenna analyzer. Let's go take a look at what I mean by that. I'll do a quick rundown of the various measurements you can make with this AA55 Zoom. We've got the ability to plot the complex impedance versus frequency on a Smith chart, as well as plotting SWR versus frequency on a traditional SWR sweep. Plot just complex impedance versus frequency, the real and reactive components. The SWR meter is a single frequency SWR meter that has a couple of interesting modes in it. All params is a way of looking at everything from the SWR, return loss, complex impedance, etc. at a given frequency. The setup function allows you to go in and set up the language, the units, whether you want it to be imperial units or metric units, set up frequency bands, amateur radio frequency bands to be in the Americas or Europe and other parts of the world. There's a calibrate function that allows you to do a full vector calibration so that you can establish a reference plane either at the instrument's connector or maybe at the end of a piece of coax. So you can actually make measurements referred to the antenna feed point impedance. You can also sweep return loss versus frequency. The multi-SWR function allows you to measure SWR at multiple frequencies. Really handy when you're trying to tune a multi-band antenna and looking for the interaction between tuning one band and seeing its reaction on another band. And there are some additional tools for coax measurements which can be really handy. A stub tuner that allows you to to measure and tune particular lengths for quarter wave and a half wavelength long hunks of coax or stubs of coax. You can also measure the length and velocity factor of coax, and also sweep the cable loss and cable impedance versus frequency. So lots of functionality and actually very easy to use. If you take a look at the icons here on the left hand side, the number is associated with the keypad number. So for the Smith chart, we would just hit number 2, and you see that key number 2 says polar, and that's essentially the Smith chart. If you want to do an SWR chart, you could just hit the number 4, and it says SWR right there. The real and imaginary impedance plot is key number 5, etc. So it's very, very easy to figure out what to do. And also, no matter where you are in a measurement or things like that, the 1 key is generally a help key, and it tells you so right here. If you hit 1, it actually gives you help, and you can scroll through and get help about what these various keys do. So you don't even have to crack the manual open, even though the manual is actually very well written. I've got access to a 20-meter antenna down here in the basement shack, so let me hook that up to the analyzer here, and we'll run through some of the measurements that we can make on this antenna. Let's start off with the very basic SWR chart. So I'll select that by either hitting 4 or arrowing up and down until I select that item and hitting OK. And right now I've got it set to sweep with a center frequency of 27.5 megahertz and a sweep 27.5 on either side, so it's the full range sweep. And if I hit OK, we're sweeping that full range of the antenna. Now what you can see on this sweep of these various colored bands, each of these colored blue bars represent amateur radio bands. In this case, I've got it set for the US and North America amateur radio bands. And we can actually see we've got a dip in the SWR right here on this band, which happens to be the 20-meter band. In fact, the minimum is being shown here at about 14,360, just outside the amateur radio band, about 1.89. Now, any of the plots that are made on the analyzer itself consist of just 100 points. So it's likely that there's a lot more going on in here. Now we can tune the analyzer a number of different ways. Just by hitting the frequency up and down keys, I can shift our measurement frequency, and then the up and down keys here will change the range. So I can zoom in on a particular area, so I can center that again and zoom in again, and then I can go and repeat the measurement and do another 100-point sweep right there. So now I can actually see I've got a little bit better granularity in the 20-meter band, and I can actually see that the minimum is sitting inside the 20-meter band. Just as an example of some of the other functions that are available to you, we'll hit the help key here. So you can do, you can just have it run once and stop by hitting the check like we've been doing. If we hit the function and checkbox, it'll continuously cycle and continue running until we hit the stop key. 0 will show the data at the cursors, and I'll show you what I mean by that. So I've got the cursor sitting right here. If I hit the 0 key, it shows me the SWR, the complex impedance and its phase, the return loss, as well as the complex impedance values that are there. Some other interesting things, let's scroll down to the next page of help. I can change frequency like I was showing you using the frequency keys back and forth, change the range by hitting the range up and down keys. The 3 key will actually allow me to enter frequencies directly a couple of different ways. We'll look at that next. And then the function in 3 key will restore you back to the full sweep of the analyzer again. Oh, and one more page on help here. Hitting the function and the side arrows will jump you to the minimum SWR. So that's really handy. If you see where the minimum is, I could jump to that frequency, then zoom in around that. The function up and down keys will change the scale or vertical scale on the plot. We can also save or load data, so you can actually save traces that you've made on previous measurements, even edit those names. So a lot of functionality that's available here. So if I hit the function and arrow keys, I can jump right to where that minimum is and then re-perform a sweep right there again. If I hit the 3 key, that allows me to go change frequencies directly. I can tell it what center frequency I want and how much I want to sweep around that. Again, hitting the function and 3 key will do the full range, but also hitting the function key allows me to now scroll up and down through the various amateur radio bands. So the 20 meter band is centered at 14.175, and then plus or minus 175 kilohertz around that. The 30 meter band is here. So if I only want to sweep just the 20 meter band, I could just select that, hit OK, and now if I sweep that, now I'm sweeping my antenna just over the 20 meter amateur radio band. If I want to go a little bit wider, I can just open up the scale and then sweep again. And again, if we move the frequency back and forth, essentially our little vertical bar here is where we're making a measurement. So in this case, if I move it over at this particular vertical bar, I can see the SWR is 1.87. If I hit the data key, I can see there's the SWR and all of the other numeric values associated with that particular measurement. Now once we've made a sweep, we can look at it in a number of different formats. For example, if I hit the polar key, or key number 2, that brings me to the Smith chart. And here's the Smith chart now of this particular antenna impedance versus frequency. You can see the little red square here. That's essentially at this frequency here, 14.215. And by hitting the frequency arrow keys, we can move that around and see where we are in the Smith chart at different frequencies. Similarly, we can hit the R, X key, key number 5, and that brings me to the complex or the real and imaginary components of this antenna. If I hit the function and range up and down keys, I can change the scale of the measurement that we're looking at here. Instead of being plus or minus 1,000 ohms, we can knock that down to look at even a finer scale, to look at the real and imaginary components of the complex impedance looking into this coax. The function 4 key will take us from the SWR plot to the return loss plot. Just another representation of essentially impedance match, and essentially we want the return loss to be as high as possible when the SWR is low as possible. So we can actually see we get return loss here of about 15 or so, 14.8 at 14.24 megahertz. So those 4 measurements, the Smith chart, SWR return loss, and complex impedance sweeps, are all kind of the swept measurements that you can make with this antenna analyzer. But there's a number of other measurements we can make which are equally useful. So if we hit the 7 key, or the SWR key, we'll get essentially a SWR meter. And by hitting the OK checkmark key here, we can start the meter reading. That's what the flashing indicator means here. And this shows us our measurement frequency, graphically and numerically showing the SWR as well as showing the return loss. Again, I can hit the frequency keys to move up and down in frequency and see how the SWR changes at different frequencies. And if I use the function and arrow keys, we can move the frequency in larger steps. And of course, hitting the frequency and range key, we can actually dial in a frequency directly if we want to do that. But there's some other interesting capability here. Let's take a look at the help key and see what I'm talking about. So we talked about how to change frequency and set frequency, start and stop the meter. But there's also this function here called SWR to air. This is actually a very interesting feature. Let's look at that right now. The SWR to air feature is really useful when the analyzer is sitting in a spot where you can't see it when you're making adjustments on the antenna. It could be that the analyzer is sitting at the end of a coax, maybe inside your vehicle or inside your Radio Shack, and you're outside making physical adjustments to the antenna, and you can't see what the meter reading is saying. So the SWR to air function basically will transmit a code to tell you what is going on with the SWR as you're making adjustments to your antenna. You set the SWR to air transmit frequency using the function 3 key, and then you start this up. Let me show you what that looks like. Now, I've already set the SWR to air transmit frequency to 144.500 megahertz, so I can hear it on this little handy talkie. So I could stick this thing in my back pocket when I'm making adjustments to the antenna, and then in order to enable this function, I hit the function and checkmark key. So let's actually go do that. So I hit the function and checkmark. You hear one short beep coming out of the radio. So the single beep tells us that we're in the 1 to 1.0 to 1.99 SWR range. As we go higher in SWR, the duration of that beep gets longer. So we can hear now that we're at 1.76, 1.77, 1.8. The length of that beep is longer than it was down here. See, it's a nice short beep now that we're below 1.5 to 1. If we go even higher in frequency, we get into the 2s. It's transmitting 2 beeps. Okay? We get into the 3s and above, it transmits 3 or 4 beeps to tell us that we're way out in SWR. So by listening to these beeps and how many are being transmitted and then the duration of them, we can see how our SWR is doing remotely without having to actually be seeing what the meter is doing. Now another handy feature for the single frequency SWR measurement is the heartbeat display. And that display is entered by hitting the function and up arrow. So if I hit the function up arrow here, we get this heartbeat display. And what this is kind of like a scrolling, almost like a heartbeat monitor, which is why it's called that. So as the SWR changes, this bar graph changes. So let's see if I can adjust frequency up and down. We can actually see the SWR changing because I'm changing frequency. So we can tell by looking at this bar graph very quickly if I'm making adjustments in the right direction, either with an antenna tuner or by actually tuning my antenna physically. So it's another easy way to kind of monitor how the changes that you're making to the antenna or your antenna tuner are affecting the SWR. Now an interesting variation on the single frequency SWR meter is the multi-SWR measurement. We hit the function and 7 key, we look at the multi-SWR measurement. Now this is allowing us to look at SWR measurements on multiple frequencies essentially at the same time. Now we can see in this case I've got a single band antenna, so I've got good SWR on the 20 meter band but very bad SWR on all the others. But if we were looking at a multi-band antenna, like a trap dipole or a multi-band vertical, oftentimes when you're making adjustments on one band, it will affect the other bands slightly. So this will allow you to kind of see the effect on all of the bands as you're making band-specific adjustments on that antenna. Very handy feature. In addition to this numeric mode for the multi-SWR, we'll also see that there's a graph mode that's entered by hitting the function and up key. So we go and hit the function up and hit OK to run. We essentially get a little graph of each one. So instead of actually looking at the numbers, you can actually see what the SWR sweep is doing in each of those particular bands. And of course, you've got the ability, no matter which mode you're in here, to make adjustments to what frequency it is that you're looking at on each of those bands. And finally, the all function, character or key number 8, will allow me to actually get live measurements of SWR, complex impedance and phase, return loss, as well as the complex impedance and the capacitive and inductive components measured kind of live. And again, we can adjust frequency and watch those things change. So as we've seen, this is a very comprehensive analyzer for looking at antenna mismatch and SWR conditions, complex impedance conditions for both swept as well as fixed and multi-frequencies. Very handy analyzer. Let's take a look at some of the other tools for doing some measurements on coax. Next we'll take a look at some of the coax measurement tools that we have. If we hit OK under Tools, the first one is the stub tuner. This tool allows us to determine the half wavelength and quarter wavelength lengths of coax. So if I hit OK on this, it tells me to connect the cable with an open or short at the far end and then press the check mark to start. So I've got this hunk of cable here that's open at the far end, and what it's telling me is that this hunk of cable is a quarter wavelength long at a frequency of 5.24 megahertz, and it's a half wavelength long at 12.6 megahertz. And again, these could be handy values because what we know from coax is that, or transmission lines, is that if you use a half wavelength at a given frequency, the impedance seen at the feed point of the coax is exactly the same as the feed point or the impedance that is present at the far end. The quarter wavelength moves us halfway around the Smith chart, essentially gives us the complex or the inverse of the impedance. So this very easily allows us to determine quarter wave and half wave lengths of coax. The next tool allows us to determine either the length or velocity factor. If you know one, you can determine the other. So in our case here, we know the velocity factor of this coax is 0.66, but I don't know the length, so I'll hit the check mark here to go measure the length. And it actually measures that length of 24.87. In this case it's feet, because I've set the analyzer to use imperial units, because that's what I use here in the US. But you could also set it to measure in meters. Now if you knew the length but you didn't know the velocity factor, you could dial in the length and actually measure the velocity factor. Now the cable loss tool allows us to measure the loss of the coax versus frequency. We start off by leaving the far end open and hit the check mark. It collects a little bit of data. Then it's going to ask us to connect up a short to the far end of the cable, which I'm doing now, and hit the OK key. Oops, hold on, let me get my short on there. Hit the OK key. We'll make some measurements on the short, and then we get the plot of loss versus frequency, and we can move our frequency back and forth to measure loss at any given frequency here. And once we've done that sweep, we can also then switch to the cable impedance tool and hit OK, and we've automatically got the results of that. And that's going to show us our coax impedance versus frequency. Now in this case you're going to see these little disturbances that are going to occur every quarter wavelength, just because of the way the impedance inverts at the quarter wavelength boundaries. But we can see that this coax is a little bit closer to 55 or 60 ohms as opposed to 50 ohms. This is an old piece of dried out coax here, so I'm not too surprised that it's not closer to 50 ohms, but very easy to get those results as well. Let's talk a little bit about the calibrate function. Of course the instrument comes fully calibrated, and the measurement plane or reference point is essentially at the connector on the top of the analyzer, so that the SWR and complex impedance is what's being seen right here. Now if you're trying to design maybe a matching circuit to fit at the base of an antenna, you really want to measure the complex impedance at the antenna feed point, not here. But if you connect up a piece of coax, the impedance seen here is not going to be the same as it is over at the antenna. So you can use a Smith chart and things like that to figure it out, or you can actually use the calibrate function to establish a reference plane at the far end of the coax. Let me show you how you do that. So just as an example, let's do a Smith chart real quick without anything connected here, so we just have an open circuit. And we can see that the results are all right here, essentially at the open circuit location on the Smith chart. Now I've connected up a short, 5 or 6 foot length of coax here, and let's run the Smith chart again. We can actually see that we're rotating essentially around the Smith chart. We went part of the way away from our open circuit point, and then as the frequency ramps up we're going a little bit further. So that now I've got the end of the coax open, so really from the end of the coax all the points should wind up right here, but because the coax transforms the impedance, we're actually moving around the Smith chart. But if I wanted to measure the impedance that appears at the far end of my coax, I need to establish the far end of the coax as the new measurement reference point. That's what we'll do with calibration. Okay, so we'll exit out of the Smith chart and scroll down to select calibrate, and I'll hit check mark to start the calibration, and it's just telling me to prepare my open, load, and short for calibration standards, which I have right here, and we'll get ready to start. And the first thing we do is connect our calibrated open to our end of the coax and hit the check mark to run that portion of the calibration. It's collecting some data. And then we connect the short to the end of the coax here, and that's this guy right here. And then we'll hit the check mark again once I've got that tightened up. And then finally, after this is done, we connect our 50 ohm load to the end of the coax here and grab data there. And once we've done that, we've collected all of the information we need to actually run the calibrations, and we hit function F2 to activate and deactivate the calibration for the measurement. Let's go look at how that affects what we saw on the Smith chart. Now remember, here's our Smith chart result that we got without calibrating to the end of the cable. By hitting the function 2 key, we can actually apply the calibration, And now if we take a look, all of our measurement points are right at the open. If I hit run again, you can just kind of see it all updating right there. So now we've got an open at the end of this length of coax, and we're actually accurately showing that on the Smith chart. So now any load that we connect here could be our antenna. What we're going to see on the Smith chart and all of the other swept measurements are going to be with respect to this location at the end of the cable. Now, as I mentioned at the beginning of the video, all of the swept measurements, whether they're Smith charts or SWR plots or things like that, will give you essentially 100 points across the frequency range that you're sweeping. You do have the option of connecting the analyzer up via a USB port to a PC, and RigExpert has software that allows you to repeat all these same measurements on the PC with up to 1,000 points in the sweep. So that could be a really handy way to get more high resolution data if you need that. Now, about the only thing we really didn't cover so far were some of the setup options. So this is where you can set the language. I've got it set to English. The color palette I've got set to orange, which is really kind of this multicolor thing we've been looking at. But there are two monochrome black and white type of displays. For high contrast is a white background with black text and things like that. Probably would work well outdoors when you've got bright sunlight. But then also you can also do the inverse of that as well. Still a black and white, but with now inverse of the other one. But the multicolor one is pretty pleasant to look at. Battery, this kind of controls when the screen will go dim and when the unit will go back to sleep. I had been running it for the video here mainly on intensive, so the display wouldn't go dim while I was doing any filming here, but under normal operation I usually leave it under optimal. Sound turns on or off as sound associated with the key presses on the membrane keypad. Again, I turned it off because I didn't want it beeping while I was doing the video here. System impedance allows you to select what system impedance you're actually dealing with. In most cases we're going to be dealing with 50 ohms, but you might be dealing with 75 ohm coax and a 75 ohm system. You can actually make all your measurements with respect to 75 ohms, SWR measurements, reference a Smith chart to that, as well as all the way up to 600 ohm ladder line feed, so whatever you're typically using. But we'll use 50 ohms in our particular case. Units again can be imperial or metric. I've got it set to imperial because I'm here in the US. The bands allows you to select the amateur radio bands for different parts of the world to make it easy to select a particular band to do measurements on. And then the default cable velocity factor, in most cases we're using kind of foam dielectric, which is a 0.66 dielectric. Any frequency correction if there's any errors you want to correct. And then you could also reset all the settings back to factory defaults. As I did mention, anytime you make a sweep, you can actually save those sweeps to look at SWR and Smith charts and things like that, at a later date. If you wanted to clear all those saved charts, you can do that right from here as well. I hope you enjoyed this review of this RigExpert AA55 Zoom. I think a really versatile analyzer, very, very easy to use, lots of ways of getting help. The on-screen icons tell you what keys do what. The keys are actually clearly labeled to what they do for both their primary function and their shifted or F function of those keys. The help key will also give you a lot of information about how to set various parameters and do various functions within any of the particular measurements. So again, a real handy analyzer. I don't do a lot of product reviews, but those that I do on products that I really enjoy, and I think this is going to be really a fantastic analyzer for my antenna experiments. So thanks again for watching. If you like what you see, give me a thumbs up. If you haven't subscribed to the channel already, please do so, and go check out the RigExpert line of antenna and cable analyzers. Really a lot of value for the money, I think. Take care, and see you next time. In today's video, we're going to take a look at bipolar transistor switching time. We'll take a look at what it is and go and make some measurements on actual transistors and show you what all the parameters are. And you'll find that bipolar transistor switching time is a little bit of a good, bad, and ugly story. The good part is that it's a pretty simple concept. It's basically looking at how well or how fast a bipolar transistor can be used as a switch. How long does it take to switch between cutoff, when the transistor is off, and essentially no collector current, and saturation, when the device is turned fully on and acting like a switch, and vice versa. So that's a pretty simple definition. The bad, though, is that there's no standard test circuit for testing the switching time, and there are no standard test conditions. The test methods and circuits will all vary by manufacturer and device type. A given manufacturer may have different test circuits and test methods for the different transistors they've got in the catalog, and then the same transistor from different manufacturers can also be tested under different conditions based on the manufacturer. So there's no consistency, so that's kind of bad. So what about the ugly? What do I mean by that? Well, the ugly is a number of things. That not only are there no consistent test methods, but the results that you get are going to depend very highly on the test conditions that you apply. And the results actually consist of 4 different measurements, sometimes even 6 different parameters depending on which manufacturer you look at. The essence of it, though, is that we're going to apply a pulse to the input of the base of a transistor, have some limiting resistor in the base, and then measure essentially how long it takes for the collector voltage to go from VCC when the transistor is off to VCE sat when the transistor is on. So that part's pretty simple. The difference, though, is that the resistors that are used, the value of VCC that is used, and even the high and low values of the pulse that are applied to the input, again, will all vary based on manufacturers. Typically, though, what you'll find is that the VH is going to be high enough to drive the transistor into saturation, which means that the base current is going to be driven to a level that is, about 1/10 or 1/20th of the collector current, sometimes even less than that, or sometimes even greater than that, even closer to the collector current. And VL is going to be sufficient to turn the transistor off. Sometimes that means just bringing VL to 0 volts to essentially just turn off the junction. Sometimes, and more often actually, VL actually goes negative to help sweep stored charge out of the base emitter junction. Sometimes you'll see different drive conditions for the turn on and turn off measurements. So there'll be a separate circuit and a separate set of conditions for the turning on characteristics, and a completely separate circuit and set of conditions for the turn off characteristics. And also you'll see sometimes for the turn off characteristics, you'll see a diode clamp that's used to when turning the transistor off, where this input voltage will be brought very negative, and clamp that voltage at some number of diode drops below some other negative voltage. And what that does is it gives the transistor a very low impedance to allow it to have the stored charge in the transistor swept out very quickly. So you got a lot of variations in the way that the switching time is measured on these transistors. So we'll build a test circuit here shortly to kind of show you how to make some of these measurements, and to see how some of the measurements actually will vary depending on the test conditions. So let's take a look at the switching time definitions. I've got 2 waveforms here. This one on the top is the voltage applied to the base limiting resistor to turn the transistor from off to on and back to off again. And then this curve here is the collector voltage. That represents when the collector current is 0, the voltage is sitting at VCC, and when the transistor is turned on, the voltage is dropped all the way down to the saturation voltage, or VCE sat, of the transistor, and then return back to VCC when the transistor is turned off again. There are 4 main parameters that are used to define the switching time. The delay time, rise time, both associated with the turn on characteristic, and then the storage time and fall time, both associated with the turn off characteristics of the device. Each of these parameters are typically measured from either the 10% or 90% points of these pulses. That's just a typical, common industry standard. However, sometimes you'll see measurements made from the 50% and 50% points of the waveforms as well. And for switching time measurements, oftentimes the rise and fall time of the input waveform are so fast that you'll consider them vertical. There's almost very little difference between the 10% point and the 90% point, or that difference is so small compared to the measurements you're making that it's kind of ignored. So the first parameter is the delay time. When you first apply the input pulse, there is a little bit of a delay before the transistor starts conducting, and that is called the delay time. So it's a measure from the 90% of the input waveform until the current has started to flow, essentially down to this 10% point of the collector current. And that's called the delay time. Then the time it takes the transistor to transition from the 10% point to the 90% point of being fully on, that's called the rise time. Now this might say, why am I calling this rise time when the voltage is actually falling? It's because we're really referring this back to the collector current, where the collector current is 0 and going up to its maximum saturation value here. So it's the rise time of the current, even though it's really the fall time of the collector voltage. Now for the turn off characteristics, when you start to turn this the base off, there's a delay time associated with turning the device off as well, but it's not called delay time, it's called storage time. And typically this is much larger than the delay time for turn on. Because as you may remember from my reverse recovery time video on diodes, when a PN junction is turned on, there's a lot of charge stored in that junction. And in order to turn that junction off, you've got to remove that stored charge. In the case of a saturated transistor, you've got stored charge in the base emitter junction as well as the base collector junction, because the base collector junction is turned on as well. So there's a lot of stored charge to remove before the collector current starts to fall, and then therefore the collector voltage starts to rise. So there's a separate measurement for that storage time. And then once it starts to move, then we have a similar measurement for the rise time. We measure essentially the fall time between the 10 and 90 or 90 and 10% points of the collector current, and measure that as the fall time. So those are the four main parameters that are typically reported on a bipolar transistor data sheet. Now some manufacturers, instead of reporting those four numbers, will just report two numbers, the T on and the T off. So that the T on is essentially a measurement of how long it takes the transistor to turn on. It's really kind of a combination of the delay time plus rise time. And then T off is kind of a combination or sum of the storage time and fall time. But they might be measured at different parameters. And there's even less consistency in terms of how the T on and T off are defined. They might be defined as the time from the 50% point of the input waveform to the 50% point of the collector current, or from the 90% and 90%, or vice versa. But there's very little consistency in how those measurements are made, and some of the data sheets don't even specify the conditions. So just take note that those combination parameters, T on and T off, are just less common, and the definitions are a little bit less consistent than the delay time, rise time, storage time, and fall time, which are the ones that are more common to see. Now, as I mentioned, there's really no consistency among manufacturers of device type as to the test conditions and voltages and things like that. So what I built here is a simple test circuit that we can use to explore the fact that the measured parameters are a function of the various test conditions, and we'll actually go take a look at that. So here's the test circuit we put together. I've got a simple power supply that I can adjust. We'll start off with it at 5 volts, but we'll adjust it up and down a little bit. I've got a 220 ohm resistor in the collector for the device under test, a 1.2 k ohm resistor to limit the base current, and I've got an arbitrary function generator that is generating this waveform. We're going to start off in idle, essentially at ground at 0 volts, so everything is just basically off and clean. And then we'll ramp that voltage up quickly. I've got about a 2.5 nanosecond rise time on my function generator. And the voltage we ramp up to will vary, so we'll see how that will change the parameters of the transistor depending on what we set VH to. And then from there we'll switch down below ground to a negative voltage for VL to sweep the charge out of the transistor and turn it off. Then we can vary that voltage up or down too and see how that affects the measurements. And then we'll return it back to 0 once the transistor is turned off. So here's the test circuit. You may notice that I've got a 50 ohm resistor in here as well. Because the edges are so fast from the function generator, I want to have a good 50 ohm termination to properly terminate the 50 ohm line from the function generator to avoid ringing and reflections occurring at the drive circuit. So I've actually put that down here as two 100 ohm resistors. So that is essentially this 50 ohm load. And then the rest of it is all done in socket, so I could actually use this fixture in the future to test different devices under different conditions by just popping different resistors in. So here's my 1.2 k ohm base limiting resistor, my transistor under test right here, And then this is my collector resistor, power supply coming in here, and I've got some decoupling caps to make sure we're nice and quiet at that point. And I've got 3 probes in here, and I've just made little ground connections here for the probes so I can slide these probes in and out. A very low inductance ground connection, again to minimize ringing and distortion on all of my measurements. So this one is actually probing the collector voltage, and then I've got probes on either side of the base limiting resistor, because then I can do some math in the scope to calculate what the base current is by taking this channel minus that channel divided by this resistor value, and I can actually see then what the base current is. So that's the test circuit that we'll use. Let's go measure some transistors and see how the switching parameters vary as a function of my drive conditions. I'm generating the input waveform using this 2-channel function generator in a kind of interesting way, because I really want to have a waveform that starts at 0, goes to a positive value that I can adjust, then goes to a negative value that I can adjust, and then returns to 0. Now I could load an arbitrary waveform in here and do that, but it doesn't make it easy to adjust those two high and low limits. So what I'm doing is I'm using the first channel to generate a pulse that goes from 0 volts to a positive level that I can adjust right here. And then I'm also using that to trigger the second channel, which is creating a negative pulse. And that negative pulse is going into the add input on the back of the generator and adding into this waveform. And I have it set up so that it's delayed by this pulse width. So I'm essentially creating this one pulse that's triggering a second pulse that's delayed that creates the negative pulse on channel 2, where I can adjust the negative drive level that's occurring after the input pulse. So by adding those two together, I can essentially create this waveform that goes from 0 to an adjustable positive to an adjustable negative and back to 0 again. Okay, so here are my basic waveforms. Channel 2 right here is the input pulse that's being applied from the function generator, measured right here with channel 2. Channel 3 is measuring the base voltage, and then channel 1 right up here at the top, the yellow one, is measuring the collector voltage. And then the red trace down here is that math trace that's taking the difference between the voltage measured on either side of the resistor divided by the resistor value, so that's representative of the base current. Now with a 5 volt supply and a 220 ohm collector resistor, we're going to wind up with 22, 23 milliamps of collector current at saturation, and that's what's represented here. And the good thing is that as we vary VCC, there isn't a huge variation in any of the real measured parameters. You can see the other waveforms are not really changing as I bring VCC up or down on the power supply here. So thankfully there's one parameter that doesn't change the test conditions here, but that's not the case for the others. Now if we adjust the high voltage of the input pulse here, a number of things will vary. Let's take a look now, for example, at the rise time, or how quickly we're dropping the collector voltage. We're measuring that as a automated fall time measurement here on the scope, but this is actually the rise time of the collector. So it's about 22, 23 nanoseconds. And that's with a 3 volt drive to that 1.2K base limiting resistor. If I bring that voltage up, okay, so we're now at 3.5 volts, that fall time, or the TR, rise time, switching time measurement, is now dropped to about 18 or 19 nanoseconds. So with just a half a volt change in that input drive, we've made a pretty big change in the TR switching time measurement. So now we're up at 4 volts and we're down to 15 nanoseconds, essentially TR switching time measurement. Now I've zoomed in on the turn on characteristics so I can now see the delay time and the rise time for the collector current. And again, we're sitting at the 3 volt drive level here. If I increase that to that 3.5 we were looking at before, we can see that the delay time has gotten shorter. The delay time again is how long the transistor stays off before it starts conducting after the pulse comes up. So we can actually see that delay time changes slightly with the input drive level. And we can see how the rise time is getting steeper as we drive it harder and harder. So we can see how those two parameters now vary with how hard we're turning the transistor on. Now how hard we turn the transistor on will also have an influence on the storage time or TS of the switching time measurements. You'll notice as I bring the on voltage higher, the storage time, how long the transistor stays on before it conducts, will grow. So if I bring this up, you can see this point lengthening out and growing. Because we're essentially turning that junction on harder and therefore storing more charge in the transistor, so it takes longer to remove that charge. So the positive drive voltage to turn the transistor on influences both the delay time, rise time, and storage time within the device. Now I've zoomed in on the turn-off characteristics to take a look at that voltage dependence a little more carefully. So here's the input drive turning off, and we can clearly see the storage time from this point here until the collector current starts falling. And as I vary this input drive level, we can see that storage time is a pretty strong function of how hard we're turning that transistor on. The harder we turn it on, the more charge that is in the base emitter and base collector junctions, so the longer it takes that charge to be removed. And we can see that in the lengthening or shrinking of the storage time as a function of the input drive level. We can clearly see the effects of that stored charge when we look at these other waveforms. We're going from our positive turn on to a negative, in this case negative 1 volt turn off characteristic. The base voltage sitting at ground turns on to the 0.6, 0.7 VBE voltage here, but then when we turn the drive off and go to negative 1 volts, the base voltage is still remaining up at the 0.6, 0.7 volt region, but the base current has reversed. We can see the base current is positive and then reverses until that stored charge is pulled out, and then it goes and falls, and then as that starts to fall, then we start to see the fall in the collector current and the subsequent rise in the collector voltage. We saw how the storage time varied pretty strongly as a function of the drive level to turn the transistor on, because of the amount of charge that remains in the junctions that need to be pulled out. But another way to influence that is to adjust how far negative we drive the base to pull current out of the base. So right now this negative portion of the turn off waveform is at minus 1 volt or 1 volt below ground. Now if we increase that to a larger value, we go down to say minus 1.5 volts right here, we can see that storage time has decreased. Let's vary that up and down. You can kind of see again how that storage time is varying as we're adjusting that negative value up or down. Because all we're doing is essentially increasing the amount of reverse base current to yank that charge out of the transistor when we drive that input pulse further negative. How quickly we pull that charge out and how far negative we drive that will also have an influence on the fall time, or TF. We take a look at it as the rise time measurement here of the collector voltage. So with a 1 volt reverse, we're getting 54, 55 nanoseconds. If I go to a 2 volt reverse, we're down to the low 40 nanosecond fall time. So we've got an influence on the storage time and on the fall time, depending on how far negative we drive the turn off waveform. So there's really a complex relationship between how hard we turn the transistor on and how hard we try to turn it off that are going to affect all 4 of these parameters: the delay time, the rise time, the storage time, and the fall time. Now these parameters will vary for different transistor types as well. We've been looking at a 2N4401 transistor here I just happen to have, and even the 2N2222 plastic transistors I have basically behave about the same, with the same delay time, rise and fall, and storage time. But let's take a look at another transistor here. Here's a 2N4124 transistor. You'll notice that the storage time is about the same as the 4401 and the 2222, but the rise and fall time are actually much faster. We're at about 12 nanosecond rise and 22 nanosecond fall, which is about half the rise and fall time of the 2222. So the storage time isn't really an indicator of how fast the transistor will switch in terms of the actual steepness of these edges. You can have the same storage time but still have a much faster transistor in that sense. Here's a 2N3904, about the same storage time, but and rise time about the same as a 2N2222, but the fall time is actually faster. So kind of interesting that you know, a faster rise and fall time doesn't always go hand in hand with different device types. Now this device came out of a bag of kind of house-marked switching transistors. There's no specification on them. I just have a little Ziploc baggie here with these little switching transistors. Don't know really what generic part number it is because it's just got a house marking on it. We can see the rise and fall times are pretty quick, about 18, 19 nanosecond rise, about 25 nanosecond fall, but you'll notice that the storage time is about half of what we were looking at with the generic 2N2222 and 3904 and 4124, etc. Now here's kind of another one of these unmarked general purpose transistors, and we can see this is actually quite slow, about a 60 nanosecond rise, a 100 nanosecond fall, and quite a long storage time here, probably close to 600 nanoseconds or so compared to the 350 that we were seeing with the 2N2222 and about the 170 or 180 nanosecond storage time that we were seeing with that unmarked switching transistor. Now here's a really fast transistor. It's a 2N5837. It's actually an RF transistor. You can see the rise and fall times are about 13 to 15 nanoseconds, and the storage time is quite short, a little less, even less than 100 nanoseconds or so. So you can see that under the same drive conditions, different transistors can have quite different values. So I hope you enjoyed this video about bipolar transistor switching time and learned a little something about the different parameters that are measured and how the parameters can vary with changes in drive conditions. And I guess the lesson here is if you need to pick a transistor to operate at a certain speed in a switching application, you can't always compare apples to apples when you're comparing datasheet specifications, because if the transistors were not tested under the same conditions, those two parameters might not really relate to each other. So the bottom line is to try to find a transistor that's specified close to your particular operating conditions in order to understand what its switching characteristics may be, or to build yourself a little circuit like this and actually characterize the device under the conditions where you're going to use it, so you've got a good understanding of what that switching speed is. And again, thanks again for watching. If you liked the video, give me a thumbs up. If you haven't subscribed already to my channel, please do so, and we'll look for you again next time. Thanks for watching.
Hi, I'm Jim W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. It's 39 degrees in the middle of April, and it's trying to snow here in California, and the sun's not up yet. It's pretty early. Want to discuss setting of miking and ALC and compression on the typical transceiver. Here's the procedure that I use for setting mic gain, and I've used it for many years, and I'd highly recommend you give it a try. I do use a compressor, and I use it all the time, and I recommend that you do that too. But for setting the mic gain, turn the compressor off, put the meter on the transceiver into the ALC position. You should be transmitting into a good antenna with about a 1.5 to 1 or less SWR or a dummy load. Turn the mic gain up with the meter in the ALC position until it indicates about 1/4 scale to 1/2 scale, never beyond 1/2. Speak in a normal voice level. If you tend to yell, then set it with it yelling. I highly recommend you don't yell because it doesn't help any, but speak in a normal volume, voice level. Set the mic gain so the ALC indicates 1/4 to 1/2 scale. On some words it may indicate 0, and that's fine. Turn the compressor on, set it so and switch the meter to the compression position. It may say processor, it may say COMP. Adjust the compression so that the meter indicates 5 dB for a stateside contact and maybe 10 dB for on occasional peaks for DX pileups, that kind of thing. But really never beyond 10 dB. When you start to get to 15 dB of processing, it can sound really off, and I'll demonstrate that in the next video. For the rest of this video, let's look at a couple of instruction books, one from ICOM and one from Yaesu, and see how they recommend that the ALC and compression be adjusted. Not going to talk about equalizers, not going to talk about splatter at this point. We're solely focused in on distorted audio and what we can do to keep that from happening. So let's switch over to the instruction book and see what they say. Okay, so this is the instruction book for the really popular ICOM 7300. It's one of the better instruction manuals. They call this the basic manual, but there's a lot of detail in here. I think one of the neat things about the 7300 is the front screen, the LCD display. There's a ton of information there. See if I can zoom in on that. And for example, it's got a pan adapter. It has its own audio scope for transmit and receive, so you can look at the waveform and the frequency response. In this case, they're looking at signals that are maybe 200 hertz to, I don't know, 2.8 or so. Clock, frequency, transmit indication, mode. That could be notch or the filter. Maybe that's the filter, shifting the filter. Anyway, a ton of stuff, and this instruction book is just so well written. I decided it would be a good one to use to see how they recommend that the ALC be adjusted. So we're going to go to section 310, which is the first step in setting up the mic gain. I should say it's really the first step in setting up the transmit audio. We're going to do two steps. One is setting the ALC, and two, setting the compression. I've gone past where I wanted to get to. Here we are. All right, adjusting the microphone gain. Let me see if I can zoom in on that. And again, this is one of the better instruction manuals. For a basic transceiver, there's just a ton of information in this. Okay, adjusting the microphone gain. Adjust the microphone gain as described below. Set the operating mode to, we're going to say SSB. Push the multi-function display, touch mic gain, and they're showing that in the picture. Transmit, the transmit indicator will light up red. Rotate the multi-control to microphone gain. In the SSB mode, adjust until the meter swings to between 30 and 50% of the ALC scale. And they're saying basically keep these little bars no further than half. My recommendation would be, yeah, no further than half, on an average probably at 25%. On some words, you may have no bars indicating, and that's fine as long as the output is good. Always keep the ALC below 50%. If you run the mic gain up to the point where these bars are lit up all the way over to here, full scale, there's going to be some distortion and clipping of the waveform. It's of the audio waveform, which is going to produce harmonics in the pass band. So there's going to be artifacts and some distortion. You want the ALC to be half scale or less, and for most of the time, much less. Also take note that in this particular situation, the SWR is about 1.4 to 1, and that can affect the ALC reading. So when adjusting the mic gain, the SWR really should be in the neighborhood of preferably 1.5 to 1 or less. So let's go back to what their recommendation is. All right, it says, while speaking into the microphone at your normal voice level, adjust the speech compressor to a level
where the compressor meter indicates 10 to 20 dB. That's a lot of compression. I'd recommend half that. What I do is try to keep it at 5 dB for stateside contacts, and for DX, maybe 10, but never 20. It's going to sound terrible at 20. Here to show you what their meter looks like. This is in the compression position, and here's the compression line: 0 dB, 5 dB, 10 dB, 15, 20, and probably 25 to 30 up here. Keep it to, I know what it says in the book here, but I'm going to recommend that you keep it at 5 dB for stateside contacts. And that means occasionally the 5 will light up, or the bars above 5 will light up. But for the most part, it's in this range. And for some words, there'll be no compression indication. So just keep it in this range. For DX, up to 10. So you'll see these bars light up and ramp up to 10. But man, never over 10. In this case, the compression is about 17 dB, which is huge, and I would suggest that if you do that, unless you know more about this than I do, and maybe you've got one, you can tell me about it. 17 dB is a lot of compression. All right, since we've looked at this, and in this book they talk about, in this instruction book or instruction manual, to set the mic gain and compression. First, turn off the compression, put the meter into the ALC position, talk into the microphone. It recommends 2 to 4 inches from the mic. Talk it up until the ALC, adjust the mic gain until the ALC is roughly 30 to 50% and not above that. Then turn on the compressor. My recommendation is set it for about 5 dB of compression on voice peaks. For DX, you can crank it up to 10, but it gets to be a bit aggressive at that point. And beyond that, it really starts to sound distorted. Okay, so now let's take a look at the ACU 950. And I'm doing this one for a reason. There's a video that's gotten about 50,000 views by a young man. And I think a lot of what he advises operators of this transceiver to do is wrong. The ALC meter in this case is right here. Let me get a little closer. And the young man is holding a pencil and pointing to the ALC meter and recommending that the audio be talked up to a point where it goes to the end, and when he transmits, actually it's out here somewhere. Okay, so here we are in the SSB mode transmission section. It says adjust the microphone amplifier gain, so mic gain, to match the microphone. And man, is that true. Different microphones have different output. Even if it's the same model, it can have dramatically different output. And match your voice level, which is to say speak in a normal voice. When you're transmitting, try to always have the same voice level. You need to kind of figure that out. Yelling into the microphone's not a good idea. It will cause distortion. Here it says press the meter so that it's in the ALC position. Close the PTT switch. Speak into the microphone in a normal voice level. Adjust the mic gain so that the meter is up to half scale deflection. So here's the ALC scale. It is just this highlighted part, not beyond that. And they're recommending that you keep it at 50% on voice peaks. Excellent advice. Again, adjust the mic gain and keep the voice peaks at about 50%. And by the way, that's with the compressor off. That's also into an antenna that has an SWR of, I'd say, 1.5 to 1 or so. Now on the next page, they discuss that, and it's the only manual I've seen where this comes up. And here it is, under advice, ALC meter deflection may be caused by excessive drive power, but also by reflected power detected in the antenna system. If the impedance presented to the transceiver is different from 50 ohms, ALC meter action may be observed that is not related to proper setting of the mic gain. Therefore, we recommend that you make the mic gain knob adjustments into a dummy load or an antenna presenting an impedance very close to 50 ohms. Okay, let's reword this just a bit because it is kind of awkward. The ALC meter may indicate incorrectly if the SWR is greater than 2 to 1, and it will. So what they're saying here is adjust the mic gain into a 50 ohm impedance. Could be a dummy load, could be an antenna that's properly matched. And in fact, they talk about dummy load here, an antenna with an impedance of 50 ohms. And it doesn't say it here, but again, keep the voice at the same level. Try to get into the habit of having some level into the microphone, speaking level into the microphone that is consistent. All right, that's their advice section, and I think that's excellent. Let's go down to set the compressor, and we're not going to talk about setting the parametric equalizer at this point. Enhancing transmit signal quality using the speech processor in the SSB mode. And yes, it can enhance the quality of the signal. The FT950 speech processor is designed to increase talk power by increasing the average power output via a sophisticated compression technique and adjusting the audio quality using the equalizer. We'll not do the second part of that. Here's the equalizers 1, 2, and 3. We're just going to talk about setting the ALC level and mic gain, and setting the compression level. So they start up by going back to page 56 to set the mic gain. Then put the meter into the compression position. Press the processor button repeatedly until the processor part comes on. Press the PTT switch on the microphone and speak into the microphone in a normal voice level. Confirm that the compression level is within 5 to 10 dB. Here's the compression indicator. Here's 10 dB, 20 dB, 30 dB. And I think their advice is very good. 5 dB is good for stateside, local contacts, 10 dB for DX. So, again, speaking in a normal voice level, it should indicate no more than 5 dB. For DX, no more than 10 dB. And if you do that, the transmitted audio is really pretty clean. It improves intelligibility. It brings up the average. You'll get comments from guys who are listening to you telling you sound good. So there you have it. We've looked at 2 instruction manuals, Yaesu and ICOM, both very good. The steps for adjusting the mic gain are simple but often confused. So turn off the compressor, make sure you're transmitting into a dummy load or an antenna that presents an SWR of something like 1.5 to 1. Adjust the mic gain while speaking in a normal voice level using the mic gain control so that the ALC meter indicates about 50% of the ALC zone. That's with the compressor off. Then turn on the compressor, put the meter into the compression or process position, talk it up to about 5 dB by adjusting the compressor control, 10 dB max for DX, and really never more than 10. And if you've got a halfway decent microphone, it's going to sound really good. You'll be more easily understood. We didn't talk about equalizers. I'm a big believer in having a lot of highs and very few lows, but we'll leave that for another time.
So that's my discussion of how to set mic gain. It seems pretty easy. You just turn the mic gain control, but actually it's a little bit more involved. And when you turn on the compressor, it's a whole lot more involved. And when you get to the equalizer, then you can you can make it sound really good or really bad. And there's some examples of that on all the ham bands. Just tune around, especially during contests, or listen to a pilot calling a D-expedition as is going on right now. I'm Jim, W6LG for Ham Radio Basics. If you've enjoyed this, please subscribe. If you have a comment or another way to adjust mic gain, post that below. You may have an idea that's a whole lot better than mine, and I'm willing to give it a try. Thanks for watching. 7-3. See you the next time, and there's going to be several videos along this line. This is just one of several, including setting the mic gain and why the meter doesn't quite indicate where the voice peaks are. We're going to do that using a light bulb. Seriously, a light bulb. All right, 7-3. See you next time. During many contacts, you might say that you're running X number of watts. Well, how do you know that? Let's find out.
Whiskey 6 Lima calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima.
Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. I cabled together a bunch of watt meters and SWR meters. Some sort of slow to indicate, others pretty fast. For example, on the top left corner is the Array Solutions Power Master. Let's see. Not only a watt meter, but it's also an SWR meter. To the right of that is the LP100A from N8LP. Again, another device that indicates power out and the SWR. Below that are 3 Drake watt meters. The one on the left is in an MN2000 antenna tuner, also happens to have an SWR function. And I'm going to use the watt meter to the right, the W4. It's set in the 200 watt scale. Below that on the left is the Elecraft K3. It also has a built-in watt meter and SWR meter. To the right of that is the Elecraft P3. And that one does have a peak reading watt meter and SWR meter. To the right of that is the Elecraft KPA 500. So that's my linear amplifier to generate a couple of hundred watts. It has a built-in power meter, watt meter, and SWR meter. Also has ramping LED scales for tuning. Above that is the KAT 500, which also has a built-in watt meter, but it's rather SWR meter, but it's not all that accurate. Let's do some tests, and this is going to be part 1 of a 2-part video on SWR and watt meters. So let's see what happens when we transmit with 100 watts with a carrier, 100 watts two-tone, 100 watts into a high SWR greater than 3:1, and then we'll do the same thing again at 500 watts and see what the differences are on the meters. Will they all read the same because they're all good meters, or will there be some variation? And to give you a clue as to what I've done behind all of that, I've hooked up lengths of coax. So they are in different locations in the feed line. So let's see what happens. I'm going to start the video now and we'll go from there. Set at about 200 watts. That one says 198, 189, 190, 192, 197, 190 roughly, 210. So they're all, and that one's reading 130. All right, let's go to a single tone. In fact, let's raise the SWR. So I'm going to change out the antenna tuner. Now it's got a 3:1 SWR, 3.5:1. It says 140, 130. It's changing just a bit. That one says 150. That one says 150. That one says 80 watts. And that one says 70 watts. And that's with a fairly high SWR. So why is that? Why is there the big difference? That one says 2 to 1, 2.0 to 1, and that one says 3 to 1. That one says 3.4 to 1. That one says 2.4 to 1. What's the difference? All right, let's do a single tone. With lower power. 3, about 70 watts, 67 watts, close enough. That one says 95 with a 2.4 to 1 SWR. That one says, again, says 2 to 1. The antenna tube is out of the circuit. And that says 80 watts. So what gives? Why is it doing that? And let's ramp up the power a bit. Okay. That one says 150 watts now. That says 123. That one says 111. That one says 175. That one says 170. That one says 140. 3.4, 3.7, 2.5, and 2.2 to 1. So why the big difference? What's going on here? All right, let's go back to matching. Okay, there's about 1.2 to 1, 1.1 to 1. Even better there. All right. So now I've got a pretty good match. 100 watts, 103 watts, so 120 watts, 160 watts, 114 watts, 90 watts. This one says about 95 watts. SWR here is about 1.1 to 1. So with a good match, they pretty much show the same SWR. 1.1 to 1. That one I'm not going to mess with. 1.2 to 1, 1.2 to 1, 1.1 to 1. But what happens when we have a mismatch? Okay, now we've got a huge mismatch. 3.2, 3.4, 71 watts, 66 watts, 95 watts, 2.4 to 1, 2.2 to 1 over here, and 80 watts. So those are reading roughly the same. But the SWR is 3, 3, 2 over here, and 2 over here. And the transceiver is seeing a 1-to-1 SWR. So what's going on here? Why the big change? And this antenna tuner is saying greater than 2 to 1. So let's run up the power just a bit. All right. There's 200 watts. So that says 180. That says 160. Notice the SWR is now reading almost 4 to 1, 2.7 to 1, 257 watts. 257 watts versus 160, 180. This, oh, it got too hot. All right. Let's turn that off. Stressing it out too much. 1, 2, 3. All right, there's 200 watts. 1, 2, 3, 4. That one's indicating about 10 watts, maybe less. That one also about 10 watts, maybe less. The scope down here is indicating 180 or so. Linear is indicating about 180, 190. So let's talk that up just a bit. Okay, 1, 2, 3, 4, 5. We're into the light bulb. 1, 2, 3, 4, 5. All right, we're into the light bulb at about 200 watts. The analog meters are indicating about 10 to maybe 20 watts on peaks, but mostly around 10 watts. The digital meters are indicating 180 to 200 down below, out of range. This one's also showing maybe 20 watts on peaks. So 20 watts here, 200 watts here. So what's the difference? Well, there's a lot. Look at the light bulb and how it glows. The light bulb takes a bit to heat up, and so does the meter. So as you transmit, you can see if I transmit a tone, it's going to get white hot. If I'm just speaking into it, it's sort of orange. So let's do a tone. All right, there we go. Okay, so if I'm the correlation between the light bulb and the meters is a bit of a stretch, but what I'm saying is it takes a while for the bulb to react, and it takes a while for the meters to react. So even though I'm running 200 watts, which is full scale here, this is indicating occasionally 20 watts. That one, it's about the same. It occasionally hits 20. Where in fact, I'm occasionally over 200 watts. So let's increase the output. Okay, that's well, let's see, that's 300 watts. Let's increase the output. And 1, 2, 3, 4, 5. Roughly 500 watts on voice peaks. And the digital meters are having a tough time coping with the change in the load because the SWR is high. Let's put the tuner back in the circuit. All right, there now these meters are indicating 500 watts. Okay, these digital meters are indicating upwards of 500 watts on voice peaks, and that one just said 600. The analog meters are indicating about 60 watts or so. In this case, in this freeze frame, the two digital meters are showing different wattage readings. One has 504, the other one 595. The difference there is just in the way the two devices sample and how quickly they can get something up on the screen. Eventually, they showed the same power within a few watts of each other. The analog meters for complex waveforms typically showed about, in the SSB mode, speaking into the microphone, they were typically showing about 10% of what the peak power probably was. In this freeze frame, the two analog meters are indicating about 50 to 60 watts. The digital meters are indicating 500 to 600 watts. Key down single tone. There were some differences, and I'll explain that in just a bit. The two-tone oscillator, where I keyed it for a long period of time, just as a rule of thumb, they're probably going to indicate about 70% of the peak power. And again, these are heavily damped Drake meters, so they're quite slow, and that's, again, something to keep in mind when you're tuning up or using
let's say you're running a linear amplifier and you're looking at the plate current meter, and the plate current meter is indicating 100 mils. It's likely to be a whole lot greater than 100 mils because the meter is slow, just like those light bulbs and the meters in this picture, to get there. So keep that in mind, that if your plate current meter is showing 100 mils, just for example, it may actually be 500 mils of plate current. And if you've tuned up the amplifier for 400 mils peak plate current, but you're actually peaking 500 mils of peak plate current, what's happening? Well, probably splatter, distortion, and other things. And you may not be aware of it. In your headphones, which are sampling in the transceiver at one of the audio stages, it sounds fine. What's coming out of the coax connector on the back of the linear amplifier may be something very different. All right. If you've enjoyed this video, and I hope you have, please do subscribe. I'm trying to get as many subscribers in this year as I can. If you have a question or a comment, and I think this is one that's going to generate lots of comments, put it below. I think this is kind of a fun one. Everything is fair game here. What do you think was going on? And again, to re-emphasize, I was using different lengths of coax, and these meters are in different places on the feed line. And that makes a big difference in what they see. To that point, I'm going to take the Power Master on the left and connect it to an antenna where I can vary the impedance. And the LP100, I'm going to use its sampling box and put it in different places in the feed line. And we're going to do that in the next video. And we're going to see what the SWR is when they're both in the same place. And what happens when the sample box is, let's say, 50, 60 feet down the line, or 20 feet, or maybe 100 feet. I've got a lot of RG8X I can use to do that. And also, how much loss is there? And how much, at one point, the losses may make the SWR look really good when in fact it's not. All right, that's the next video. Thanks for watching. I'm Jim, W6LG for Ham Radio Basics. See you on the next.
I recently published a number of videos on the Smith chart, including how to design an impedance matching network using the Smith chart. Now, of course, in order to do this, you need to know the complex impedance of the device that you want to match. One problem that many people run into is that some of the very common antenna analyzers that are out there, like this MFJ259B, don't tell you the sign of the reactive component. In other words, they don't tell you whether X is positive or inductive, or if X is negative or capacitive. So how do we determine what that is? One very common method that you'll see written up is to increase the measurement frequency slightly and note what happens to the reactive component. If it increases, then it's inductive or positive. If it decreases as you increase the frequency, then it's capacitive or negative. The problem is this isn't always true. In fact, it does not apply when you're measuring an antenna or a load through a transmission line, because the transmission line will do some transformations on the impedance. So if we can't follow this method when measuring a load through a transmission line, what do we do? Now the answer, of course, is Smith chart to the rescue, using a very simple process. We make 3 measurements of the resistive and reactive components at 3 frequencies in increasing order. And we plot these on the Smith chart twice, once for each sign of X, and then connect each of these sets of 3 points with a curve. So we wind up with 2 curves on the Smith chart. Now the sign that results in an arc that rotates clockwise as the frequency increases is the correct one. This is simply just a very convenient property of the math behind the Smith chart. So let's go run an example and show you how it works. I've got a transmission line and a complex load connected to my analyzer here. So let's make 3 measurements. At 4 megahertz, the resistive part is 49 ohms, and the reactive part is 19 ohms. Let's adjust up to, say, 4.2 megahertz, and we'll record 59 ohms and 26 ohms reactive. And then if we go to 4.4 megahertz, we'll record 64 ohms and 46 ohms reactive. Now, of course, if we followed this method up here, the increasing value of x as frequency increases would tell us that this is an inductive load. Let's go see if that's true. Now, of course, in order to plot these values on the Smith chart, we've got to normalize them to our system impedance of 50 ohms. So that's simply taking each of these values and dividing them by 50. And I just finished completing those. So these are the values that we're going to plot on the Smith chart. We'll start off with a 0.98 and 0.38. So 0.98 in the real axis is going to be really close to this unity circle. And the 0.38, let's start with the positive one, is going to be very close to the 0.4. So our first point is right here. And then to plot the negative version of that, we go down here and plot down here for negative 0.38. So those are our first 2 points. Okay, with the remaining points plotted, we can now kind of connect these up with a curve. And this one curve goes this way. And again, the frequency is increasing in this direction here. Okay, and the other curve goes down in this direction, this way. Okay, and in that case, the frequency is increasing in that direction. Now, if we take a look at these two curves, this is the one that's going in a clockwise direction. This one is rotating in a counterclockwise direction. So that's not the right answer, and this tells us that the x component here is indeed negative, meaning that it is capacitive. We're on the lower half of the Smith chart. And just to be sure we've got it right, let's plot the Smith chart here on my Rig Expert antenna analyzer. And this one will actually show us the curve. And indeed, the Smith chart is showing that our curve is here on the capacitive side, and the x component is indeed capacitive. And there you have it. If your analyzer is like this MFJ259B, and does not give you the sign of the reactive component, you can follow this simple process and determine that for sure by yourself. Now, thanks again for watching. If you like what you see, please give me a thumbs up. If you haven't subscribed to the channel already, please do so, and of course tell your friends. Thanks again for watching, and look forward to all your comments. Thank you. In my previous video, I showed you how to use the Smith chart to determine whether the reactive component of a complex impedance reported by something like an MFJ259 is either inductive or capacitive, or positive or negative, by plotting each polarity of x and then figuring out which one of those curves traces out a clockwise path as the frequency increases. Now, there is one situation where this method could prove a little tricky and just requires a little attention when you're collecting data, and that's when you happen to pick a frequency set of points that crosses the real axis. Maybe it crosses over in this direction like that, in which case the real values of the imaginary component might be positive and negative within the same data set that you collect. So you just have to take a little bit of care when you're taking the measurements. Let me show you what I'm talking about. So I've placed a different load on my analyzer here, and let's take these three frequency range readings at 3.5 megahertz, R is 28, and my reactive component is 6. Let's go up to 3.7. You'll notice right at around 3.7, the x value gets very close to 0, or actually is 0, but really, really close. So let's actually plot that as, say, 35 and 1, and then let's go up to 3.9 megahertz, and 3.9 gives us, let's see, right about there, 49 and 11. Okay, now you'll notice that the x value went from some value down very close to 0 and then back up again. And that's going to be now your indication that you may have changed polarities between one end or the other. Now, this one could be plus or minus, but it's so close to 0 that it probably doesn't matter. So when you're taking your measurements, you want to pay careful attention to, if between some of your values we actually cross through a lower value and then come back up again. That may be your indication that you've changed polarity from one end to the other. Well, I've finished normalizing these values, but the x values that we're going to plot, we're going to try to take into account that polarity change that we suspect is happening. So what we'll do is we'll make the two plots, but say this one with the plus value and this one with minus and minus, and then do this one as a minus value and this guy is a positive and positive. So these two sets of the x value are what we're going to plot on the Smith chart, and then see which one of those gives us the clockwise curve as the frequency increases. Okay, so here are those plotted values. I used a circle symbol for this set here, and that's these points right here, and then we traced that curve out, and then I used a square symbol to plot this set of polarities going that direction. And we can see that this one here is slightly curved in that direction. This is the one that's tracing out the clockwise curve as the frequency is increased. So this set is the right set, and the circle value is not the right set. Let's verify that on the analyzer. Okay, I'm going to sweep the same frequency range, 3.5, 3.7 to 3.9, so that's what this is going to define here. And we'll just plot the Smith chart out, and yes indeed, that's plotting the same curve that we saw in the Smith chart, going from capacitive to inductive. And that's the curve that we verified right here with our plots. Okay, so the bottom line here is when you're taking the measurements of the complex impedance using an analyzer that doesn't give you polarity, take note of what the X value is doing as you're increasing the frequency. And if it looks like it dips down and possibly goes through 0 and then comes back up again, take that into account when you put your plots together, and then you can determine the proper polarity of the reactive component and design your matching network accordingly. Of course, there is the possibility that you're going to collect data on a portion of a curve that comes down to but doesn't cross the real axis. That's not going to occur very often, and you could always take a couple of more measurement points on either side in frequency to kind of see where you are. Anyway, I hope you got something out of this video and the previous one. If you like it, again, give me a thumbs up, and if you haven't subscribed, again, please do so. Thanks again, as always, for watching, and I hope this video helps you out. Take care.
Hi, I'm D6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. This is one of my dummy loads, and that's a bird dummy load that will produce about a 1-to-1 SWR. This one is about 6-to-1 at 10 meters, and I have others I can put in parallel to make the impedance even more weird, off of 50 ohms. The goal is to get to about 6-to-1, and that's not going to be hard. What am I doing? Well, come back in a few seconds and I'll show you. It's going to be kind of fun.
Whiskey 6 Lima calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. This is one of my dummy loads, and it is currently getting a few hundred watts put into it through an antenna tuner because it presents about a 6-to-1 SWR. That's also one of my dummy loads. That's a bird, and it's 1-to-1 and good for 500 watts for 30 minutes, I think. It's oil filled and has some fins. With a fan on it, I think it lasts even longer. What am I doing? Well, in the prior video, I showed that watt meters indicate different things depending on where they are in the feed line. That analog meters indicate 10 to 20% of the peak wattage or the peak voltage or the peak current. They lag way behind due to the mechanical movement of the meter. What I'm going to do in this video is continue on with that just a bit. We'll discuss a little bit about tuning up amplifiers. We're going to again measure the loss through the antenna tuner. Had a lot of emails about the last one where I measured the loss through a tuner, the big one, and a lot of guys thought it was not a fair test because the SWR wasn't high enough. So we're going to do 6-to-1, and if I can get it higher, I will, and we'll run some horsepower and see what happens. Also going to hook up lengths of coax and see what kind of losses are incurred. If I can do it on 6 meters, I will, but I don't think that's going to work. For sure I can do it on 10, and we can measure the loss in the coax on 10 meters. It should be interesting, and again, a little bit controversial, but the takeaway is, what happens when there's a high SWR at the feed point to the antenna? What does it look like in the shack? And is that reading in the shack, the SWR in the shack, the same as the SWR at the antenna? And what happens if I add a few feet of coax? What happens if I add 3 or 4 feet? Let's say quarter wave length is 8 feet. What if I add 4 feet? That would split the difference. What happens if I add another 100 feet? What does that do to the SWR, and what does it do to the line? All right, I'm going to move the cameras around and point them at the watt meters, get the coax hooked up, do a few things, and we'll run a couple of quick tests, and from those tests we'll draw some conclusions. As far as lag effect goes, if you watch how this bulb lights up, it's a pretty good example of how it takes a while for it to heat up. Same thing with the a de-arsenal movement. It takes a few while for the field to energize and for the coil to move. If I say a long word, then it comes up to speed, but it's never going to indicate on a regular de-arsenal movement the PEP power, the peak current, or the peak voltage, unless there's another device added to make it do that. And then when that happens, the accuracy of the meter then depends on how the device is calibrated and what it uses. All right, back in about 5 seconds on the clock. We'll hook up stuff and see what happens. And I think this one's going to be pretty interesting. How much loss is there going to be through the tuner when the mismatch at the feed point is fairly large? I'm Jim, W6LG. Stand by, I'll be right back.
Okay, I've got my light bulb set up as a dummy load, and I'll superimpose on that picture the watt meter that has two couplers set up. Right now you can see the SWR is about 5.5 to 1, 6 to 1. And I'm going to adjust the antenna tuner manually. I need to put the band switch to the right place, so switch it to 10 meters and try again. So I'll tune for minimum SWR, and as I do, you can see the light bulbs light up a little. I'm not driving them with a lot of wattage at this point. Just the K3 into a KPA 500. KPA 500 is throttled back. So there's coupler number 2 is showing the SWR at the light bulbs. So that's with the arrow down, and there's roughly 13 watts and about an almost 6 to 1 SWR, 5.5 to 1. And coupler number 2 with the arrow up is the SWR that the transceiver is seeing because it's going through the antenna tuner. So there, after I tune the feed line, I'll dial it down just a bit. There the SWR is roughly unity, 1.04 to 1, and it's showing 14 watts. Okay, I'm going to increase the drive just a bit to see what happens as I run the power level up. Okay, now I'm at about 40 watts of drive. There's roughly 43 watts with a 6.5 to 1 SWR and about 1.2 at the transceiver. So there's 40 watts, 42 watts at the light bulbs, and using about 46 watts of drive. So about 4 watts. I think it's about 4 watts difference. So roughly 10%. Okay, there's 45, 46 watts at the dummy with 50 watts of drive. 45, 46 watts. So again, about a 10% loss through the antenna tuner with a greater than 6 to 1 SWR, now showing about 6.5 to 1. All right, let's add some coax and see what happens. I'm going to add in 100 feet of coax. Okay, now I'm getting about 23 watts at the light bulbs with 66 watts of drive. So I've got 66 watts going into the coax and about 23 watts coming out the other end. So in round numbers, without a calculator, that's about 2/3 loss. So 17 divided by 48 is 35%. So 65%, or roughly 2/3 of the power, is being lost between the antenna tuner and the coax, and the vast majority of that is being lost because of the coax. So of that 65% loss, maybe 10% is in the tuner, 55% is in the coax. So again, I've gone over the same kind of territory, and the answer comes back the same. Even in the face of a fairly high SWR, the antenna tuner has relatively low losses. We're probably not going to be able to detect a 10% loss in the coax or be able to hear it. But at 55%, yeah, that's 3 dB down, and that's a lot. We also learned that coax connectors contribute very little to the loss of the system. So as we talk about antenna systems, and we include antenna tuners, and I'm not happy with the description antenna tuner, but be that as it may, the most important part of that system in terms of losses is the coax or feed line, and it becomes a huge loss. Lesson learned is spend money on coax. If you put up a nice antenna, you certainly don't want to use lousy coax to that nice antenna, because in the long run, anything you might have gained in the antenna is going to be lost in the coax. Why is RG8X such a lossy coax? It has to do with its diameter and the way it's constructed. There are no specifications, legal specifications, for RG8X. So how it's made, the kind of shield that it has, the kind of dielectric it has, the kind of jacket can vary from manufacturer to manufacturer. But in testing several lengths of RG8X here from different manufacturers, the answer was still the same. A better coax would be RG213. You might want to look at our LMR 400. Now, LMR 400 does have a spec. There are copies of it, but the manufacturer does have a specification. Next size up might be LMR 600, or perhaps a hardline of some kind, which is what I use. Found it at a swap meet, and I haven't looked back. It's great stuff. All right. That's the story, and I'm sticking to it. Coax connectors, not so much loss. Antenna tuner, maybe 10%, depending on a lot of things. Coax losses can be 50% easily, and even more. So look real hard at the coax that you're using. Thanks for watching. If you enjoyed this, or if you think you might have learned a little bit more about antenna tuners and coax connectors, please do subscribe. I'm working on a couple of other videos right now, and I hope to get them finished actually today. This is Jim, W6LG73. Thanks for watching. See you the next time. Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. As a former building inspector and a guy who's looked at a lot of houses that burned, I messed up big time, and I'll show you why in a few seconds. Stand by.
Whiskey 6 Lima Golf calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
During the years I worked for the county, I worked as a real estate appraiser and a building inspector. And also after that, I was on my own as a building inspector and worked for
Allstate Insurance and a couple of other places. Did look at some houses that burned. Usually, it was my experience that the fire was either a brush fire or something really dumb happened inside the house. And by that, I don't mean necessarily that the owner did something to cause it. The one I remember the best was in the living room, there had been a 20-inch fan standing upright. So it's a box fan. And apparently the dog knocked the fan over, the fan blade jammed, the cord got red hot over time, set the carpet on fire, and burned most of the house down. I almost had a similar thing happen, and it's just about as dumb, and it was my mistake. Here's what the plug looks like on my linear amplifiers. There's a plastic cover and 3 screws that appear to be brass, but may not be, and they connect to the prongs. So I turned on the amp, and it sort of faulted, and I was going to do a video on RG8X and put a kilowatt into it with the Drake amps. They're pretty forgiving of high SWR, and they don't throttle back as much. Well, I turned it on, and it sort of faulted, and then I turned it on again, and it faulted again, and it made a buzzing sound. I thought, what the heck? So I turned it off, killed the breaker, unplugged it from the wall. And here's what I found when as I looked at the plug, I could see that the area around one of the prongs was badly burned. Opened the thing up finally. I had to cut the cover away, and found that most of the inside had been charred, and I mean big time. So how did that happen? As near as I can tell, the screw worked loose. I had tinned the wire, and maybe that was a mistake. So the screw worked loose, started to form carbon, and went downhill rapidly from there. Plug was on the cord maybe 2 years. Did I smell it? Nope. Did I see the high voltage dip? Nope. It's got a big power supply. I just luckily pulled the plug after I killed the breaker and saw the black mark around the one prong, and decided that I better take a look inside. So you can see how this is just eaten away, burned away. The original one side by side with, or one that's pristine rather, with as a comparison. I won't use this plug again. It's made overseas, not a good device, and I think I bought it because it was inexpensive. But I was well within the ratings of the plug and didn't exceed its ratings in the amplifier, well within the limits that it says in the instruction book. What happened apparently was I had tinned the wire, cranked the screw down, and it worked this over time because the wire couldn't be crushed because I had tinned it. So it was a huge mistake on my part. All right, that's the story. If you have a comment, please post it below. If you have a suggestion about this, maybe you're a fire inspector or building inspector or electrician or an engineer, I'd love to hear the comments. Yeah, it's my fault, I know. Hi, I'm Jim W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. This is the dipole antenna, and it may not look like any dipole you've ever seen. It really is a dipole. It's center fed and a half wave. Its overall length is about 4.5 feet. Its frequency is about 14 megahertz, 20 meters. Yeah, it really is. And we'll find out why and a couple things that we can learn from this dipole antenna right after this.
Calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Okay, this dipole antenna, even though it's about 4.5 feet long, each one of these tubes is 2 feet, it actually is tuned to 20 meters. Reason for that is, I'm going to turn on my antenna analyzer here. The reason I was able to do that is that there are loading coils in the middle that effectively shorten the length. And by doing that, I can lower the frequency, and I can lower it bunches by doing that. That roughly would be, I think, 80 meters. There's a coil wound on phenolic, and there's a contactor that makes contact with the coil and out to there. So what's the point? Well, if we want to study antennas, sometimes it's easier in a room to show a shortened antenna versus one that would be, let's say, on 20 meters would be 32 feet. And that's one of the reasons why I configured this coil. The other thing is it's adjustable, so I can shift frequency and tune the antenna to show a couple of different things. One thing I'm going to show is the, let me get this going. One of the things that I can show is, and that I want to demonstrate, is the following. The resonant frequency of this antenna and the point where the SWR is the lowest are not the same. And if I got it just right, which I could, the SWR could be 1-to-1 on a certain frequency, like 14,100. But in fact, the resonant frequency of the antenna is 14 megahertz with an SWR of 2-to-1. I'll explain that in just a minute. If that's a new concept, then good, because this is why I built this dipole, and I'll do it using this antenna analyzer. I'm going to sweep the antenna, see where it ends up. Okay, the antenna analyzer is sending out a series of pulses into the antenna, and at each successive pulse it's raising the frequency just slightly. The purple line that's approaching 0 is the resonant frequency of the antenna, and that occurs where there's no reactance, and that was 14,100. The minimum SWR occurred at about 14,200. It says 14,216. So the difference between the resonant frequency of the antenna and where the minimum SWR occurred is about 100 kilohertz. 14,216 versus about 14,100. So when someone says that they've tuned their antenna to resonance using an SWR meter, that may not be the case. The resonant frequency may actually be very different from where the minimum SWR occurred. Okay, the last thing I wanted to show was a graphic indicating where the high current and high voltage locations are on a dipole antenna. High current is at the feed point in the middle of the half-wave dipole. High voltage occurs at the ends. The ends are the high impedance places on the antenna. The low impedance place on the antenna is in the middle of the feed point. Most of the radiation occurs at the high current or middle of the antenna. The least amount of radiation occurs at the ends. So as we look at this antenna, and as the waves arrive, this antenna is switched from one side of the waveform to the other, and in this case it's tuned to 14 megahertz or 14 million times per second. The waves are arriving at that antenna, and it's being switched back and forth very, very rapidly. And again, the high voltage is on the ends, and the high current is in the middle, and most of the radiation occurs in the middle. So that's a dipole antenna as it radiates a signal. We'll hold it at that point for now. So if you have a question, post it below. If you haven't subscribed, please do so. And we'll continue to play with this antenna in upcoming episodes because it's so flexible. I can do a lot of things with it. For example, if I take this off the bracket, rotate the bracket 90 degrees, we'd have what? A vertical dipole. If I take the bottom half off and have just the top half, then I have a quarter wave vertical or ground plane. I need some radials, but it'll work. If I make it a little bit longer, it could be 5/8 wave. So there's a lot to be said for this antenna and using it for demonstration purposes. All right, for now, 73, I'm Jim, W6LG. Thanks for watching. See you the next time.
In today's video, we're going to take a look at the basics of bias tees. These coaxial RF components are used whenever you want to add a source of DC power or even control signals to an RF line. And you might want to do this to power up a transistor, a photodiode, a laser diode, a low noise amplifier, or something like that that might be at the far end of an RF line. Even control remote RF hardware such as an antenna tuner or coaxial switch or even an RF amplifier. You may also want to couple low-speed control and communication signals onto an RF line to maybe communicate with some remote RF hardware that's at the far end of a piece of coax. Or even add a DC offset to a high-speed signal, such as a high-speed serial signal. We'll go into some of these applications in a bit more detail later in the video. But first, let's take a look at what a bias tee is. The circuit for a bias tee is really ideally quite simple. It's simply just two components, a capacitor and an inductor. And the operation is really straightforward. The capacitor will pass the RF through this path here, but block DC, and then the inductor or RF choke will pass the DC signal out this path, but block the RF from going back up to the DC path. So on one side we've got RF, and on the other side we've got RF plus our DC signal. Now the series capacitor in the RF path will determine the low frequency operating limit by simply this formula, 1 over 2 pi RC, where R is the combination of the load impedance and the source impedance. The high frequency limit is, you might say, well, that should just work to extremely high frequencies. The reality is that the inductor properties and the capacitor properties and their parasitics and the layout and materials used are really going to determine the high frequency performance or how high in frequency the RF path can go. Some of the basic specs for a bias tee will include certainly the frequency range and insertion loss and even VSWR of the RF path. And those are going to be determined largely by the capacitor choice, the layout, the inductor parasitics and such. The DC characteristics or DC specifications for how much voltage you can apply and how much current you can supply through the DC path is going to be limited by things like the inductor construction in terms of the size of the wire that's used, saturation of any cores that it might be in the inductor, and also the voltage rating for the capacitor itself. So things can get a little tricky when we start looking at the practical details of a real bias tee's construction. While the schematic of a bias tee is really quite simple, the practical details of designing a wideband bias tee can sometimes be pretty tricky, and it's mainly due to the parasitic properties of the various components. Let's start with the capacitor. Any capacitor has got some parasitic inductance, and at some frequency the capacitor itself will resonate with the parasitic inductance and start to look inductive instead of capacitive. We call that the self-resonant frequency of the capacitor. So the physical design of the capacitor, the choice of materials and things like that will all help to determine the self-resonant frequency of a capacitor. Above that self-resonant frequency, the impedance is going up when we really don't consider it a capacitor anymore. Similarly, the dielectric that's used will determine the loss tangent or dissipation factor for the capacitor, especially how much loss you have in it. So all of these things will make it very difficult to get a very wide frequency range with a simple series capacitor. And while the selection of a capacitor for good wideband RF performance can be tricky, the selection of the inductor is even worse. Inductors have got parasitic capacitance. The larger the inductance value, the more turns we have in the inductor, so the more capacitance it has. That lowers its self-resonant frequency. So we have to have small value inductors for the high frequency components and have to have large value inductors for the low frequency components. There's also loss associated with the inductors. We have to worry about the core saturation, the core material that might be used in the wound inductor. For all these reasons, the inductor is often a series of several inductors in practical applications of a bias tee. But then you might set up other resonances between the parasitic elements of these series inductors and the layout and everything else. So oftentimes there are other parts that are added, resistors or even other components to help DQ these other resonances that might be set up. So the practical reality is that very simple inductor shown in the bias tee schematic is often a complex RLC circuit to give broadband blocking of the RF out of the DC port. and still give good RF performance through the RF path. Let's take a quick look at how these two particular bias Ts are designed. This one is rated from 100 kHz to 4.2 GHz. And if we pull the cover off of this, we can see a little bit of RF absorbing material attached to the lid. And if we look inside, here's our DC blocking cap, our series cap going from the RF to the RF plus DC output. But we could also see 3 separate inductors as well as a dequeuing resistor as part of an RL network here to provide the DC path to give us good broadband DC blocking over that operating frequency range. This next device is rated from 200 kHz to 12 GHz. And let's take a look inside this one here. And a little bit different. Here's my coupling capacitor through the RF path here. But I can see 4 separate inductors that are used in here. This one also has got a pair of decoupling capacitors on the DC input port, so we get a little bit of power supply or DC decoupling to ground right at the input, in addition to the broadband inductor providing the DC path onto the bias T output. Let's take a closer look at how bias Ts are used in some common applications, and we'll even run some experiments. Probably one of the most common uses for a bias T is to power up an LNA or low noise amplifier that might be mounted at an antenna, maybe up a mast or something pretty far away from where the receiver is. The bias T would be applied here so that we can apply a power supply voltage to the center of the coax to run out to the amplifier and power the amplifier up, and then the RF from the amp will just simply pass through the bias T to the receiver. Another application is RF applications or other applications like that for optoelectronic components like laser diodes or photodiodes. Again, to provide the bias to a laser, for example, to get it into its active region, you might bias it up through a current source through the DC path to get the laser ready to go, and then couple your high-speed RF signal onto it. Photodiodes, for example, will operate at very high speeds when they're reverse biased to extend the depletion region, reducing its capacitance. So a DC bias is often applied to a pin diode, like a photodiode, to increase its speed, and then the high-speed optical RF signal can be coupled into the detector, and then coupled through the RF path into a preamp or something like that, or some kind of a receiver. Now here's an example of using the bias T to add a DC offset to a high-speed serial data signal. So here we see on the scope the data signal centered right around 0 volts, right around DC. We're passing it through the bias T right here, and I'm applying a adjustable power supply to this input here, and we're taking a look essentially at the output now on the scope. If I grab the knob for the power supply and started bringing the power supply up, we can see that coming up on the voltmeter, and we can see we're just adding a DC offset to that high-speed serial signal. So we can use this to maybe put that high-speed serial signal within the common mode voltage range of a high-speed serial data receiver or comparator or something like that at the far end. Now here's an interesting application where we're using 2 bias Ts to look at the RF performance of a bipolar junction transistor. I'm using one bias T to turn on and bias the transistor to a desired level and bring in an RF signal and terminating here on a test fixture, and then taking the output through another bias T using the a voltage source to set the collector emitter voltage to a desired level, and then coupling the RF signal into, in this case I'm using an oscilloscope to make the measurement. So here's the basic setup. I actually have my RF signal coming in into a splitter right in here. One output from the splitter is going right out to channel 1 on the scope, which is the yellow trace here on the scope, so I can see the signal that's being applied into the input of the bias T without actually having to probe it. Now, the bias T is going into my little test fixture that I put together here, my AC coupled 50 ohm termination, and a little test socket for the device under test. And then the output is just coupled through a 50 ohm line into a bias T here, and the other output here is coupled into channel 2 on the scope. The DC port on the output bias T is coupled in through these 2 leads right here, going through my DMM to measure collector current. And then the bias T at the input is coupled in through here. And actually inside this heat shrink tubing is a 27 k ohm resistor that allows me to more precisely adjust the base current into the transistor to a desired collector current level. I've got a power supply over here that is being used to set up the collector emitter voltage. Another power supply up on top of the bench that is being used to drive the base current input of the bias T here. Now, one of the reasons for running a test like this might be to evaluate the RF performance or gain bandwidth product of a transistor under different operating conditions. So in order to evaluate that, I did a little trick in the scope here. I've got the scope actually doing a little bit of a math for me, taking the RMS value of the output divided by the RMS value of the input. That's giving me a red trace. A little bit tough to see here, but then I've got a measurement on that. So this measurement right here that shows 10.14, 10.13 right down here, that's actually the gain of the circuit. Remember, the DMM is showing me collector current, so right now that's running at about 10 milliamps. I would say I've got a gain of about 10.1. If I increase the base drive to the transistor, reaching up to the other power supply here, and let's go up to, say, 20 milliamps on this transistor or so, right about there, we can see that the gain at this same 10 megahertz that I'm applying now is a gain of about 14 instead of 10. So we can actually see now what the dependence is on bias conditions for the RF gain of that transistor. And the last application example we're going to take a look at is adding a low-speed DC control signal to an RF path. And the example here is tuning a remote antenna. And here I'm going to actually be using an antenna analyzer feeding into the bias T, and I'll apply a DC voltage that goes to a remote antenna controller that will tune the antenna up or down to adjust its resonant point. It will monitor the behavior of that on the antenna analyzer. The antenna I'm using is this Yaesu ATAS 120, a remotely tuned called a screwdriver antenna, which is located on the other side of my shop right here for convenience. Now, if you look very carefully at it, as I apply power to the antenna, you'll see that top section start to come down. Here we go. So that's tuning the antenna down. And if I apply a different voltage to the antenna, we can see it now tuning back up again. So that's adjusting the length of a loading coil in the antenna. Let's go monitor the effect of that on the antenna analyzer. Okay, so we've got the antenna being swept by the analyzer here. I want to move the resonant point to be within the 20 meter band. So let's move that antenna a little bit. Let's see if we went in the right direction here. Nope, I need to change the power supply to go the other way. And bring it in a little bit, see where we are. Bring it in a little bit more. Oh, we're getting close. A little bit more, and a touch more. Boom, now I've been able to tune that antenna remotely through the bias T and monitor its performance on the analyzer. Well, I hope you enjoyed this look at the basics of bias Ts and now understand a bit more about what bias Ts are, how they're designed, some of the practical limitations of bias Ts, and how they're used. If you like what you see, give me a thumbs up. Pass it along to your friends, and if you haven't subscribed to the channel already, please do so. Thanks again for watching, and we'll see you next time.
Hey everyone, it's Amateur Radio Field Day 2018. This is W2AEW. And we thought we'd put a video together to show you how I set up my field day site. Okay, figure a good apropos site for setting up a field day site is this Guglielmo Marconi Memorial Park in Somerset, New Jersey. It was the site of the East Coast transmitting station from one of Marconi's first transatlantic wireless broadcasting stations. So let's go get set up.
And if you've watched any of my videos, you've probably seen this go bag that I have. This is my field day and field operating amateur radio bag. It has my radio, antennas, battery, and a bunch of other accessories. First thing we got to do is get an antenna up in this tree. The antenna we're putting up is this tri-band end-fed antenna by Par Electronics, and I'm going to use my throw bag and some throwing line to get a line into the tree to tie the antenna to haul it up.
Okay, the antenna is successfully hung in the tree. We follow that line all the way up there and got a pretty good hook on that branch up there. We are now all set to go. We've got the ICOM 703 set up here with the lithium iron phosphate battery ready to go. Looks like we've got about 7 minutes to spare before the official start of ARRL Field Day 2018. Logbook's ready, antenna's up in the air, and we're good to go.
Echo 1, Lima Delta calling CQ Field Day and standing by.
Whiskey 2, Alpha Echo Whiskey, QRP.
Okay, the Whiskey QRP, go ahead.
Yeah, this is Whiskey 2, Alpha Echo Whiskey, QRP. We are 1 Bravo Battery, Northern New Jersey, NNJ, over.
Okay, Whiskey 2, Alpha Echo Whiskey, QRP. I got 1 Bravo Battery and November Juliet, QSL.
QSL, and I copy your 2 Alpha Maritime, Roger?
Roger. Actually, you're doing real well here. Nice and clear and strong, QSL.
QSL, thank you for that. Good luck.
Good luck.
Whiskey 2 Alpha Echo Whiskey, QRP.
The QRP station, say again?
Whiskey 2 Alpha Echo Whiskey, QRP.
Whiskey 2 Alpha Echo Whiskey. Okay, very good. Please copy 1 Alpha Quebec Charlie. 1 Alpha Quebec Charlie, go ahead.
Roger, I copy your 1 Alpha Quebec Charlie. Please copy 1 Bravo Battery, Northern New Jersey, NNJ, over.
Yes, sir. We got that? Okay, we got it all. Battery, fantastic. Good signal, QRP. 7-3.
All right, 7-3, good luck.
Good luck to you, too. Jordan, that's Victor Echo 2 Charlie, United Radio.
Whiskey 1 November Victor Tango.
Whiskey 2 Alpha Echo Whiskey, QRP.
KW2 Alpha Echo Whiskey 2 Alpha Vermont.
Thank you for the 2 Alpha Vermont. Please copy 1 Bravo Battery, Northern New Jersey, NNJ, over.
Thank you. Whiskey 1 November Victor Tango.
Go ahead, QRP station.
Whiskey 2 Alpha Echo Whiskey, QRP.
The QRP station, Alpha something, again, only.
Whiskey 2 Alpha Echo Whiskey, Whiskey 2 Alpha Echo Whiskey, QRP.
The QRP station?
That's Whiskey 2 Alpha Echo Whiskey, Whiskey 2 Alpha Echo Whiskey.
Alright, Whiskey 2 Alpha Echo Whiskey, thanks for sticking in there. Please copy my 3 Alpha Mike India, 3 Alpha Mike India, QSL.
QSL, thank you for 3 Alpha Mike India. You are 1 Bravo Battery, Northern New Jersey, NNJ, Northern New Jersey, over.
Northern New Jersey, thanks for Northern New Jersey. This is Whiskey 8 Lima Radio Charlie, QRZ.
Whiskey 2 Alpha Echo Whiskey, QRP. Whiskey 2 Alpha Echo Whiskey, QRP.
Whiskey 2 Alpha Whiskey something, QRP, go ahead.
This is Whiskey 2 Alpha Echo Whiskey, QRP.
There we go. Whiskey 2 Alpha Echo Whiskey, QRP. Please copy 3 Alpha Victor Tango.
Roger, got you 3 Alpha VT. Please copy 1 Bravo Battery, Northern New Jersey, NNJ, Northern New Jersey.
Thank you for the 1 Bravo, Northern New Jersey, and QRP is making it real good up here in Vermont. 7-3, Whiskey 1 Bravo Delta.
7-3, thanks. Whiskey 2 Alpha Echo Whiskey, QRP.
Okay, QRP station, come again?
This is Whiskey 2 Alpha Echo Whiskey, QRP.
Alright, Whiskey 2, stand by 1 second. We're having a log issue. You are 2 Alpha in Vermont with a great signal. Come again, QRP.
Okay, thank you for the 2 Alpha Vermont. This is Whiskey 2 Alpha Echo Whiskey. We are 1 Bravo Battery, Battery, Northern New Jersey, NNJ, Northern New Jersey.
Very good. We copy 1B. Can I get your call one more time?
Sure, it's Whiskey 2 Alpha Echo Whiskey, Whiskey 2 Alpha Echo Whiskey.
Thank you very much. You are 2 Alpha Vermont and QRZ from November 1 Foxtrot Sierra.
Whiskey 2 Alpha Echo Whiskey, QRP.
Whiskey 2 station, please go ahead.
Here's Whiskey 2 Alpha Echo Whiskey running QRP. We're 1 Bravo Battery, Northern New Jersey, NNJ.
Okay, 1 Bravo, Northern New Jersey from Whiskey 2 Alpha Echo Whiskey. Please copy 5 Alpha Connecticut, over.
I copy your 5 Alpha Connecticut. Great signal into New Jersey. Thanks again.
Hey, you have a great signal for QRP, 73. Good luck.
Well, I hope you enjoy this little taste of Field Day 2018.
It's literally one of hundreds or thousands of activities you can get involved with amateur radio. So if you don't have your license, go get one. It's a lot of fun. And thanks again for watching, and we'll see you all again next time.
Today's video is a recording of a talk that I gave at the Fairlawn Amateur Radio Club earlier this year. The title of the talk is The Basics of Oscilloscopes and Their Use in the Ham Shack. This video is a recording of Part 1, The Basics of Oscilloscopes. It also talks about how to use them and some of the fundamental differences, advantages, and disadvantages between analog and digital oscilloscopes. Be sure to visit some of the links that I'll link down below in the video description that will take you to the Fairlawn Amateur Radio Club website, as well as their YouTube channel, which features additional videos of other speakers that they've had at their club meetings. So sit back and enjoy and learn a little something about oscilloscopes.
Brad, here he is. Okay, back to you. Thank you.
All right, our presenter tonight is Alan Wolke, W2AEW. He's a good friend, and he was willing to come out here and give us a nice demonstration of oscilloscopes in the ham shack. So I'll turn over to him.
So we'll see how I do with the microphone, otherwise I might have to put it down. Can you hear me okay with this?
No.
Bring it up. A little bit better? Is that better? Okay. So anyway, that's me. I'm actually the technical coordinator for the Northern New Jersey section of the Hudson County Division, the ARRL. The way to get a hold of me, just my call sign, W2AEW@ARRL.net. It's an easy way to get a hold of me. I also have a YouTube channel, just youtube.com/mycallsign, and we've got a little over 10 million views on that. So a lot of what I'm going to do here are things that I actually have done videos on in the past. So if you want to go back and review, you can watch the video from tonight, or go back and watch some of the other individual videos of what we've done. So first question before we start off, how many folks have got oscilloscopes in their ham shack? Now be honest, how many of them are sitting under the bench collecting dust? That's what I thought. Because they don't know how to use it, or afraid to use it, might blow it up, not sure what to do, so we're going to try and clear some of that stuff up tonight. Any questions that you have, certainly let me know. That's the reason why we're here, is so you guys can learn. So not just to hear me go through the slides. I apologize right away for any potential spelling errors you might see. I was editing these slides up until last night. Okay, so our agenda tonight, talk about the basics of an analog oscilloscope, what it is, how it works. I'm a firm believer, if you understand how something works, you can always use it better and use it more efficiently. So we'll talk about the display characteristics, the vertical, horizontal, and trigger sections of an analog scope, what they do and how you use them. We'll talk about the basics of a digital oscilloscope and compare and contrast the analog scopes and digital scopes. Talk about when an analog scope might be better for you, or a digital scope might be better, or when it doesn't really matter. Okay. And then we'll talk a little bit about probes, an often misunderstood topic about why we use probes and things like that. So we'll talk about probes, why we use them, how to use them properly. And then we'll get into a couple of applications of using an oscilloscope in a ham shack. We'll do a little TDR demo, actually measure the length of coax using an oscilloscope, pretty cool. Maybe monitor the output of a little RF transmitter I've got here, my little ICOM 703. And even measure some unknown inductors and capacitors. So a couple of interesting little things that we'll do, some potential applications where you can use a scope in your shack. So first off, let's talk about the old cathode ray oscilloscope. And these are the old analog scopes that have got a CRT. The CRT's got radicals that kind of have divisions, both vertically and horizontally. And basically the way this works is they're just like the old TV tubes. We're shooting an electron beam out of the back of the CRT up to the face of the screen. That lights up the phosphor. And then the scope is really just steering that beam around. And the controls on the scope are really just there to steer it around in a way that is useful for us to make measurements. Okay, so we're going to cover each of the various sections in the oscilloscope and how it controls what's going on the screen, so you can really understand what it's doing. So the first thing we'll talk about is the display system. There are controls just for the display. And those controls are things like the intensity and focus. Those are pretty self-explanatory. Obviously, how bright we're going to make the screen or the trace, and how clear and how crisp it is. And these don't automatically focus like your cameras do. You often had to adjust that. And sometimes on the older scopes, as you change the intensity, you had to kind of twiddle the focus as well to kind of make it sharp.
You'll also notice a lot of scopes will have usually a screwdriver control for trace rotation, and that just is changing the tilt of the trace on the scope screen. So we'll say, why don't they just adjust that at the factory? Well, the reason is that sometimes that tilt on the screen, because this beam is steered magnetically, if you move the scope around to a different spot in your room or change its orientation, the Earth's magnetic field can cause that scope, the trace, to tilt one way or the other. Some of the real inexpensive scopes, the trace rotation was literally loosening the CRT and turning it in its housing. Okay, whereas some of the other more, more advanced scopes had actually a trace rotation control. There's another one here called beam find. And what beam find does is, how many of you turned on your scope, you go to use it and there's no trace? Well, is there no trace because I'm not probing the right spot, or I'm not triggering, or the scope is broken, or is it off the screen somewhere? What beam find does is it reduces the deflection voltages, both X and Y, to compress things on the screen so you can kind of see, oh, there's my trace way up there. If I go push the beam find button here on my on this scope, you can see how it just kind of compresses everything down into the center of the screen. So you at least know something's working, the CRT's working, that type of a thing. So it's just a handy thing to say, yeah, my scope's not broken, I just don't have it adjusted right. Okay. But these are all the basic controls for just the display control for the CRT. Okay. Now the next thing we'll talk about is the vertical system. Because one way to think about an oscilloscope is really what it is it's a voltmeter. Right? It's a graphical voltmeter that can plot out voltage versus time. That's really all we're doing. So just like on your voltmeter, you've got settings for AC volts, DC volts, different sensitivity settings for different ranges and things like that. I'm talking about the old analog meters that actually had to switch, not these really easy ones that are just auto ranging for you. Okay, but you actually have controls to do that. So the vertical system on oscilloscope kind of works the same way. We'll talk a little bit about coupling and volts per division, what that means. Now notice the design here. We've basically got an input signal going into a variable attenuator and then into a preamp. Okay. When you adjust the vertical sensitivity on the scope, you're not really adjusting the gain of that front end. Generally, there's a fixed amount of gain essentially from this point forward to drive the scope. What you're adjusting is the level of the signal going into that fixed gain amplifier. Now the reason we do that, it's a lot easier to make a wideband amplifier at a fixed gain and just adjust the amplitude going in, as opposed to developing an amplifier that can be adjusted over 20 to 30 dB and keep it linear over that wide frequency range. Just the same reason we have super heterodyne radios, right? You got everything, all the processing going on in an IF, because you can do everything at a constant IF frequency and just vary what lands in that IF. So we're kind of doing the same thing in a scope, just for gain control and amplitude flatness, regardless of what the vertical setting is. And of course, there are controls for position of where that trace is going to be. And there's a delay line. The reason for that is because we'll trigger the sweep of the scope based on the input signal. And if we just basically kick that sweep off, by the time the signal propagated down to the display, the edge of the signal that triggered it is no longer visible. So what we do is we send that signal through a delay line so that you can actually see the edge that you triggered on. So get a little bit of pre-trigger information to see that. Okay. So we're going to talk about trigger in a little bit. Let's look at some of the other controls on the vertical system. And I've got a couple of pictures here of different scopes, because depending on what scope you have, the controls will look a little different. There's typically a volts per division, and that's really the sensitivity control. And this is the adjustment of that vertical attenuator, saying how many volts does it take to move the beam from one division to the next division on the screen. Okay, so if I'm at 1 volt per division, a 2 volt signal coming in will move me 2 divisions. Okay, pretty simple. All right, so you can actually see the scale. A lot of the scopes is going from 2 millivolts per division up to 5 volts per division here. Many of the scopes will have a variable control, because if you turn the variable control all the way one way until it locks, then you're in kind of that calibrated position. If you rotate it off, you'll change the gain, and you won't have a fixed, predictable volts per division. But there may be reasons why you want to do that. You might want to make the signal on your screen a given size for a particular measurement. Now, actually, we're going to do an example of that later on. Many scopes will have coupling or termination controls or coupling controls So we can, most of the scopes will have a 1 megohm input impedance. That's kind of standard with all scopes. They have a 1 megohm input impedance. But some of the higher bandwidth scopes will also have a switch to give you a 50 ohm termination. It's like we need for RF, and that's the reason why it's there. You also have the ability to take the signal coming in and DC couple it, so that if you put a DC signal on, it's going to shift the trace up or down. And you can also AC couple the signal to remove the DC content and just look at the AC content of the signal. Good for looking at things like ripple on a power supply, for example. We'll do a quick example of that just in a moment. Something else to look at is that all the scopes will list what the scope input impedance is, generally by the connector. And the reason this is important, it says 1 megohm, they all are, but what will vary is the value of capacitance, okay, for that particular scope. Wider bandwidth scopes have a lower shunt capacitance, the slower speed scopes have a larger capacitance. Why do we care? Well, when we start talking about probes, the probes have to be compensated for that capacitance. So when you look for a probe for your scope, you've got to make sure you get one that can cover the input capacitance for the particular scope you want to use it with. So we'll talk about some of these other controls here in a moment, but let's go take a look at this AC and DC coupling example here over on the scope. So if we take a look over at the scope on the display here, I gotta put my glasses on. Sorry. So I've got two signals on here. One is a square wave, and one is actually this channel right here is actually probing the power supply. And if we look right here, that 2 means I've got 2 volts per division. That's on channel 2, and I've also got 2 volts per division on channel 1. So you can see this signal is going, a little over 2 volts, about 2.5 volts of deflection on that little square wave. But then I'm also, if I switch the channel 2 down to ground, you can see there's where ground is on the scope. So I can adjust the position and say there's ground. So if I switch back to DC coupled, I can actually see that's actually the power supply. It's a 5-volt power supply that I'm powering up the circuit with. Now let's say there's some ripple on that. I really can't see it so well. In fact, I'm going to turn off channel 1 to make it clearer. You can see there's a little bit of ripple on that signal. But what if I want to look at that? I'll change the sensitivity of the scope to say 1 volt per division. See, now the signal's up there. I'm starting to see it a little better. I made it more sensitive. But now it's up towards the top of the screen. Let's go down another click. Well, 500 millivolts per division, the trace is up here somewhere, right? So let's take our position control and bring it down. Now I start to see that ripple a little bit better. Let's go one more click down. Now I'm at 200 millivolts a division, but I can't get the signal down anymore. I've run out of range on the position control, okay? So what I can do is switch myself to AC coupling. And now that I'm AC coupled, I can position my signal right here and go even more and more sensitive. And now I can actually see the amount of ripple that's on my power supply here very clearly. So what's interesting is that oftentimes you'll use AC coupling when looking at DC circuits. Okay, so it's not like the voltmeter where you use AC for an AC range or DC for a DC voltage. Here we're just talking about the coupling that we're using to affect a certain measurement. So oftentimes we'll use an AC coupling to look at the small little variations sitting on top of a supply rail. Similarly, we'll often use DC coupling when looking at AC signals. If you're probing through, say, an audio chain in an amplifier, and your audio is getting clipped, if you're AC coupled, you really can't tell why. But if you DC couple through that amplifier, you can see that I'm clipping at the top here because my audio is hitting the supply rail, or it's saturating a transistor. If you're AC coupled, you really can't tell what's going on, but if you're DC coupled, you can see the bias on the transistor as well as the signal. So, like I said, so sometimes we use DC coupling on AC signals and AC coupling on DC signals. So don't think of those as the type of signal you're looking at, but think about what it's doing and how it's coupling the signal into the scope to actually go take a look at. Everybody good on that? Okay. Where did I put my clicker? All right. So vertical modes. Most of these scopes these days have 2 or more channels. How we display those channels are called the vertical modes. So we can turn channel 1 on or off, channel 2 on or off, pretty easy. Then there's these 2 modes called alt and chop. Because even though these scopes have got multiple inputs and multiple channels, I'm going to turn channel 2 back on here again, they're not really 2 separate traces, okay, on the scope. the oscilloscope tube is only producing one trace. When you're in the alt mode, what it's doing is sweeping, channel number 1, but the next time it triggers, it sweeps channel number 2. Then it switches back to 1. It alternates back and forth between 1 and 2. It's doing it fast enough that you can't see it. Now, if you're operating at a very slow sweep speed, and we'll just turn this way down here, I can actually see that, right? So we're sweeping one channel, sweeping the other one. Okay, that's the alt mode. Okay, let's turn this back up here again. Once I start going fast enough, your eye can't see that difference anymore. Okay, the other mode is chop. Now what chop does is during the sweep, it's alternating back and forth between those two signals very quickly. You can't see the change from one to the other, okay? But it's really useful when you go down to these slower sweep speeds, because now both traces will always be there, okay? Now, when you get up to some of the higher sweep speeds, you might actually start to see the chopping happen, and you switch to alt mode. Okay, but that's why the two were there. Because there were a couple of scopes that Tektronix made back in the 60s that were actually true dual beam scopes. Actually, we're sending two traces, but the vast majority of oscilloscopes are single beam scopes. So you've got to do some of these little tricks in order to get more than one trace on the screen. Now these little guys here add and invert. Okay, they're here as well. You see them here as well. What they're used for is, you might say, well, okay, I've got a signal I'm looking at on channel 1, and another signal I'm looking on channel 2. Adding them doesn't really help me. There might be some instances where adding those traces might be a useful measurement. But what's really useful sometimes is to take the difference between the two, because that would allow you to measure the voltage across a component. Right, because with a voltmeter, you can take those two probes, stick them anywhere. Stick them across the resistor, stick them across the transistor, whatever it might be, to see what's going on in that circuit. You can't do that with a scope probe, because a scope probe has got a single input and a ground. You can't clip the ground in any arbitrary place on the circuit because it's ground, okay? So in order to measure the difference, the voltage difference across a component, you basically connect to either side of the component with two probes. You could invert one channel and then add them. So we're adding channel 1 to the inverse of channel 2, which is the same thing as doing channel 1 minus channel 2. And that's why you've got these add and invert controls, okay, to make a differential measurement across a component or something like that in a circuit. Some of the more modern scopes have got available differential probes to do that right with the probe. But in most cases, this is the way we did it in the old days, okay? So let's talk a little bit about the horizontal system. The horizontal system is going to be responsible for moving the sweep across the display, right? Because the vertical system controls sensitivity and everything that's going on vertically. But you got to move that beam across the screen to actually trace out what the waveform is doing. So that's going to basically set the voltage across the horizontal deflection plates to move the trace across. So typically with an analog scope, that involves a sweep generator. We're basically generating a ramp voltage. As that ramp voltage goes up, it's moving the beam from one end of the screen to the other. So there's controls for that in terms of how quickly we're going to move it across, called the sweep speed. Okay, we're going to talk about we'll talk a little bit about trigger hold off, and there's also some modes associated with the horizontal controls, and of course there's a position control here as well. So we've been doing that here on the scope. I just changed my you can see it says seconds per division right here by the knob. And we speed it up, we can actually start zooming in, actually see the ringing that's going on right on top of that power supply voltage. And all we're doing is moving that beam faster, so we're stretching that waveform out so you can see those details. Now, when it comes to talking about sweep, there's really kind of two types of analog scopes. And I mentioned this just a little kind of historically, because if you go back to the really old scopes from 40s and 50s and 60s, especially those that you found in like TV shops and things like that, these inexpensive scopes you can get that were called service scopes, or even like an old SM220 station monitor, you got one of those Kenwood station monitors, they're what are called recurrent sweep scopes. Now what that means is the sweep voltage is basically a sawtooth oscillator that is continuously running. It's always just sweeping across. And you can usually tell a recurrent sweep scope because you've got like a frequency vernier as well as a range selector. You can say, I want to sweep at 1 kilohertz, and I can adjust the vernier of it to kind of adjust that sweep speed. It's not calibrated, and it's very difficult to trigger with, We'll talk about trigger in a moment. I would say these days, there's so many lab-grade, engineering-grade oscilloscopes that are available. There's no excuse for you to be using a recurrent sweep scope anymore. Okay, you can pick up a real scope, I should say, a real analog scope, pretty inexpensive these days. So a trigger sweep scope, the sweep will kick off and move that beam across the screen in response to some trigger. So now what that means is we can synchronize our waveforms to the sweep. Whereas if we just had a free-running oscillator here, the waveforms aren't going to be stable on the screen. Let's talk a little about what I mean by that. So, and really when we talk about that, we'll talk about triggering. Triggering is saying, when am I going to sweep that signal across? Okay, when am I going to start that sweep? And ideally, you want to start that at the same location in time on a particular waveform. So each sweep that you get is going to overlay that waveform right on top of the last sweep that you had. And these old analog CRTs need to overwrite a waveform, many times so you can actually visually see it. So it lights up enough of the phosphor for you to actually see the trace on the screen. Now these old recurrent sweep scopes didn't have a trigger because it's just a free-running oscillator. They had what was called a sync control, and what all that did was it took a piece of the input signal and jammed it into the oscillator to try to injection lock that horizontal oscillator to some component in your signal. And if you tweaked around with the vernier control and horizontal, and you just tweaked around with the sync amplitude, you can kind of get the waveform to be stable. But nothing was calibrated. It's just a pain in the neck. So I say, yuck, it really is not what you want to use. Okay, a triggered sweep scope, we basically kick off that sweep each time the signal crosses a trigger event that we're going to talk about here in a moment. So this is really what you want to be using these days, is anything with a triggered sweep scope. If you're walking around a Hamfest and you're looking at a scope, how do I know the difference? Like I said, the recurrent sweep scopes will have that horizontal vernier frequency control. They'll also have like a sync selector and sync amplitude controls. You're not going to see that on the triggered sweep scopes. The triggered scopes will have something that says triggering and have some trigger controls we'll talk about here in a moment. So again, look for a triggered sweep scope. A lot more useful and a lot easier to use and to get some useful measurements out of. So let's talk about the trigger source and trigger mode. So the trigger source is what signal do we want to look at to synchronize my sweep that's going across? Most times we're looking at the signal we're applying. We're going to take that internal signal that's sitting in the scope that we've coupled in through a probe and take a piece of that and a characteristic of that and trigger on that. Maybe when the voltage crosses a certain threshold or something like that. Okay, so that's what's called the internal trigger. Okay, we're just going to take a signal that's already coming through the vertical section, take a piece of it, and use that to develop our trigger to scoop that trace across. There's also an external trigger on many scopes. There'll be another input. You could use another input on the scope and bring a trigger signal into that, and then have other traces be displayed with respect to that particular trigger signal. That's what external trigger is. There's also a line trigger, and that basically triggers on the line voltage, 60 hertz. So if you're looking at something that is going to be, like you're looking at power supply hum or something like that, that's going to be synchronous to the 60 hertz line voltage, and it's a very small voltage, it might be tough to trigger on, switch to line trigger, and then you can actually go look at it. Another useful place for line trigger is if you're looking at a signal that is not necessarily something you want to trigger on, but you just want to look at wave shapes. A good example of that is when we're looking at the output of a transmitter, looking at your single sideband modulated envelope of your RF signal. You don't necessarily have to trigger on that, you just kind of want to see what that shape looks like. But setting it to line trigger, it's going to trigger at 60 hertz, which is going to eliminate any kind of flicker or anything like that, and you can kind of see your signal, not have to worry about trigger settings at all. There's also this concept of trigger mode. Okay. Now trigger mode, we're going to talk about here in a moment. Most of the scopes will have an auto trigger mode, and it's not what you think. We'll talk about that next slide. Okay. Normal trigger mode is basically what we've been describing. When the input signal satisfies the trigger criteria, we send that trace across. If the trigger conditions aren't met, we don't send a trace at all. That's what normal trigger means. Single would just send a single trace and then wait for another trigger. It won't continually update. Not really useful on the analog scopes unless you have a camera sitting in front of them. Okay? That's why most of these old scopes have got a little groove right here along the top. There are actually scope cameras that clipped onto that, little Polaroid film packs in the back. And I remember when I got out of school, one of your rites of passage when you got your first job was someone came running up to you with a scope camera, stuck it in your face and took your picture. And it was sitting up, pasted up on the wall in the lab, all curly black and white Polaroid picture, your nose about all the scope camera captured. That's what they did. And then some of the scopes that you'd find in a TV shop also had TV trigger modes to trigger on the horizontal vertical frames in an analog TV video signal. And just like we had coupling controls for the vertical path, we also can change the coupling going into the trigger circuit. Remove the DC offset by using AC coupling. There's some other things like high frequency reject, noise reject, DC coupling, things like that are available. I'll give you a little bit of a hint. For most Tektronix scopes, old analog scopes, a lot of these trigger controls are all kind of next to each other. They're all typically like these big lever switches. If you want to just get the scope running and have something displayed, take all those lever switches and bring them all to the top. Okay, that's the kind of trigger. Put you in auto trigger, DC coupled, ready to go, it starts triggering, and you're good to go. So it's a good starting point. These old scopes don't have a reset button. You can't reboot them. That's kind of the auto set, if you will. So what is auto trigger? As I mentioned, it's not what you think. It doesn't automatically set up your trigger settings for you. Okay? But what it does do, it's a usability aid. Because as I mentioned, if the scope is sitting there waiting for a trigger, it's not setting the sweep across, so you don't see anything on the screen. Is it broken? If I don't have the scope adjusted right, what's going on? You can't tell, right? What auto trigger does is it's waiting for a trigger. If the trigger event doesn't happen in 50 to 100 milliseconds, depends on the scope, then the scope basically self-triggers. It sends a trace anyway. And what this does is it puts a trace on the screen, okay, even if the trigger settings aren't satisfied. So you can at least see what's going on. Okay, you set up a trigger, now I see a signal, but it's way over here, it's wiggling around, or something's going on. At least you know something's happening. If we look at this guy, this scope is triggered right now. But if I misadjust my trigger settings, I see some traces on the screen. I'm not synchronized. Where if I switch this to normal trigger, I don't see anything. Okay, because the normal trigger is waiting for this trigger event to be satisfied. And if I don't have it adjusted right, and I got a blank screen, I don't know why. Okay, the auto trigger will actually send a trigger internally so I can see what's going on. And then say, oh, well, I don't have something going on here, let me play with my trigger settings. Oh, there we go, now I've got my signal back. So that's what auto trigger is, and now you know what it is. It's not, it doesn't automatically set things up for you. So some of the more important controls for triggering are level and slope. Most times, all we're looking for is we're looking at some kind of a waveform on the screen. It could be a sine wave, it could be an audio signal, it could be a square wave, or we're looking at a clock and a microprocessor or data or something like that. So we want to trigger on usually when that voltage crosses through some threshold, either rising up through it or falling down through it. Okay? So whether we're going to trigger on a rising edge of a signal or a falling edge of a signal is determined by the trigger slope. Okay? So here's an example where the trigger slope is up, so we're going to trigger on the rising edge, so you can see we're starting that trace, that signal's on its way up. Okay? Here we're triggering on the negative slope, so the signal's on its way down, crossing through some threshold. And then that threshold is adjustable through the level control. So with it, I got adjusted a little bit positive here, so we can see we're starting kind of a little bit above the baseline, where this knob is turned a little bit toward the negative, so we're starting the waveform down here. So that's where our threshold is. So if the threshold is here, I'm going to trigger on a positive slope coming through that threshold. That's why the signal's starting right there. Okay? In fact, a good way to look at this here, let me see. Let's take this signal here. I'm going to put this scope up on the display here. This is something easy for me to show you. Let's bring our trigger level down. Point. Okay, so we can actually see, I got just a sine wave here, right? If I adjust my trigger level, you can see that it actually draws a level on there. See, as I adjust that level, where that trace is starting is now is where I'm crossing that. And I'm actually triggering on, so my trigger menu here, I'm triggering on the rising edge. Okay, you see the rising edge right? Oh, I'm sorry. Tell me when this thing doesn't come up here. Okay, so here I've got my sine wave here. So I'm triggering on a rising edge, and there's my level, so you can see where the waveform is starting. And if I adjust that level up or down, you can actually see how that waveform is starting at a different spot, because I'm crossing at a different spot. If I switch my slope to the negative, now I'm starting when that signal's coming down through that threshold. Okay, so it's very easy to kind of see how. So those are the two most common controls. Those are the two most common controls you're going to use for triggering are level and slope. Oftentimes you don't really care about the slope, you just want to get the level right. Okay. And again, auto trigger will kind of send a trigger if you don't have these things adjusted right, so you see what's going on the screen to give you some aid in terms of setting it right, setting it up for you. Everybody good so far? No snoring? That's good? Okay. All right, so let's talk a little bit about digital scopes, okay, and what some of the differences are. Remember, the analog scopes where all the controls in the scope are controlling the deflection voltages for vertical and horizontal to steer this beam around that's being squirted out from the inside of the end of the scope CRT. That beam is being squirted out and then being steered vertically and horizontally. Okay, so all of our controls are geared towards that. And since that's kind of our paradigm and how we use scopes, we built analog scopes to have similar controls, or we built digital scopes to have similar controls, but obviously operates very differently. A digital scope essentially is taking a signal that is coming in through the probe and taking pictures of it, sampling it, okay, and storing those sample voltages into memory. Okay, and then once we got all those samples in memory, we're just essentially using a computer or some kind of a processor to take those numbers and display a waveform. So we're not directly affecting the position of a beam on a CRT. We're basically building an array of data and displaying that data for you in a way that, oh, it looks like the old analog scope, okay? But that's really what's going on. So there's still the front end is very similar. In fact, let's talk a little bit about it. The front end is still very similar. You've got the adjustable input attenuator, some kind of a preamp that's going into now an analog to digital converter. Okay, so that analog to digital converter, just like a voltmeter, is sampling that waveform and essentially creating voltage samples that then get processed, and we're sampling all the time. So now the trigger has a little bit of a different function. Whereas the trigger on an analog scope basically said, this is when I want to kick the stream off. The trigger on a digital scope kind of looks like it's doing the same thing, but really what it's doing is deciding what do I want to put in memory. So I'm looking at all these samples, and if I got some samples that met the threshold or the trigger criteria I've set up, take those samples around that trigger and save those and display those. Because we're sampling all the time, okay? It's just what do we want to display to you? So the trigger is now a little bit different because we are triggering all the time, we got the ability of displaying what was going on before the trigger happened. So it's kind of like getting some premonition of what led up to that trigger event. Because I'm sampling all the time, and if I told it I want the trigger to be right in the middle of the screen, everything to the left occurred before the trigger was done. Okay? But since we're storing all this stuff kind of in a circular buffer, we can say, okay, I'm storing all this data. Oh, and there I triggered this, grab some more, and display all that. So that's how you get the pre-trigger information. So again, you've got the same basic front end, feeding an ADC. We're processing that data with the trigger, so we can then take the waveform that we're going to capture, stick it in memory, do some more processing on it to display it to you. And do all this fast enough so it looks like an analog scope. Okay? The digital scopes of 20 or 30 years ago didn't do things very quickly, very well. Modern digital scopes are pretty good at replicating the responsiveness and capability of the analog scopes from that standpoint. Something I want to talk about is something called sample rate. How quickly are we going to take those snapshots? That's going to determine how fast of the signal we can look at and some other properties we'll talk about here in a moment. But all the processing is now done on that sampled signal. Okay, everybody digital scope experts now? So let's talk about sample rate and memory depth. These can be confusing topics. Because if you think about it, I'm going to have a certain amount of time that is represented across the screen. And how many samples do I want to put across that time? That's the sample rate. How many samples, how many times am I going to take a picture of this waveform as it's varying? Okay, so that kind of determines our sample rate, or essentially our resolution. How much time do I have from one sample point to the next? Now, a lot of what will drive that is memory. Right? Ideally, I'd want to sample this thing millions of times across the screen so that I get a very faithful representation of that signal. But if I do that, that waveform is going to encompass many, many, many samples. So I got to have a lot of memory to do that. So as you can imagine, waveform memory, sample rate, and the acquisition length or horizontal settings are all related. In fact, it's a very simple relationship. The amount of memory we need to display a waveform is a function of the sample rate and the acquisition length. And remember, on the analog scope, how much time we display across the screen is a function of that time per division control. If I set it to millisecond per division, I've got 10 divisions, the screen would show me 10 milliseconds worth of data. We have the same concept here, except on digital scopes we call it horizontal scale. When I'm demonstrating a digital scope to people, I still call it sweep speed, even though there's no sweep in the digital scopes, okay? But it's still the same concept. It's still so many, nanoseconds, microseconds, picoseconds, whatever, per division. But at the end of the day, it really is an acquisition length of what we're putting in memory, okay? So if you want to have a very high resolution for a given horizontal scale, we need to sample very, very quickly. Okay. The other thing we got to worry about with sampling is to ensure that we oversample the signal enough to not alias the signal. Who's familiar with what aliasing is? Okay. If you ever watched an old Western on TV, you see the guys, the horses pulling a carriage, and sometimes it looks like the wagon wheels are turning the wrong way, right? That's aliasing. We'll talk about that here in a moment, okay? Now, oftentimes, the scopes will have a lot more memory than they can actually display. Most of these displays are just LCD displays these days, right? So what kind of resolution you can get on an LCD display? 1024 by 768, 1280 by 1024, something like that. So I maybe have 1,000 points across the screen. But I might have a scope that's got 20 million points of memory. How do I do that? So what most of the modern scopes will do is take all of the samples that lie within one display point interval, and then basically plot them on top of each other and do almost like an intensity grade to kind of mimic what the analog scopes did with intensity grading. Right? Because the analog scopes, the brighter the trace is, it's the more times that trace has gotten overwritten, overlaid. That'll make that trace brighter. Infrequent things will be dim, most frequent things will be bright. By doing this, you can kind of get the same effect on a digital scope. Okay. Actually, let me switch back to the scope here for a second, just to kind of point out a lot of the scopes will actually help you out with this. So let's wait till this kind of, there it is, okay. So if we look right here, we can see that I'm using 10,000 points of memory. And at this particular setting of 2 microseconds per division, so I've got 2 microseconds per division, so 20 microseconds across the screen, over 10,000 points. I'm sampling at 500 million samples per second, 500 megasamples per second. If I change my horizontal scale, I hate to say that, change my sweep speed, there we go. Okay, make the sweep speed slower. So now I'm at 10 microseconds a division, or 100 microseconds across the screen. Now I'm only sampling at 100 megasamples per second. If I sweep faster, okay, now I've got 200 nanoseconds per division, or 2 microseconds across the screen. I'm now sampling at 5 gigasample per second. Okay, so you can see how these things are all related. And most of the scopes will actually tell you, and give you a little bit of a hint, somewhere on the screen, what you're actually sampling at. Okay? And why we care about that, we'll talk about in a moment. Again, it comes down to aliasing. These are all issues and problems that exist in digital scopes that don't exist in analog scopes. So some digital scope advantages. One of the things you can actually do is capture a signal in a single shot, then zoom in on it. Because it's a picture, it's a movie that's captured in memory. Right? So now once I capture the data, all those points are there. I can zoom in, I can make measurements and things like that. We can do single shot captures. We can get that pre-trigger information because we can tell it I want the trigger to be in the middle of the screen or over here, and I can get data leading up to the trigger and data after. You can't do that with an analog scope. You also have many, many different trigger types. We just talked about a simple edge trigger, but now you can do things like pulse width trigger, timeout triggers, logic triggers, all different types of things because we're all just doing processing on samples to evaluate and determine what that trigger condition is. So there's a lot more possibilities to trigger on particular unique events that you might be looking at. We don't really use that much in the ham shack, but it's an advantage that the digital scopes bring. But another big advantage is automatic measurements. Because now I've got these samples in memory, what's the peak-to-peak voltage? Well, I don't have to go counting divisions, okay, to see, okay, I got 1 volt per division, I'm going 3.5 divisions, so that's 3.5 volts. I can just ask it, give me peak-to-peak voltage, give me RMS voltage, give me rise time, give me fall time. It just does the math, okay? So you can't do that on an analog scope, okay? Even things like frequency counters, that kind of stuff. Even doing things like Fourier transforms to give you the spectral content of the signal coming in. You get these kind of things, almost like a spectrum analyzer functionality, okay? By just taking and doing math on that input waveform to give you these things. So you can do all different types of math on waveforms. Like this screenshot right here, if anybody's watched I think the most recent video I did was on transistor switching times, and this is waveforms from that. So this is the collector voltage, base drive voltage, excuse me, drive voltage into the circuit, base voltage, and this is a math waveform that takes these two voltages, subtracts them, and divides them by the input base resistor. So it's actually a plot of base current. Okay, to kind of show that the base current reverses when you shut the transistor off and that type of a thing. That kind of stuff you can do very easily on a digital scope, and you really can't do that on an analog scope. So you get some of this advanced waveform math, Fourier transforms, things like that. So a lot of nice advantages for that. Now what are some of the disadvantages for digital scopes? Because I made them all sound wonderful, but they can be a pain in the butt. Now a lot of people will complain that, oh, I don't like a digital scope because it's noisy. Like the traces are kind of fuzzy and noisy. The traces look really nice and sharp on my analog scope. And the reason for that is that the digital scope, because it's capturing all these samples, will show you all those samples. Even if you got a very infrequent little blip or glitch or noise spike or something like that, you see them because it's a captured sample point. On an analog scope, if it doesn't happen all the time, it only happens during one sweep, you're not going to exist long enough on the phosphor to light up the phosphor to see it. So it's almost like a natural filter to get rid of those things. So the reality is the digital scopes aren't really noisier than the analog scopes, but they appear to be because of the way they display your data. And that could be a detriment for what you want to do, right? Now aliasing is, like I said, if you're sampling signals at too low of a frequency. And this is that wagon wheel effect, where the wagon wheels turn backwards because whenever the camera captured a screenshot, it captured the wheel in a different position. And it happened to capture it, and it's, the wheel's rotating really fast, but we're sampling it fairly slow. You might capture it in a different spot that makes it look like the wheel's going backwards when you play those frames back together. This is what it looks like graphically. So if our actual input signal is a signal that's moving very fast, this red one that's going here, but if I sample it too slowly with the green samples there, and I connect those dots, the scope is going to show me that lower speed waveform. It's going to alias the signal. Okay, it's basically a mixing process, and this is essentially what can happen. So if I'm looking at an RF signal at a very slow sweep speed, I might see this low frequency signal and say, what the heck is that? It's because you're aliasing the signal because we're not sampling fast enough. What you can do is turn the memory up on the scope. That will increase the sample rate and avoid aliasing, but you have to kind of know that that can happen. Okay, and you'll see that. Another disadvantage for digital scopes, besides them possibly lying to you, is that they can be pricey. So if especially if you're going to buy something new, they can be pretty pricey. They can range from a couple of $100 new to hundreds of thousands of dollars new, depending on what you're doing. So, and they also have a lousy XY mode of operation. XY mode is where instead of letting the horizontal portion of the scope drive the sweep, we drive the horizontal position with another input. Okay, there's actually some useful things we could do with that, but digital scopes do it kind of lousy. The analog scopes are a lot better at this. So we'll talk about that application here in a moment too. So everybody good? Analog, digital scopes, advantages, disadvantages, memory? Yes, you have a question?
How
the digital scopes different than the sampling scopes from the 60s?
That's a great question. So the question was, how are the digital scopes that we're talking about here different from the sampling scopes? And they were, back in the 60s we had sampling scopes, so even today we have them. And you might say, well, a digital scope is a sampling scope. Well, the reality is there is a little bit of a difference in nomenclature. The kind of digital scopes we've been talking about here are what we can call real-time sampling or real-time digitizing scopes, where we're going to sample a waveform so that even with a single shot, we can get a representation of that waveform. Now, another type of scope is called a sampling scope, sometimes called an equivalent time sampling scope, or sometimes a random equivalent time sampling scope. And what that does is it grabs one sample per trigger event. And then next trigger, grab another sample. And then over hundreds or thousands of trigger events, I've captured enough points that it can connect the dots. You can see the waveform. Now, why would I want to do that? Well, what you can do is you would have a very fast sample and hold circuit. So even though this sampler could be running very slow, maybe 10 kilohertz, 100 kilohertz, we're sampling very, very slowly. We're going to very precisely be able to capture a snapshot at an instant in time, like a very high-speed shutter on a camera. And as long as we know the timing relationship between that sample that you capture and the trigger, we can position it in the right spot on the screen, and then over time, you've built up a waveform. So what it did back in the 60s, before we had enough bandwidth to sample at gigasamples per second, and we were looking at very, very fast signals, we just had to make sure that we captured a signal at a precisely known time with respect to the trigger, and then build up the waveform over time. That's called a random equivalent time sampling scope. It relied on the fact that the signals you were looking at were repetitive with respect to the trigger, but it gave you, even in the 60s, multiple gigahertz worth of bandwidth. Okay, and even today, sampling scopes can go into the tens or even hundreds of gigahertz worth of bandwidth, because all you got to do is have a very precise sample and hold that can open and close a shutter and make a measurement with respect to a trigger at a very precise time. So that's a great question. Thank you.
What's the bottom graphic on that?
Well, this bottom one down here?
Yeah.
So this is what a waveform would look like if you were aliasing it. Yeah, because you might say, hey, I'm triggered, but the signal's moving all back and forth because you're doing that undersampling. And so it looks like this randomly moving, untriggered type thing, even though you really are triggered. Okay. So let's talk a little bit about probes, why we use it. Obviously, we've got to connect the signal that we're interested in somehow to the scope. When we're talking about RF signals, oftentimes they're going to come in with just coax off of a sampler, or they're going to come in with just coax off of a sampler or something like that. But when we're talking about probing into a circuit to actually understand or make a measurement to troubleshoot a radio or something like that, we're going to want to get in there with something just like we use probes on a multimeter. Okay? But there are some special probes that we'll use, and we'll talk about why. We want to minimize the loading on the circuit, right? We don't want to affect its operation by touching it and looking at it. So we want probes that don't really load the circuit much or change its operation. So the most common probes that you'll see are what are called 1x and 10x passive probes. We'll talk about these in just a second. Less common, but